simply was no opportunity for an improvement by natural selection. The process of natural selection, as conceived by Darwin, is fundamentally different from the process of elimination of the essentialists. The concept of a static type is replaced by that of a highly variable population. New variations are produced continuously, some of them superior and some of them inferior to the existing average. Since one sees this type of variation in every human population, it is difficult to understand why population 490 thinking was so rare prior to Darwin, and why it took so long to be generally accepted after Darwin. Population thinking was virtually non-existent prior to 1800. Even such a vigorous anti-essentialist as Lamarck thought only in terms of identical individuals, not in terms of variable populations consisting of uniquely different individuals. Natural selection would have made as little sense to Lamarck as to the strictest essentialist. Up to the present day many authors fail to understand the populational nature of natural selection. It is a statistical concept. Having a superior genotype does not guarantee survival and abundant reproduction, it only provides a higher probability. There are, however, so many accidents, catastrophes, and other stochastic perturbations that reproductive success is not automatic. Natural selection is not deterministic, and therefore not absolutely predictive. This was perceptively pointed out by Scriven, 1959, but still causes problems to philosophers raised in an essentialistic tradition. On the other hand, the evolutionary theory permits numerous probabilistic predictions. Williams, 1973a. Following his usual strategy, Darwin advances a number of arguments showing that the interpretation of the essentialists and natural theologians is not valid. There is room for improvement in all species. He documents this, Origin, 82, by the success of so many introduced species over the native fauna and flora. If the natives had been perfect, they would not have succumbed so easily. Therefore extremely slight modifications in the structure or habits of one inhabitant would often give it an advantage over others. Natural selection would of course be helpless if there were not abundant intraspecific variation. Unless profitable variations do occur, natural selection can do nothing. p. 82. Darwin places great stress on the occurrence of useful variations. Since among domestic animals variations occur that are useful to man, he asks, can it, then, be thought improbable that other variations, the causation of evolution, natural selection, useful in some way to each being in the great and complex battle of life, should sometimes occur in the course of thousands of generations? If such do occur, can we doubt, remembering that many more individuals are born than can possibly survive, that individuals having any advantage, however slight, over others, would have the best chance of surviving and procreating their kind? Pages 80-81. This leads him to the following definition. This preservation of favorable variations and the rejection of injurious variations, I call natural selection. p. 81. Variation and its inheritance belong to the subject matter of genetics, and Darwin's assumptions and theories will be analyzed in detail in Chapter 16. Interestingly, among the factors that control natural selection, Darwin, following Lyell, always thought that biotic factors, the interaction among competing species and their relative frequency, was more important than the physical environment. Accordingly, any change in the numerical proportions of some of the inhabitants, independently of the change of climate itself, would most seriously affect many of the other species. p. 81. Darwin also fully realized a fact forgotten by many later authors, that not only the adult phenotype is a target of selection. Natural selection will be enabled to act on and modify organic beings at any age, by the accumulation of profitable variations at that age, and by their inheritance at a corresponding age. p. 86. In social animals it will adapt the structure of each individual for the benefit of the community. p. 87. Darwin's debt to Malthus. Social historians have from time to time advanced the thesis that the theory of evolution by natural selection was inspired by the social and economic situation of England in the first half of the 19th century. This thesis is based on the logic that natural selection is the result of the struggle for existence, about which Darwin, it was claimed, had learned from Malthus. More broadly, the claim is made that Darwin's theory was a product of the Industrial Revolution with its fierce competition, misery, poverty, and struggle for survival, or else a product of the replacement of feudalism, monarchy, by democracy. Is there any validity to these claims? Young and others have made valiant efforts to substantiate the thesis that Darwinism is the product of Malthusianism. Some of these writers do not even bother to partition Darwinism into its several components, even though they all agree that the concept of natural selection arose from an interest in racial, national and class forms of war and conflict, and that Darwin's principles were the application of social science concepts to biology. Harris, 1968, 129. Unfortunately, all those who have defended this thesis have confined themselves to such broad, general statements. By contrast, all the serious Darwin students who have thoroughly analyzed the sources of Darwin's theory, most recently Herbert, Limoges, Gruber, Cohn, Mayr, agree that Malthus's influence on Darwin was very limited, one sentence, and 492 highly specific. What Darwin and Wallace had taken from Malthus was the populational arithmetic, but not his political economy. The Marxist claims that Darwin and Wallace were extending the laissez-faire capitalist ethos from society to all nature to make a Weltanschauung out of the new captains of industry's utopia of progress through unfettered struggle is not supported by any evidence whatsoever. Hodge, 1974. To be sure, Darwin did not live in an ivory tower. He must have seen what went on in England all around him. He read all the relevant literature. Schweber, 1977, Mayr, 1978, and this might have facilitated his acceptance of certain ideas. Yet, if the theory of natural selection were the logical and necessary consequence of the zeitgeist of the Industrial Revolution, it should have been widely and enthusiastically adopted by Darwin's contemporaries. Actually, just the opposite is true. Darwin's theory was almost universally rejected, indicating that it did not reflect the zeitgeist. As my analysis of the 8 components of Darwin's theory has revealed, none of them was original with Malthus, and all of them had been encountered by Darwin in his earlier reading, most of them repeatedly. The struggle for existence was forever talked about from the Greeks to Hobbes, Herder, de Candolle, and Lyell, although no one stressed its intensity more than Malthus. The various checks on overpopulation were widely discussed in the literature. Individuality, population thinking, was a concept wholly alien to Malthus, and without it, of course, natural selection is unthinkable. Why then did the reading of Malthus's comment on the potential geometric increase of populations have such an impact on Darwin? The answer is that Darwin read him at a moment when some of his other thinking had matured to a point where high fertility had acquired a new meaning. There is now good evidence from Darwin's notebooks for a considerable shift in his thinking in the half-year prior to September 1838. Under the impact of studying the writings of the animal, the causation of evolution, natural selection, breeders, Darwin was beginning to be converted from essentialistic to population thinking. In his earlier notes, Darwin applied variation, competition, and extinction quite typologically to species or to incipient species, for example, to the varieties of mockingbirds. The discussions of the breeders made him appreciate for the first time the enormous importance of individual variation. In his third notebook, just a few pages, d. 132, before his famous Malthus statement, d. 135, he emphasizes that individual variation makes every individual a spontaneous generation. This is when Darwin suddenly saw that there is competition not only among species but indeed among individuals, and it was this individual variation which made natural selection possible. The ironic aspect of his debt to Malthus is that Darwin uses the new insight to come to conclusions diametrically opposed to those of Malthus. Malthus' principal argument had as its object to refute the claims of Condorcet and Godwin of an unlimited perfectibility of man. By adding the ingredient of population thinking, Darwin arrived precisely at the opposite conclusion to Malthus. It is even more ironic that Malthus was fully aware of the successes of breeders due to artificial selection. I am told that it is a maxim among the improvers of cattle that you may breed to any degree of nicety you please, and that some of the offspring will possess the desirable qualities of the parents in a greater degree. 1798, 163. However, Malthus uses this very statement only to refute it, at least as far as unlimited perfectibility is concerned. It was as unthinkable for him as for Lyell to accept any transgressions of the limits of the type. For both of them all individuals are essentialistically alike. It is thus evident, to repeat once more, that the role of Malthus was very much that of a crystal tossed into a saturated fluid. If Darwin at this moment had read Franklin's pamphlet or some of the natural history literature stressing superfecundity and its consequences, it is quite likely that it would have electrified him just as much as did the sentence in Malthus. It was a clear case of the prepared mind seeing something that he had not seen when he was not yet prepared. Some sociologists have also construed a debt of Darwin to Spencer. There is no basis for such a claim. Darwin's theories of evolution were essentially completed by the time Spencer, 1852, first thought of evolution. Furthermore, Spencer's ideas, with their reliance on finalistic principles and Lamarckian inheritance, were totally irreconcilable with Darwinian evolution. As Freeman has rightly concluded, 1974, 213, the theories of Darwin and Spencer were unrelated in their origins, markedly disparate in their logical structures, and differed decisively in the degree to which they depended on the supposed mechanism of Lamarckian inheritance and recognized progress as inevitable. The misconception that Spencer's evolutionism was the same as Darwin's has been a great handicap to anthropology and to sociology. A.R. Wallace and natural selection. The enormous resistance which Darwin's theory encountered in the ensuing 80 years proves conclusively how difficult it is to put its 8 components together properly. It is not like many of the discoveries in the physical sciences, where at a given period the same discovery is often made simultaneously by several people because they were looking for the missing piece in a jigsaw puzzle. Merton, 1965. That a second person, without knowing of Darwin's work, would come up with the same theory of evolution by natural selection would seem utterly improbable. This theory was so novel, in such a contrast to anything that anybody had ever thought before, that it took nearly another 100 years before it was generally accepted. That another person, among the relatively few people thinking about evolution, would come up with essentially the same theory, at the same time, was totally unexpected, and yet it happened. 6. The story about Darwin receiving Wallace's essay in June 1858, see Chapter 9, raises numerous questions. Was Darwin justified in writing to Lyell, "I never saw a more striking coincidence, if Wallace had my MS sketch written out in 1842, he could not have made a better short extract. Even his terms now stand as heads of my chapters." Was Wallace's theory really so nearly identical with Darwin's? How did Wallace assemble the pieces of his theory? Did he arrive at it by the same steps as Darwin, or by a process of convergence? We must remember that Wallace had been convinced of evolution since about 1845, and that in 1855 he had published his evidence for speciation. From that time on he searched for the factors that are responsible for evolutionary change. It is relevant to stress here once more the important influence of Lyell's principles of geology. Wallace had read Lyell's superbly argued case against the modification of species as carefully as had Darwin. A good deal in the similarity of the arguments of Darwin and Wallace is clearly due to the fact that both men attempted to refute the causation of evolution, natural selection. The very specific points raised by Lyell. By the concreteness of his anti-evolutionary objections, Lyell had prepared the ground for specific counterarguments. McKinney, 1972, 54-57. Even though constantly thinking about these problems, Wallace's ideas apparently made little progress from 1855 until a memorable day in February 1858. At that time I was suffering from a rather severe attack of intermittent fever malaria at Ternate in the Moluccas, and one day while laying on my bed during the cold fit, wrapped in blankets, though the thermometer was at 88° F, the problem of how species transformation occurs again presented itself to me, and something led me to think of the positive checks described by Malthus in his essay on population, a work I had read several years before and which had made a deep and permanent impression on my mind. Wallace, 1891, 20. As in the case of Darwin, the illumination was sudden, and caused by thinking about Malthus's essay on population. A close reading of Wallace's 1858 essay on the tendency of varieties to depart indefinitely from the original type shows, however, that the parallelism is not complete. Wallace states his thesis with extraordinary clarity: there is a general principle in nature which will cause many varieties to survive the parent species, and to give rise to successive variations, departing further and further from the original type. 1858, 54. The language in which this observation is presented is rather typological. Wallace's conclusion, however, clearly contradicts Lyell's claim that varieties have strict limits, and can never vary more than a small amount away from the original type. The most important aspect of Wallace's analysis is that he carefully stayed away from the quagmire of the morphological controversy on species and varieties but based his conclusion on a rather strictly ecological argument. He concluded that population size of a species is not at all determined by fertility but by natural checks on potential population increase. An enormous number of animals must die each year to keep the number constant, and those that die must be the weakest, the very young, the aged, and the diseased, while those that prolong their existence can only be the most perfect in health and vigor, those who are best able to obtain food regularly and avoid their numerous enemies. It is, as we commenced by remarking, a struggle for existence, in which the weakest and the least perfectly organized must always succumb, pages 56 to 57. In this early part of Wallace's discussion his emphasis is on 495. Regulation of population size, on stabilizing selection, elimination, and on competition between species. He is now in a condition to proceed to the consideration of varieties, to which the preceding remarks have a direct and very important application. In the ensuing discussion Wallace applies the term variety to variant individuals, that is, individuals within a population that do not share the same properties. If a species produces a superior variety, that variety must inevitably in time acquire a superiority in numbers, p. 58. Curiously, Wallace's account is marred by the same weaknesses as Darwin's. There is still a good deal of typological thinking, particularly in reference to the nature of varieties, and like Darwin he still accepts the effectiveness of use and disuse, a process rather universally believed in at that period. Like Darwin, Wallace rejects the hypotheses of Lamarck in a formulation that indicates that it was taken straight from Lyell. Instead, Wallace explains the short, retractile talons of the cat tribe and the elongated neck of the giraffe in strict selectionist terms. Indeed, Wallace emphasizes strongly that the acquisition of new adaptations is completely consistent with the interpretation that they are the result of selection. He concludes his essay with these words: "We believe we have now shown that there is a tendency in nature to the continued progression of certain classes of varieties further and further from the original type, a progression to which there appears no reason to assign any definite limits. This progression, by minute steps, in various directions, but always checked and balanced by necessary conditions, subject to which alone existence can be preserved, may, it is believed, be followed out, so as to agree with all the phenomena presented by organized beings, their extinction and succession in past ages, and all the extraordinary modifications of form, instinct, and habits which they exhibit, p. 62. Let us now try to compare Wallace's chain of argument in more detail with that of Darwin. 7. Both of them started out with the species problem, or, as Wallace himself said, in a retrospective account in 1908, with the thought of the possible causes of the change of species. Nevertheless, Wallace's own analysis was in some ways more a study of population ecology than a study in speciation, which he presumably thought he had dealt with adequately in 1855. Wallace, quite in contrast to Darwin, relates the problem of evolution very directly to man. What had long puzzled the causation of evolution, natural selection. Him, who for 8 years had lived among natives, was what the checks were that kept all savage populations nearly stationary. These checks enumerated by Malthus disease, famine, and accidents, war, etc. are what keep down the population, and it suddenly occurred to me that in the case of wild animals these checks would act with much more severity, and as the lower animals all tended to increase more rapidly than man, while their population remained on the average constant, there suddenly flashed upon me the idea of the survival of the fittest. Wallace, 1903, 78. As in the case of Darwin, the crucial component of the theory was the recognition of individuality. Precisely 50 years later, in 1908, Wallace reports this as follows: "Then there flashed upon me, as it had done 20 years before upon Darwin, the certainty, that those which, year by year, survived this terrible destruction must be, on the whole, those which have some little superiority enabling them to escape each special form of death to which the great majority succumbed, that, in the well-known formula, the fittest would survive. Then I at once saw, the ever-present variability of all living things would furnish the material." As stated, there are subtle differences between the interpretations of Wallace and of Darwin. Wallace apparently had been far more impressed by the general thesis of Malthus and particularly by the enormous annual losses which keep populations at a steady level, the positive checks. Population thinking, apparently, had different sources in the two authors of natural selection. It was animal breeding and taxonomic work in Darwin, it was the study of human populations and taxonomic work in Wallace. Wallace had a low opinion of the value of studying domestic varieties and concluded that we cannot draw inferences as to varieties in a state of nature by observing domestic animals. For this and other reasons he did not use the term selection in his essay and apparently was always somewhat unhappy about this term. In spite of these finer differences in approach, Wallace entirely agreed with Darwin in the final conclusion: unlimited variability in populations exposed to drastic regular decimation must lead to evolutionary change. In due time, however, the thinking of Wallace diverged increasingly from that of Darwin, as far as natural selection was concerned. For instance, by 1867 Wallace renounced any reliance on use and disuse, and in the 1880s he was one of the first to endorse enthusiastically Weismann's rejection of any inheritance of acquired characters. Wallace did not believe in a separate category of sexual selection and least of all in female choice, Chapter 12. He also believed that reproductive isolating mechanisms were strictly the result of selection. Yet, he lost his nerve when it came to applying this consistent selectionism to man, since he considered it impossible that natural selection could have endowed primitive man with such a large brain as well as with his capacity for morality. Some superior power must have been responsible for this. Wallace, 1870. Wallace did not return from the East Indies until 1862, 4 years after his paper had been read at the Linnean Society. He was never jealous of Darwin, indeed he always was a great admirer of his, even though they later disagreed on the answers to certain problems. Wallace eventually acquired fame on his own account, particularly through his splendid Malay archipelago and his geographical distribution of animals, 1876, the classic of zoogeography for the next 80 years. Forerunners of natural selection. Two methods of attack are used most frequently against a new theory. The first one is to claim that the new theory is wrong, the second one is to claim that it is not new. True to the second part of this tradition, after the publication of The Origin one claim after the other was made of priority in publication of the concept of natural selection. 8. Because an essentialist simply cannot conceive of evolutionary change through natural selection, all claims prior to 1800 are inadmissible for this reason alone. There are, however, a number of proposals of genuine natural selection prior to Wallace and Darwin in 1858. William Charles Wells, 1757 to 1817, an English doctor who had lived in South Carolina for a while, advanced in 1818 the theory of natural selection in a sort of postscript to an essay dealing with a human color variant. Wells, 1818. Wells stated, as had quite a few others before him, that Negroes are far more resistant to tropical diseases than whites. Conversely, Negroes are far more susceptible to the diseases of the temperate zone. Regarding then as certain that the Negro race is better fitted to resist the attacks of the diseases of hot climates than the white, it is reasonable to infer that those who only approach the black race will be likewise better fitted to do so than others who are entirely white. This, he says, is indeed true for mulattoes. He then refers to the practice. The causation of evolution, natural selection. Of animal breeders, when they find individuals possessing in a greater degree than common, the qualities they desire, couple a male and female of these two together, then take the best of their offspring as a new stock and in this way proceed till they approach as near the point in view as the nature of things will permit. But what there is done by art seems to be done with equal efficiency, though more slowly, by nature in the formation of varieties of mankind, fitted for the country which they inhabit. He declares that this is the way in which human races develop in the different climatic zones of the world. Although Wells clearly proposes a theory of evolution by natural selection, it is only evolution of adaptation to local climates within a species, and at that for man only. The principle is never applied to genuine evolution, to the multiplication of species, to a development of higher taxa or to common descent. The person who has the soundest claim for priority in establishing a theory of evolution by natural selection is Patrick Matthew, 1790 to 1874. He was a wealthy landowner in Scotland, well educated, very well read, and well travelled. Wells, 1974. His views on evolution and natural selection were published in a number of notes in an appendix to his work on naval timber and arboriculture, 1831. These notes have virtually no relation to the subject matter of the book, and it is therefore not surprising that neither Darwin nor any other biologist had ever encountered them until Matthew brought forward his claims in an article in 1860 in the Gardener's Chronicle. Matthew's background was very much the same as that of many of Darwin's friends among the landed gentry, having to do with animal and plant breeding. He enunciates clearly that success in this endeavor depends on the selection, a word he uses repeatedly, of the best suited individuals. Indeed, the main thesis of his book is that this principle should also be applied to tree culture. The choice of words indicates that he had read Erasmus Darwin, Lamarck, Malthus, and Lawrence. He clearly adopts a theory of evolution and, quite remarkably, evolution by common descent. Are they species the diverging ramifications of the living principle under modification of circumstances? He considers gradual evolution as much more probable than total destruction and new creation, catastrophism. He rejects Linnaeus's origin of species by hybridization and believes that the progeny of the same parents, under great difference of circumstance, might, in several generations, even become distinct species, incapable of co-reproduction, p. 384. The remarkable similarity of Matthew's thinking to that of Darwin is clearly indicated in his statement: the self-regulating adaptive disposition of organized life may, in part, be traced to the extreme fecundity of nature, who, as before stated, has, in all the varieties of her offspring, a prolific power much beyond, in many cases 1,000-fold, what is necessary to fill up the vacancies caused by senile decay. As the field of existence is limited and preoccupied, it is only the hardier, more robust, better suited to circumstance, individuals, who are able to struggle forward to maturity from the strict ordeal by which nature tests their adaptation to her standard of perfection and fitness to continue their kind by reproduction. The breed gradually acquiring the very best possible adaptation of these to its condition which it is susceptible of, and when alteration of circumstances occurs, thus changing in character to suit these as far as its nature is susceptible of change, p. 385, Patrick Matthew undoubtedly had the right idea, just like Darwin did on September 28, 1838, but he did not devote the next 20 years to converting it into a cogent theory of evolution. As a result, it had no impact whatsoever. Pritchard, Lawrence, and Naudin have also been mentioned as having anticipated Darwin, but their statements are weak and inconclusive when compared to those of Matthew. They either refer to the improvement of the human species or to choosing plant varieties, but the appreciation of the possibilities of selection are not utilized for the development of a theory of evolution. A careful indication of sources of ideas was not the tradition of the times. Lamarck, for instance, hardly ever cited the authors whom he had used. Not surprisingly, it has therefore been claimed repeatedly that Darwin had been aware of these forerunners and had used their findings without giving due credit, but not a shred of evidence supports these claims. There is every reason to believe that Darwin did not know the relevant writings of Wells or Matthew, and that the statements of Lawrence, Pritchard, and Naudin, if known to Darwin, were too vague and too unrelated to a theory of evolution by common descent to have attracted his attention. It is true that authors whose writings Darwin had used are rarely cited in the Origin by name, but this is due to the fact that he considered this work an abstract and that he would provide detailed references in his more complete work. Now that Natural Selection has been published, 1975, it is much easier to determine what earlier publications Darwin had used, and what he had not. The causation of evolution, natural selection. This emerges even more clearly from his notebooks and other manuscript material, and they document convincingly that Darwin had been unaware of the writings of either Wells or Matthew. The impact of the Darwinian revolution. The Darwinian revolution has been called, for good reasons, the greatest of all scientific revolutions. It represented not merely the replacement of one scientific theory, immutable species, by a new one, but it demanded a complete rethinking of man's concept of the world and of himself. More specifically, it demanded the rejection of some of the most widely held and most cherished beliefs of Western man. Mayr, 1972b, 988. In contrast to the revolutions in the physical sciences, Copernicus, Newton, Einstein, Heisenberg, the Darwinian revolution raised profound questions concerning man's ethics and deepest beliefs. Darwin's new paradigm, in its totality, represented a most revolutionary new Weltanschauung, Dewey, 1909. The sweeping nature of the changes proposed by Darwin is best documented by listing some of the more philosophical implications of Darwin's theories. 1. The replacement of a static by an evolving world, not original with Darwin. 2. The demonstration of the implausibility of creationism, Gillespie, 1979. 3. The refutation of cosmic teleology. 4. The abolition of any justification for an absolute anthropocentrism by applying the principle of common descent to man. 5. The explanation of design in the world by the purely materialistic process of natural selection, a process consisting of an interaction between non-directed variation and opportunistic reproductive success which was entirely outside the dogma of Christianity. 6. The replacement of essentialism by population thinking. To this list must be added various philosophical methodological innovations, such as the consistent application of the hypothetico-deductive method, Ghiselin, 1969, Roos, 1979a, a new evaluation of prediction, Scriven, 1959, and the bringing of the study of ultimate, evolutionary, causations into science, Mayr, 1972b. How ready was the world to accept these revolutionary new concepts, or, to put it differently, how much time did it take before Darwin's thought was adopted? The impact of the Origin was unprecedented. Except for Freud, perhaps no other scientist has been translated so extensively, reviewed so frequently and in such detail, and had so many books written about him. All the numerous quarterlies and review journals of the period had extensive reviews, and so did most of the religious or theological periodicals. So rich is this literature that a secondary literature has developed which deals with this review literature, For example, Elgard, 1958, Hull, 1973. Another category of literature deals with Darwin's impact and gradual acceptance in various parts of the world. No other phase in the history of biology has been described by historians with more loving detail than the battles resulting from Darwin's theory. Kellogg, 1907, Vortimer, 1970, Glick, 1974, Conry, 1974, Moore, 1979. The nature of the opposition to Darwin can be understood much better if one realizes the general attitude toward evolution in the middle of the 19th century. Prior to Darwin, the consideration of evolution was thought to be part of the realm of philosophy. Indeed, virtually all of those who had speculated on evolution were theologians or other non-biologists who basically had no competence whatsoever to deal with this complex biological subject matter. Even Lamarck, Darwin's most distinguished forerunner, failed to marshal systematically facts to support his evolutionary speculations or to provide a detailed analysis of the possible mechanisms of evolution. In line with the concepts of the period, he entitled his work Philosophic Zoologic, 1809, and indeed it was a philosophy rather than a zoology. Darwin was the first author to deal with the subject of evolution strictly scientifically. He supported his thesis by a massive body of facts, and this rich evidence changed the situation quite fundamentally. As long as the discussions about evolution were conducted on a philosophical basis, the argument could be stated in metaphysical terms. The publication of The Origin made this approach impossible, once and for all time. Darwin showed, implicitly and explicitly, that there are three and only three possible explanations for the diversity of the living world and for the ingenuity of its adaptations. This challenge forced every thinking reader of his detailed and perceptive analysis into the uncomfortable position of having to make a choice in favor of either one or the other of these three possible explanations. The causation of evolution, natural selection. The first one is that of a continual creation, involving the perpetual intervention of the Creator in replacing species and faunas that had become extinct, and in creating ever new adjustments and adaptations. Lyell and Sedgwick were among the many scientists who up to a point adopted this explanation. It included the belief that every feature of every species was specially created to adapt the species for the environment into which it was placed. It is probable that in 1859 this theistic explanation of the world was still the majority opinion, at least in Great Britain. However, such a perpetual intervention hypothesis, as Lyell called it, Wilson, 1970, 89, was too extreme even for many devout scientists. Even Lyell and Agassiz had misgivings. This led them to a second, deistic theory of evolution, a belief in the existence of teleological, evolutionary laws, ordained at the time of creation, that would lead to ever greater perfection and adaptation and would guarantee an orderly replacement of faunas in the geological sequence. It would account for any other kind of order and regularity found in nature. Bowler, 1977b, Osbavet, 1978. Lamarck, who originally seems to have adhered to such a theory, eventually realized the absence of a consistent trend toward ever greater perfection. The difficulties increased as biological knowledge grew. Much of Darwin's argumentation in The Origin was directed toward uncovering irregularities in the patterns of distribution of faunas and floras and of morphological trends which defied any interpretation in terms of progressive laws. No other phenomenon was more awkward for the deists than the production of new species to replace those that had been lost by extinction. That God was responsible for their appearance was taken for granted. To ascribe their creation to a miracle was, of course, unacceptable to scientists like Herschel and Whewell. Thus, whistling in the dark, they ascribed their origin to intermediate causes or causal laws governing the introduction of new species instituted by the Creator, see Chapter 9. How could such laws possibly operate? There were actually only three possibilities: 1. Special creation, which would be a miracle; 2. Spontaneous generation, an origin that was not respectable scientifically, at least as far as higher organisms are concerned; nor would it explain the perfect design of each species, or, 3. Derivation from other species, and that would be evolution. Lyell, unlike Gray, was not ready to accept evolution by natural selection as an intermediate cause. Herschel and Lyell did not know enough natural history to appreciate that there are no conceivable mechanisms by which such secondary laws could be implemented without coming into conflict with the laws of physics and chemistry. 9. It was precisely this insight which induced Darwin to postulate the third of the three possible explanations, a strictly non-teleological mode of evolution in which random variation is converted into directional trends and into adaptation by natural selection, without any recourse to supernatural forces, not even at the beginning. It is not admissible to judge the debate following the publication of The Origin within the framework of modern thinking. 504. One must remember how powerful in the 1850s and 1860s the hold was which creationism still held, particularly in England. Virtually all of Darwin's peers were creationists, most of them even rather orthodox theists, who found nothing unscientific in invoking supernatural forces in their arguments. Hopkins, one of Darwin's reviewers, called Darwin unscientific for postulating that the trilobites, a group of extinct fossil invertebrates which suddenly appeared in the fossil record, were derived from ancestors still unknown as fossils. Yet the same Hopkins did not hesitate to believe that the trilobites had been created at the time when they first showed up in the fossil beds. Hull, 1973. It is evident that a creationist interpretation was, to those who believed in a personal God, as legitimate, in fact even more so, as a so-called scientific explanation. The battle about evolution, and particularly natural selection, was not a purely scientific controversy, rather it was a struggle between two ideologies, natural theology and objective science. I will not here report on the struggle between religion, church, and science, 10 since this volume deals with biological thought. However, since creationism, at least in England, was a dominant scientific school in the 1850s, Darwin had to adopt the bold strategy of showing for one natural phenomenon after another that it could be explained quite reasonably as the product of evolution, but that it did not fit at all what one would expect from the action of a wise, benevolent, and all-powerful creator. Why, it may be asked, has the supposed creative force produced bats and no other mammals on remote islands? Origin, 394. Here and in about 30 other places in the Origin, Darwin argues that a given phenomenon is consistent with evolution or with common descent but makes no sense when ascribed to a special act of creation, p. 55. Again and again, Darwin repeats, on the view that each species has been independently created, I can see no explanation. The causation of evolution, natural selection. Darwin's 5 theories. The rich literature on the impact of the Origin is unfortunately badly flawed since it takes insufficiently into consideration that Darwin had actually proposed 5 largely independent theories. As a result, when a historian or philosopher speaks of Darwinism, one rarely knows whether he means evolution as such, man's descent from the apes, natural selection, or what. The word Darwinism has continued to change its meaning over the years. In the period immediately after 1859 it referred most often to the totality of Darwin's thinking, while it strictly means natural selection for the evolutionary biologist of today. Darwin himself contributed to this ambiguity by referring in The Origin to the theory of evolution 10 times as my theory but designating natural selection only 3 times as my theory. Indeed, there is considerable evidence to indicate that Darwin considered all components of his evolutionary theory as a single indivisible whole. One can infer this from the fact that he mingles in many chapters of The Origin seemingly unrelated subjects. For instance, in the first chapter, the causes of variability, the problem of species versus varieties, and artificial selection. In the second chapter he deals with variation in nature and with the species problem. The next 2 chapters deal with mechanisms of evolution, struggle for existence, natural selection, speciation, divergence of characters, extinction, and the theory of common descent. In spite of the beauty and brilliance of individual discussions, much of the organization of the origin strikes the modern reader as rather chaotic. It is this, probably, which has induced many readers of the origin to complain that it was a difficult book. Although I find his arguments not completely convincing, Hodge, 1977, makes a case that Darwin had a clear tripartite organization in mind, and that he more or less followed it. Many subsequent writers adopted Darwin's belief that common descent, gradualness, and natural selection are an indivisible single paradigm, and this belief induced these writers to treat these subjects jointly when discussing the post-1859 fate of Darwinism. Actually, a much clearer picture emerges if 5 strands of Darwin's thought are treated separately. That they do not constitute an indivisible whole is demonstrated by the fact that so many evolutionists accepted some of Darwin's theories but rejected others. Table 3. Table 3. The composition of the evolutionary theories of various evolutionists. All these authors accepted a 5th component, that of evolution as opposed to a constant, unchanging world. Common descent. Gradualness. Populational. Speciation. Natural selection. Lamarck no yes no no. Darwin yes 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 yes. Haeckel yes yes p in part. Neo-Lamarckians yes 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 no. Th Huxley yes no no, no. De Vries yes no no no. Th Morgan yes, no, no unimportant. The full title of Darwin's work, On the Origin of Species by Means of Natural Selection, or the Preservation of Favored Races in the Struggle for Life, has added to the erroneous impression that only a single theory is involved. The fact that Darwin treated speciation, in Chapter 4, under natural selection has reinforced this interpretation, but it is quite wrong. Let me illustrate with an example that speciation and natural selection are 2 independent processes. A population could become established on an island and could, theoretically, eventually become so different from the parental population merely by random genetic processes, genetic drift, that it is no longer able to reproduce with the parental population, that is, it would have speciated, without any contribution at all of natural selection. The same virtual independence of 2 evolutionary phenomena is true for patterns of geographic distribution. They are largely due to accidents of dispersal superimposed on geographical and geological processes that also go on independent of natural selection. To imply, as Darwin did, that natural selection explains patterns of distribution is quite misleading. Let me now attempt to particularize the various theories of which Darwin's evolutionary paradigm is composed. As such, the theory that the world is not constant, but the product of a continuing process of evolution was, of course, not new with Darwin. Yet, in 1859, in spite of the writings of Lamarck, Meckel, and Chambers, the majority opinion still was that the world is stable. A number of rather peculiar compromises, such as progressionism, were defended between 1800 and 1859, in order to the causation of evolution, natural selection. Avoid having to accept evolution. However, the massive evidence which Darwin presented was so convincing that within a few years every biologist became an evolutionist, even Owen, Mivart, and Butler in England, who opposed Darwin's other theories. Agassiz, a holdout to the end, died in 1873. France was actually the only country where evolutionism as such had to battle for acceptance. Conry, 1974, Boesiger, 1980. For many biologists of today, evolution is no longer a theory but simply a fact, documented by the changes in the gene pools of species from generation to generation and by the changes in the fossil biota in accurately dated geological strata. Current resistance is limited entirely to opponents with religious commitments. By common descent. Darwin, curiously, was the first author to postulate that all organisms have descended from common ancestors by a continuous process of branching. When accepting the splitting of a parental species into several daughter species, he was led to the concept of common descent almost by necessity. By tracing the ancestry up into the higher taxa, Darwin was led to consider all living beings as the lineal descendants of some few beings which lived long before the first bed of the Silurian system, origin, 488, and that life had been originally breathed into a few forms or into one, p. 490. A continuing multiplication of species thus could account for the total diversity of organic life. By reducing the problem of origins to a single one, that of the first origin of life, common descent made spontaneous generation, a process quite incompatible with Darwin's continuistic ideas, superfluous. Even though the solution of this ultimate problem was clearly outside the capacities of contemporary science, Darwin could not resist speculating about it. LLD 3:18. The theory of common descent greatly facilitated the acceptance of evolution, as Darwin himself said in the Ong-In, because of its power to explain so much in comparative anatomy, biogeography, systematics, and other areas of biology that had previously been puzzling. Even Lyell and the botanist George Bentham, who had originally been opposed to it, had by 1868 adopted the theory of common descent. It has become customary in the literature of the history of biology to refer to the Darwinian revolution. This term, which I myself have used, is ambiguous, however, since the total corpus of Darwin's thought ushered in several intellectual revolutions. Particularly well defined are two. The first one is that by including man in the phyletic tree of common descent, Darwin took away from man his privileged position in nature assigned to him in the Bible and in the writings of virtually all philosophers. This, so to speak, dethroned man. It was a truly revolutionary concept, quite different from considering man the pinnacle of the chain of being. The second revolution was natural selection, see below. Gradualness of evolution. Darwin's insistence that evolution is entirely gradual encountered almost as much resistance as his theory of natural selection. This had both empirical and ideological reasons. A gradual change from one type to another is simply unthinkable for an essentialist, typologist. Lyell and others insisted that the potential for variation of a species has fixed limits which no amount of selection could transcend. Every species was separated from every other species by an unbridgeable gap, and if one wanted to postulate evolution, one would have to postulate the sudden origin of new types by assaltation. This is why Lyell postulated the steady occurrence of the introduction of new species, a discontinuous process. Darwin's theory that populations are the locus operandi of speciation and that this permits every grade of intermediacy between geographical varieties and species undermined the essentialistic argument. On the other hand, certain empirical findings seem to support the essentialist position. Comparative anatomists, with few exceptions, stress the fundamental differences between the structural plans of the higher taxa, differences which, they said, could not be explained by gradual evolution. Paleontologists, likewise, insisted on the sudden origin of new types in the fossil record and on the total absence of any intermediate types. Wherever one looked in nature, its most impressive aspect was discontinuity. Experimental biologists, all of them solidly essentialists, found it particularly difficult to comprehend gradual evolution. Unused to thinking in terms of variable populations, they could not conceive of the origin of anything new except through the saltational production of a deviating individual, a hypothetical process, later called macrogenesis. Nageli, his, Kaliker, W. H. Harvey, Mivart, Gabon, and other distinguished authors publishing in the 1860s, 70s, and 80s supported macrogenesis. Still, until the 1890s this was a minority opinion. Obviously, macrogenesis is incompatible. The causation of evolution, natural selection. With gradual natural selection, and Darwin never had any use for it. Darwin, more clearly than any of his opponents, saw that the observed discontinuities are, so to speak, artifacts of history. He explained the gaps between genera and still higher taxa by the dual processes of character divergence and extinction, an explanation that is now universally adopted. Competition and the invasion of new niches and adaptive zones leads to steady divergence, but the extinction of intermediate types and connecting links is responsible, more than anything else, for the observed discontinuities between the higher taxa. Thus, such breaks are secondary artifacts rather than a reflection on the original process of the formation of the taxa. The source of Darwin's strong belief in gradualism is not entirely clear. In part it was evidently the result of observation, such as the gradual differences among Galapagos mockingbirds and finches or the historically documented continuity among the most aberrant races of dogs, pigeons, and other domestic animals. But as Gruber, 1974, points out, there may have been a metaphysical component in Darwin's belief. As a result of studying the writings of the theologian Sumner, 1824, 20, Darwin had come to the conclusion that all natural things evolve gradually from their precursors, while discontinuities, such as sudden saltations, are indicative of a supernatural origin, that is, indicative of intervention by the Creator. All of his life Darwin took great pains to reconstruct a gradual evolution of phenomena that at first sight seemed clearly the result of sudden origins. Natural selection. In spite of occasional flashes of insight among his forerunners and the simultaneous proposal by Wallace, there is no question that it was Darwin who established the theory of evolution by natural selection, who supported it by numerous well-chosen examples and carefully reasoned arguments, and who, by tying it in with an equally well-substantiated theory of evolution, brought it to the attention of the Western world. By explaining design in nature as the result of a purely non-teleological, materialistic process, the theory of natural selection eliminated the need for any global teleology. Darwin's theory provided a causal explanation of the seemingly perfect order in living natui, that is, of the adaptation of organisms to each other and to their environment. Clearly the theory of natural selection was the most revolutionary concept advanced by Darwin. By providing a purely materialistic explanation for all phenomena of living nature, it was said it dethroned God. Rightly, the theory of natural selection can be designated a second Darwinian revolution. The resistance to natural selection. If a modern biologist speaks of Darwinism, natural selection is the component of Darwin's paradigm he has in mind. Darwin realized from the beginning that it was the most revolutionary of his ideas. Not surprisingly, it was the one his opponents reacted to most violently, beginning with Herschel, who called it the law of the higgledy-piggledy, and Sedgwick, who considered it a moral outrage. Natural selection was the component of Darwinism that offended Darwin's opponents most deeply. It dethrones God, and which, not unnaturally, is even today resisted most strenuously. Darwin's friend Asa Gray, a devout Christian, was one of the very few Darwinians who succeeded in reconciling natural selection with a belief in a personal God. And it was not only theologians, philosophers, and lay people who opposed this thesis but, up to the evolutionary synthesis of the 1930s and 40s, even the majority of biologists, Mayr and Provini, 1980. Even Darwin's friends and sympathizers were, at best, lukewarm about natural selection. 1-2 Natural selection was not stressed in a single one of the favorable reviews of the Origin that were published after 1859, Hull, 1973. The endeavor to explain the world, including all living organisms, in a purely materialistic manner was distasteful to most of Darwin's supporters. Lyell never accepted natural selection, and when he finally accepted evolution, he most often referred to it as Lamarck's theory, to the great annoyance of Darwin. T.H. Huxley, Darwin's bulldog, was a staunch defender of natural selection throughout Darwin's life, and yet Poulton, 1908, provides good evidence that he was at no time a convinced believer in the theory he protected. Huxley was a morphologist, physiologist, and embryologist, and the evolution of the organic world was to him equivalent to the evolution, as he called it, of the chick embryo in the egg. LLD, 202. Natural selection did not fit too well with this concept, and in a historical paper about Darwin, The Coming of Age of the Origin of Species, The Causation of Evolution, Natural Selection. 1893, 227 to 243, Huxley makes no reference at all to natural selection. When using the word Darwinism, Huxley applied it as often as not simply to the theory of evolution by common descent. There are indications that he was by no means sure that the theory of natural selection would prove ultimately valid. This is implied by his words, whatever may be the ultimate fate of the particular theory put forth by Darwin. Huxley thought that major saltations could achieve what gradual evolution by selection could not, see Chapter 11. The only solid support Darwin received for natural selection was from the naturalists. In the first place there was of course his co-discoverer, Wallace, who was an even more unreserved champion of selectionism than Darwin himself. He drew the line only when it came to man and his mind. Wallace's South American companion Henry W. Bates made important contributions to selectionism, and so did Fritz Müller in Brazil, another naturalist, see below. The botanists, on the whole, were opposed to selection, but Darwin's friend J.D. Hooker always expressed himself on selection in the sense of Darwin, and later so did Thieselton Dyer. Abroad, nobody was as convinced a selectionist as August Weismann, at least after 1880. In fact, as we shall see, he was perhaps the first evolutionist to ascribe evolutionary change exclusively to natural selection. It is clear from Weismann's biography and from his research on butterflies that he had been an ardent naturalist all his life. It is always said that the 1858 publication of the Darwin-Wallace theory of natural selection had at first been totally ignored. This is not correct. The ornithologist Alfred Newton describes how he and his friends had been arguing for years about the origin of species, and what an exciting surprise the Darwin-Wallace issue of the Tinnian Journal had been. I sat up late that night to read it. Point 1 went to bed satisfied that a solution had been found. 1888, 241. Newton, in turn, called the paper to the attention of Canon Tristram, who in a careful study of desert larks interpreted their cryptic coloration as the result of natural selection. 1 month before the publication of The Origin, Tristram, 1859, 429. Indeed, he describes in full detail under what conditions paler individuals and individuals with longer bills would be favored by selection. Owen mentioned the Darwin-Wallace paper favorably, in 1858 in a presidential address, but turned against selection after the publication of The Origin. Selectionism probably had its best support in the 1880s after Weismann had refuted the inheritance of acquired characters and had converted Lancaster, Thieselton Dyer, and others, see Chapter 12. By the 1890s it lost again much support, and it was not until the occurrence of the evolutionary synthesis of the 1930s and 40s that the theory was finally adopted by virtually all biologists. Since the criticism of natural selection was almost universal, it is impossible to try to review it. An exception will be made for one critique because it is always said to have been particularly effective. No other attack on Darwin's theory has drawn more attention than that of the physical scientist and engineer Fleming Jenkin, 1867. This is in part due to Darwin's own statement, Fleming Jenkin has given me much trouble, but has been of more real use to me than any other essay or review. Letter to Hooker, 1869, MLD, 2, 379. When read by a modern reader, Jenkins' review seems anything but impressive. It is based on all the usual prejudices and misunderstandings of the physical scientists. Though Jenkin admits that all must agree that the process termed natural selection is in universal operation, what he understands by natural selection is actually the essentialist's process of elimination. If Jenkin had understood that reproductive success is the basic principle of natural selection, he would not have written, "The tendency to produce offspring more like their superior parents than their inferior grandfathers can surely be of no advantage to any individual in the struggle for life." On the contrary, most individuals would be benefited by producing imperfect offspring, competing with them at a disadvantage. Jenkin agrees with Darwin and most contemporaries that two distinct kinds of possible variation must be separately considered. First, that kind of common variation, which is referred to as an individual variation. And secondly, that kind of variation which occurs only rarely, and may be called briefly a sport, as when a child is born with 6 fingers on each hand. As far as individual variation is concerned, Jenkin, like File, Owen, and all essentialists, asserts that natural selection would soon exhaust the available reservoir of such variation. Individual variation, he insists, can never pass beyond the confines of a definite sphere of variation. It can never step outside the type. Selection can make a dog run faster or improve his olfactory faculty, but it can never make it into something that is not a dog. He repeats again and again that no species can vary beyond defined limits. This widespread assumption is not only an automatic the causation of evolution, natural selection, sequence of essentialistic thinking, but it represents also the experience of animal and plant breeders who had found that the available variation in a closed flock or herd is soon exhausted by intense artificial selection. This ignores, of course, that the situation in nature is radically different because the reservoir of variation is continuously replenished by gene flow and mutation. In small, closed populations, continued natural selection can be effective only if new genetic variation is produced abundantly. Like the early Mendelians, Jenkin postulated an enormous mutation pressure, with natural selection actually contributing nothing to the evolutionary change. Owing to his complete inability to understand natural selection, he asserts again and again that its efficiency is limited to the cases in which the same variation occurs in enormous numbers of individuals. It does not apply to the appearance of new organs or habits. Here Jenkin approaches the core of his criticism. Even if one were to admit the gradual improvement of species by the selection of individual variation, this does not help us at all, says Jenkin, as the origin of species requires not the gradual improvement of animals retaining the same habits and structure, but such modification of those habits and structure as will actually lead to the appearance of new organs. It is obvious that Jenkin, like Mivart, was particularly impressed by the difficulty of explaining the origin of new organs. As an essentialist, he could not imagine that this could occur in any way other than by saltation, and this leads him to turn his attention to the second type of variation. Darwin had occasionally referred in The Origin to sports, or as he also called them, single variations, because, as he said, they offer such simple illustrations. LLD, 289. One might suggest that new structures which carry species beyond their normal sphere of variation arise by sports. This, says Jenkin, is highly improbable for a number of reasons, but particularly because when a sport breeds, his progeny will on the whole be intermediate between the average individual and the sport. In other words, Jenkin postulated the universal occurrence of what in the later genetic literature was called blending inheritance. This claim was particularly astonishing considering that Jenkin had chosen families with 6-fingered individuals as typical illustrations of spoites. It was known since Maupertuis and Reaumur that polydactyly, 6-fingeredness, is inherited without any intermediacy. Darwin could have easily refuted Jenkin by pointing out that 6-fingered individuals do not have children with half fingers and grandchildren with half fingers, nor are the descendants of albinos half-pigmented. The animal breeders had reported literally countless cases where such sports, by back-crossing, had become standard breeds, such as the Ancon sheep referred to by Darwin, Origin, 30. If Jenkin's claim of intermediacy had any validity, all such sports would have been quickly extinguished by back-crossing. The fact that Darwin did not use this argument confirms that Darwin himself was rather confused on the problem of variation, see also chapter 16. As it was, he meekly accepted Jenkin's argument of blending, and it induced him to stress even more than before the unimportance of sports for evolution. What Darwin also failed to see was that the same argument of blending would hold for individual variation if it reflected genuine genetic change. Vortimer, 1963, 1970, has rightly pointed out that Jenkins' review had only minimal effect on Darwin, earlier claims by historians notwithstanding. It is quite erroneous, in my opinion, to cite Jenkins' review as a brilliant and devastating criticism of Darwin. In fact, it contains more erroneous assumptions and misleading conclusions than the parts of the origin which it attacks. Particularly weak in his argument are his inappropriate analogies of biological processes with physical phenomena, as for instance the comparison of evolutionary change with the flight of a cannonball. To a modern reader, it is astonishing that such physical scientists as Houghton, Hopkins, and Jenkins thought that by applying the thinking of the physical sciences, they could cope with such extraordinarily complex phenomena, unparalleled in the inanimate world, as the evolution of biological systems. Hull, 1973. Reasons for the strength of resistance to selection. Considering how rapidly the theory of evolution was accepted by biologists, it is puzzling how reluctant they were to adopt natural selection. It was not until the evolutionary synthesis, see Chapter 12, of the 1930s that natural selection was accepted by the majority of the biologists as the exclusive direction-giving mechanism in evolution. And even then natural selection remains so alien a concept to philosophers and non-evolutionists that, to the present day, evolutionists have to make great efforts to demonstrate the efficacy of selection to non-evolutionists. The opposition, of course, was not total. Almost all oppo the causation of evolution, natural selection. Nance allowed for some selection but claimed that major evolutionary phenomena and processes could not be explained by it. Darwin himself, as we know, allowed for some non-selectional processes, such as the effect of use and disuse. Still, for him selection was by far the most important mechanism of evolutionary change. Most of his opponents considered its importance minor, if not negligible. What were the factors that contributed to the extraordinary strength of the anti-selectionist resistance? It seems that it cannot be ascribed to any one factor but that it was due to the great range of opposing arguments. No one has yet tabulated and analyzed all the objections that were raised, but the more important ones can be found in the writings of Kellogg, 1907, Delage and Goldschmidt, 1912, Plate, 1924, Hertwig, 1927, Tchelok, 1929, and various French authors such as Colly, Quinot, Vandal, and Gros. Arguments by philosophers were stated by Cassirer, 1950, and Popper, 1972. What follows is a partial listing of the major factors contributing to the resistance to natural selection. Threat to the argument from design. Explaining the perfection of adaptation by materialistic forces, selection removed God, so to speak, from his creation. It eliminated the principal arguments of natural theology, and it has been rightly said that natural theology as a viable concept died on November 24, 1859. This is what so outraged not only theologians but all those naturalists for whom natural theology was their basic Weltanschauung. For them the theory of natural selection was thoroughly immoral. This is what Sedgwick meant by his anguished outcry: the pretended physical philosophy of modern day strips man of all his moral attributes. By repudiating final causes, Sedgwick continued, Darwin's theory indicates a demoralizing understanding on the part of its advocates. What is it that gives us the sense of right and wrong? Of law? Of duty? Of cause and effect? Hull, 1973. God had given purpose to the world and the moral world order was part of his purpose. If you replace this purpose by the automatic process of natural selection, you not only remove the Creator from our concept of the world but you also destroy the foundation of morality. Sedgwick's outcry thus reveals that much more was involved than the refutation of Paley's concept of designed adaptation. This is made even clearer by K. E. von Bayer's 1876, Opposition to Darwin. Von Baer was a committed teleologist. The organic world. 516. Was not only Zweckenszeig, a term very popular with Kant meaning well adapted, but also Zielstrebig, goal directed. Owing to the existence of goal-directedness, so he claims, adaptation precedes the formation of new structures, while according to Darwin adaptation is the result of the formation of structures through natural selection, 1876, 332. For a teleologist, a trend toward greater perfection, to ever-increasing harmony, is inherent in nature. As Agassiz also stressed, indications of an underlying plan could be seen everywhere. Such a plan could be effected only through the existence of laws, and several such laws were proposed in the pre-Darwinian period, like Maclay's quinarianism as the basis of classification, or Edward Forbes' law of polarity to explain distribution, or Agassiz's threefold parallelism between ontogeny, fossil progression, and morphological progression, Bowler, 1977b. The acceptance of evolution made the problem of a well-ordered world particularly acute. If the world had been created in a single instant, or in 6 days, and had remained constant ever since, its harmony could be explained as the product of a well-conceived plan. The maintenance of order, however, became a serious problem in an evolving and continuously changing world. For the early evolutionists, the Nader Philosophin, Lamarck, and Chambers, it was axiomatic that evolution was an upward movement. From raw matter and the simplest organisms, infusoria, there was a steady progression, culminating in the evolution of man. The acceptance of cosmic teleology was thus a necessary corollary to the acceptance of evolution. Being able to explain a temporalized scala naturae was thus bought at the price of now having to explain final causes. In fact, so impressive was the image of progressive evolution that even after it had ceased to be a problem for those who accepted the theory of natural selection, it largely retained its credibility not only among a surprisingly large segment of the biological community but particularly among laypeople and theologians. The fight against cosmic teleology, necessity, was the principal object of Monod's Chance and Necessity, and the same objective has been explicit or implicit in the writings of all evolutionists who have dealt with so-called progressive evolution, for example, Simpson. Yet, to convince someone who is not familiar with the evolutionary mechanisms that the world is not predetermined and so to speak programmed seems hopelessly difficult. How can man, the porpoise, birds of paradise, or the honeybee have evolved through chance, is the standard question one receives surprisingly often even today. Does not the causation of evolution, natural selection, world without purpose also leave man without purpose, it is asked. The acceptance of natural selection thus seems to pose a serious metaphysical dilemma. 1-3 The situation in the 1860s and 1870s was aggravated by battles between liberals and conservatives among the theologians, with the liberals trying to accommodate Darwin's thought, and between church and state. For some evolutionists, none more so than Haeckel in Germany, the main significance of evolution and the refutation of all finalism was that this served as a pacemaker of materialism. As Weismann stated it, 1909, 4-5, the principle of selection solved the riddle, how it is possible to produce adaptedness with massykeit without the intervention of a goal-determining force. Hence natural selection not only eliminated the need for a designer but it also spelled the end of cosmic teleology, finalism. Eventually it became clear that the term teleological had been applied to a very heterogeneous medley of phenomena, some of which, but not cosmic teleology, are valid scientific processes, see Chapter 2. 1-4 Finalism died a slow death, even in evolutionary biology, and was revived by some post-Darwinian evolutionists under the concept of orthogenesis, or related concepts, see below. The publication of The Origin produced a decisive change in the relation between science, biology, and religion, particularly in England. Up to 1859 creationism, natural theology, creationist idealistic morphology, and other explanatory theories in which God played an important role were considered legitimate scientific theories. In the controversies, scientist opposed scientist. After 1859 religious arguments quickly disappeared from the statements of scientists, and, as Gillespie, 1951, has pointed out perceptively, the controversy became one between organized religion, churches, and scientists. The power of essentialism. Natural selection is meaningless to an essentialist, for it can never touch the underlying essence, it can only eliminate deviations from the type. For him, natural selection is by and large only a negative process, able to eliminate the unfit but unable to play a constructive role. Lyell specifically referred to the purely eliminative power of natural selection and postulated that it would require some truly creative natural forces to produce the highest plants, animals, and man. It has been claimed that natural selection, although rejected by vitalists, which indeed it was, by contrast, accepted by most mechanists. The facts do not substantiate this claim. Virtually all experimental biologists were mechanists, and yet until rather recently, that is, until the evolutionary synthesis, they rejected natural selection almost unanimously. Only those who had adopted population thinking accepted it. The embryologists, in particular, who were always working with a given individual organism and until recent times never studied populations, found it most difficult to understand natural selection. This is very evident 518 in the writings of T. H. Morgan and of E. B. Wilson, who, according to Muller, 1943, 35, as late as the 1930s was not yet quite ready to admit that higgledy-piggledy can provide an adequate explanation of organic adaptations. It is one of the paradoxes of the field that several well-known experimental biologists who were thoroughly familiar with selectionism nevertheless used essentialist arguments in their evolutionary analyses. This is true, for instance, for two such distinguished biologists as Waddington and Monod. It was characteristic of the arguments of the physicists and mathematicians attending the Worcester Conference, Moorhead and Kaplan, 1967. The ambiguity of the term selection. Darwin himself was never entirely happy with the term selection, many of his supporters disliked it, and his opponents criticized and ridiculed it. What he later called natural selection, Darwin called wedging on September 28, 1838, one may say there is a force like 100,000 wedges trying to force every kind of adapted structure into the gaps in the economy of nature, d. 135. He adopted the term selection in early 1840, when the analogy with the artificial selection of the breeders occurred to him. Osbovit, 1979. Limoges, 1970, 144 to 146, points out quite correctly that there was considerable doubt in the post-Darwinian literature about the nature of natural selection. Is it an agent, a process, or the result of a process? The greatest weakness of the term is that it implies someone who selects. Darwin's critics were quite outraged by his uninhibited personification of nature. Wherever the natural theologian might have invoked God, Darwin invokes nature. Nature cares nothing for appearances, except in so far as they may be useful to any being. She can act on every internal organ, on every shade of constitutional difference, on the whole machinery of life. Origin, 83. Natural selection is daily and hourly scrutin. The causation of evolution, natural selection. Ising, throughout the world, every variation, even the slightest, p. 84. Had not Darwin abolished the God of the Bible only to replace him by a new God, nature? Unhappiness among his friends about the term natural selection induced Darwin to adopt Spencer's metaphor survival of the fittest in the later editions of the Origin. This was rather unfortunate, because now the objection was raised that the entire theory of natural selection rested on a tautology: who survives? The fittest. Who are the fittest? Those that survive. Darwin, of course, never said anything of the sort. All he said was that among the countless variations that occur in every species, some that are useful in some way to each being in the great and complex battle of life should sometimes occur in the course of thousands of generations. Origin, 80, and that individuals having any advantage, however slight, over others, would have the best chance of surviving and of procreating their kind, p. 81. There is nothing circular in this statement. Williams, 1973b, and Mills and Beatty, 1979, have analyzed the logical basis of Darwin's argument and have likewise concluded that no tautology is involved, but see Kaplan, 1978. Repeated attempts were made in the ensuing years to find a better term than either natural selection or survival of the fittest, but none was successful. Darwin himself thought of natural preservation, but even that term fails to bring out the creative component of natural selection, which is due to the alternation between genetic recombination and reproductive success, an aspect of natural selection emphasized by Julian Huxley, Dobbs-Hansky, and other recent evolutionists. The modern generation of biologists has been so thoroughly habituated to the term natural selection that it no longer experiences the misgivings of the Darwinian period. Due to accident. Darwin's theory rejected uncompromisingly the existence of any finalistic factor in the causation of evolutionary change, and this strengthened the resistance of many to natural selection. Most of his contemporaries could see only a single alternative to teleological determination, this being accident. Indeed, until modern times many scientists and philosophers have rejected selection, saying that it was unthinkable that the marvelous harmony of organisms could all be due to accident. Those who raised this objection overlooked the fact that natural selection is a two-step 519 process. At the first step, the production of genetic variability, accident, indeed, reigns supreme. However, the ordering of genetic variability by selection at the second step is anything but a chance process. Nor is selection, as has sometimes been claimed, something that is intermediate between chance and necessity, but something entirely new that escapes the dilemma of a choice between these two principles. No one has stated this better than Sewell Wright, 1967, 117. The Darwinian process of continued interplay of a random and a selective process is not intermediate 520 between pure chance and pure determination, but in its consequences qualitatively utterly different from either. It is remarkable how generally it is overlooked that with natural selection Darwin had introduced an entirely new and revolutionary principle which is not at all vulnerable to the objection that his theory relies entirely on accident. Darwin himself apparently forgot this occasionally, since he confessed at one time that he was greatly bothered by the extreme difficulty or rather impossibility of conceiving this immense and wonderful universe as the result of blind chance or necessity, 1958, 92, as if these were the only two available options. Natural selection has been particularly puzzling to the physical scientists, because it is so different from physical theories and laws. It is neither strictly deterministic nor predictive but probabilistic with a strong stochastic element. Whether one likes or dislikes such an undisciplined process is irrelevant. The fact is that it occurs in nature and that it is of overwhelming importance for the fate of genotypes. Methodological objections to natural selection. Scientific objections to the theory of natural selection were not the only ones to be raised. It must be remembered that in the origin the principles and the methodology of evolutionary biology were presented to the world for the first time. Nearly all of Darwin's opponents were mathematicians, engineers, physicists, philosophers, theologians, or other kinds of scholars whose knowledge of biology was deplorably limited. Nevertheless, they felt that evolution was a subject of sufficient importance to justify anybody's participation in its discussion. Being unable to come up with scientific arguments, they resorted instead to the claim that Darwin had violated the canons of sound scientific methodology, Hull, 1973. They said that his work was speculative, hypothetical, inferential, and premature. They also criticized his conclusions on the causation of evolution, natural selection. The basis that they had not been reached by induction, which they claimed was the only sound scientific method. Furthermore, again and again, the theory of evolution was declared to be unacceptable because it was not based on experiment, as late as 1922 by Bateson. Comparative observational evidence was not scientific, it was said, it had to be experimental. These criticisms are all based on the assumption, now fully understood to be wrong, that phenomena and processes containing time-generated information must be studied by the same methods as purely functional processes. More broadly, it assumes that the methods that had been found useful in the physical sciences, with its very limited universe of phenomena, are fully sufficient for all sciences. The critics who accused Darwin of not following proper scientific methods and of not supplying ironclad proof did not realize that science in the mid-19th century was undergoing a methodological revolution. Darwin's consistent application of the hypothetico-deductive method, Gazellin, 1969, greatly helped to establish the respectability of this method and led to a revision of the criteria needed to establish the validity of a theory, see Chapter 2. It was Darwin more than anyone else who showed how greatly theory formation in biology differs in many respects from that of classical physics, Hull, 1973, Hodge, 1977, 1981. Historical narratives can only rarely, if at all, be tested by experiment. However, one can speculate about them, as Darwin would have said, that is, one can formulate hypotheses based on observations, which can then be tested by further observations. And this is what Darwin did incessantly. Darwin's speculating was a well-disciplined procedure which he used, as does every modern scientist, to give direction to the testing of further observations and, where feasible, to the planning of experiments. By far the most important departure in Darwin's methodology was that he demonstrated the legitimacy of why questions. Evolutionary causations can be analyzed only by asking why questions. Why is a leaf insect green, is not a search for final causes but for past, or current, selection pressures. Why are the animals of the Galapagos more closely related to the animals of South America than to those of other Pacific islands, again is a perfectly legitimate scientific question. The hypothetical answer that the fauna must have reached the islands by transoceanic colonization permitted all sorts of predictions, for instance that this fauna came most likely from the nearest source area, South America, or 521. That non-flying animals, unless they had special means of dispersal, would have much greater difficulties in reaching islands than flying animals. Indeed, terrestrial mammals are rare or absent from true islands, but bats reach most of them. By his new methodology Darwin transferred the whole realm of ultimate causations from theology to science. He was fully aware of what he was doing. For one set of phenomena after another, he asked, is this better explained by special creation or as the result of evolution by common descent? Gillespie, 1979. 522. Absence of proof. Even some of Darwin's most ardent supporters admitted that the theory of natural selection was based almost entirely on deductive reasoning. His opponents called this method pure speculation and demanded inductive or experimental proof. Almost the only thing Darwin could offer was analogy with artificial selection. But, as T.H. Huxley admitted, no animal breeder had ever succeeded in producing a new, reproducitively isolated species by selection. And the most aberrant races of dogs and pigeons were called pathological by Colliker, who quite rightly insisted that they would never be able to maintain themselves in nature. The discovery of mimicry by H. W. Bates, 1862, came as a godsend, and Darwin at once wrote a joyous and highly laudatory review of it. What Bates had observed was that each species or geographic race of the unpalatable, if not poisonous, heliconid butterflies was associated where it occurred with one or several species of edible butterflies which mimicked them in coloration, Batesian mimicry. But more than that. When a heliconid species varied geographically, and most of them do, often very strikingly, its mimicking satellites underwent exactly the same changes as their unpalatable models. Bates, 1862, 512, quite rightly concluded that this type of variation could only be due to natural selection, the selecting agents being insectivorous animals, which gradually destroy those sports or varieties that are not sufficiently like their models to deceive them. The geographical variation of the butterflies, some of it being very gradual, showed furthermore that the mimicry was not acquired by major saltations but gradually by natural selection. Later genetic analysis confirmed this conclusion. 1. Bates' work, a most brilliant piece of natural history research, was soon confirmed by other investigators. Wallace discovered a similar situation in Indomalayan papilionid butterflies and knew the causation of evolution, natural selection. Instances of various kinds of mimicry are discovered each year. The most important extension of the mimicry principle was due to Fritz Müller, 1879, who showed that mutual mimicry may also occur among unpalatable, poisonous, or venomous animals such as wasps and snakes, Müllerian mimicry. Since their potential predators apparently have to learn, at least in part, which color pattern to avoid, it pays for a guild of owners of warning coloration to adopt a single pattern in a given region. There is a selective advantage for any member of the guild to have this warning color pattern. Not surprisingly, in line with the demands of natural selection, all species belonging to a single Müllerian complex vary geographically in a parallel manner. Turner, 1977. Much research in evolutionary biology, particularly after 1930, has been devoted to the endeavor to establish the selective value of various attributes of plants and animals, see Chapter 12. Impossibility of falsification. According to Popper, only such theories are scientific that can be falsified. Several philosophers opposed to natural selection have stated that it is impossible to falsify any claims made on behalf of natural selection. Here one must make a distinction between the theory of natural selection as such and the application of natural selection to specific cases. As soon as one deals with specific cases, one can make predictions that can be falsified in principle, by testing them against various assumptions. It is, of course, also true that the exclusive reliance on falsifiability is questioned by several contemporary philosophers. Finally, since few if any neo-Darwinians claim that every component of the phenotype and every evolutionary change is the result of ad hoc selection, the non-falsifiability argument has not much force. Ideological resistance. Inevitably, the concept of natural selection was eventually applied to man. This resulted in various excesses, such as racism, but also in the counter-claim that an assumption of genetic differences of selective significance in man was in conflict with the principle of equality. Extreme egalitarianism led to the development of strongly environmentalist schools, particularly in American anthropology and in behaviorist psychology. As noble as these movements were in their basic ideology, and perhaps as necessary as they were to combat racism and social prejudice, the major claims of these schools were not substantiated by any concrete evidence. 523. But were based on an unbiological concept of equality. The situation was made worse when Lysenkoism raised its ugly head in the USSR and when certain Marxist groups in the Western countries decided to attack genetics and to promote environmentalism. Some of the attacks against sociobiology in recent years originated from the same ideology. Linking Darwin's name with Herbert Spencer's social Darwinism was also detrimental for the acceptability of natural selection. Freeman, 1974, Nichols, 1974, Hertwig, 1921, Green, 1977, Bannister, 1979. 524. Empirical objections. The students of diversity raised some observational objections to natural selection. On the basis of the survival of superior individuals and the gradual change of populations, one would expect complete continuity in nature, they claimed. What one actually found was nothing but discontinuities. All species are separated from each other by bridgeless gaps, intermediates between species are not observed. How could the sterility barrier between species have possibly evolved by gradual selection? The problem was even more serious at the level of the higher categories. Higher taxa, like birds and mammals, or beetles and butterflies, are far too distinct from each other, the skeptics said, to permit the explanation of their origin through gradual evolution by natural selection. Furthermore, How can selection explain the origin of new structures like wings, when the incipient new organs can have no selective value until they are large enough to be fully functional? Finally, what is the role of the very small differences among the individuals of a population, seen in all gradual evolution, including geographic variation, when, it was said, the differences are far too small to be of selective significance? The defenders of gradual evolution had to be able to refute these objections and had to provide evidence in favor of a rather formidable list of prerequisites of their theory. 1. Availability of an inexhaustible supply of individual variation. 2. Heritability of individual variation. 3. A selective advantage of even the slightest variation to be of evolutionary significance. 4. No limits in the response to selection. 5. An explanation by gradual variation of major evolutionary novelties and the origin of higher taxa. The causation of evolution, natural selection. Neither Darwin nor his supporters were at first able to supply this evidence. As a result, the traditional objections were raised again and again, up to recent times, most forcefully by Schindewolf, 1936, Goldschmidt, 1940, and some French zoologists, Bozeiger, 1980. It was not until the period of the new systematics that Ernst, Mayr, and others demonstrated the populational origin of the discontinuities, Mayr, 1942, 1963, and that the geneticists supplied the evidence on the variation needed to permit natural selection to be effective. Alternate evolutionary theories. The acceptance of the theory of evolution created a dilemma for all those who rejected Darwin's explanatory principle of natural selection. What else could be the factor, or factors, controlling evolution if it was not natural selection? Many alternate explanations were proposed in the 80 years after 1859 and were in fact far more popular during that period than natural selection. In order not to misrepresent the climate of opinion, let me emphasize that natural selection was not totally condemned. Many biologists admitted, of course, natural selection occurs, but it cannot be the exclusive causal factor in evolution because too many evolutionary phenomena cannot be explained by it. One must therefore remember that the mere acceptance of a certain amount of selection did not make an author a Darwinian if he simultaneously accepted the existence of other controlling factors in evolution. The three theses of Darwin and the neo-Darwinians that were found to be particularly unacceptable by the anti-Darwinians were gradualism, the rejection of soft inheritance, and the rejection of holism, teleology. One can classify, therefore, the various anti-Darwinian theories according to which of these three components of Darwin's theory they opposed specifically. They will therefore be discussed under these three headings: 1. Saltationist theories, 2. Neo-Lamarckian theories, and 3. Orthogenetic theories, Kellogg, 1907, Mayr and Provini, 1980. Saltationist theories. Early theories that opposed Darwin's gradualism, his, Kadaliker, and others, have already been discussed, see above. They had relatively few followers in the 1860s to 1880s. After 1894, saltationist theories gained rapidly in popularity and were dominant. 525. 526. Early in the century under the name mutationism. The role of these theories in the 20th century controversies will be discussed in Chapter 12. Neo-Lamarckian theories. The most determined and most successful opposition to Darwinism was posed by theories usually combined under the name Neo-Lamarckism. 1/6. The paradoxical aspect of this designation is that the most fundamental component of Lamarck's theory that there is a finalistic element in evolution leading phyletic lines of organisms to ever greater perfection was not the principal thesis of Neo-Lamarckism. Admittedly, however, Neo-Lamarckism shared with Lamarck two major concepts: that evolution is vertical evolution, consisting in an improvement of adaptation, neglecting or disregarding altogether the origin of diversity, and second, that acquired characteristics of an individual can be inherited, soft inheritance. Neo-Lamarckism, thus, can be considered as much a theory of inheritance as a theory of evolution, and a discussion of soft inheritance is therefore included in Chapter 16. The idea that the environment exerts a decisive influence on the characteristics of an organism goes back to ancient folklore. The idea was exceedingly popular among philosophers, particularly in the period preceding and during the Enlightenment, Locke, Condillac. Among English writers, David Hartley, 1749, is a good example of an extreme environmentalist. That changes in the conditions of life greatly contribute to the variation of the type was accepted by Buffon, Linnaeus, Blumenbach, and Lamarck, all of whom also accepted to a greater or lesser degree that such acquired characters could be inherited. Blumenbach, for instance, believed that the dark-skinned human races had been derived from light-skinned races by the action of the strong sunlight in the tropics on man's liver. Darwin was no exception, see Chapter 16. He always believed in some effect of use and disuse and its inheritance, and he adopted the theory of pangenesis to account for it. However, he attributed to it only a minor role in evolution, as compared to selection. Neo-Lamarckism covers an exceedingly heterogeneous group of ideas. No two Neo-Lamarckians had quite the same views, but it would lead too far to describe their various theories in detail. One of them, designated as Geoffroyism, ascribes evolutionary change to the direct influence of the environment. Even though the causation of evolution, natural selection. Lamarck had expressly rejected the occurrence of such direct induction. Those who, late in the 19th century, believed in such a process were included among the Neo-Lamarckians. Many naturalists believed in it as a process coexisting with natural selection. They argued, for instance, that gradual geographic variation could not be explained except through environmental induction. Geoffroyism had many followers, particularly in the early decades of the 20th century, as an opposition party to mutationism with its reliance on discontinuous saltations as the only source of evolutionary change. Environmental induction seemed to be the only way to account for gradual variation as it was everywhere observed by naturalists. Concepts related to use and disuse, combined with an inheritance of acquired characters, were prominent among the Neo-Lamarckians' theories. This is true for Cope's law of growth and effort. An organ that had become more useful in a new environmental situation would have its growth enhanced in each generation and thus become ever better adapted to its environment. This is, of course, very similar to some of Lamarck's ideas. The suggested mechanism for such a process was that the germ cells carry a record of the past efforts of the growth force in a manner analogous to memory. Bowler, 1977a, 260. Here Cope had a mechanism that would produce adaptation naturally without recourse to design or supernatural forces. Most American evolutionists prior to 1900 were Neo-Lamarckians. Many Neo-Lamarckian theories invoke mental forces. This started with Lamarck's own efforts to satisfy needs, erroneously interpreted as willing to produce new structures. Consciousness is mentioned by Cope and other Neo-Lamarckians, and reaches its climax in Polypsycho-Lamarckism, which had a considerable influence on Bovary and Speymann, Hamburger, 1980. What characterized all Neo-Lamarckian theories was the postulate that something experienced by one generation could be transmitted to the next generation and become part of its heritage. Consequently, all Neo-Lamarckians supported the inheritance of acquired characters. As long as the nature of the genetic material was unknown, Neo-Lamarckism explained adaptation far better than the haphazardous process of random variation and selection. As soon as many mutations and recombination were recognized as the genetic material of evolution and the assumption of soft inheritance had been refuted, the conversion of the younger Neo-Lamarckians to Darwinism took place quite rapidly. 527. Orthogenetic theories. The third set of anti-Darwinian theories, likewise originating in remote history, is based on the concept that somehow evolution is due to a holistic component. 17 Although the scala naturae was static and although the author of Genesis was not at all thinking of evolution when he had God create man on the sixth day of creation, a necessary sequence from lower to higher is nevertheless implicit in both cases. Indeed, the assumption of some sort of cosmic teleology was very widespread among philosophers and in many religions. Erasmus Darwin considered the faculty of continuing to improve as one of the basic properties of life itself. Would it be too bold to imagine, that in the great length of time, since the earth began to exist, perhaps millions of ages before the commencement of the history of mankind, would it be too bold to imagine, that all warm-blooded animals have arisen from one living filament, which the first great cause endued with animality, with the power of acquiring new parts, attended with new propensities, directed by irritations, sensations, volitions, and associations, and thus possessing the faculty of continuing to improve by its own inherent activity, and of delivering down those improvements by generation to its posterity, world without end. 1796, I. 509. For Lamarck, evolution was clearly a movement to ever greater perfection, and the progressionists among the geologists also saw an upward trend in the creation of each new fauna and flora, a trend that would keep organic life perfectly adapted to the changing conditions of the earthly environment. Agassiz, 1857, Bowler, 1974b. It is immaterial whether the presumed mechanism was a set of laws that would automatically guarantee perfect adaptation or the constant immediate attention of the creator, the end product was the same, an inexorable movement toward perfection. Teleological thinking was extremely widespread in the first half of the 19th century. For Agassiz and other progressionists, the sequence of fossil faunas simply reflected the maturation of the plan of creation in the mind of the creator. Theistic as well as deistic philosophers needed to uphold the universal operation of final causes in nature, since it was one of the most important, if not the only piece of evidence for the existence of a creator. Theists like Sedgwick and K. E. von Baer saw purpose everywhere in nature. In a review of Darwin's Origin, von Baer, The Causation of Evolution, Natural Selection, wrote, "My goal is to defend teleology because natural forces must be coordinated or directed. Forces which are not directed, so-called blind forces, can never produce order. If the higher forms of animal life stand in a causal relationship to the lower, developing out of them, then how can we deny that nature has purposes or goals?" Louis Agassiz, likewise, sarcastically rejected the efficacy of blind forces. Even Darwin had originally accepted finalism, hence his remarkable statement, Notebook B, p. 169, "If all men were dead, then monkey make men, man makes angels." As Herbert, 1977, 199, 200, points out, the study of geographic variation soon made Darwin give up any orthogenetic notions. Comparing vicarious species, he found no evidence for necessary, built-in progressive trends. And after he had adopted natural selection, he had no longer any need for a finalistic principle. Among the numerous defenders of a finalistic principle in evolution, Nageli, 1865, 1884, and Mayr, 1888, developed the most elaborate theories. These were based either on the assumption that a perfecting principle is immanent in all organic life, or else that the genetic constitution places a constraint on all organisms in such a manner that evolution can proceed only in a more or less rectilinear direction. Mayr, adopting a term first proposed by Haeckel, called the perfecting principle orthogenesis. Other biologists and philosophers coined different names for essentially the same postulated force in evolution: Berg, nomogenesis; Henry Fairfield Osborn, Aristogenesis; and Teilhard de Chardin, the omega principle. A belief in some sort of intrinsic, direction-giving force was particularly widespread among paleontologists, who everywhere saw evidence for evolutionary trends, extending over millions, if not tens or hundreds of millions, of years. The thesis, widespread among anthropologists, that human evolution goes by necessity through a definite series of stages likewise belongs here. White, 1959. When it came to explaining the causation of the orthogenetic principle, there was much vagueness and uncertainty among its defenders. Some of them saw in evolution simply the unfolding of the potential of a basically unchanging essence, evolution in the most literal sense. It was, one might say, an application of the principle of preformation, in embryology, to evolution. This was essentially Louis Agassiz' thinking, and it was endorsed as recently as 1914 by the geneticist Bateson. Others referred to mysterious laws which cause orthogenetic evolution, evolution of organisms. 529. Is the result of certain processes inherent in them, which are based upon law. Purposive structure and action are thus a fundamental property of the living being. Berg, 1926, 8, a statement which, of course, explains nothing. Mayr attempted to get away from an immanent teleological principle by suggesting that the environment directed variation, but the adequate response of the organism still rested on an immanent teleological capacity. The Darwinians rejected any internal direction-giving mechanism or purposive principle for a number of reasons. First, because 530 the defenders of orthogenesis were quite unable to provide any reasonable mechanism consistent with a chemico-physical explanation. Second, because a detailed study of such trends invariably revealed numerous irregularities and sometimes even complete reversals. Simpson, 1953. Finally, because when evolutionary lines split, the daughter lines may have very different trends, an occasional one even reversing the previous trend. Again, this is incompatible with an integral mechanism. The observation that larval and adult stages of metamorphosing insects and marine organisms often display entirely different trends was rightly cited by Weismann and Fritz Müller as a further argument against orthogenesis. In due time all theories defending orthogenesis were refuted, but this does not justify ignoring this literature. The major representatives of orthogenesis, whether paleontologists or other kinds of naturalists, were keen observers and brought together fascinating evidence for evolutionary trends and for genetic constraints during evolution. They were right in insisting that much of evolution is, at least superficially, rectilinear. In horses, the reduction of the toe bones and the changes in the teeth are well-known examples. In fact, the study of almost any extended fossil series reveals instances of evolutionary trends. Such trends are of importance to the evolutionist because they reveal the existence of continuities that are worth exploring, and have therefore been given much attention in the current evolutionary literature. Trends may have a dual causation. On the one hand, they may be caused by consistent changes of the environment, such as the increasing aridity of the subtropical and temperate zone climate during the Tertiary. This set up a continuing selection pressure which resulted in the toe and tooth evolution of the horses. A response to such a continuing selection pressure is what Plate had in mind when he introduced the term orthoselection, 1903. On the other hand, trends may be necessitated by the internal. The causation of evolution, natural selection. Cohesion of the genotype which places severe constraints on the morphological changes that are possible. 1-8 Hence, evolutionary trends are readily explained within the explanatory framework of the Darwinian theory and do not require any separate laws or principles. Evolutionary progression, regularities, and laws. The Darwinians had considerable difficulty in making it clear to their opponents that to deny the existence of an internal perfecting principle did not mean a denial of observed evolutionary progression. Denial of a progression from the infusorians to the angiosperms and vertebrates might well imply a rejection of evolution altogether. Darwin, fully aware of the unpredictable and opportunistic aspects of evolution, merely denied the existence of a law-like progression from less perfect to more perfect. It was in this spirit that he once reminded himself never to say higher or lower. Of course, Darwin did not follow his own advice and referred in The Origin frequently to evolutionary progress, pages 149, 336, 338, 388, 406, 441, and 489. This was necessary not only to refute Lyell's concept of a steady-state world but also to counter a newly developed school which denied any difference in perfection between the simplest and the most complex organisms. Ehrenberg, for instance, claimed that there is no structural advance from the lowest organisms, the infusorians, to the highest, the vertebrates. All of them have the necessary structures to perform all animal functions. All are perfect. This curious claim completely ignored the fact that there is a tremendous advance from the diffuse nerve fiber of a coelenterate to the magnificently evolved central nervous system of a cetacean or primate. Ehrenberg's claim, of course, had strong anti-evolutionary implications. Lyell likewise tended to deny any aspect of progression in the sequence of faunas from the lowest fossiliferous beds to the present, with the single exception of the recency of man. Obviously these claims constituted an implicit denial of improvement through natural selection. Darwin realized that naturalists have not as yet defined to each other's satisfaction what is meant by high and low forms, and yet, he continues, the most recent forms must, on my theory, be higher than the more ancient, for each new species is 531. 532. Formed by having had some advantage in the struggle for life over other and preceding forms, origin, 337. Indeed, the series of morphological and physiological innovations that have occurred in the course of evolution can hardly be described as anything but progress. I think of such phenomena as photosynthesis, eukaryote, organization of the nucleus, multicellularity, metazoans, metaphytes, diploidy, homoeothermy, predation, and parental care, to mention only a few of such evolutionary innovations made in the 3 billion years since the origin of the first prokaryotes. On almost any measure one can think of, a squid, a social bee, or a primate, is more progressive than a prokaryote. Yet, the word progressive implies a linearity which one does not find. Nor does one find only a single sequence, since there is progressive evolution in plants, in arthropods, in fishes, in mammals, indeed in almost any group of organisms, each lineage displaying a very different expression of progress. A careful analysis of everything Darwin wrote on evolutionary progress shows that he did not contradict himself. What he objected to was finalism, that is, a belief in an intrinsic drive to perfection, controlled by natural laws. Where Darwin encounters improvements in the course of evolution, he finds that they can be easily explained as the a posteriori results of variation and natural selection. Evolutionary progress, where it occurs, is not a teleological process, a conclusion in which all evolutionary biologists agree with Darwin. The main objection raised by the anti-Darwinians has always been that the living world is full of progressive trends, but that it is inconceivable they should be caused by random variation and natural selection. The Darwinian answers, why not? After all, any improvement, any new structural, physiological, or behavioral invention made in any gene pool can lead to evolutionary success and thus to progress as it is traditionally defined. This Darwin had already seen quite clearly. A far more intransigent problem has always been how to define progress. Here no two authors agree. Complexity is certainly not necessarily a measure of progress, for in many evolutionary lines the oldest members are the most complex, and progress has consisted in simplification. Almost no one has been able to sidestep entirely Lamarck's measure of progress, a comparison with man. When Julian Huxley, 1942, makes control of the environment a measure of progress, there is no doubt that this sets man on a pinnacle well above any other organism, even though the causation of evolution, natural selection. Mites, bees, and some other organisms have been reasonably successful in controlling their environment. Independence of the environment is perhaps a better measure, another good one being the capacity of the nervous system to store and utilize information. Open behavior programs must surely be considered as more progressive than rigidly closed ones. In spite of all these manifestations of evolutionary advances, Darwinians, on the whole, have been rather reluctant to talk of evolutionary progress. They seem to be afraid that this might be interpreted as an endorsement of the existence of teleological factors. Also, there seems to be an intellectual contradiction between the spirit of progress and the materialistic means, struggle for existence, by which it is achieved. Finally, the staggering frequency of extinction adds to the questionable value of any temporary progress seemingly achieved by any evolutionary line. When all these difficulties are kept in mind, it becomes apparent why the definition of evolutionary progress is so difficult, if not impossible. 19 Not all, and perhaps only the smallest amount, of evolution consists of progress. Much of the genetic change caused by natural selection simply serves to maintain a status quo. In order to keep step with the evolutionary, genetic, changes of one's competitors, enemies, sources of food, and even of the physical environment, a population must change from generation to generation. This is what Van Vallen, 1973, has referred to as the Red Queen principle: one must run in order to be able to stay at one's place. More importantly, any gain in fitness by one unit of evolution is balanced by losses in fitness by others. This is true at various levels. Macromolecules, for instance, regularly replace amino acid residues in order to maintain an optimal interaction with their molecular milieu. When an organism, population or species, falls behind in its race for maintaining the optimal balance, it faces extinction. In many cases, success simply consists in becoming different or more different, thus reducing competition. Darwin, Origin, 111, saw this clearly when he proposed the principle of character divergence. It promotes continuous change, but not necessarily progress. Indeed, it has induced endless phyletic lineages to enter evolutionary dead-end streets. A denial of evolutionary progress does not necessarily mean that the process of evolution is chaotic. That it is not has been stressed by a number of authors who have recognized evolution. 535. 534. Airy laws, for example, Wrench, 1960. One particular regularity, the one which relates ontogeny to phylogeny, has been considered by numerous authors from Haeckel, 1866, and Severtsov, 1931, to living authors. This subject is a terminological and conceptual jungle into which Gould, 1977, has brought some light and order. Two trends are encountered most frequently: 1, an addition of new characters late in ontogeny, and 2, a shift in the maturation of the gonads, with the result that the organism either reproduces in an immature or larval stage, neoteny, or that it postpones adulthood, retardation. Obviously, these various life history strategies are selected for the greater reproductive success which these shifts in maturation guarantee. Although these processes are particularly important in plants, Stebbins, 1974, 1979, and invertebrates, man has often been described as a fetalized ape, Boak, 1915. There are, however, several ways by which the changes of human life history, as compared to that of apes, can be described, and no consensus has yet been achieved. Stark, 1962. Any shift in the adaptive zone which an organism occupies will initiate new evolutionary trends. For instance, there are well-known trends in the restructuring of cave animals and of parasites. In plants there are trends leading from trees to perennial herbs and to annuals. There are trends involving modes of reproduction and the nature of the karyotype. All this demonstrates that the mere fact that variability as such is indirect does not preclude the possibility that natural selection converts such variability into more or less regular trends. New trends may originate when organisms invade new adaptive zones or when the environment undergoes a change, including the occurrence of new predators or new competitors. Each new level of complexity in organic systems favors the beginning of new trends. Huxley, 1942, Stebbins, 1969, 1974. 20. 12. Diversity and synthesis of evolutionary thought. The diversity of opinion among evolutionists in the 80 years following the publication of The Origin of Species is quite extraordinary. Each branch of biology had its own tradition, and so did each country. Germany embraced evolutionism quickly and rather completely, LLD, 3, 88. Ernst Haeckel, Germany's most enthusiastic evolutionist, both helped and hindered the spread of Darwinian thinking. He did a very effective job of popularizing Darwinism, but used it at the same time as a weapon against all forms of supernaturalism, particularly Christianity, thereby provoking counterattacks in which evolutionism was equated with materialism and immorality. This could not prevent the spread of evolutionary thinking as such, but it was an important factor in the almost universal rejection in Germany of the theory of natural selection. One evolution by descent with modification was rather generally adopted also in England within the decade after the publication of The Origin, at least by the biological community. Natural selection, by contrast, was largely found unpalatable. It was accepted only by a few naturalists, Wallace, Bates, Hooker, and some of their friends, and later by Poulton, Meldela, and other entomologists, but not by a single experimental biologist. Two of decisive importance for subsequent developments in Britain was the fact that Ray Lankester was converted to selectionism by reading some of Weismann's essays. He enthusiastically supported the invitation issued to Weismann to give lectures in England. It was Ray Lankester who founded a school of selectionism at Oxford, represented through several generations by E. S. Goodrich, Julian Huxley, G. de Beer, and E. B. Ford. There was nothing like it at Cambridge or at University College, London, until R. A. Fisher and J. B. S. Haldane began to publish. In the United States, in spite of Asa Gray's enthusiastic support, evolutionism had a much harder time. There being only a small professional class of biologists and paleontologists, much of 535. 536. The controversy was conducted by writers, theologians, and philosophers. Still, with the death of Agassiz in 1873 and the acceptance of evolution by Dana in 1874, all resistance to evolution ended among the professionals. 3. The theory of natural selection, by contrast, encountered continuing resistance. The situation was complicated by the temporary popularity of Spencer's so-called social Darwinism. 4. Partly as a reaction to it and partly as a result of traditional American egalitarianism, an extreme environmentalism developed in psychology and anthropology which minimized, if not denied altogether, any genetic contribution to the differences among human individuals. Up to a point this tradition is alive even at the present day. It is evident that, except for details of chronology, the history of the acceptance of Darwin was essentially the same in Germany, Britain, and the United States. Evolution was accepted quickly but natural selection at first by only a minority. In France the resistance to Darwin was much greater than in any other major Western country. Not a single leading French biologist came out in favor of selection after 1859, and even evolutionism as such did not begin to spread until the 1870s. 5. The first chair of evolutionary biology at the Sorbonne was created for Jard in 1888. When evolution was finally adopted in France in the 1880s and 90s, it was in the form of neo-Lamarckism, which at the same period enjoyed considerable popularity also in the United States and in Germany. Although natural selection was temporarily supported by an occasional author and was adopted by T. Sear and L. Haratir in the 1930s, its more general acceptance did not take place in France until after 1945, Bose-Iger, 1980. Paradoxically, considering the subsequent success of Lysenko, in the period up to the end of the 1920s there was probably no other country in which Darwinism, including the theory of natural selection, was as widely accepted as in Russia. Originally this was primarily for political reasons, but in part it was also due to the flourishing condition of population systematics in Russia. Adams, 1968. The impact of this situation on the further development of population genetics will be discussed below. Diversity and synthesis of evolutionary thought. Neo-Darwinism. As is described in Chapter 16, Darwin, although largely a champion of hard inheritance, still allowed some scope for the effects of use and disuse and other aspects of soft inheritance. As the knowledge of cytology and particularly that of chromosomes grew, several authors began to question any inheritance of acquired characters. These doubts were expressed rather casually and did not receive much notice. The rejection of soft inheritance made no real headway until Weismann, in 1883 and 1884, published his germ tract theory and proposed a complete and permanent separation of soma and germ plasm. The total rejection of any inheritance of acquired characters meant a rejection of all so-called Lamarckian, Geoffroyian, or Neo-Lamarckian theories of evolution. In fact, it left only two conceivable mechanisms of evolution: saltation, evolution owing to sudden, major departures from the existing norm, and selection among minor variants. Weismann adopted an uncompromising selectionism, a theory of evolution designated by Romanes, 1896, as Neo-Darwinism. It may be defined as the Darwinian theory of evolution without recourse to any kind of soft inheritance. Indeed, Weismann accepted most other components of Darwin's theory except pangenesis, now no longer needed. The elimination of soft inheritance, which up to that time had been considered a major source of individual variability, obliges the evolutionist, said Weismann, to look for a new source of the phenomenon, upon which the processes of selection entirely depend. His knowledge of cytology permitted him to name the particular phenomenon most likely to supply the needed genetic variability. It was the process now called crossing ovi. If such a rebuilding of chromosomes during gamete formation, meiosis, did not exist, genetic variation, except for occasional new mutations, would be limited to a resortment of the parental chromosomes. By contrast, chromosomal recombination has the consequence that no individual of the second generation can be identical with any other. In every generation combinations will appear which have never existed before and which can never exist again. No one before Weismann had understood the extraordinary power of sexual recombination to generate genetic variability. 537. The importance of recombination in evolution was at first rather neglected in the genetic literature which, written in terms of beanbag genetics, see Chapter 13, presented evolution by the formula mutation and selection. Actually, the genotypes which are the target of selection are the immediate product of recombination rather than of mutation. It was not until the work of C. D. Darlington, 1932, 1939, 7 and Stebbins, 1950, Chapter 5, that the evolutionary significance of systems of recombination, genetic systems, was fully appreciated. Much has been written about Weismann's genetical and cytological theories, but the development of Weismann's ideas on evolution has been rather neglected by historians. Until such an analysis has been made, only a few tentative statements can be offered. In 1872 Weismann entered into the controversy between Moritz Wagner and Darwin on the role of geographic isolation and displayed a rather remarkable lack of understanding of the problem. Certain comments made later in the 1870s indicate that Weismann at that time still believed in soft inheritance. It was not until 1883 that he categorically rejected soft inheritance, and in the next few years he emphasized the role of recombination amphimixis. It was in these years that he developed the theory, until quite recently almost universally adopted, that the selective advantage of sex is its capacity to multiply genetic variability at a high rate, and thus provide more abundant material for selection. Weismann was the first to ask questions about the regulation of the lifespan, age at time of death, by natural selection, see also Korschelt, 1922. More broadly, he introduced an entirely new way of looking for the meaning, that is, the selective value, of every aspect, morphological or otherwise, of organisms. Everything in the living world was for him the product of the Allmachter Nederzechtung, power of natural selection. After Weismann had passed the age of 60, however, he began to become somewhat uncertain about the ability of selection to control evolutionary trends unaided, and he proposed the principle of germinal selection, admitting the improbability that the adaptations necessary for the existence of organisms could originate by accidental variations. He postulated therefore the occurrence of directed variation, which is caused and guided by the conditions of life of the organisms, 1896, 4. Weismann categorically rejected any inner, orthogenetic, drives, and postu diversity and synthesis of evolutionary thought. Lated instead that the selection of certain characters, let us say longer tail feathers in a bird, favors simultaneously those genotypes that have a tendency to vary the length of the tail feathers. What Weismann did was to make a distinction between a given genetic variant and the capacity of the organism to produce variants of the given character, and to point out that both can be selected for. His thinking was ambivalent, however, and he conceded that the extraordinary similarity of model and mimic in certain butterflies cannot be due to accidental, but must be due to directed variation which is caused by the utility itself. 1896, 45. Weismann now admits that the Lamarckians were iiite, when they insisted that what up to now one has exclusively admitted as selection, i.e. the selection of individuals, was not sufficient to explain all phenomena. 1896, 59. Random variation, ordered by selection, was thus no longer considered by Weismann as sufficient. The evolutionary phenomena that troubled Weismann, such as similar trends of variation in many species of the same genus, or the gradual reduction of useless or rudimentary organs, such as the loss of eyes in cave animals, no longer pose serious problems to the evolutionary geneticist of today. The harmonious integration of the genotype places definite constraints on possible genetic variation, and this, as well as selection for or against certain regulatory genes, can account for all observed orthogenetic trends. These constraints and regulations are the modern equivalent of Weismann's germinal selection. Weismann's impact on evolutionary biology was FAI leaching. He forced every biologist to take a position on the problem of the inheritance of acquired characters. By insisting that there is only one direction giving force in evolution, selection, even if slightly watered down by his belated theory of germinal selection, he forced his opponents to produce evidence supporting their opposing theories. For the next 50 years most evolutionary controversies dealt with the problems which Weismann had posed with such uncompromising clarity. Furthermore, by his imaginative genetic theories he prepared the ground for the rediscovery of Mendel, an event which ultimately led to the solution of the evolutionary problems that had stumped Weismann. 539. 540. The growing split among the evolutionists. The evolutionists presented a rather solid front as long as they still had to convince the world of the fact of evolution. This was largely true until about 1882, the year of Darwin's death. In the next 20 years, however, more and more events took place which sowed seeds of dissension among them. The first of these was Weismann's uncompromising rejection of any inheritance of acquired characters. The reaction which this provoked was a hardening of the claims of the Neo-Lamarckians. Far more important, although this was probably not fully recognized at the time, was the growing disciplinary radiation of biology. The rise of evolutionism after 1859 coincided with an increasing breakup of zoology and botany into special fields, such as embryology, cytology, genetics, behavioral biology, ecology, and others. Many of these new disciplines of biology were primarily experimental in their approach, and this resulted in the development of an ever-widening gap between the experimental biologists on one hand and those others, mostly zoologists, botanists, and paleontologists, who had been raised as naturalists and worked with whole organisms. The experimentalists and the naturalists not only differed in their methods but tended also to ask different questions. Both groups were interested in evolution, but had very different approaches and stressed different aspects of evolution. The experimental evolutionists, most of them originally embryologists, entered the newly developing field of genetics. Their interest was the study of proximate causations, with particular emphasis on the behavior of genetic factors and their origin. Bateson, De Vries, Johansen, and Morgan were typical representatives of this camp. Several of them had a strong interest or background in the physical sciences and in mathematics. The naturalists, by contrast, were interested in ultimate causations, they tended to study evolutionary phenomena in nature and were particularly concerned with problems of diversity. Paleontologists, taxonomists, naturalists, and geneticists spoke different languages and found it increasingly difficult to communicate with one another. The naturalists, from the beginning, were particularly fascinated by diversity, its origin and meaning. The species problem was at the center of interest for the taxonomists, whereas evolutionary trends and the origin of the higher taxa intrigued the diversity and synthesis of evolutionary thought. Paleontologists and comparative anatomists. By contrast, diversity was almost totally excluded from evolutionary discussions of the pre-synthesis geneticists. They were only concerned with transformational evolution. Their focus was entirely on genes and characters, and on their changes, transformation, in time. They wrote as if they were unaware that there are taxa, and that they, different populations, species, and so on, are the real actors on the evolutionary stage. Even a phenomenon like adaptive radiation, as Eldridge says correctly, 1979, 7, is viewed as a problem of divergent anatomical specializations among a series of related organisms, rather than as a spectrum of discrete species occupying a diverse array of ecological niches. The emphasis was on transformation, not on diversity. It was this total neglect of diversity, or at best its deus ex machina explanation by de Vries mutations or Goldschmidt's hopeful monsters, which left the naturalists completely dissatisfied. The disagreement affected almost any aspect of the interpretation of evolution. The three questions that were disputed particularly heatedly were, 1. Whether all inheritance is hard, as wise men believed, or whether some is soft, 2. Whether mutation, selection, induction by the environment, or intrinsic tendencies are the principal direction-giving factors in evolution, and, 3. Whether evolution is gradual or saltational. Kellogg, 1907, has well described how many different combinations of opposing interpretations were held by different evolutionists. The disagreement was polarized by the rediscovery of Mendel's rules in 1900, which induced the early Mendelians to use the particulateness, discontinuity, of the genetic factors as evidence for the importance of saltational processes in evolution, particularly in the origin of species. From that date on, one could speak of two camps of evolutionists, the Mendelians and the naturalists, Mayr and Provini, 1980. 8. The interpretation of evolution by either camp was an unfortunate mixture of valid ideas and of misconceptions. The naturalists had erroneous ideas on the nature of inheritance and of variation, while the experimental geneticists, dominated by typological thinking, ignored the existence of populations, and concerned themselves with the frequency of genes in closed gene pools. They ignored the problems of the multiplication of species, of the origin of higher taxa, and of the origin of evolutionary novelties. Both camps were quite unable to understand and therefore to refute effectively the arguments of their opponents. 541. 542. The two camps also represented different research traditions. The naturalists very much continued in the original Darwinian tradition of studying natural populations and paying particular attention to the problem of the origin of diversity. Most importantly, they continued Darwin's tradition of asking questions about ultimate causation. Any question concerning the why of an adaptation or of any other biological phenomenon was answered prior to Darwin with, it is due to design, or it is the result of natural law laid down by the Creator. Both answers excluded the given phenomenon, for all practical purposes, from scientific analysis. Darwin's theory of natural selection provided the first rational approach to the study of ultimate causes, and such causes were the foremost interest of the naturalists. The experimental geneticists, by contrast, had derived much of their methodology and thinking from the physical sciences. They were convinced that their methods were more objective, more scientific, and hence superior to the speculative approach of the evolutionary naturalists. T. H. Morgan, 1932, for instance, was convinced that only the experimental method would permit an objective discussion of the theory of evolution, in striking contrast to the older speculative method of treating evolution as a problem of history. The inability to understand the arguments of the opponents was aggravated by the fact that experimentalists and naturalists dealt, on the whole, with different levels in the hierarchy of natural phenomena. The geneticists dealt with genes while the naturalists dealt with populations, species, and higher taxa. It is only in rather recent years that the difficulty of transferring the findings and conclusions of one hierarchical level to another one, particularly to a higher one, has been fully recognized. Patty, 1973. Furthermore, the geneticists, on the whole, worked with the one-dimensional system of a single gene pool, while there were multidimensional components of geographical space and time in the considerations of the naturalists. The issue, however, which separated the two camps most decisively was whether evolution was gradual or saltational. Gradual evolution or saltations. Any group of individuals of a species, from the lowest sexually reproducing organisms to man, shows individual variation. This means that the individuals differ from each other in size, proportions, intensity of coloration, and many other characteristics. Diversity and synthesis of evolutionary thought. Takes that can either be measured or graded. This variation is also referred to as continuous variation, because one extreme end of the curve of variation usually grades imperceptibly into the other extreme, let us say the smallest and the largest individual, if a large enough population sample is available. A seemingly entirely different type of variation is represented by the occurrence of an occasional individual that falls way outside the norm of variation of a species population. Is such an individual perhaps a new species? According to the creationist dogma, which was so powerful from the 16th to the 18th centuries, all new species have been created in the beginning, that is, at the time of the original creation recorded in Genesis. The spontaneous occurrence of an occasional individual that fell way outside the normal range of variation of the known species was referred to as discontinuous variation, thus a source of considerable puzzlement. Was this perhaps evidence for continuing creation, as postulated by St. Augustine, or did this indicate a far greater plasticity of the species' essence than had hitherto been accepted? Darwin had a rather low opinion of the evolutionary importance of discontinuous variation. The occurrence of variant individuals who in some character rather strikingly differ from their parents and siblings, and indeed from all other members of their population, is mentioned in The Origin only casually. When Fleming-Jenkin attacked him in 1867, Darwin reduced the number of references to such variants even more. As he wrote to Wallace, LLD Ill, 108, I always thought individual differences more important, but I was blind and thought that single discontinuous variations might be preserved much oftener than I now see is possible or probable. I believe I was mainly deceived by single variations offering such simple illustrations, as when man selects. For one like Darwin, who was always searching for causal explanations, such unique saltations were singularly unsatisfactory. They were seemingly accidents of nature and most authors who wrote about them never even attempted an explanation. When one reads Darwin's discussions of variation, one senses that he felt that it would be easier to explain ordinary continuous variability. His theory of natural selection was based on the assumption of an unlimited supply of individual variation, and this in turn was based on his observation that every individual is uniquely but very slightly different from every other one. He refers to these individual variants again and again. We have many slight differences which may be called individual differences, such 543, 544, as are known frequently to appear in the offspring from the same parents. These individual differences are highly important to us, as they afford material for natural selection to accumulate. I believe mere individual differences are amply sufficient. Darwin's thesis that the gradual accumulation of very slight variants by natural selection was the mechanism of evolution was not popular among his contemporaries. He was criticized not only for failing to explain the causation of this continuous variation but also for ignoring or at least underestimating the widely accepted importance of discontinuous variation. T.H. Huxley, who retained considerable allegiance to essentialism all his life, disagreed with Darwin's downgrading of saltations. In his famous Times Review, April 1860, he remarked, "Mr. Darwin's position might, we think, have been even stronger than it is, if he had not embarrassed himself with the aphorism natura non facit saltum, which turns up so often in his pages. We believe that nature does make jumps now and then, and a recognition of the fact is of no small importance." Huxley was not alone in this opinion. Among those who accepted evolution after 1859 were not a few who were far more impressed by the occurrence of sudden mutations than was Darwin. Botanists and horticulturalists, in particular, cited numerous cases, more or less in the same category as Linnaeus's Peloria, see Chapter 6, where a strongly deviant type suddenly originated. Nevertheless, Darwin and his friends, such as Asa Gray, continued to deny that such aberrant types were of evolutionary importance. By the end of the 1880s this apparently had become the prevailing opinion. Darwin's tendency to equate discontinuous variation with the production of monstrosities and his argument that complex new adaptations could not possibly be acquired by a single sudden jump seemed to have carried the day. Weismann, 1892, was as convinced a gradualist as Darwin. An abrupt transformation of a species is inconceivable, because it would render the species incapable of existence, 2nd ed., p. 271. But more and more other evolutionists concluded that gradual variation was insufficient to account for the ubiquitous discontinuities observed between species and between higher taxa. One who was particularly unhappy over the emphasis on the role of gradual change in evolution was the British zoologist William Bateson, 1861–1926, who later played such a decisive role in the rise of genetics. His first important work was on the embryology of the hemi-chordate balanoglossus, work done in the lab. Diversity and Synthesis of Evolutionary Thought. Oratory of the American zoologist William K. Brooks. There Bateson became interested in the problem of evolution and particularly in the role of variation, without which natural selection is meaningless. Variation, whatever may be its cause, is the essential phenomenon of evolution. Variation, in fact, is evolution. The readiest way, then, of solving the problem of evolution is to study the facts of variation. 1894, 6. As far as Darwin's reliance on continuous variation as the basis of evolution was concerned, Bateson, like T.H. Huxley before him, objected to the gratuitous difficulties which have been introduced by this assumption. p. 15. Species are discontinuous, may not the variation by which species are produced be discontinuous too? p. 18. He lapiates the suggestion in his conclusion. Discontinuity has its origin not in the environment, nor in any phenomena of adaptation, but in the intrinsic nature of organisms themselves, manifested in the original discontinuity of variation. p. 567. At that time, curiously, Bateson's interest in variation was entirely evolutionary rather than genetic. He assembled an enormous amount of material, 598 pages, on variation in natural populations and its possible role in speciation in his materials for the study of variation. To be sure, many variants were simply monstrosities. Bateson, however, concentrated on those deviations from the norm that were of the magnitude of species differences. From this evidence Bateson concluded that the discontinuity of which species is an expression has its origin, in the intrinsic nature of organisms themselves, manifested in the original discontinuity of variation. p. 567. It suggests that the discontinuity of species results from the discontinuity of variation. p. 568. Bateson did not think in terms of populations but in terms of discrete types, and he did not change this interpretation to the end of his career. See his Toronto address of 1922. Discontinuous variation, thus, was for him the key to evolution, and this is why he started his program of work on inheritance, see chapter 16. The events of the ensuing years indicate that Battison's argument decisively influenced the thinking of many of his contemporaries. At the turn of the century, two works appeared that promoted even more vigorously the thesis that new species originate by sudden saltation. The Russian botanist S. Korshinsky, 1899, 1901, further developing a thesis proposed by Kolliker in 1864, asserted that all organisms have the capacity to produce occasionally an offspring which differed discontinuously from other members of the species, heterogenesis. Going beyond Darwin, 1868. 545. Who had reported many such cases among cultivated plants, Korshinsky emphasized that the deviations from the type were not always drastic but might represent any grade of difference from the normal condition. The production of such deviant individuals was not caused by the environment but was due to an intrinsic potentiality. De Vries's mutationism. Saltationism received its greatest boost from De Vries's Muta 546tion theory, 1901-1903. Like Battison, De Vries started from the assumption that there are two kinds of variation. Among these, the ordinary or so-called individual variability cannot lead to a transgression of the species border even under conditions of the most stringent and continued selection, 1901-4. Hence speciation must be due to the spontaneous origin of new species by the sudden production of a discontinuous variant. The new species thus originates suddenly, it is produced by the existing one without any visible preparation and without transition, p3. Unfortunately, De Vries's argument was entirely circular. He called any discontinuous variant a species, hence species originate by any single step that causes a discontinuity. The origin of species, he says, is the origin of species characters, p. 131. De Vries had no concept of populations or of species as reproductive communities. He was a strict typologist. His theory of evolution thus was based on the assumptions, 1. That continuous, individual variation is irrelevant, as far as evolution is concerned, 2. That natural selection is inconsequential, and 3. That all evolutionary change is due to sudden, large mutations and, furthermore, that species have mutable and immutable periods. De Vries describes how from 1886 on he had studied variable species in the surroundings of Amsterdam in order to find one that was truly mutable. I have taken into culture in the course of years far more than 100 such species, but only a single one lived up to my hopes, p. 151. All other species, he said, were in an immutable period. The only mutable species was Oenothera lamarckiana. One can only shake one's head when one reads De Vries's Die Mutationstheorie. This brilliant physiologist and geneticist, whose 1889 book on intracellular pangenesis was, prior to 1900, the most sensible and prophetic discussion of the problems of inheritance, violates all the canons of science in his mutation theory. Not only are most of his conclusions circular, but he builds his entire theory on a single exceptional species, postulating without the shadow of diversity and synthesis of evolutionary thought. A proof that the far more than 100 other species which did not behave like Oenothera happened to be in an immutable period. He finally concludes, p. 150, that species do not originate by the struggle for existence and natural selection, but are exterminated by these factors. 10. In spite of its evident shortcomings and the vigorous opposition by leading naturalists, for example, Poulton, 1908, De Vries's work dominated the thinking of biology from 1900 to 1910. As Dunn, 1965a, 59, rightly has said, in some ways the publication of the HRST volume of De Vries's great work in 1901 made a greater impression on biology than the rediscovery of Mendel's principles. The leading textbook of genetics during the De Vries era, Locke, 1906, 144, summarizes the thinking of the Mendelians in the statement, species arise by mutation, a sudden step in which either a single character or a whole set of characters together become changed. Th. Morgan, at first, 1903, was most enthusiastic about de Vries's theory. The Mendelians thought that such evolution by mutation refuted gradual evolution by selection. Consequently, Bateson claimed that the transformation of masses of populations by imperceptible steps guided by selection is, as most of us now see, so inapplicable to the fact that we can only marvel both at the want of penetration displayed by the advocates of such a proposition, and at the forensic skill by which it was made to appear acceptable even for a time. 1913, 248. Johansen was even more opposed to any role of selection in evolution. To show how totally he rejected Darwin's theory of natural selection, Bateson remarked condescendingly, "We go to Darwin for his incomparable collection of facts but reject his theoretical explanations. For us he speaks no more with philosophical authority. We read his scheme of evolution as we would those of Leucurtius or of Lamarck." 1914, 8. In this rejection of Darwin, Bateson went far beyond de Vries, who insisted that his theory was a modification of Darwin's, not a replacement for it. R. A. Fisher, 1959, 16, appraised the situation quite rightly when he said, "The early Mendelians could scarcely have misapprehended more thoroughly the bearings of Mendel's discovery on the process of evolution. They thought of Mendelism as having dealt a death blow to selection theory. A particulate theory of inheritance implied to them a corresponding discontinuity in evolution. As a result, the opinion was widespread that Darwinism was dead." This led Nordenskjöld in his otherwise so authority. 547. 548. Tentative History of Biology, 1920–1924, to the statement, "The Darwinian theory has long ago been rejected in its most vital points. The objections made against the theory on its first appearance very largely agree with those which far later brought about its fall." Morgan, among others, thought that mutation pressure alone could achieve everything that Darwin had ascribed to natural selection. What upset the naturalists most was the frequent assumption made by Mendelians, for example, by de Vries, that so-called individual or fluctuating variation lacked a genetic basis. This was of decisive importance for the evaluation of geographic races, some of which were considered by the Darwinians to be incipient species. De Vries had to reject the concept of geographic speciation because it was in direct conflict with his mutation theory, speciation by genetically different individuals. He stated this quite clearly with respect to geographic races in man. The variability exhibited by man is of the fluctuating kind, whereas species arise by mutation. The two phenomena are fundamentally different. The assumption that human variability bears any relation to the variation which has or is supposed to have caused the origin of species is to my mind absolutely unjustified. Favorable and unfavorable conditions of life, migration to a different climate and so forth affect the fluctuating characters of man to no small extent. But only for a time. As soon as the disturbing factor is removed, the effect which it produced disappears. The morphological characters of the race on the other hand are not in the least affected by such influences. New varieties do not arise by this means. Since the beginning of the diluvial period, man has not given rise to any new races or types. He is, in fact, immutable, albeit highly variable. Another of de Vries's claims without any basis of fact. 1901, I. 155–156, the interpretation of evolution by the early Mendelians can be summarized in the following conclusions. 1. Every change in evolution is due to the occurrence of a new mutation, that is, of a new genetic discontinuity. Hence the moving force in evolution is mutation pressure. 2. Selection is an inconsequential force in evolution, at best playing a role in eliminating deleterious mutations. 3. Since mutation can explain all evolutionary phenomena, individual variation and recombination, neither of which produces anything new, can be disregarded. Most continuous individual variation is non-genetic. Diversity and synthesis of evolutionary thought. The naturalists were dismayed. All that they had discovered and described since Wallace's pioneering paper of 1855 was ignored by the experimentalists. As Rothschild and Jordan said, 1903, 492, whoever studies the distinction of geographic varieties closely and extensively, will smile at the conception of an origin of species per saltum. The naturalists saw gradualness everywhere, and they all believed, at least to some extent, in natural selection. Poulton, 1908, 18, not without justification, ridiculed the mutationists by stating, mutation without selection may be left to those who desire to revive special creation under another name. But the naturalists also had misconceptions. For instance, they were so sold on gradualness that they even belittled Mendelian inheritance. To be sure, discontinuous characters might obey the Mendelian rules, they admitted, but, after all, such characters were of little evolutionary consequence. Gradual, quantitative characters, the only ones of importance in evolution, did not follow the Mendelian rules laid down by De Vries and Bateson, the naturalists claimed, hence one would have to search for another solution. And they found this solution either in some orthogenetic capacity of evolutionary lines or in neo-Lamarckism. Natural selection, even though acknowledged by most of them as an evolutionary force, was not the major factor in evolution. Rather, the naturalists continued to believe in the effects of use and disuse, a direct induction by the environment or other manifestations of soft inheritance. Up to the 1920s and 1930s, virtually all the major books on evolution, those of Berg, Bertalanffy, Bjorlin, Boker, Goldschmidt, Robson and Richards, Schindewolf, Willis, and those of all the French evolutionists, including Quinot, Colli, Vandel, Guyenot, and Rostand, were more or less strongly anti-Darwinian. Among non-biologists, Darwinism was even less popular. The philosophers, in particular, were almost unanimously opposed to it, and this opposition lasted until relatively recent years. Cassirer, 1950, Green, 1959, Popper, 1972. Most historians likewise rejected selectionism: Roddy, Nordenskjöld, Barzun, Himmelfarb. In various confrontations between the two camps there was no evidence of a willingness to compromise. All the argument was directed toward trying to prove that the other camp was wrong. At a meeting between geneticists and paleontologists at Tübingen in 1929, the paleontologists adopted the worst possible strategy, Weidenreich, 1929. Instead of concentrating on the evolutionary phenomena which the geneticists, particularly the Mendelians, had 549. 550. Not been able to explain, they concentrated on trying to prove the existence of an inheritance of acquired characters, a subject which they were in no manner whatsoever qualified to discuss. And yet, there were numerous evolutionary problems that were not at all explained by the changes in the frequency of genes. Concept of evolution of the geneticists, such as highly uneven rates of evolution, the basic constancy of major structural types, the absolute discontinuities between them, and the problem of the multiplication of species. When the controversy between the two camps had started, in the 1890s and the early 1900s, both camps held ideas that were incompatible with the ideas of the other camp. More importantly, both camps supported certain explanations that could be refuted by the other camp. But it was impossible to recognize this until both camps had clarified and, in part, considerably revised their own ideas. In order to be able to understand the eventual resolution of the conflict, it is necessary to describe the advances made in both camps, in evolutionary genetics, after about 1906, and in evolutionary systematics, from the post-Darwinian period to the 1930s. These advances eventually made a reconciliation of the two opposing camps possible and led to a synthesis of the valid components of the two research traditions. Advances in evolutionary genetics. What de Vries, Bateson, and Johansen had been doing was only one of several possible kinds of evolutionary genetics and did not outlive the first decade of the century. The teachings of Bateson's opponents, the biometric Ians, Provini, 1971, see Chapter 16, were even more short-lived. The simplistic ideas of these pioneers were subjected to a rather radical revision by a new generation of geneticists. Schools that originated in experimental zoology, like that of T.H. Morgan at Columbia, stayed closest to the original evolutionary ideas of Mendelism, stressing mutation and the discontinuous independence of individual genes, Allen, 1968. But other geneticists who had entered genetics from natural history or from animal or plant breeding, like Nilsson L. in Sweden, East, Jones, Jennings, Castle, and Payne in the United States, and Bauer in Germany, made findings which showed that there is no conflict between the genetic evidence and either natural selection, gradualness of evolution, or population thinking. Diversity and synthesis of evolutionary thought. A detailed history of these findings is presented in Chapter 17. Those of the greatest importance for the interpretation of evolution may be summarized in these statements. 1. There is only one kind of variation, large mutations, and very slight individual variance being extremes of a single gradient. 2. Not all mutations are deleterious, some are neutral and some are distinctly beneficial. 3. The genetic material itself is invariant, constant, that is, there is no soft inheritance. 4. Recombination is the most important source of genetic variation in populations. 5. Continuous phenotypic variation can be explained as the result of multiple factors, polygenes, together with epistatic interactions and is not in conflict with particulate inheritance. 6. A single gene may affect several characters of the phenotype, pleiotropy. 7. Experimental as well as observational data demonstrate the effectiveness of selection. These findings completely refuted the anti-selectionist, saltational evolutionary theories of de Vries and Bateson. Curiously, this by no means spelled the end of saltationism, which continued for several decades to have substantial support, as for instance by the geneticist Goldschmidt, 1940, the paleontologist Skindie-Wolf, 1950, and other, particularly German, paleontologists, the botanist Willis, 1922, 1940, and some of the philosophers. Eventually it was universally accepted that an origin of species and higher taxa through individuals does not occur, except in the form of polyploidy, principally in plants. The phenomena which the adherents of macrogenesis had used as support could now be readily explained in terms of gradual evolution. Particularly important for the reconciliation was the recognition of the importance of two previously neglected evolutionary processes, drastically different rates of evolution in different organisms and populations, and evolutionary changes in small, isolated populations. It was not until the 1940s and 50s that well-argued defenses of macrogenesis disappeared from the evolutionary literature in the wake of the evolutionary synthesis. Evolution by mutation pressure, a concept popular from Bateson and de Vries to Morgan, also lost ground after 1910 but did not disappear entirely, being revived recently by the Propos. 551. 552. Of non-Darwinian evolution. A belief in mutation pressure was losing ground not only because the sentiment in favor of selection continued to grow stronger, particularly in the 1920s, but also because of the discovery of reverse mutation. Steady evolutionary change through mutation would be possible only if there was a cascading of mutations all in the same direction. However, if the probability of mutating from A to A is no greater than that of the reverse mutation from A to A, then no evolutionary trend can develop. After Morgan had discovered eosin in 1913, a reverse mutation from to Hittite, more and more reverse mutations were discovered, and in many cases the frequency from wild type to mutant was no greater than the reverse from mutant to wild type, as shown by Muller and Timofey Fresovsky, Muller, 1939. The assumption that directional evolution, evolutionary trends, could be caused by mutation pressure was made exceedingly improbable by these findings. Perhaps the most important contribution made by the new genetics was the decisive refutation of soft inheritance. This had been delayed again and again by claims of an experimental substantiation of an inheritance of acquired characters. Some of these claims were based on experimental error, others quite clearly were fraudulent. Burckhardt, 1980. It is of extraordinary interest how often experimenters, when they are convinced of the to-be-expected outcome of their tests, produce data which they were unable to get in their actual experiments. This psychological phenomenon has also been observed in other areas of experimental biology, such as cancer research and immunobiology. Although the final DISP proof of soft inheritance had to wait for the demonstration, by molecular genetics, that information acquired by the proteins cannot be transmitted back to the nucleic acids, and this was not proven until the 1950s, nevertheless the geneticists showed, and this was accepted by such naturalists as Sumner, Wrench, and Mayr, that all the phenomena of gradual evolution and adaptational variation that had previously been cited as evidence for an inheritance of acquired characters could be interpreted in terms of constant genes. Contrariwise, all endeavors to demonstrate soft inheritance were failures, see Chapter 17. From the beginning some geneticists were more interested in the mechanics of inheritance, others in the evolutionary aspects. Those who wanted to understand the genetic basis of evolution increasingly appreciated that evolution was a population phenomenon and that it had to be studied as such. A Held began to diversity and synthesis of evolutionary thought. Developed that later was designated as population genetics. Workers interested in statistics, like Ewell, Pearl, Norton, Jennings, Robbins, and Weinberg, made the first important contributions to this Held. We still lack a good history of this period, but it seems that these authors had already arrived at many of the later conclusions of population genetics. Most of their findings were published in technical journals and did not become as widely known as they deserved. Regrettably, the naturalists were largely unaware of this work. Eventually it became customary to designate as population genetics that brand of genetics that investigates the changes of gene frequencies in populations. The term population genetics is actually ambiguous, because two largely independent lineage diagrams were involved. One is represented by mathematical population genetics connected with the names R. A. Fichet, J. B. S. Haldane, and Sewell Wright. Its populations were statistical populations, and research in this Held could be done with pencil and paper, later with a calculator, and now with the computer. The other population genetics dealt with actual populations of living organisms studied in the Held and in the laboratory. The history of that branch of population genetics has not yet been written. It is represented by the work of Schmidt, Zorses, Goldschmidt, Limentria, Sumner, Peromyscus, Langlet, Pinus, Bauer, Antarinum, Chetverikov, Timofey Fresovsky, Dobbs-Hansky, Drosophila, Kane, Shepard, Lamotte, Sepia and Ford and Shepard, Panaxia, Mamala, to mention the names of some of the many students of the distribution of genes in natural populations and their changes in time. To distinguish it from mathematical genetics, Ford, 1964, has appropriately designated this Held as ecological genetics. Mathematical population genetics had its beginnings in the controversy between the Mendelians, Bateson, in particular, and the biometric Ians, Weldon, Pearson. The biometric Ians, although quite correctly stressing the importance of continuous variation as the material of natural selection, had assumed inheritance to be blending. The early Mendelians, cognizant of the particulate nature of inheritance, had stressed discontinuous variation. The MAM development of evolutionary genetics was to show that there is no conflict between particulate, non-blending, inheritance, continuous variation, and natural selection. The basis of all mathematical population genetics is the so-called Hardy-Weinberg equilibrium principle, established in 1908. 553. 554. It states that two alleles, A and O, will remain at the same frequency in a population from generation to generation unless their frequency is affected by immigration, mutation, selection, non-random mating, or errors of sampling. For a history of the discovery of this principle, see Provini, 1971, 131-136. Much of mathematical population genetics of the ensuing 30 years dealt with the question of how the genetic composition of populations of various sizes is affected by different rates of mutation, different selection pressures, and errors of sampling. The first question to be studied was how effective selection is when the selective advantage of a new allele introduced into a population is only slight. The British mathematician H.T.J. Norton worked this out for different selection intensities of genes occurring at different frequencies, 1915. To the surprise of almost everybody, he was able to show that even rather small selective advantages or disadvantages, less than 10%, led to drastic genetic changes in relatively few generations. This finding greatly impressed J.B.S. Haldane, who published a series of researches on the mathematics of selection in the 1920s, and the Russian naturalist geneticist Chetverikov. The conclusion that alleles only slightly differing in selective value could replace each other rather rapidly in evolution later induced several neo-Lamarckians, Ernst and Mayr, for example, to abandon their belief in soft inheritance. For it was now evident that phenomena like climatic races and other environment-correlated adaptations could be interpreted in terms of selection acting on multiple alleles and genes. Beginning with 1918, R. A. Fisher, 1890–1962, published a series of papers on the mathematics of gene distributions in populations. These researches dealt with the partitioning of genetic variants into an additive portion, caused by alleles or independent genes with similar effects, and a non-additive portion, epistasis, dominance, and so forth, with the conditions under which balanced polymorphism would be maintained, with the role of dominance, and with the rate at which a favorable gene would spread in populations of different sizes. Some of his findings, as on balanced polymorphism, are now so well established that we can hardly comprehend that someone had to be the first to work this out. Others of his researches are so fertile in conclusions that it is only in the last decades that they have been fully applied. Fisher's most important conclusion was that much of continuous variation, at least in man, is due to multiple Mendelian factors rather than to environmental influences. His stress on genes, diversity and synthesis of evolutionary thought, with small phenotypic effects, was a major contribution to the coming reconciliation between geneticists and naturalists. Like most mathematical geneticists, Fisher tended to minimize the effects of an interaction among gene loci. Fisher always thought in terms of large populations, and although he was fully aware of the existence of errors of sampling, he thought that, owing to the selective differential of competing genes and to recurrent mutation, such errors of sampling would be in the long run of little evolutionary consequence, as is indeed true for large populations. Another geneticist, Sewell Wright, B. 1889, disagreed with Fisher on this point, and this revived an old argument which, as a matter of fact, is not entirely settled to this day. The first person to advance the thesis that much evolutionary change is simply a result of chance variation was J.T. Gulick, 1872. He was led to this thesis when observing the incredible diversity of local populations of Hawaiian land snails, Acadenella, and their seemingly haphazard variation in the absence of definable differences in environmental factors. From that date on, the thesis that much variation is selectively neutral was proposed again and again. Fisher, 1922, 328, called such random variation the Hagedorn effect after two Dutch investigators who had brought together a great deal of evidence in its support. Their thesis, like that of Gulick, was based on the assumption that much of such variation is effectively neutral as far as selection is concerned. Fisher, by contrast, thought that most allelic polymorphism in populations was due to a superiority of heterozygotes. Sewell Wright, a student of William E. Cassell, had worked since 1914 on color inheritance and on the effects of inbreeding in guinea pigs. This work had persuaded him that effective breeding populations, later called demes, even in wild animals often were of sufficiently small size to make errors of sampling a non-negligible factor. Although gene flow from adjacent populations would usually prevent the random fixation of genes, there would nevertheless be sufficient genetic drift to favor gene combinations that would be unlikely to occur in large populations. In his first major account, Wright, 1931a, expressed himself in a way that sounded as if he were proposing genetic drift as an alternative mechanism to natural selection, and this caused considerable confusion. Through Dobzhansky's book, 1937, Wright's thesis became widely known among evolutionists, and a tendency developed in the 1940s and 50s to ascribe to genetic drift almost any puzzling evolutionary phenomenon. Drift played an important role in the writings of Dobzhansky and also in Simpson's, 1944, concept of the inadaptive phase of quantum evolution. Eventually a reaction to the liberal invoking of genetic drift set in, as described by Mayr, 1963, 204-214. As a student of Kassel, Wright had had considerable contact with naturalists and was particularly interested in the 1920s in the researches of F. B. Sumner, Provini, 1979. As a result, Wright tended to think in terms of natural populations and was aware of the changing fitness values of genes. Genes favorable in one combination are extremely likely to be unfavorable in another, 1931, 153. Unfortunately, he made little use of this insight in his equations and graphs, where he deals almost exclusively with single genes and with constant fitness values. Wright, like Cherenkov, was greatly impressed by pleiotropic effects. Since genes as a rule have multiple effects, it is probable that in time a gene may come to produce its major effects on wholly different characters than at HRST, 1931a, 105. Owing to his background, Wright, among the mathematical geneticists, was in his thinking closest to the thought of the naturalists. That he regarded species as aggregates of populations was a prerequisite for his later collaboration with Theodosius Dobzhansky, 1900-1975. Cherenkov. A rather different school is represented by the population genetics that originated in Russia, primarily through the work of Sergei S. Cherenkov, 1880-1959, and his students. Russia differed in its traditions quite significantly, not only from the United States but also from Western Europe. Natural selection had been much more widely accepted, prior to the 1920s, than elsewhere, and natural history seems to have had a much higher prestige and influence at the universities. Even today most zoology students, in Moscow for instance, spend their summers at biological field stations or elsewhere doing field work. Also, in the USSR there were a number of genetics institutes, 2 in Leningrad, 1 in Moscow, and it would seem that in the 1920s the number of geneticists in the USSR was as large as all of the rest of continental Europe together. Cherenkov was the head of the Department of Genetics from 1924 to 1929 in Koltsov's Institute of Experimental Biology in Moscow. He was a passionate butterfly specialist, still describing a new species from the Ural Mountains when he was 76 years old. He was equally interested in evolution, publishing in Diversity and Synthesis of Evolutionary Thought, 1906, a seminal article on population fluctuations, the evolutionary importance of which, particularly the bottlenecks, no one had previously fully appreciated. From the early 1920s on, Cherenkov taught genetics and became the leader of a large informal group of genetics enthusiasts. In 1929 he had to leave Moscow for political reasons and was no longer able to continue his genetic researches. Adams, 1968, 1970, 1988. Owing to his own background as a naturalist, Cherenkov answered the questions and objections of the anti-Mendelians FAI more effectively than did either Morgan or the mathematicians. In one of the most important publications in the whole history of evolutionary biology, 1926, he sets himself the goal of clarifying certain questions on evolution in connection with recurrent genetic concepts, p. 169. First, he showed that there is a complete, almost imperceptible transition from mutations that have completely normal viability to mutations of ever lower viability and even lethality. The claim that all mutations are deleterious is not true. Indeed, as was later shown by Dobzhansky and others, mutations may occur that are of higher fitness than wild type. Chetverikov saw clearly, as had Fischer and others before him, that a new mutant always first appears as a heterozygote and that, if it is recessive, it may long remain concealed in the population, unless lost by errors of sampling, because only homozygotes will be exposed to selection. He therefore came to the conclusion that a species, like a sponge, soaks up heterozygous mutations, while remaining from first to last externally, phenotypically, homozygous, p. 178. Thus a great deal of concealed genetic variability ought to exist in every species. To test his hunch, he trapped 239 wild Drosophila melanogaster females near Moscow, and brother-sister mated their offspring. In this small sample he found no less than 32 loci which segregated for visible recessives, thus confirming his supposition. No one before him had suspected the amount of concealed variation in a wild population. His students, particularly N.V. Timofey Fresovsky, B.L. Astorov, N.P. Dubinin, and D.D. Romashev, rigorously began to analyze genetic variation in wild populations, integrating it with experimental research in the laboratory. Dobzhansky, although not himself a member of the group, he worked with Filipchenko in Leningrad, keenly followed these researches, which were one of the influences on his later Drosophila researches. For Chetverikov, changes in populations were not the result of mutation pressure but of selection. Basing his argument on 557. 558. Norton's table, 1915, he concluded that even the slightest improvement of the organism, a slightly superior gene has a definite chance of spreading throughout the whole mass of individuals comprising the freely crossing population, species, 1961, 183. It does not matter whether the new gene is dominant or recessive, nor whether its selective advantage is 50% or only 1%, the complete replacement of a gene by a better adapted one always proceeds to an end. In contrast to Fischer and Haldane, who devoted most of their efforts to proving the effectiveness of selection, Chetverikov, in line with the Russian tradition, took selection far more for granted. This enabled him to turn to other problems. Most of Chetverikov's conclusions were eventually also reached independently by Fischer, Haldane, and Wright and entered the evolutionary literature of the West primarily from them. Where Chetverikov was way ahead of the Western group was in his much clearer recognition of the evolutionary importance of gene interaction. He emphatically rejected the former notion of the mosaic structure of the organism consisting of various independent genes and concluded that each inherited trait is determined by not just some one gene but by their whole aggregate, their complex. No gene has a constant fitness value, because the very same gene will manifest itself differently, depending on the complex of the other genes in which it finds itself, p. 190. The phenotypic expression of each gene is determined by its genotypic milieu. Chetverikov had based these conclusions on the discovery, particularly by the Morgan group, of pleiotropic gene action, that is, the effect of a gene on several components of the phenotype, see chapter 17. His student Timofey Fresovsky had discovered important manifestations of pleiotropy, 1925. By contrast, the mathematical population geneticists, especially Fischer and Haldane, concentrated, for reasons of simplicity of a first approach, on the behavior of individual genes. In their equations as well as in their graphs, they illustrated the increase or decrease in the frequency of individual genes under the effects of selection, mutation, and errors of sampling. Genetics textbooks in the 1940s and 50s suggested laboratory exercises in which genes were represented by beans of several colors, placed in a bag, mixed and assembled for each generation, according to certain experimental specifications. Since any interaction among genes was excluded in these exercises, Mayr, 1959d, dubbed the kind of genetics which ignored gene interaction as beanbag genetics. Unfortunately, diversity and synthesis of evolutionary thought. Too much of mathematical population genetics at that time was beanbag genetics. Even an author like Sewell Wright, who was fully cognizant of the importance of gene interaction, dealt in his calculations and illustrations almost exclusively with the behavior of individual genes. As a result, it was not until the 1950s and later that Chetverikhov's concept of the genotypic milieu was fully incorporated into the thinking of evolutionary biologists. In spite of the fact that Russian language publications we hardly ever read outside the USSR, the work of Chetverikhov's school was not entirely unknown in England and the United States. Not only Chetverikhov's 1927 article but at least 3 papers by Timofey Fresovsky were published in English or German language publications, and a complete translation of Chetverikhov's 1926 paper was available in Halden's laboratory. After leaving the USSR, both Timofey Fresovsky and Dobzhansky further helped to spread the ideas of the Chetverikov school. There is no doubt that it made a substantial contribution to the evolutionary synthesis. Chetverikov and the mathematical population geneticists completed the destruction of the genetic theory of evolution of the Mendelians. They confirmed the importance of selection and the non-existence of mutation pressure. They established the genetic basis of gradual Darwinian evolution and confirmed the non-existence of soft inheritance. Finally, they showed that there is no conflict between the discontinuity of genes and the continuity of individual variation. An important foundation was thus laid for a bridge to the camp of the naturalists, who had rejected all along the Davriesian macromutations and mutation pressure and had likewise emphasized the importance of gradual evolutionary changes and of natural selection. Advances in evolutionary systematics. The rapid advances made in evolutionary genetics were paralleled by similar advances in systematics or, more broadly, by advances in the understanding of organic diversity by naturalists. As a matter of fact, the type of population genetics conceived by Chetverikov involved little more than the transfer of concepts and methodologies to genetics that had existed in systematics for more than 100 years. I am referring to the study of different 559 graphic races of a species casually discussed by Buffon, for North American animals, and Pallas, for Siberian animals, and fully developed by Gloger. 1-3 The more perceptive taxonomists since that time have given much thought to innate differences among different populations, particularly geographical races of species. Such population differences are referred to by Linnaeus, 1739, Buffon, 1756, Blumenbach, 1775, Pallas, 1811, von Buch, 1825, and Gloger, 1827, 1833. It was generally known to foresters from Sweden, Germany, and France from the middle of the 18th century on. Langlet, 1971. The fact that pines and rhododendrons from different altitudes in the Himalayas greatly differ in frost hardiness was discovered by Hooker, 1853, and quoted by Darwin, 1859, 140. It was soon recognized that this variation was closely correlated with the nature of the environment, and the term climatic race was introduced in the middle of the 19th century. In botany this was extended to a study of edaphic factors, the combination of edaphic and climatic factors being responsible for the development of ecotypes. Turison, 1922. More geographical in treatment was the work of Bauer on Antirrhinum populations in Spain, Scaemon, 1935, Stubb, 1966. In zoology, these interests led to the studies of Schmidt, 1917, on fishes, of Goldschmidt on Lymantria, and of Sumner on Peromyscus. None of this material was as suitable, however, for a detailed genetic analysis as Drosophila. It is important to recognize that Chetverikhov's work consisted largely in the application of a classical phlogiston to a new and particularly suitable material. The development of population systematics that could easily be translated into population genetics was a major contribution of the naturalists. They were continuing a tradition, to which Darwin himself had belonged, which was concerned with the study of natural populations, with variation within populations, and with the changes on geographical gradients from population to population. They adopted the population as the unit of evolution, rather than the phyletic line favored by the comparative anatomists and paleontologists. The naturalists were the only biologists who studied isolation and the role of geographical as well as of individual variation. Except for the animal breeders, they were the first ones to understand individuality and to base their methodology on this knowledge, resulting in the admonition to collect series or to make mass collections. This, in turn, led to the application of statistics, and Galtonian statistics at that, which stresses variance rather than mean values. Unfortunately, no adequate history of diversity and synthesis of evolutionary thought. Evolutionary natural history is so far available, although some of the developments are described in Stresemann's Ornithology, 1975, and in historical comments made by Mayr, 1963. The most important contributions made by the naturalists were conceptual ones. A true understanding of natural selection, speciation, and adaptation was not possible until population thinking had displaced typological thinking. The population thinking of the naturalists had a particularly important impact on Chetverikov and his school. But it was not the naturalists alone who helped to spread this concept. A second source of population thinking were, as in Darwin's day, the animal and plant breeders. Those geneticists, like Castle, East, Emerson, and Wright, who had the closest contact with breeders, also avoided most successfully the pitfalls of typological thinking. Among the naturalists, it led to the new concept of races as variable populations, each with a different geographical history. It led to the development of the biological species concept, and ultimately it culminated in the so-called new systematics, more correctly called population systematics, see Chapter 6. It was the naturalists who solved the great species problem, a problem which the geneticists either sidestepped altogether or answered unsuccessfully in a typological manner. The naturalists showed that species are not essentialistic entities, to be characterized morphologically, but that they are aggregates of natural populations that are reproductively isolated from each other and species-specific niches in nature. A full understanding of the nature of species could not be achieved until a number of further insights had been acquired, such as the distinction between taxon and category, and the realization that the word species is a relational term like the word brother, and that, philosophically speaking, a species taxon is an individual, the members of a species being parts of this individual. The truth of this assertion becomes evident when one considers that the genes of all the members of a species are components of the same gene pool. Gazellin, 1974b, Hull, 1975, see also Chapter 6. Speciation. The new understanding of the nature of populations and of species enabled the naturalists to solve the age-old problem of speciation, a problem that had been insoluble for those who looked for the solution at the level of genes or genotypes. At that level, the only solution is instantaneous speciation by a drastic mutation or other unknown processes. As de Vries, 1906, had stated, the theory of mutation assumes that new species and varieties are produced from existing forms by certain leaps. Or as Goldschmidt, 1940, 183, had stated, the decisive step in evolution, the first step toward macroevolution, the step from one species to another, requires another evolutionary method, that is, the origin of hopeful monsters than that of sheer accumulation of micromutations. The naturalists realized that the essential element of 562, the speciation process, is not the physiological mechanism involved, genes or chromosomes, but the incipient species, that is, a population. Geographic speciation, consequently, was defined by Mayr in terms of populations, A new species develops if a population which has become geographically isolated from its parental species acquires during this period of isolation characters which promote or guarantee reproductive isolation when the external barriers break down. Mayr, 1942, 155. The most important conceptual advance was a clear formulation of the problem. In order to explain speciation, it is not sufficient to explain the origin of variation or of evolutionary changes within populations. What must be explained is the origin of reproductive isolation between populations. Speciation, thus, is not so much the origin of new types as the origin of effective devices against the inflow of alien genes into gene pools. This insight had a history of more than 100 years. The first person to state that speciation is in most cases geographical was von Buch, 1825. The concept was strong in Darwin's 1837-38 notebooks and in his 1842 and 1844 essays, Kotler, 1978, Sulliway, 1979, as well as in Wallace's 1855 paper. But it rather weakened in later years, see Chapter 9. Beginning with the 1850s, Darwin thought that speciation, particularly on continents, could also occur without strict geographical isolation, and this involved him in a heated controversy with Moritz Wagner. The role of isolation. Moritz Wagner, 1813-1887, a celebrated explorer, collector, and geographer, had devoted 3 years, 1836-1838, to the exploration of Algeria. Here he found that each species of flightless beetles, Pamelia and Melosoma, invariably was restricted to a stretch of the north coast between two rivers descending from the Atlas Mountains. As soon as one crossed a river, a different but closely. Diversity and synthesis of evolutionary thought. Related species appeared, Wagner, 1841, 199-200. Wagner was able to confirm such an isolating capacity of rivers during his later travels in Western Asia and extended it by comparing faunas at either side of mountain ranges, for example, the Caucasus, or, in the case of montane species, for major peaks separated by valleys such as the great volcanoes of the Andes. This led him to the conclusion, the formation of a genuine variety which Mr. Darwin considers to be an incipient species, will succeed in nature only where a few individuals transgress the limiting borders of their range and segregate themselves spatially for a long period from the other members of their species. The formation of a new race will never succeed, in my opinion, without a long continued separation of the colonists from the other members of their species. Unlimited crossing, the uninhibited cross-fertilization of all individuals of a species will always result in uniformity and will turn back to the original condition any variety the characters of which have not been fixed through a series of generations. All this sounds like a rather reasonable description of the process of geographic speciation. Unfortunately, Wagner combined this with some peculiar ideas on variation and selection. He felt that the isolation of the founder population resulted in increased variability, and he also thought that it was only in such an isolated population that natural selection truly had an opportunity to operate. Sulliway, 1979. This was too much for Darwin, who not only insisted quite rightly that natural selection and evolutionary change could take place without isolation, but also implied rather clearly that isolation was not a necessary condition for species formation. Darwin concludes his rejection of Wagner's thesis with the emphatic statement, "My strongest objection to your theory of geographic speciation is that it does not explain the manifold adaptations in structure in every organic being." LLD, 3, 158, as if speciation and adaptation were mutually exclusive phenomena. Perhaps Darwin was forced into this extreme stand by Wagner's claim, "Organisms which never leave their ancient area of distribution will never change," 1889, 82, a statement obviously not strictly true but perhaps closer to the truth than was thought in the first 75 years after it was made. In due time Weismann was drawn into the controversy. He published, 1872, a rejoinder to Wagner which is perhaps the 563 weakest of Weismann's otherwise so outstanding publications. Wagner's original question, can species multiply without geographic isolation, was changed into the question, is isolation itself the factor which is responsible for the changes in isolated populations, and is isolation necessary for varieties to become constant? As in Darwin's writings, the question of the acquisition of reproductive isolation is nowhere mentioned, and the entire emphasis is on the degree of morphological difference. How little Weismann and his contemporaries understood what really the ES564 eels of the problem of the multiplication of species are may be illustrated by this quotation. In this it is quite unimportant how the endemic species occurring in isolated areas originated, whether by amixia in a period of variation or by natural selection, which tried to adjust the immigrants to the new environmental conditions of the isolated area. The change can even have been caused by influences which had nothing to do with the isolation, as for example the direct influence of the physical environment or the process of sexual selection, 1872, 107. Wagner remained very much alone in his insistence on the importance of geographic isolation. A.R. Wallace completely sided with Darwin and concluded that geographical or local isolation is by no means essential to the differentiation of species, because the same result is brought about by the incipient species acquiring different habits or frequenting a different station, and also by the fact that different varieties of the same species are known to prefer to pair with their like, and thus to bring about a physiological isolation of the most effective kind. Needless to say, Wallace brought forth no proof whatsoever for any of these assertions. The ironic aspect of the controversy between Darwin and Wagner is that both of them consistently argued past each other. Wagner insisted that reproductive isolation could ordinarily not be acquired without geographic isolation. Darwin, at that time very much fascinated by the principle of divergence, answered that neither isolation nor time by themselves do anything for the modification of species, LLD, 2, 335-336, as though Wagner had denied the occurrence of phyletic evolution. In his entire correspondence with Wagner, Semper, and Weismann it is quite evident that Darwin failed to understand how difficult a problem the acquisition of reproductive isolation is. One of the major difficulties was that most of those who joined the controversy in the ensuing years, Romanes, Gulick, and even Wallace, Lesk, 1975, made no clear separation of geographical diversity and synthesis of evolutionary thought, and reproductive isolation, nor of individual and geographical variation, and often dealt with speciation as if it was the same as natural selection. For the confusion is particularly painful in the writings of Romanes, who invented the misleading term physiological selection for reproductive isolation. There still is no completely critical analysis of this literature, but one can, on the whole, recognize two camps: those who followed Darwin in not clearly distinguishing the two kinds of isolation, among them, Weismann, Semper, Romanes, Gulick, and Wallace, and those who, following Wagner, considered geographical isolation as a factor sui generis and indispensable for speciation, for example, Seebohm, K. Jordan, D. S. Jordan, Grinnell, a good many entomologists such as H. W. Bates and perhaps Meldala and Poulton, as well as Kerner and Wettstein among the botanists. After 1900 the theory of speciation through geographic isolation suffered an almost complete eclipse, because in the theory of mutationism, as developed by Bateson and de Vries, isolation was no longer considered necessary. Owing to the efforts of D. S. Jordan, K. Jordan, Stresemann, Ranch, Mertens, and other taxonomists, the importance of geographical isolation during speciation was not forgotten altogether. Yet as late as 1937 Dobzhansky included both the intrinsic genetic factors and the extrinsic geographical barriers in his list of isolating mechanisms. It was one of the major theses of Mayr's Systematics and the Origin of Species, 1942, that there is a fundamental difference between the two kinds of isolating factors and, as Wagner and K. Jordan had previously insisted, that geographical isolation is a prerequisite for the building up of intrinsic isolating mechanisms. A further conceptual clarification was achieved by a populational definition of isolating mechanisms, Mayr, 1970, 56. However, even today some authors confound the mechanisms of speciation, genes, chromosomes, and so forth with the location of the populations involved in speciation, that is, whether the populations are sympatric or allopatric, not realizing that the two aspects are independent of each other and both are by necessity involved simultaneously. Since 1942, the importance of geographic speciation, as worked out by the naturalists, has not been denied. The main question that has remained controversial is the relative importance of alternate processes, such as instantaneous speciation, by polyploidy and other chromosomal reorganization, and sympatric speciation. One further contribution to evolutionary thought made by the naturalists was their recognition of the adaptive nature of 565. Graphic variation within species. This strongly reinforced the belief in gradual evolution. It had been observed by perceptive naturalists long before 1859 not only that different populations in many species differ from each other, geographic variation, but also that much of this variation is gradual and correlated with factors of the environment, that it is adaptive. Gloger, 1833, Bergman, 1847. The intensive study of such climatic variation by Allen, 1870s, Sumner, 1920s, and Ranch, 1920s and 30s, provided powerful support in favor of Darwin's thesis of the 566 gradualness of evolutionary change as well as of the importance of the environment. Mayr, 1963, 309-333. Similar but less systematic studies were made in plants, particularly through the transplantation of northern individuals of tree species to southern latitudes, experiments which confirmed climate-correlated geographic variation. Langlet, 1971, Stebbins, 1979. However, in the period during which the early Mendelians insisted that genetic variation is drastic and discontinuous, such adaptive geographic variation was considered by most naturalists, prior to the early 1930s, as important evidence in favor of soft inheritance. Ranch, 1929. The evolutionary synthesis. Through the first third of the 20th century, the gap between the experimental geneticists and the naturalists seemed so deep and wide that it looked as if nothing would be able to bridge it. The distinguished German biologist Buddenbrock said in 1930. The controversy is as undecided today as it was 70 years ago. Neither party had been able to refute the arguments of their opponents, and one must assume that the situation is not going to change very soon. p. 86. The members of the two camps continued to talk different languages, to ask different questions, to adhere to different conceptions, as is abundantly evident from the contemporary literature. Mayr and Provini, 1980. How could this stalemate be broken? How could both camps be persuaded to admit that some of their assumptions were erroneous, or else, particularly in the case of the experimentalists, that their explanatory framework omitted important components? Two conditions had to be met before the two camps could unite. 1. A younger group of geneticists had to arise who took an interest in diversity and in the populational aspects of evolution, and diversity and synthesis of evolutionary thought. 2. The naturalists had to learn that the genetic interpretation of this second generation of geneticists was no longer opposed to gradualism and natural selection. When this state had been reached, a meeting of the minds came quite suddenly and completely in a period of about a dozen years, from 1936 to 1947. It was in these years that biologists of the most diverse subdivisions of evolutionary biology and from various countries accepted two major conclusions. 1. That evolution is gradual, being explicatory in terms of small genetic changes and recombination and in terms of the ordering of this genetic variation by natural selection, and 2. That by introducing the population concept, by considering species as reproductively isolated aggregates of populations, and by analyzing the effect of ecological factors, niche occupation, competition, adaptive radiation, on diversity and on the origin of higher taxa, one can explain all evolutionary phenomena in a manner that is consistent both with the known genetic mechanisms and with the observational evidence of the naturalists. Julian Huxley, 1942, designated the achievement of consensus on these points as the evolutionary synthesis. It required that the naturalists abandon their belief in soft inheritance and that the experimentalists give up typological thinking and be willing to incorporate the origin of diversity in their research program. It led to a decline of the concept of mutation pressure, and its replacement by a heightened confidence in the powers of natural selection, combined with a new realization of the immensity of genetic variation in natural populations. This tells us what happened during the synthesis, but it does not tell us how it came about. There is now a rather general agreement that the reconciliation was the work of a handful of evolutionists who were able to build bridges among different fields and remove misunderstandings. The architects of the evolutionary synthesis. What qualifications did an evolutionist have to have in order to be able to function as a bridge builder? First of all, he had to be more than a narrow specialist. He had to be willing to become acquainted with areas of biology outside his own field of specialization, and to learn the new findings in these other fields. He had to be flexible, able to discard earlier ideas, and able to accept new ones. For instance, Sumner, Ernst, and Mayr, who had originally believed in soft inheritance, adopted a strict neo-Darwinian 567 interpretation after becoming acquainted with the new genetic findings. What is still lacking is a critical analysis of the writings of the architects of the synthesis. What, if any, were their new ideas? Was it a rich assembly of facts that had the decisive impact? Was it the focusing of attention on concrete evolutionary phenomena, speciation, adaptive radiation, evolutionary trends, and so on, that was particularly effective? Which new genetic insights were most helpful in eliminating misunderstandings? What was the particular role played by each of the bridge builders? None of 568 these questions, and there are many others, has yet been fully answered. Evidently, only a beginning has been made in the study of the evolutionary synthesis, Mayr and Provini, 1980. If we define as the architects of the synthesis those authors who in major publications actually constructed bridges among various fields, 6 names in particular come to our mind: Dobzhansky, 1937, Huxley, 1942, Mayr, 1942, Simpson, 1944, 1953, Ernst, 1947, and Stebbins, 1950. It must be stressed that there were numerous other evolutionists who had helped to clear the terrain so that the bridges could be built and who had supplied important building materials. This includes, first of all, Chetverikov and Timofey Fresovsky in the USSR, Fisher, Haldane, Darlington, and Ford in England, Sumner, Dice, Sturtevant, and Wright in the United States, Bauer, Ludwig, Stresemann, and Zimmermann in Germany, Tessier and El Heritier in France, and Buzzetti Traverso in Italy. 2 multi-author volumes have also contributed to the synthesis: Heberer's edited volume, Die Evolution der Organismen, 1943, and Julian Huxley's The New Systematics, 1940. When one looks at the 10 to 12 people most active in the synthesis, one finds that each of them occupied his own special niche. Mentioning the names Dobzhansky, Simpson, Mayr, Ernst, Huxley, and Stebbins makes this very evident. Yet, they all had one thing in common: they had recognized the communication gap between the various evolutionary schools, and had attempted to bridge it by reconciling the gene frequency approach of T.H. Morgan, R.A. Fisher, and others with the population thinking of the naturalists. As astonishing as its sudden arrival was the rapidity with which the synthesis spread through evolutionary biology. At an international symposium at Princeton, New Jersey, held January 2 to 4, 1947, in which representatives of the most diverse fields and schools, except hardline Lamarckians, participated, there was unanimous Diversity and synthesis of evolutionary thought. Universal and unanimous agreement with the conclusions of the synthesis. All participants endorsed the gradualness of evolution, the preeminent importance of natural selection, and the populational aspect of the origin of diversity. Jepson, Mayr, and Simpson, 1949. Not all other biologists were completely converted. This is evident from the great efforts made by Fisher, Haldane, and Muller as late as the late 1940s and 50s to present again and again evidence in favor of the universality of natural selection, and from some reasonably agnostic statements on evolution made by a few leading biologists such as Max Hartmann. There is complete agreement among the participants of the evolutionary synthesis as well as among historians that it was one particular publication that heralded the beginning of the synthesis, and in fact was more responsible for it than any other, Dobzhansky's Genetics and the Origin of Species, 1937. As L. C. Dunn rightly said in the preface, the book symbolized something which can only be called the Back to Nature movement. The very first chapter was devoted to organic diversity, and other chapters covered variation in natural populations, selection, isolating mechanisms, and species as natural units. Dobzhansky had successfully integrated the naturalist's profound understanding of evolutionary problems with the knowledge which he had acquired in the preceding dozen years as an experimental geneticist. Truly he was the first to build a solid bridge from the camp of the experimentalists to that of the naturalists. The evolutionary synthesis settled numerous old arguments once and for all, and thus opened the way for a discussion of entirely new problems. It was clearly the most decisive event in the history of evolutionary biology since the publication of The Origin of Species in 1859. Yet, historians and philosophers of science have been puzzled over just exactly how the synthesis fits into the theory of scientific advance. It was definitely not a revolution, since it was clearly only the final maturation of Darwin's theory of evolution. But does it even deserve the epithet synthesis? This I assert emphatically. I described above the radically different thinking and preoccupations of the two camps of evolutionary biologists, that of the experimental geneticists and that of the population naturalists. They truly represented two very different research traditions, as Lawton, 1977, has called it. Lawton observes that there are times when two or more research traditions, far from mutually undermining one another, can be amalgamated, producing a syn. 569. Thesis which is progressive with respect to both the former research traditions, p. 103. What happened in evolutionary biology from 1936 to 1947 was precisely such a synthesis between two research traditions that had previously been unable to communicate with each other. There was no victory of one paradigm over another, as described in Kuhn's theory of scientific revolutions, but rather an exchange of the most viable components of the two previously competing research traditions. For this reason it would be incorrect to state that the synthesis was merely the AC 570 septans by the naturalists of the newer findings of genetics. This would ignore the numerous concepts contributed by the naturalists, population thinking, the multidimensionality of the polytypic species, the biological species concept, with the species defined as a reproductively and ecologically autonomous entity, the role of behavior and of change of function in the origin of evolutionary novelties, and the entire emphasis on the evolution of diversity. All these concepts are indispensable for a full understanding of evolution, and yet they had been virtually absent from the conceptual framework of the experimental geneticists. In the short run, it was perhaps the refutation of a number of misconceptions that had the greatest impact on evolutionary biology. This includes soft inheritance, saltationism, evolutionary essentialism, and autogenetic theories. The synthesis emphatically confirmed the overwhelming importance of natural selection, of gradualism, of the dual nature of evolution, adaptation and diversification, of the populational structure of species, of the evolutionary role of species, and of hard inheritance. Even though this amounted to a drastic narrowing down of the options available to an evolutionist, it left many problems unsolved. These problems fall into two categories, indicated by these two questions: 1. What is the meaning of a given phenomenon, selection, gradual evolution, biological species, and so on? And, 2. How does a given evolutionary principle or phenomenon actually operate in an individual case, and what new problems does this raise, as applied to selection, isolation, the production of variation, stochastic processes, and so on? 13. Post-synthesis developments. A number of reasonably well-delimited periods can be recognized in the history of evolutionary biology. The main concern of evolutionists in the period from 1859 to about 1895 was the proof of evolution and the establishment of the various lines of common descent. Phylogenetic research was the major preoccupation of evolutionists. From about 1895 to the beginning of the evolutionary synthesis, 1936, controversies within the held dominated research and writing. The great questions of the period were: is evolution gradual or saltational? Is inheritance soft or hard? Is genetic change due to mutation pressure or selection pressure? The period from 1936 to the 1960s was dominated by the evolutionary synthesis and the working out of the finer details of the new insights. The populational approach dominated all investigations, and there was a new interest in diversity, particularly at the level of populations and species. The adaptational aspects of variation were analyzed as due to selection forces, but all genetic interpretations were dominated by the gene frequency concept. Later developments in evolutionary biology are diffuse. They include a strong interest in the stochastic components of variation and a recognition of the diversity of the genetic material, in the form of various types of DNA. Broad contacts were established with ecology and behavioral biology, and the study of the evolution and evolutionary role of macromolecules became an ever more important branch of evolutionary biology. As a result of all these developments, the study of evolution has become a highly diversified science. More than that, the expansion of evolutionary thinking to all branches of biology led to a tearing down of the walls between evolutionary biology and other fields of biology, to the extent that it is now impossible to say whether such fields as evolutionary ecology, evolutionary ethology, and molecular evolution should be included with evolutionary biology or with the adjacent fields with which they have been fused. What is perhaps most significant is that it has finally become respectable for a biologist to ask why questions without being suspected of being a teleologist. The unified interpretation of the evolutionary process had a highly beneficial impact on the standing of evolutionary biology in the whole field of biology. By eliminating all interpretations that signaled an implicit conflict with physico-chemical explanations, namely, those theories that were vitalistic or teleological, evolutionary biology became far more respectable than it had been during the preceding period, when it was maligned by the ex-per 572 mentalists as speculative. The new insight which emerged from the elucidation of the structure of DNA in 1953, that living matter consists of two fundamentally different components, a historical one, the genetic program, and a functional one, the translated proteins, necessitated at once an extension of the causal analysis of all biological phenomena to the historical component. This led to the recognition that it is not only legitimate but indeed essential to any reasonably complete biological analysis to include a study of the evolutionary history of all components of living organisms. This extension of evolutionary thinking has affected every branch of biology. Evolutionary biology certainly represents a splendid example of shifting interests and research programs in a field of science. My simplified description conceals, however, that hardly any line of approach is ever completely terminated, even when more promising new approaches open up, nor does it mention that the roots of any new approach usually reach back several decades prior to the date when it became productive. Every new technique and every switch of an investigator from one field of competence to another is likely to initiate new approaches. Obviously, it is impossible to represent adequately the full complexity of the advances in evolutionary biology, or for that matter in any field of science. In 1946 a special society was established in the United States to cultivate the study of evolution, and in 1947 Ernst Mayr founded evolution, a journal devoted to research in evolutionary biology. The American Naturalist, which in the 1930s had been largely converted into a journal of experimental biology, returned after the synthesis to its specialization in evolutionary biology. Other periodicals devoted to evolution were founded in the United States and in other countries. The number of new textbooks on evolution has grown steadily, and so have courses in evolutionary biology given at colleges and universities. The literature has grown to such an extent that frequent review papers are now necessary. Post-synthesis developments. This prodigious activity poses a serious problem for the historian. It has now become quite impossible to analyze the recent advances anywhere near adequately. The best I can do is to sketch the major outlines of some recent researches and to mention at least some of the unanswered questions that appear particularly intriguing to the current generation of evolutionists. For a listing of the relevant literature I must refer to the contemporary journals and some recent textbooks. 1. Let me begin by mentioning evolutionary problems that have occupied, in recent years, the attention of population genetics and of molecular biology. Population genetics. Population genetics since the 1930s had as its major objective to test the conclusions of mathematical population genetics in the held and in experimental populations in the laboratory. This work was dominated by the definition of evolution as the change of gene frequencies in populations. Outstanding in this research tradition is the important series by Dobzhansky and Associates entitled The Genetics of Natural Populations, 1938 to 1976, dealing largely with Drosophila pseudo-obscura and its sibling species, Lewontin et al., 1981. What Dobzhansky attempted to determine were numerical values for selection pressure, gene flow, effective population size, frequency of lethals and other concealed recessives, and other factors of potential evolutionary significance. 2. Of particular advantage in this research was the fact that this species, like most other species of Drosophila, is rich in paracentric chromosomal inversions, recognizable in the banding pattern of the giant salivary chromosomes, each with a somewhat different geographic range. Dobzhansky found that the relative frequency of a given inversion may vary not only geographically but also seasonally and in some cases through a series of years. A number of regularities indicated that the frequency was controlled by selection, and this was confirmed experimentally. Mayr, 1945, attempted to interpret the gene arrangements as ecotypes adapted in such a way that the bearers of different inversions could utilize different local niches. This has been subsequently confirmed by Coluzzi et al. 1977, tour gene arrangements in mosquitoes, Anopheles. What is most remarkable is that bearers of different gene arrangements not only have a different fitness in different niches but also the behavioral capacity to search out the right niche. 575. 574. A major technological advance in the study of Drosophila populations was made by THIRD and Heritier, who invented population cages in which populations of Drosophila of various sizes and of various genetic heterogeneities could be continued for many generations without the input of new alien genes. Keeping these cages under different conditions of temperature and food supply, one could test different genes and gene combinations for relative fitness and calculate selection pressures. Dobzhansky and others soon took up this technique, which is now utilized in numerous genetics laboratories, with all sorts of modifications. It provided an excellent method for the experimental study of natural selection in populations. Molecular biology. Many of the findings of biochemistry, ever since there has been such a branch of biology, were important for evolutionary biology, even though this was not at first recognized. One might mention here the discovery of nuclein by Mayr in 1869, the work of Nuttall in immunology, that of Garrett on inborn errors in metabolism, of Landsteiner on blood groups, and the later work of Beadle and Tatum. Yet, the phoenix-like rise of molecular biology did not really start until the discovery of the structure of DNA in 1953. This, at first, had little impact on previously established evolutionary concepts. Of the greatest immediate importance was the finding that the translation from nucleic acids to peptides and proteins is a one-way street, the central dogma. This discovery supplied the last and most conclusive proof for the impossibility of an inheritance of acquired characters. The extraordinary precision and reliability of the replication of the germ plasm during each nuclear division was, until recently, not a conceptual problem. Essentialists took it for granted and believers in soft inheritance considered it irrelevant. Biophysicists, however, were rather puzzled by the almost error-free performance of the complicated replication process. An occasional error, of course, was recorded, and this is what the geneticist calls a mutation. For the evolutionist, the margin of error was not particularly disturbing since he knows what immense numbers of gametes and zygotes are lost anyhow prior to or during development. What was unexpected was the discovery of repair mechanisms which permit the subsequent repair of errors in post-synthesis developments. Replication. The existence of these mechanisms poses problems concerning the definition of rate of mutation, but they do help to explain the infrequency of observed errors of replication. The finding that the genetic code is, on the whole, identical in all organisms, including the prokaryotes, was an important addition to the evidence that all life on Earth, as it exists now, can be traced back to a single origin. This and some other discoveries of molecular biology have helped to simplify and unify biology, but there have been other findings that may require certain modifications in genetic theory or at least in our understanding of genetic processes. Most of the early analysis in molecular biology was done on viruses and bacteria and, following Occam's razor, the assumption was made that the findings in prokaryotes could be applied to the eukaryotes without modification. Recent studies indicate, however, that this assumption is not necessarily valid. In particular, it is now evident that the eukaryote chromosome has a very complex structure, radically different from the simple tandem DNA double helix of the prokaryotes. Instead, the DNA is intimately associated with various proteins, particularly hist-1s, with which it forms molecular aggregates, nucleosomes, of various sizes, which seem to differ functionally. At the present time these researches are primarily of interest for physiological genetics, but there can be little doubt that eventually the knowledge of the organization of DNA in the eukaryote chromosomes may give answers to various not yet solved evolutionary problems, such as the control of evolutionary trends, the stability of the phenotype in many evolutionary lines, rapid shifts to new evolutionary grades during genetic revolutions, and others. It is quite possible that we stand on the threshold of major discoveries. When Nirenberg and Matthaei succeeded in 1961 in breaking the genetic code, it was widely believed that the last major problem of molecular biology had been solved. Actually, the frequency of altogether unexpected discoveries has since accelerated. The major bearing of these discoveries, up to now, has been on aspects of gene physiology, but there is little doubt that all these aspects of genes are also of evolutionary importance, as will surely become apparent when the molecular processes are fully understood. The structures that control genetic processes are of submicroscopic dimensions, and molecular biologists have been extraordinarily ingenious in developing new techniques that permit M. 575. Phalanx on molecular structures and processes and on their variation. In fact, at this point more is being learned about molecular evolution by the application of new techniques than by the development of new concepts. One of the most important of these techniques, first employed by Clem Markert, is that of starch gel electrophoresis. 3 soluble proteins migrate in a gel in an electric held different distances, depending on their size and their electrical qualities, and can thus be separated from each other. Each protein can be made visible in the gel by a different staining Tech 576 technique. By this method the genotype of an individual can be determined directly without any breeding analysis. In fact, 20, 30, or even more than 70 gene loci can be analyzed simultaneously for the existence of alleles. The method makes possible what no method had permitted before, the determination of the level of heterozygosity of individuals and of populations. It also permits the comparison of different geographic populations of a species, and of related species, to determine what fraction of the spectrum of alleles is the same or different. The greatest weakness of the method is that it reveals the variation only of structural, enzyme, genes. A second weakness is that it cannot separate alleles that have the same electric load, and it underestimates therefore the number of alleles. By using additional methods, heat degradation, change in pH, further alleles are often discovered. Since only a few enzymes have been analyzed thoroughly, it is still controversial what fraction of genetic variability is overlooked during the conventional electrophoresis method. The elegance of the technique and the ease by which it can be applied even by a non-biochemist have led to a veritable explosion of studies of enzyme variation ever since Hubby and Lewontin, on Drosophila, and Harris, on man, first used this technique in 1966 to estimate heterozygosity in individuals and populations. The number of discoveries made possible by this technique is large: new sibling species, a quantification of degrees of difference between closely related and more distant species, a correlation, or not, of enzyme change with speciation events, a correlation, or not, of geographic variation of enzymes with climatic and other environmental factors, and many others. One of the conclusions drawn from these studies, more or less confirmed by the behavior of other macromolecules, is that there are regularities in the rate at which molecules change over geological time, that is, the rate at which amino acid residues are being replaced in evolution. It has therefore been postulated by post-synthesis developments. Certain authors, first by Pauling and Zucker-Kandel and later particularly by Sarek and Wilson, that one can utilize this regularity to construct a molecular clock and infer the date of the bianching point between two evolutionary lines from the degree of difference of homologous molecules, Wilson et al., 1977. At the present time there are considerable discrepancies between the chronologies of the branching points calculated by the molecular clock and those calculated by paleontologists on the basis of the, admittedly scanty, fossil record. And there is other evidence that the concept of the molecular clock must be applied with caution. For instance, the same molecule may change during the same geological time interval more rapidly in some phyletic lines than in others. Also, it seems that the rate of change may occasionally be drastically slowed down in certain phyletic lines. The molecular distance between man and chimpanzee, for instance, is smaller than that between certain species of Drosophila. The other difficulty is that the concept of the molecular clock implies a built-in regularity, one might almost say an autonomy of the changes. The clock has sometimes been described in such terms as the occurrence of one mutation every 2 million years. Such a formulation is of course utterly misleading. Mutations at the same gene loci occur quite frequently, but are consistent while eliminated by errors of sampling or by natural selection until the molecular milieu has changed sufficiently to favor a change in the three-dimensional structure of the molecule. In other words, molecular clocks are governed by natural selection, not by rates of mutation. This has been shown for many macromolecules, but to none more convincingly than for hemoglobin. Here the replacement of even a single amino acid among more than 300 can be highly deleterious. Thus, sickle cell anemia is caused by the replacement in the beta chain of hemoglobin of a single glutamic acid residue by valine. In man more than 200 different hemoglobin mutations are now known, discovered as private blood types, and even though in many cases they are not the cause of a pronounced blood disease, not a single one of these mutations has succeeded in becoming either fixed or polymorphic in the hominid ancestry. That these mutations are being discriminated against by natural selection is indicated by the fact that our distant relative, the chimpanzee, has a hemoglobin almost ident with ours in spite of the documented high mutation rate OT hemoglobin. The explanation of the molecular clock phenomenon is pre. 577. 578. Sumably that each macromolecule regularly interacts in the cell with some 10 to 25 other macromolecules. However, when some of these other molecules evolve, by answering specific selection forces, These changes sooner or later produce a selection pressure on the original molecule to replace an amino acid residue in order to achieve the best possible fit with its genetic milieu and restore a steady state. Kinds of DNA. Because all genes consist of DNA, it was assumed after 1953 that all genes were basically identical in their function and evolutionary characteristics. The researches of the last 2 decades have revealed that this is not the case. There are a number of categories of genes such as enzyme genes, genes for structural, non-soluble, proteins, regulatory genes, and perhaps many more kinds of which so far we have not even an inkling. A higher organism may have enough DNA in its nucleus for about 5 million genes, and yet genetic research finds evidence for only about 10,000, or at most 50,000 traditional, enzyme, genes. They, together with other kinds, are among the so-called unique sequences, but there are also several classes of repetitive DNA and much seemingly silent DNA, the function of which is quite puzzling. Much of the DNA that is not accounted for by the enzyme DNA evidently has regulatory functions. Only the very first beginnings have been made in the study of the differences in the evolutionary behavior of the various kinds of genes. Davidson and Britton, 1973, 1979. New discoveries in molecular genetics have been following each other since the late 1960s, and particularly since 1975, at such breakneck speed that it is quite impossible for a non-specialist to keep up with them. Furthermore, some of these discoveries were so unexpected that their interpretation is still altogether controversial. These discoveries concern the structure of the eukaryote genome. For instance, it was found that some genes, transposable genes, may change their position on the chromosome. Even more surprising was the discovery that many genes include sequences, introns, that are not transcribed into the messenger RNA, mRNA, but are excised during the transcription process, and the remaining parts of the genes, exons, are subsequently spliced together into the functional mRNA. 2 questions arise: how could such a peculiar system have ever evolved? Are the introns merely inert ballast, or do they have a still unknown func? Post-synthesis developments. The teleological answer that the seemingly functionless DNA is stored up in order to have it available in future times of need is altogether unsatisfactory. One interpretation that is rather popular at the moment, Orgel and Crick, 1980, is that this extra DNA is, so to speak, parasitic, the organism being helpless to prevent its replication and accumulation. Although valid arguments in favor of this hypothesis exist, it is intuitively distasteful to a Darwinian. Surely natural selection, a Darwinian would say, should be able to come up with a defense mechanism against such an expensive type of parasitism. Considering how very little is known about the functioning of gene regulation, it is premature to write off the introns as genetically inert. For all we know, it might be very important to keep certain segments, exons, of the gene separated from each other prior to translation. Indeed, there is now evidence that the introns help to regulate gene splicing. Equally puzzling is the fact that closely related species or genera may drastically differ from each other in their repetitive DNA and in other components of the genome without much visible morphological change, and sometimes even without a loss of the ability to hybridize. How this may affect evolutionary potential is still entirely unknown. Ever since the pioneering work of Mirsky and RIS, 1951, it has been known that different groups of organisms have differing amounts of DNA in their cells, nuclei. The smallest amounts are found in prokaryotes and fungi, the largest amounts in urodels, lungshees, and some groups of plants. Some regularities are known, nearly all of them with exceptions, such as that annual plants usually have less DNA than related perennials or trees. Species with slower growth rates, longer developmental times, tend to have more DNA than their relatives. The enormous differences in amount of DNA in different taxa seems to support the idea that much of the excess DNA cannot be of very high selective significance. Further evolutionary speculations, however, are premature as long as our knowledge of gene regulation in eukaryotes is as rudimentary as it is today. Evolutionists since Lamarck have been familiar with the principle of mosaic evolution, which says that different components of the phenotype may evolve at highly unequal rates. It is now being discovered that such inequality of evolutionary rate is also true for molecular evolution. Wilson and colleagues, 1974, for instance, believe that enzyme genes in mammals and anurans, such as frogs, evolve at about the same rates, while the regulatory genes which control morphological evolution change at a much higher 579. 580. Rate in mammals than in frogs. In South American mimicking butterflies, the genes controlling color patterns show very strong geographic and virtually no individual variation, while the enzyme genes of these species show very high individual and virtually no geographic variation. Turner, Johnson, and Eames, 1979. Also, a strong difference in variability between enzyme genes and other protein genes was found by recent investigators. Finally, the genes that control speciation seem to vary quite independently of the enzyme genes. Here is a new frontier of evolutionary biochemistry which I rather suspect will produce major surprises in the near future. This much is evident already, that different groups of genes seem to answer to different selection pressures and follow their own evolutionary pathways. The results of the study of one group of genes, let us say enzyme genes, cannot be generalized to apply to all categories of genes. This seems equally true for response to selection pressure, to variability, level of heterozygosity, and to molecular clocks. Chromosomal changes also have very different evolutionary rates in different organisms. The karyotype seems to be exceedingly stable in some groups and to change very rapidly in others, for instance in certain groups of mammals. Each set of genes may play a different role in evolution. Enzyme gene differences apparently accumulate at a fairly regular rate and are thus ideal yardsticks for molecular clocks. Speciation events seem to be largely independent of enzyme genes. The reason why there are different kinds of genes is that they have different functions. However, our understanding of these functions is as yet very elementary. Chetverikhov's concept of the genetic milieu is beginning to acquire a new meaning. The study of the action of genes, it is now being realized, must be supplemented by the study of the interaction of genes. A pioneering discussion of the functioning of genotypes was Lerner's Genetic Homeostasis, 1954, in which massive evidence for the importance of gene interaction was presented. Dobzhansky's research on synthetic lethals reinforced this thinking. He showed that certain genes or chromosomes could convey superior fitness in some combinations, and be lethal in combination with other chromosomes. This spelled the end of the faith in constant fitness values of genes, even though these findings, in the absence of an analysis of the causes of such relativity, are only a starting point in a new area of research. See Mayr, 1963, Chapter 10, see also Mayr, 1974, Carson, 1977. The study of molecular evolution has revealed the surprising post-synthesis developments. Fact that most macromolecules of higher organisms can be traced right back to the prokaryotes. And yet a prokaryote may have only a fraction, 1/I0,000, of the amount of nucleic acid of a high-A organism. Where do all the other genes come from? The first geneticists who speculated about this were apparently members of Morgan's group, Metz, 1916, Bridges, 1918. The sophisticated researches of Sturtevant, Bridges, and Muller revealed that new genes arise when new pieces of chromosome are inserted into an existing chromosome. This is either effected by unequal crossing over or by a major chromosomal mutation, particularly a translocation. The analysis of salivary chromosomes in Drosophila provided a welcome opportunity to confirm the occurrence of duplications inferred on the basis of purely genetic evidence. In other cases, whole chromosomes may be added to the genome, owing to non-disjunction, or the chomosome set as a whole may be duplicated, by the process of polyploidy. The work of the early pioneers on gene duplication has been greatly expanded in recent years, for example, Ono, 1970. The evolutionary advantage of small-scale duplications is that they interfere much less with the normal functioning of the genome than do sometimes major translocations or the addition of whole chromosomes, as in Down syndrome, or chromosome sets. Small duplications are, thus, more easily incorporated into the gene pool. The duplicated genes can assume new functions and by divergent mutation become increasingly more different from their sister gene. It has been questioned whether such duplication can lead to the production of entirely new proteins, but the evolutionary history of far too few macromolecules is known to permit such sweeping conclusions. It is, however, quite possible, if not probable, that the most important classes of macromolecules were invented in the very early history of life. Origin of life. When Darwin in 1859 proposed the theory of common descent, he realized that at the beginning there had to be a first life, and he expressed it in the somewhat biblical sentence of life having been originally breathed into a few forms or into one origin, 490. This was a most daring formulation, since at that time the differences among the numerous kinds of organisms appeared far too great for a single origin. Even after the students of phylogeny had succeeded in tracing animals and plants back to 581 simple algae and flagellate ancestors, a common origin of the prokaryotes, bacteria and relatives, and of the eukaryotes, higher organisms, seemed still altogether unlikely. And yet this is now well established through the researches of molecular biology. Not only the general chemical similarity of all forms of life, but specifically the fact that the genetic code is identical everywhere, including the prokaryotes, leaves no longer any doubt that life, as it is now found on Earth, originated only a single time. And there are now sound theories concerning the origin of the eukaryotes. Margulis, 582-1981. All organisms now living on Earth unquestionably descended from a single ancestral stock. If there had been several independent origins of life, all the others succumbed to the competition of the stock which now rules the world. An origin of life from inanimate matter would be spontaneous generation. It so happens that, precisely at the time when the theory of common descent was proposed by Darwin, the concept of spontaneous generation was under particularly heavy attack, owing to the experimental refutation of such a possibility by Pasteur and others. Farley, 1974. This posed a real dilemma for the evolutionists, and Darwin stated with resignation, 1863, "It is mere rubbish, thinking at present of the origin of life, one might as well think of the origin of matter." But then, of course, being the inveterate speculator that he was, he mused in 1871, "It is often said that all the conditions for the first production of a living organism are now present, which could ever have been present. But if, and oh, what a big if, we could conceive in some warm little pond, with all sorts of ammonia and phosphoric salts, light, heat, electricity, etc. present, that a protein compound was formed, ready to undergo still more complex changes, at the present day such matter would be instantly devoured or absorbed, which would not have been the case before living creatures were formed." LLD, 3, 18. For the reason why the problem of the origin of life was so intractable for several generations after 1859 was that the whole question had to be reformulated. One thought typologically of a living species suddenly arising from inanimate matter, and one thought of the Earth as if its atmospheric and other environmental conditions had remained constant throughout all geological ages. These assumptions had to be thoroughly revised. The botanist Schleiden, 1863, was apparently the first to suggest that an origin of life, a first cell, might have been possible under the entirely different atmospheric conditions of the young Earth. This post-synthesis developments has now been thoroughly substantiated. The young Earth is now believed to have had a reducing atmosphere, consisting mostly of water vapor, methane, and ammonia. Free oxygen, which would oxidize and thus destroy any possible precursors of life, was virtually absent at the time when life originated on Earth, about 3.5–3.8 billion years ago. The oxygen which, from about 1.9 billion years ago on, began to accumulate on Earth was produced by the photosynthetic organisms which had evolved by then. The second revision concerns life. Here the essentialistic concept of its sudden origin had to be replaced by the evolutionary concept of gradualism. We now realize that the origin of life was as gradual as the origin of man. Just as Homo sapiens is connected with the lower primates by a series of intermediate hominids, so did life have a series of precursors. Such intermediate molecular stages between inanimate matter and well-organized living beings are not now found in nature. They would not be able to survive in an oxidizing atmosphere and exposure to the enormous variety of microorganisms that subsist on organic molecules. In a reducing atmosphere, ultraviolet radiation and lightning can indeed produce organic compounds such as purines, pyrimidines, and amino acids that serve as the building stones of life. This was experimentally demonstrated by Miller, 1953, following a suggestion by Urey. Haldane, 1929, and Oparin, 1924, had already previously suggested scenarios to explain how the gap between inanimate matter and life could be bridged. Fox, 1977, has made very imaginative contributions toward the solution of this problem. Curiously, the findings of molecular biology have complicated the task of explanation rather than simplified it. Polypeptide chains, proteins, even in the simplest organisms, are assembled from amino acids under the guidance of a nucleic acid genetic program. Indeed, there is now such a complete symbiosis between nucleic acids and proteins that it is difficult to imagine either being able to function without the other. How then could the first proteins have been assembled and replicated without nucleic acids, and how could nucleic acids have originated and been maintained in the primeval organic soup if they had no other meaning than to control the assembly of proteins? See Chapter 10, for a further discussion of this problem. The problem of the origin of life, that is the reconstruction of the steps from simple molecules to the first functioning organism, is one that poses a keen challenge to the students of molecular evolution. 5. A full realization of the near impossibility of an 583. Origin of life brings home the point how improbable this event was. This is why so many biologists believe that the origin of life was a unique event. The chances that this improbable phenomenon could have occurred several times is exceedingly small, no matter how many millions of planets in the universe. The preceding short review of recent advances in molecular biology indicates the close connection between research in molecular biology and in evolutionary biology. The vital interest of the molecular biologist in evolution is documented by the founding of a journal for molecular evolution and by a series of recent symposia and review volumes, for example, Ayala, 1976. As the evolutionist would say, the study of the evolution of molecules has become an important branch of evolutionary biology. The assertion is sometimes made that, in addition to the Darwinian theory of evolution, there is now a molecular theory of evolution. The validity of this claim is doubtful. Two of the more important evolutionary phenomena that occur at the molecular level, hard inheritance, as espoused from Weissman, 1883, to the Morgan School, and mutation, De Vries, 1901, Morgan, 1910a, were accepted, at least in principle, decades before the rise of molecular genetics. At this time it is still uncertain whether some of the recent discoveries of molecular genetics, repetitive DNA, gene splicing, wandering genes, do or do not require any revision of the synthetic theory of evolution. Presumably, the new discoveries enlarge only the amplitude of genetic variation that is available for the exercise of natural selection, as well as forming constraints on the action of natural selection. I have used molecular biology as an illustration of the increasingly close relationship between evolutionary biology and other branches of biology. An equally active interaction has developed between evolutionary biology and many other biological disciplines. At the present time, evolutionary questions seem to dominate the field of ecology. They are also of great importance in behavioral biology. This is well illustrated in recent textbooks of ecology and of animal behavior. Even though the evolutionary synthesis did not solve all the problems of evolutionary biology, at least it created a united front. A glance at the current evolutionary literature shows how much disagreement in the interpretation of certain specific problems of evolution still exists. Yet, the opposing viewpoints do not question any of the basic theses of the synthetic theory, they merely have different answers for some of the pathways of evolution. I will post-synthesis developments. Attempt to demonstrate the nature of these disagreements by discussing some of the open questions in three major areas of evolutionary biology: the theory of natural selection, the problem of speciation, and the processes of evolution above the species level, macroevolution. Natural selection. The strong resistance to natural selection which had characterized the post-Darwinian period and Mendelism was largely broken by the synthesis. The resistance had been so powerful because it was the one thing which all anti-Darwinians had in common, for the Neo-Lamarckians opposed selection as fervently as did the mutationists. The most widely known selection experiments of the first third of the century were those of Johansen. Having received much of his training in chemical laboratories, he approached his task in the most unbiological manner. In order to have suitable experimental material, he first attempted to establish homogeneous classes, pure lines. Not surprisingly, such samples of genetically identical individuals, the result of many generations of inbreeding, did not respond to selection. From this Johansen concluded, 1915, 609, 613, that selection cannot produce a deviation from the mean in self-fertilizing species, and even the most careful experiments with cross-fertilizing plants and animals confirm most convincingly our interpretation of an inability of selection to achieve more than a mere isolation or separation of previously existing constitutionally different organisms. Selection of different individuals creates nothing new, a shift of the biological type in the direction of selection has never been substantiated. He finally concludes that it is completely evident that genetics has deprived the Darwinian theory of selection entirely of its foundation, and the problem of evolution is still an entirely open question, p. 659. This conclusion was widely accepted among the experimentalists, and even T.H. Morgan, 1932, stated, the implication in the theory of natural selection that by selecting the more extreme individuals of a population, the next geneation will be moved further in the next direction, is now known to be wrong. As late as 1936, two distinguished British zoologists, G.C. Robson and O.W. Richards, concluded, we do not believe that natural selection can be disregarded as a possible factor in evolution. Nevertheless, there is so little positive evidence in its 585, 586 favor, that we have no right to assign to it the main causative role in evolution. No wonder that in this intellectual climate of the 1920s and 30s the Darwinians had to devote so much effort to the refutation of anti-selectionist arguments. The skepticism of the anti-Darwinians was not entirely unjustified. Direct proof for the occurrence of natural selection in nature and even in the laboratory was very scanty almost up to the middle of the 20th century. The demonstration by Bumpus, 1896, of differential mortality in sparrows, as a result of an ice storm, was for several decades the only evidence, and thus forever cited by selectionists. To make matters worse, the Darwinians themselves were rather divided about selection in the pre-synthesis period. As we saw, most of them, following Darwin's lead, accepted some soft inheritance, such as use and disuse. Wallace clearly was the most consistent of the early selectionists and the first to endorse Weismann's thesis that there is no soft inheritance and hence an Allmacht der Eichtung. In fact, Wallace ascribed even the origin of isolating mechanisms strictly to selection, in conflict with Darwin, who could not visualize such a sympatric process. Modern students of speciation tend to agree with Darwin. But Weismann and Wallace were very much in the minority in their unconditional support of natural selection. Most other evolutionists held various reservations. For objections that were raised against the efficacy of natural selection, see Chapter 11, for more detailed presentation see Kellogg, 1907, Mayr and Provini, 1980, and numerous volumes in the anti-Darwinian literature. Many factors played a role in the changing climate of opinion concerning natural selection. The following were perhaps the most important ones. 1. The actual demonstration of the effectiveness of selection in selection experiments in the laboratory as well as in the work of numerous animal and plant breeders. Experiments carried out in nature, such as those of Kettlewell on industrial melanism, Ford, 1964, were particularly convincing. The introduction of the method of population cages by T. Sear and L. Haratier in the 1930s, see above, a technique soon adopted by Dobzhansky and other Drosophila workers, gave rise to an active program of experiments on natural selection under different conditions of temperature, humidity, food supply, crowding, and competition of different genetic stocks. 2. The refutation of the existence of soft inheritance by GE. Post-synthesis developments. Geneticists, which left virtually no alternative than to explain gradual evolution by natural selection. 3. The refutation of the claim that most attributes of organisms are without selective value. Even Haldane, 1932, 113, had admitted, there is no doubt that innumerable characters of animal and plant species show no sign of possessing selective value, and, moreover, these are exactly the characters that enable a taxonomist to distinguish one species from another. Eventually it was shown by various investigators, for instance Wrench and particularly E. B. Ford's Oxford group, that many of the characters that had previously been called neutral have a selective value when carefully investigated. 4. The calculations of Norton, Haldane, Fisher, and others showing that even very slight selective advantages are important when continued over many generations. 5. The spread of population thinking, in particular the demonstration by the new systematists that discontinuities among species and higher taxa could be explained as originating gradually through geographic speciation and extinction, hence not acquiring saltations. In his Genetics and the Origin of Species, 1937, Dobzhansky devoted an entire chapter of 43 pages to the subject of natural selection. What made his presentation particularly effective was that he treated selection not merely as a theory but as a process that could be substantiated experimentally. Furthermore, he showed that there is no conflict between gradual adaptive geographic variation, as reflected in Wrench's climatic rules, for instance, and selection. This removed any need to take refuge in Lamarckian explanations, as the naturalists had been forced to do previously, owing to the arguments of the mutationists. Mayr, 1963, 182-203, analyzed in detail many of the problems which selectionism had raised in the preceding decades. Among these problems 5 will be singled out for further discussion. Kinds of natural selection. There are several ways in which kinds of natural selection can be classified. One of these is based on the portion of the curve of variation to which selection pressure is applied. Stabilizing selection refers to selection directed against both tails of the curve of variation. This corresponds to the elimination of the essentialists, that is, all deviations from the normal are discriminated against. D. 587. 588. Rective selection is said to occur when one tail of the curve is favored and the other is discriminated against by natural selection, resulting in a steady advance of the mean value of the curve. Diversifying, disruptive, selection favors both tails of the curve over the mean, resulting in a bimodal curve, as is found in species with mimetic or other forms of polymorphism. The probabilistic nature of natural selection essentialists have had great difficulty in understanding that selection is a statistical rather than an all-or-none phenomenon. The philosopher Charles Sanders Peirce saw this perhaps more clearly than his contemporaries and remarked that even though natural selection may fail in an individual case, variation and natural selection, in the long run will adapt animals to their circumstances. Mayr, 1963, 184, likewise emphasized the probabilistic nature of selection. Even though philosophers may still refer to survival of the fittest, biologists no longer use such deterministic language. The target of selection. By adopting the formulation evolution is caused by mutation and selection, some geneticists contributed to a widely held misconception. This formulation has been interpreted to mean that the mutated gene is the actual target of selection. By contrast, naturalists from Darwin on and the more perceptive geneticists have always emphasized that not genes but whole organisms potentially reproducing individuals are the unit of selection. This means that the effects of recombination and of gene regulation, as well as the capacity of developing phenotypes to respond to the environment, are as important for selection as is mutation, indeed quantitatively actually more important by several orders of magnitude. A difficulty arose, however, when Fisher, 1930, and other mathematical geneticists chose the gene to be the unit of selection and attributed to each gene a definite fitness value. Fitness was redefined as the contribution a given gene makes to the gene pool of the next generation, see also Haldane, 1957. This, in turn, led to a very questionable definition of evolution, change of gene frequencies in populations, and to the legitimate criticism that frequency changes in single genes left many, in fact most, evolutionary phenomena unexplained. Some, if not most, of the current criticism of the theory of selection consists of attacks on the un-Darwinian assumption of genes as units of selection. Post-synthesis developments. This must be emphasized, because it demonstrates how misleading and confusing the concept of internal selection is, which has been promoted by several recent authors. It is quite impossible to partition selection into two parts, one caused by the external environment and another one caused by the internal factors of physiology and development. Such a partition is impossible because the result of selection is determined by the interaction between the external environment and the physiological processes of the organism as a whole. There is no internal selection. All developmental and regulatory processes contribute to the fitness of an individual either favorably or unfavorably, but this is evaluated when the individual is exposed to the external environment, including competition from individuals of the same 0-1 size. Darwin already was fully aware of the importance of these internal factors, as is evident for instance from his discussion of correlation, Origin, 143-150. When a modern author still ascribes to the Darwinians the obsolete formula mutation and selection, it is not surprising that he considers it as insufficient to explain appropriate evolutionary response. No one who still uses this formulation can possibly understand the actual causation of evolutionary change. Leading evolutionists have rejected the mutation as the target of evolution for more than 40 years. The product of selection as a compromise. Since the phenotype as a whole is the target of selection, it is impossible to improve simultaneously all components of the phenotype to the same degree. Selection cannot produce perfection, for in the competition for reproductive success among members of a population, it is sufficient to be superior and not at all necessary to be perfect. Furthermore, every genotype is a compromise between various selection pressures, some of which may be opposed to each other, as for instance, sexual selection and crypsis, or predator protection, Endler, 1978. Owing to the cohesion of the genotype, it is sometimes not possible to improve one component of the phenotype without damaging some other component. After each shift into a new adaptive zone, certain adaptations to the previous zone become liabilities. The aquatic mammals had to reduce and eliminate so far as possible all specific adaptations for a terrestrial mode of living. The bipedal hominoids are still burdened by their quadrupedal past. What evolutionists had long called the compromises of evolution is called by modern ecologists the optimization process of 589. Evolution. There is a cost to every evolutionary advance, such as running faster, having more offspring, utilizing a new source of food, and selection determines whether or not the added advantage is worth the cost. The result is that the phenotype is often a patchwork of features that were specifically selected for a particular function, or as the answer to a particular selection pressure, and others that are the byproduct of the genotype as a whole and are simply tolerated by selection. From Darwin's time on, naturalists have asked themselves into which of the two categories they 590 should class differences among species. For instance, is the difference in the striping of Burchell's and Greavy's zebra a result of different selection pressures in the different parts of Africa where these species originated, or, as is more likely, was there simply a selection for striping to which the genotypes of the two species responded differently? As long as certain geneticists believed in an independent fitness of every gene, each having one optimal fitness value, one could believe that every aspect of the phenotype was the appropriate response to ad hoc selection. But the fact that the individual as a whole is the target of selection and, furthermore, that many, if not all, genes are interacting with each other, sets severe limits for the response of the phenotype to selection. This is why man still has an appendix, a vulnerable sacroiliac joint, and poorly built sinuses. Gregory, 1913-1936, called the totality of the ad hoc adaptations the habitus and the tolerated remnants of the past the heritage. The conclusion that not every detail of the phenotype is shaped by ad hoc selection is reinforced by a phenomenon which Bach, 1959, has designated as multiple pathways. For instance, pelagic marine invertebrates have a great diversity of mechanisms by which to stay afloat in the water, gas bubbles, oil droplets, or an enlargement of the body surface. In each case natural selection, which is always opportunistic, made use of that part of the available variation that led most easily to the needed adaptation. The misguided atomistic reductionist strategy of dissecting an organism into as many parts as possible and demonstrating the selective value of each of these pieces has brought the whole concept of adaptation somewhat into dispute. To that extent, some of the objections to natural selection brought forth by opponents of selectionism, for example, Gross, 1977a, were perfectly valid. Selection is probabilistic, errors of sampling in small populations inevitably have stochastic effects, and the integration of the organism as a whole always places severe constraints on the response. Post-synthesis developments of individual features. To be sure, organisms on the whole are well adapted to their environment, because those that were not had too low a reproductive success to survive. But this does not mean that every aspect of the phenotype of an organism is optimal in its construction and functional efficiency. Selection as a creative force. Selection, for an essentialist, is a purely negative factor, a force which eliminates deleterious deviations from the norm. Darwin's opponents, therefore, insisted in the spirit of essentialism that selection could not create anything new. By saying this, they revealed that they had neither understood the two-step process of selection nor its populational nature. The first step is the production of an unlimited amount of new variation, that is, of new genotypes and phenotypes, particularly through genetic recombination rather than by mutation. The second step is the test to which the products of the first step are subjected by natural selection. Only those individuals that can pass this scrutiny became contributors to the gene pool of the next generation. Chetverikov, Dobzhansky, and others have rightly stated that this back and forth between genetic recombination and the selection of a highly limited number of progenitors of the next generation is indeed a creative process. It provides in each generation a new starting point and a new opportunity to take advantage both of new environmental and of new genetic constellations. Unresolved issues in natural selection. The interpretation of the 5 selectionist problems here discussed is relatively uncontroversial. By contrast, some other problems still give rise to unresolved disagreements among evolutionary biologists. Some of these problems shall now be discussed. Variability and natural selection. For the last 50 years, two schools have disagreed with each other on the level of genetic variability in natural populations. For H. J. Muller and most classical geneticists, each allele had a different selective value, one of them, normally the wild type, being the best and thus the prevailing gene in the population. He considered it the function of natural selection to eliminate other, inferior, alleles, the supply of which is continuously replenished by mutation. It is concluded from this reasoning that most individu 591. 592. ALS in a population should be homozygous at most loci, since the burden of deleterious recessives, the genetic load, would otherwise become too great. Muller, Crow, and their associates were the most vigorous proponents of this traditional view. The other school, of which Dobbs-Hansky was the leader, also Mather, Lerner, Mayr, B. Wallace, and their students, considers the genotype a harmoniously balanced system of many genes with the heterozygotes often superior to the homozygotes of any of the alleles. Furthermore, this school denies absolute fitness values of genes so that several alleles could be the best, depending in each case on their genetic milieu and on the prevailing external selection pressures. The thinking of the balanced school had its beginning in Chetvertov's concept of the genetic milieu, a concept which was expanded in the theory of the genotype as a balanced system, Dobbs-Hansky, 1951, Mather, 1943. To determine the frequency of concealed recessives in a population with the help of the classical techniques of genetic analysis was not feasible, because only one locus at a time could be made homozygous. It was therefore impossible to settle the argument between the classical and the balanced school. Finally, in 1966, the application of the enzyme electrophoresis method enabled Hubby and Lewontin to establish for Drosophila and simultaneously Harris for men an amazingly high level of allelic polymorphism. They found, and this was abundantly confirmed by later investigators, that even a single individual may be heterozygous for 10% or more of its loci, and a species for 30 to 50%. It thus seemed as if the issue had been clearly decided in favor of Dobbs-Hansky's balance theory. It also seemed a vindication of Darwin's faith in the existence of a virtually inexhaustible supply of genetic variation. However, as is the case with most new lines of research, the study of enzyme variability raised more new questions than it answered. Why do certain species have a much higher level of variability than others? What is the relation between the level of variability and the ecology of a species? What portion of the variability is maintained in the population by selection and what other part by chance, the mutation of virtually neutral alleles? What relation is there between the variability of enzyme genes and the variability of the other DNA of the genotype? In the endeavor to answer these questions, the study of the variability of enzymes by the electrophoresis method is now one of the most active fields of evolutionary genetics. Lewontin, 1974, Ayala, 1976, Ayala et al., 1974b. Post-synthesis developments. The most controversial problem concerning this high genetic variability is its source. One would expect that errors of sampling and selection pressure against inferior homozygotes would drastically reduce the level of allelic variability. How can 4, 6, or even more than 10 alleles at a single locus be simultaneously maintained in a population? Random walk evolution. When the enormous genetic variability of natural populations was discovered in the 1960s, the thesis of a selective neutrality of much of this variation was once more advanced. The proponents of this theory, King and Jukes, 1969, and Crow and Kimura, 1970, refer to genetic change owing to stochastic processes, essentially neutral mutations, as non-Darwinian evolution, a term which is quite misleading since Lamarckism, orthogenesis, and mutationism are also forms of non-Darwinian evolution. Others have called it, perhaps more appropriately, random walk evolution. Ever since then, an active controversy has been going on concerning the proportion of observed genetic variability in natural populations which is due to selection to that which is due to chance. Curiously, ideological commitments seem to play a role in this controversy, since Marxists, on the whole, attribute a greater role to random walk evolution than non-Marxists. My own feeling is that selection is far more important than admitted by the piomotors of non-Darwinian evolution, but that indeed there is a random component in much of the variation at some gene loci. What has become rather probable is that a selective superiority of heterozygotes alone would not be able to maintain such high levels of genetic diversity. But there are other factors that favor genetic diversity. Mayr, 1963, 234-258. In the case of polymorph snails and insects, a rare phenotype is somewhat protected against predators because the predator's search image has become conditioned to the more common phenotype, apostatic selection. Clark, 1962. It has also been shown, first by Petit and Ehrman, 1969, that females of many species have a mating preference for males with rare genotypes. This also helps to prevent the loss of rare genotypes from populations. Other cases of variable selective values have been discovered, and it seems probable that frequency-dependent selection is a rather important mechanism by which the genetic variability of populations is maintained. Evidence is now also accumulating that different genotypes are not only superior in different subdivisions of the species niche, 593, but may also have a preference for such subniches and the ability to find them. This agrees with the finding that genetic diversity is usually greater in diversified than in simpler habitats. Nevo, 1978, Powell and Taylor, 1979. A further mechanism by which genetic variability is maintained is defense against parasites and pathogens, as Haldane pointed out long ago, 1949. High genetic variability in immunity-giving genes, antibody producers, and so forth, protects populations against devastating losses because the pathogens will be unable to cope with rare immune genes. Finally, if 594 epistatic interactions are important, as we believe they are, genes at low frequency may be maintained because they are of high selective value in certain combinations. Considering how many of such selection-controlled mechanisms have now been discovered, all of which permit the diploid gene pool to store genetic variability, one is forced to conclude that much of the observed genetic variability of populations may well be the result of natural selection. 6. The cost of selection. Haldane, 1957, and Kimura, 1960, made some calculations which showed how expensive it is to replace one allele in a large population by a selectively superior one. They concluded from this that evolution would have to proceed very slowly, that is, on relatively few loci simultaneously, or else the total mortality would be forbiddingly high. This conclusion was in apparent conflict with well-established rapid rates of evolutionary change, as for instance in freshwater fishes, as well as with the high level of heterozygosity in most natural populations. Obviously Haldane had made some unrealistic assumptions. Mayr, 1963, 262, and later several other authors, Lewontin, 1974, called attention to the kind of simplifying assumptions made by Haldane. For instance, in a species in which only a small fraction of all the offspring reproduce owing to density-dependent competition, there is so much mortality in every generation anyhow that weighing down this expendable surplus with deleterious homozygotes is no great burden. More important is the fact that Haldane's calculations pertain to large populations, while rapid evolutionary changes happen most frequently in small populations, see below. Haldane may indeed be right for large, populous species. This is indicated by the evolutionary inertia of such species as revealed by the fossil record, but his calculations are not valid for small, particularly for founder. Post-synthesis developments. Populations, the very populations in which most of the crucial evolutionary events seem to take place. Natural selection as a unitary phenomenon. As long as the theory of natural selection was severely questioned, not much thought was given to possible subdivisions of natural selection. Now, with the validity of natural selection firmly established, new questions have come to the fore, for instance whether or not there is a process that might be called group selection, and whether or not it is legitimate to differentiate sexual selection from natural selection, as Darwin had done. Both questions have led to extensive controversies, and it is necessary to say a few words to explain the nature of the argument. Group selection. The thesis that the individual is the principal unit of selection has been challenged by some evolutionists who postulate a process of group selection. Wynne Edwards, 1962. Those who support this kind of selection claim that there are phenomena that could not possibly be the result of individual selection. They refer in particular to characteristics of entire populations, such as aberrant sex ratios, rates of mutation, distance of dispersal and various other mechanisms favoring either inbreeding or outbreeding in natural populations, and degrees of sexual dimorphism. Such differences among populations, say the proponents of group selection, can be established only when an entire population, deme, is favored over other demes because it differs in its genetic constitution for the stated factor. Whether, and to what extent, such group selection actually occurs is still actively discussed in the current literature, but the general consensus is that most of such cases can be interpreted in terms of individual selection, except perhaps in social animals. Lack, 1968, Williams, 1966. The controversy concerning group selection has led to the realization that there are indeed uncertainties concerning various aspects of selection. Evolutionists have become aware that a number of rather different phenomena had been lumped together in the past and that they will not fully understand the workings of selection until they have partitioned the field into its components. Sexual selection. As early as the late 18th century, some animal breeders had suggested that females show a preference for more vigorous 595 males and that this explains sexual dimorphism. The process by which an individual gains reproductive advantage by being more attractive to individuals of the other sex was designated by Darwin as sexual selection. Darwin clearly distinguished it from natural selection, sensu stricto, which conveys superiority in general fitness, environmental tolerance, resource utilization, predator thwarting, disease resistance, and so forth. Darwin's interest in sexual selection was already evident in early handwritten notes, around 1840, but he allotted less than 3 pages to the subject in the 596 Origin, 1859, 87-90. Yet, in The Descent of Man, 1871, the discussion of sexual selection occupies more pages than the evolution of man. However, nothing demonstrates Darwin's intense interest in the subject better than his extended correspondence with Wallace on the causation of sexual dimorphism, Kotler, 1980. The Darwin-Wallace correspondence was the inauguration of a controversy concerning the significance of sexual selection that is not yet at an end. For a review of the early phase of the controversy, see Kellogg, 1907, 106-128. Darwin's effort to keep sexual selection distinct from natural selection encountered strenuous objections. In 1876 even Wallace abandoned sexual selection, and so did most experimental biologists in the ensuing years, since, like T.H. Morgan, they were interested only in proximate causations, for example, what hormones or genes are responsible for sexual dimorphism. The recognition of sexual selection was entirely rejected by the mathematical population geneticists, who considered evolution as a change in gene frequencies and defined fitness simply as the contribution of a gene to the gene pool of the next generation. Since this definition, indeed, applies equally to natural and sexual selection, any distinction between the two kinds of selection is obliterated. In recent years the individual has been reinstated as the principal target of selection, and it has become respectable to revive Darwin's concept of sexual selection. Campbell, 1972. Admittedly, Darwin had included under sexual selection aspects of sexual dimorphism that would be better listed under natural selection, such as some aspects of male aggressiveness. What is left, however, are all those aspects of male adornment and song, which Darwin had explained as being due to female choice. Even though the principle of female choice was defended by most naturalists for the last 100 years, it was rejected by the majority of biologists and by virtually all non-biologists for the reason that it credited females with a discriminating ability which they could post-synthesis developments not possibly have. Recent studies of ethologists and field naturalists, however, have proved conclusively that females not only in vertebrates but also in insects and other invertebrates, i.e. usually very coy, by no means accepting for copulation the first male they encounter. Indeed, the selection of the male which finally is admitted for copulation is often a very protracted process. Female choice in these cases is an established fact, even where the criteria are not yet known on the basis of which the females make their choice. This strongly contrasts with males, who usually are ready to mate with any female and quite often do not even discriminate among females of their own and of other species. The reasons for this drastic difference between males and females were pointed out by Bateman, 1948, and further elaborated by Trivers, 1972, on the basis of the principle of investment. A male has sufficient sperm to inseminate numerous females, and his investment in a single copulation is therefore very small. A female, by contrast, produces relatively few eggs, at least in species with female choice, and may furthermore invest much time and resources in blooding the eggs or developing the embryos and in taking care of the brood after hatching. She may lose her entire reproductive potential by making a mistake in the selection of her mate, for instance, by producing inferior or sterile hybrids. The principle of female choice explains also a number of other phenomena that were previously puzzling, for instance, why polymorphism in species of butterflies with Bachian mimicry is usually limited to females. Females would discriminate against males that deviate too far from the species-specific image of the mating partner, releasing mech. Anaism. 7. There is now a justified tendency to interpret sexual selection rather broadly as any morphological or behavioral characteristic that gives a reproductive advantage. 8. Mayr, 1963, 199-201, called attention to the potentially selfish aspects of some kinds of natural selection, specifically those which enhance the reproductive success of individuals without adding to the general adaptedness of the species. Hamilton, 1964, Trivers, 1972, and Dawkins, 1976, have shown how widespread this kind of sexual selection is and how profoundly it affects animal behavior and evolutionary trends. Wilson, 1975, has reviewed much of the relevant literature. Reproductive selfishness would seem a milder equivalent of the struggle for existence than nature red in tooth and claw made proverbial by the social Darwinists. 597. 598. During the 1880s and 90s, when social Darwinism was confused with real Darwinism, cooperation and altruism were often cited as evidence for the evolution of human ethical tendencies that could not possibly have been the product of natural selection. This claim overlooked the fact that cooperating, particularly in social organisms, may be of selective advantage. Darwin had already recognized this when he said, "I use the term struggle for existence in a large and metaphorical sense, including dependence of one being on another." 1859, 62. The problem of altruism and its evolution, which Haldane raised in 1932, is now again the focus of attention. Altruism is usually defined as an activity that benefits another individual, the recipient, to the seeming disadvantage of the altruist. Haldane pointed out that an altruistic trait would be favored by natural selection if the beneficiary was sufficiently closely related, so that his survival benefited the genes which he shared with the altruist. For instance, if there is 1 chance in 10 that an altruistic act would cost the life of the altruist, but the beneficiaries were the children, siblings, or grandchildren of the altruist, with all of whom he shares more than 10% of his genes, selection would favor the development of altruism. This particular form of selection has also been designated as kin selection, and the fitness which refers to all the carriers of the same, or similar, genotype is known as inclusive fitness. Haldane's rather simple theory has since been elaborated by Hamilton, Trivers, Maynard Smith, G.C. Williams, Alexander, West Eberhard, and many others, and has become part of sociobiology. 9. Sociobiology, broadly speaking, deals with the social behavior of organisms in the light of evolution. there is little argument that much if not most of social behavior in animals has a strong genetic component. The part of sociobiology that is being attacked is that which deals with man. Can man's social behavior be compared with that of animals? To what extent is the social behavior of man part of his primate heritage? These are among the questions that have been asked. Much of the argument seems to be semantic. For instance, E.O. Wilson and other sociobiologists have been accused of preaching the genetic determinism of behavior. This does not represent their views accurately. All they have said, and one can argue about the validity of this claim, is that much of man's social behavior has a genetic component. But that is not the same as genetic determinism. It must be remembered that a behavior may be controlled by closed or open post-synthesis developments programs, and that even open programs have a considerable genetic component. The profound differences in social behavior among human groups, some of them closely related, show how much of this behavior is cultural rather than genetic. The evolutionary significance of sex. Several recent authors have been puzzled about the possibility that there may be a conflict between Weismann's theory of sex and the principle of reproductive success. A species with uniparental reproduction can generate twice as many reproducers as a sexually reproducing species that wastes half of its zygotes on males. Accordingly, one would expect natural selection to favor uniparental reproduction, for example, parthenogenesis, over sexual reproduction. Williams, 1975, Maynard Smith, 1978. Uniparental reproduction indeed is widespread both among plants and animals, and yet it is of much lower frequency than sexual reproduction. No explanation has yet been advanced that would satisfactorily explain this puzzle. Undoubtedly, in the long run, sexual selection is superior because it provides an escape in case of any major change in the environment. However, in the short run, in relatively stable environments, one would expect the doubled fertility of uniparentals to carry the day. Perhaps one should again invoke the principle of the expendable surplus. Even in sexually reproducing organisms there is already a sufficiently large expendable surplus. A doubling of it would not be of any particular selective advantage. Moreover, there is little doubt that abandoning sexuality cuts down drastically on future evolutionary options. Evolutionary lines that switch to uniparental reproduction most likely become extinct sooner or later, and with this also any mechanisms that would permit such a switch. What are left are strictly sexual lineages unable to switch to uniparentalism but able to fill the niches vacated by extinct uniparental lineages. Sexual reproduction is, of course, obligatory wherever there is the possibility for a second parent to participate in parental care. There are many other correlations between sexuality, behavior, and niche utilization. Gazalin, 1974a. It has long been known that there is a regular alternation between sexual and parthenogenetic geneations among a large assemblage of organisms, certain parasites, freshwater plankton, aphids, and that the shift from one to the other state is closely correlated with changes in the environment. Natural selection is indeed often puzzling, and the modem evolutionist is as perplexed about the selective aspects of some. 599. Natural phenomena as were Darwin and Wallace. Considering how useful an organ the human brain is, the question is sometimes asked, why did not selection produce as large a brain in all organisms? Yes, why? Or to turn this argument upside down, what selection pressure gave Neanderthal man a brain as large as that of Darwin, Einstein, or Freud? It was this inability to account for the large brain of our primitive ancestors which made Wallace doubt that selection could account for the origin of man as man. What Wallace overlooked is that the crucial moment in all selection is an emergency or catastrophe. An organ or function is usually not altered by selection during normal times, rather, it is selected at a time when it represents the tail end of the curve of variation and permits its carrier to survive in an emergency when the other thousands or millions of individuals of the species succumb. Catastrophic selection, as Lewis, 1962, has emphasized quite rightly, is a very important evolutionary process. Modes of speciation. Darwin, as the first avowed representative of population thinking, stressed the gradualness of the process of geographic speciation, see Chapter 11. The Mendelians emphatically denied Darwin's conclusion, assuming instead, as it was stated by de Vries, that new species and varieties are produced from existing forms by certain leaps. The mode of speciation was a major bone of contention between the naturalists and the Mendelians, Mayr and Provini, 1980. Comparative anatomists, students of phylogeny, and even experimental geneticists thought of evolution strictly in vertical terms, and the phyletic line was for them the unit of evolution. It was a major contribution of the new systematics to have adopted the population as the unit of evolution and to base the explanation of speciation on this concept. New species, the new systematists asserted, originate when populations become isolated, and this thesis was defended by Mayr, 1942, with the support of rich detail. Nothing was said, at first, about the size of such isolated populations, except that Wright, 1932, called attention to the fact that genetic drift might occur in small and very small populations as a result of errors of sampling. The theory of geographic speciation was based primarily on birds, butterflies, and other wide-ranging insects, some groups of post-synthesis developments, snails, and other groups of animals with well-defined patterns of geographic variation. Geographic speciation is so well established in these groups, and the sequence of steps through which isolated populations become differentiated is so abundantly documented, that no doubt could remain after 1942 that geographic speciation is an important and presumably the prevailing mode of speciation in animals. Since the number of insuperable geographical barriers, mountains, water, and so forth, on continents is limited, some other kind of barriers must be responsible for the evidently active speciation on continents. Various authors, see Mayr, 1942, suggested that it might be vegetational barriers or other kinds of uninhabitable terrain. Keast, 1961, showed the truth of this assumption very convincingly for Australian birds. Hafer, 1974, found that the alternation of humid and dry Pleistocene periods in the Amazon basin had been responsible for the extremely active speciation of birds there, and Williams and Vanzolina showed the same for reptiles and Turner for butterflies. The effectiveness of any vegetational belt as a barrier depends on the dispersal facilities of a given species. For flightless grasshoppers or subterranean mammals, even a remarkably narrow zone of ecologically unsuitable terrain can be an effective dispersal barrier. A failure to recognize vegetational barriers has led some authors, White, 1978, to postulate non-geographical speciation mechanisms. In textbook illustrations until rather recently, geographic speciation was usually shown in a diagram in which a widespread species was cut in half by a geographical barrier. The two halves, while isolated from each other, would in time become so different that they would react to each other as different species when contact was re-established at a later period. More detailed studies of the distribution patterns of speciating groups, and particularly of species that seem to have originated recently, suggest a different solution, however. When Mayr in the 1940s and 50s worked out the geographic variation of South Sea Island birds, he was impressed how frequently the most peripheral population was the most divergent one, often reaching such a level of distinctness that it had been ranked as a distinct species or even genus. Mayr recorded in 1942 several cases of highly distinct allopatric genera which distributionally were nothing but far distant subspecies. At that time his emphasis was on taxonomic questions, how to classify such populations, but he continued to speculate on the 601. 602. Causal background of this phenomenon. Being aware of the frequency of founder populations beyond the periphery of the solid species range, it finally occurred to him that such founder populations would be the ideal place for a drastic genetic reorganization of the gene pool in the absence of any noticeable gene flow and under conditions of a more or less strikingly different physical and biotic environment. Mayr, 1954. There were two reasons why Mayr postulated the importance of founder populations. One was the observation that aberrant populations of species almost invariably are peripherally isolated and that, more often than not, the most aberrant population is the most distant one, like D. tristrami, San Cristobal, in the genus Diceum, D. galeata, Marquesas, in Ducola, and literally scores of similar examples listed by Mayr, 1942, 1954. By contrast, the amount of geographic variation in contiguous species ranges is usually minor. The other reason, pointed out by Haldane, 1937, 1957, is that large, widespread populations, in fact all more populous species, are evolutionarily inert, because new alleles, even favorable ones, require very long periods of time to spread through the entire species range. Genetic homeostasis, Lerner, 1954, strongly resists any changes in a large, undivided gene pool. The facts of geographic isolation do not seem to support Sewall-Wright's model, according to which the most rapid evolution takes place in large species consisting of only partially isolated demes. In fact, populous, widespread species often continue virtually unchanged through the fossil record from the time of their first appearance until the time of their extinction. By contrast, the evolutionary fate of peripherally isolated populations is often very different. They are usually founded by a small number of individuals, indeed often by a single fertilized female, and contain only a small fraction of the total genetic variability of the parent species. This, Mayr postulated, would lead to greatly increased homozygosity and to a change in the fitness value of many genes in a drastically changed genetic milieu. Many epistatic interactions would be quite different from what they had been in the parental population. Mayr postulated therefore that such founder populations are particularly well situated to undergo a drastic genetic restructuring, sometimes amounting to a veritable genetic revolution, Mayr, 1954. That such founder populations might undergo drastic genetic changes can hardly be questioned. The brilliant researches of Hampton Carson, 1975, on speciation in post-synthesis developments. The genus Drosophila on the Hawaiian Islands have convincingly substantiated Mayr's theory. There is little doubt observationally that rapid speciation is most easily accomplished in very small populations. That chromosomes may play an important role in speciation had been recognized since the first quarter of the century. Almost a third of the first edition of Dobbs-Hansky's Genetics and the Origin of Species, 1937, is devoted to a discussion of chromosomal phenomena, and chromosomes played an even more important role in the botanical literature. To be sure, de Vries' Enothera mutations were eventually shown to be mostly chromosomal rearrangements and not a normal mechanism for speciation. However, soon afterwards polyploidy was discovered, a process in which, by a doubling of the chromosome set, new species can originate in a single step. Stebbins, 1950, Grant, 1971. The discussion of the role of chromosomes in speciation, however, has suffered from two misconceptions. The first misconception is the assumption by some specialists of one group of organisms that their findings extend to all organisms. That this is not legitimate has been pointed out by a number of investigators. The claim, for instance, that all speciation is due to chromosomal reorganization was refuted by Carson, 1975, who showed that active speciation in Hawaiian Drosophila can take place without any visible change in the chromosomes. Since these Hawaiian species can be analyzed in great detail with the help of their giant salivary chromosomes, whatever structural chromosomal changes may occur during speciation must be very minute. In other groups of organisms, closely related species often differ strikingly in their karyotype by inversions, paracentric or pericentric, translocations, Robertsonian fusions, or fissions, or other changes of chromosome structure. Different groups of organisms specialize in different mechanisms of chromosomal change. Mayr, 1970, 310-319, White, 1974. The second misconception was the assumption that chromosomal speciation is an alternative to geographic speciation. Actually, chromosomal and geographic speciation represent two entirely different dimensions. The kind of chromosomal differences one finds as differentiating closely related species, in contrast to those characterizing chromosomal polymorphism, almost invariably reduce the fitness of the heterozygotes, owing to all sorts of disturbances during meiosis. Such chromosomal rearrangements. 603. 604. Would have little chance of establishing themselves in a large population where they would have to pass through many generations of heterozygosity. It is only in a small founder population with a high level of inbreeding that they would have a chance to pass quickly through heterozygosity to the fitter homozygous condition of the new chromosomal type. What is true for chromosomal rearrangements is also true for new epistatic balances of genes, for the acquisition of new isolating mechanisms, and for new endeavors in niche utilization. They all are more easily acquired during the passing through the bottleneck of a founder population than by a slow process of selection in a large, populous species. There is no contradiction in saying that a certain new species originated by geographic and chromosomal speciation. The term peripherally isolated becomes somewhat ambiguous in species with low population density and very much reduced dispersal facility. In such cases a species may consist of numerous more or less isolated colonies, and a new isolated colony may be founded in a previously vacant portion in the midst of the species range. Yet even such a founder population would go through the same steps of inbreeding and homozygosity as if it were isolated beyond the periphery of the species range. Some evidence is now beginning to be found that ease of speciation is largely, and negatively, correlated with population size, and that rapid speciation is not necessarily limited to founder populations. A drastic reduction of population size, as has, for instance, occurred in many Pleistocene refuges, also speeds up speciation, as was demonstrated by Haffer, 1974, and others for the forest refuges in the Amazon basin. However, such species are apparently never even nearly so aberrant as are some of those that originated in peripheral isolates. A second major controversy in the held of speciation concerns the old argument between Darwin and Wagner of the 1860s and 70s as to whether geographic isolation is necessary at all. Mayr, 1963, Soloway, 1979. Again and again mechanisms were suggested that would permit the division of a single deme into two reproductively isolated ones, sympatric speciation, without any extrinsic barriers to gene flow. Three mechanisms of sympatric speciation have been suggested most frequently: 1. Diversifying, disruptive, selection, which would pull apart a bimodal gene distribution; 2. Allochronic speciation, owing to a drifting apart of the breeding seasons; and 3. Colonization of a new host, in the post-synthesis developments. Case of host-specific species. Sympatric speciation by host specialization is a concept that was highly popular from Darwin to the evolutionary synthesis and again enjoys considerable popularity. Bush, 1974. However, as I pointed out in 1942, even though conditioning to new hosts is potentially an important method of sympatric speciation in monophagous species, and in particular in plant feeders, the occurrence of such speciation is subject to many limitations, and the frequency of cases where it is more probable than is geographic speciation is still an open question. White, 1978. I rather suspect that here also the problem is distorted when a strict separation is made between geographic speciation and speciation by colonization of a new host. It is evident that the shift to a new host is much easier in a small founder population in nature or in the laboratory than within the continuous range of a large populous species. 10. The greatest unsolved problem in speciation research remains that of the genetic basis of speciation. To describe the process of speciation, one still relies in the main on inferences from patterns of distribution. It will not be possible to resolve the controversies on the frequency and validity of the various possible modes of speciation until we have acquired a better understanding of the underlying genetic processes. As recently as 1974, p. 159, Lewontin said quite rightly, we know virtually nothing about the genetic changes that occur in species formation. This is, unfortunately, largely still true today. The older literature, Jameson, 1977, has been made virtually obsolete by the discovery of the heterogeneity of the DNA. At first, it was thought that a comparison of the frequency of enzyme alleles in populations before and after speciation would provide a decisive answer. Such investigations attempted, rather in the spirit of beanbag genetics, to construct a quantitative theory of speciation in terms of genotypic frequencies, Lewontin, 1974, 159. However, all the evidence gathered through this line of research indicated that shifting frequencies of enzyme alleles are not a primary agent in speciation. For instance, the degree of difference in isozymes among closely related species varies greatly in different genera. The passing of the species threshold does not seem to coincide with a drastic shift in gene frequencies. This was interpreted by some authors as constituting a falsification of Mayr's theory of genetic revolutions in founder populations. This it would be indeed if the enzyme genes were the primary genetic mecha. 605. 606. Nism for reproductive isolation. It is becoming increasingly probable that there are special genetic mechanisms or regulatory systems that control the degree of reproductive isolation. Such mechanisms may be limited to a relatively small number of genes or to a restricted portion of the karyotype, Carson, 1976. They may be found in the various new kinds of DNA, such as middle repetitive DNA, that have been identified in recent years. The rapid and quite unexpected discoveries in molecular genetics make it seem probable that a major revision of our interpretation of the genetics of speciation may be in the offing. If only a limited portion of the DNA controls the reproductive isolation between species, it would be possible that rather few mutational steps or limited karyotypic restructuring could initiate the speciation process. This would be far easier in a founder population consisting of a few individuals than in a widespread populous species. On the other hand, the multiplicity of isolating mechanisms separating most species indicates that full species rank is acquired in most cases only through a protracted process. Since speciation is gradual, that is, extending over a number of generations even in founder populations, one would not expect that it would happen through a single mutation. And all the indications are that it does not. But just exactly what happens during speciation is still a riddle. Carson, 1976, 220, suggests that it is a shifting internal balance of gene interactions in which a strong role is played by regulatory genes. What Mayr's theory had left altogether unexplained was the irregularity of genetic revolutions. They occur in some but not in all peripherally isolated founder populations. Why? Much progress has been made in the understanding of the genome since 1954. It is now evident that some parts of the DNA, the isozyme genes, are less affected by the genetic revolution than others, presumably some of the regulatory systems. Templeton, 1980, has speculated on some of these factors and, in particular, why genetic revolutions occur only under certain conditions. 1. It is still too early, considering our limited knowledge of the role of various classes of repetitive DNA and other recently discovered aspects of the genotype, to provide a definitive explanation. However, all the recent researches have provided further evidence in support of Mayr's theory that decisive evolutionary events occur most often, by way of genetic revolutions, in peripherally isolated founder populations. Post-synthesis developments. Macroevolution. A third major area of activity after the evolutionary synthesis, in addition to natural selection and speciation, was macroevolution. Macroevolution has been defined in various ways: evolution above the species level, evolution of the higher taxa, or evolution as studied by paleontologists and comparative anatomists. By about 1910, paleontology, particularly invertebrate paleontology, owing to its success in determining stratigraphy, had become very much preoccupied with geological questions, a preoccupation which resulted in a loss of interest in evolutionary history. The study of macroevolution prior to the evolutionary synthesis was conducted by the paleontologists without any effective connection with genetics. Only very few paleontologists were strict Darwinians, accepting natural selection as the dominant agent in evolution. Most paleontologists believed either in saltationism or in some form of finalistic autogenesis. Macroevolutionary processes and causations were generally considered to be of a special kind, quite different from the populational phenomena studied by geneticists and students of speciation. All this changed dramatically with the evolutionary synthesis. Its major effect was to discredit some of the beliefs most widely held previously among students of macroevolution. Important assumptions that were now rejected include the following. 1. That major saltations are indispensable in explaining the origin of new species and higher taxa. 2. That evolutionary trends and the continuous improvement of adaptations require the existence of autogenetic processes, and 3. That inheritance is soft. It was a major achievement of Wrench and Simpson to be able to show that an explanation of the phenomena of macroevolution does not require the acceptance of any of these three theories, and that in fact the phenomena of evolution above the species level are consistent with the new findings of genetics and microsystematics. Obviously, this conclusion had to be based on inference, consisting of morphological, taxonomic, and distributional evidence, since higher taxa were at that time and, except for molecular evidence, are still today inaccessible to genetic analysis. 607. In defense of paleontology, it must be said that although saltationists and defenders of autogenetic processes were very much in the majority, there were also quite a few gradualists and some defenders of natural selection. As early as 1894, W. B. Scott had vigorously defended the gradualness of evolutionary change against Bateson. Even though in all species there is more or less pronounced variation around the normal, says Scott, new departures in phylogeny do not come from the extreme variance but rather from a gradual shifting of the normal, p. 359. Osborn and 608 other advocates of orthogenesis also supported gradual evolution against saltationism. Natural selection likewise had its defenders. Even though most paleontologists agreed that natural selection was insufficient to explain the phenomena of macroevolution, there were some rather vigorous supporters of natural selection, such as Dollo, Kovalevsky, Abel, Goodrich, and Matthew. However, it is not clear from their writings whether they considered natural selection alone as sufficient to explain all evolutionary phenomena. The writings of these and other contemporary macroevolutionists have not yet been sufficiently analyzed to determine this. Simpson, in the introduction to Tempo and Mode in Evolution, 1944, stated that his work was an attempt to achieve a synthesis between paleontology and genetics. Building a bridge between the two fields was made doubly difficult by the almost exclusive attention of geneticists to changes in gene frequencies, based on the assumption that non-additive gene effects were of negligible importance. This restriction was adequate in the interpretation of only some macroevolutionary problems, such as evolutionary trends, but not of others, for example, the origin of diversity. The synthesis between genetics and paleontology occurred in two steps, so to speak, represented by these questions. 1. Are there macroevolutionary phenomena that are clearly in conflict with the genetic interpretation of the Darwinian theory? 2. Can all the laws and principles of macroevolution be developed simply by studying gene frequencies in populations? Eventually it became evident that both questions had to be answered no. The first task of the Darwinian macroevolutionists was to refute the claim of the anti-Darwinians that there are macroevolutionary phenomena which are in conflict with the formula genetic variation and natural selection. This refutation was successfully carried out by Wrench and Simpson. Both of them, and also Julian Huxley, showed that there is no need to invoke a post-synthesis developments mysterious autogenetic factor to explain evolutionary trends, but that increases in the size of the entire body, changes in the proportions of individual structures, such as teeth, the reduction of certain parts, for example, toes in horses, eyes in cave animals, and other long-continued evolutionary regularities can readily be explained by natural selection. It has since been pointed out that genetic as well as functional constraints reinforce the effectiveness of natural selection in controlling trends. Reef, 1975. Various authors as far back as Geoffroy Saint-Hilaire have proposed evolutionary laws. In every case it was shown that the law in question can be expressed in terms of natural selection. This includes, for instance, Dallow's so-called law of irreversibility, which states that structures that had been lost in evolution can never be reacquired exactly in the same way. This finding is an obvious consequence of the fact that the genotype is constantly changing during evolution, and that if the need again arises for a structure that had been previously lost, the structure will be generated by a very different genotype than that which had produced the original organ, and thus the new structure will not be identical with the previously lost one. Gregory, 1936. Most evolutionary phenomena relate to complex structures, organ systems, whole individuals, and populations. No approach was less able to lead to a full explanation than the reductionist one of expressing everything in terms of gene frequencies. Such reductionism, however, is not at all demanded by neo-Darwinism. Much of the objection of the anti-Darwinians became pointless as soon as the exclusive reliance on the reductionist approach was abandoned. Simpson was particularly interested in rates of evolution. He showed that some evolutionary lines change rapidly, others exceedingly slowly, while the majority of lines have an intermediate rate. Furthermore, he showed that in the course of evolution a phyletic line may either accelerate or slow down its rate. The most rapid rate of evolutionary change was designated by Simpson as quantum evolution, which he defined as the relatively rapid shift of a biotic population in disequilibrium to an equilibrium distinctly unlike an ancestral condition. 1944, 206. Simpson thought that this explained the well-known observation that major transitions do take place at relatively great rates over short periods of time and in special circumstances. p. 207. From the context of his discussion in 1944 and in his later writings, 1949, 235, 1953, 350, 1964b, 211, it is evident that what Simpson had in mind, 609, primarily was a great acceleration of evolutionary change within a phyletic line. Simpson's thinking was clearly influenced by Sewell Wright's, 1931, model of an inadaptive phase of genetic drift followed by natural selection. Extreme changes in evolutionary rates are, of course, well documented in the fossil history. Bats apparently originated from insect ivers within a few million years but experienced no further major structural modification in the 50 million years since then. The shift from thecodont reptiles to Archaeopteryx likewise required relatively few million years, but the 610 class of birds as a whole has not been materially modified since the appearance of the first modern birds more than 70 million years ago. Such drastic changes in rates of evolution do not in the least imply a conflict between the origin of the bat or bird morphotype and the Darwinian theory. The problems connected with rates and trends of evolution could be interpreted in terms of the geneticist's formula that evolution is a change in gene frequency. However, this is a meaningless formulation as far as most other problems of macroevolution are concerned, and is one of the reasons why genetics made such a relatively small contribution to the solution of macroevolutionary problems. This inappropriate formulation is also responsible for the considerable time lag between the synthesis and an adequate treatment of some of these problems. Airy novelties. One of the most frequently raised objections to Darwin's gradualism was that it was unable to explain the origin of evolutionary novelties, that is, of entirely new organs, new structures, new physiological capacities, and new behavior patterns. For instance, how can a rudimentary wing be enlarged by natural selection before it enables its possessor to fly? It was asked. In fact, how can any incipient organ be favored by natural selection until it is fully functional? Darwin, 1859, 1862, provided the answer to this question by pointing out that a change in function of a structure is the key element in the solution of this problem. His solution was rather generally ignored until it was further developed by Dorn, 1875, by Severtsov, 1931, and by Mayr, 1960. During such a shift of function, a structure always passes through a stage when it can simultaneously perform two functions, like the antenna of a Daphnia, which is a sense organ as well as a swimming paddle. This duality of function is made possible because the genotype is a highly complex system which always, post-synthesis developments, produces certain aspects of the phenotype that had not been directly selected for but are simply byproducts of the selected genotype. Such byproducts are then available as the machinery for new functions. This is what permits an anterior extremity, with a patagium, of a tetrapod to function as a wing, or a lung in a fish as a swim bladder. There are numerous neutral aspects in the phenotype of any organism that are permitted by natural selection, not selected against, but that had not been specifically selected for. Such components of the phenotype are available to take on new functions. Shifts in function are also known for macromolecules and for behavior patterns, such as when feather preening becomes a courtship display in certain ducks. As Severtsov showed, an intensification of function is often all that is needed to permit a structure to adopt a seemingly new function. In this manner, for instance, the anterior extremity of a walking mammal is converted into the digging shovel of a mole, the wing of a bat, or the flippers of a whale. All that is needed as the starting point for the development of eyes is the existence of light-sensitive cells. Natural selection will then favor the acquisition of any needed auxiliary mechanism. This is why photoreceptors or eyes have evolved independently more than 40 times in the animal kingdom, Plauen and Mayr, 1977. In most cases, no major mutation is necessary in order to initiate the acquisition of the new evolutionary novelty. Sometimes, however, a phenotypically drastic mutation seems to be the first step, as in the case of mimetic polymorphisms, but once this step is made, minor modifying mutations will accomplish the finer calibration. Turner, 1977. The crucial factor, however, in the acquisition of most evolutionary novelties is a shift in behavior. Behavior and evolution. Behavior was for Lamarck an important evolutionary mechanism. The physiological processes initiated by behavioral activity, use versus disuse, combined with an inheritance of acquired characters, were for him the causes of evolutionary changes. After the invalidity of this proposed evolutionary mechanism had been demonstrated by genetics, the mutationists went to another extreme. According to them, major mutations generate new structures, and these go in search of an appropriate function. The modern evolutionist rejects both interpretations. For him, changes in behavior are indeed considered important pacemakers in evolutionary change. However, the chain of causations is quite different. 611. 612. And from that envisioned by Lamarck or by the mutationists. The modern interpretation is that changes in behavior generate new selection forces which modify the structures involved. Mayr, 1974a, showed that different kinds of behavior play different roles in evolution. Behavior that serves as communication, for instance courtship behavior, must be stereotyped in order not to be misunderstood. The genetic program controlling such behavior must be closed, that is, it must be reasonably resistant to any changes during the individual life cycle. Other behaviors, for instance those that control the choice of food or habitat, must have a certain amount of flexibility in order to permit the incorporation of new experiences. Such behaviors must be controlled by an open program. New selection pressures, induced by changes in behavior, may lead to morphological changes facilitating the occupation of new ecological niches or adaptive zones. For instance, Bach, 1959, showed that the primitive woodpeckers, which had switched to the behavior of climbing on tree trunks and branches, still had essentially the ancestral foot structure. However, the new habit created selection forces in several lines of woodpeckers, which led to various highly efficient specializations of foot and tail structure adapted to more efficient climbing. Many if not most acquisitions of new structures in the course of evolution can be ascribed to selection forces exerted by newly acquired behaviors. Mayr, 1960. Behavior, thus, plays an important role as the pacemaker of evolutionary change. Most adaptive radiations were apparently caused by behavioral shifts. Phylogenetic research. Classical phylogenetic research was almost entirely looking toward the evolutionary past. It asked, what was the structure of the common ancestor, and how can he be reconstructed through a study of the homologous features of his descendants? To document the validity of Darwin's theory of common descent was the primary objective of this discipline. Its major interest was to determine for isolated types and phyletic lines where they should be placed on the phylogenetic tree. Common descent was the main emphasis of comparative anatomical research from T.H. Huxley and Gegenbohr to Remini and Romer. Dissatisfied with the diminishing returns which this approach produced, a group of younger evolutionary morphologists began to ask why questions. They developed a new methodology by turning the evolutionary tree upside down, so to speak, that is, by making the common ancestor the starting point of their inquiry. Post-synthesis developments. They asked, why did the lines diverge that originated from a common ancestor? What factors permitted certain descendants to enter new niches and adaptive zones? Was a change in behavior a crucial component in the adaptive shift? The emphasis in this new approach was clearly on the nature of the selection forces. Severtzov, Boker, Dwight Davis, Bach, von Wallert, and Gans were among the pioneers in this new evolutionary morphology. Their approach built a bridge between morphology and ecology, leading to the establishment of a new borderline held which is still in its youth and on the threshold of further interesting developments. A few of the more interesting results of these researches may be mentioned. One was the refutation of the concept of the harmonious development of the type, a major dogma of idealistic morphology. When Australopithecus was discovered, for instance, the anatomist Weidenreich remarked to me that it could not be ancestral to man. It could not be a link between anthropoid and man, owing to its disharmonious type, advanced pelvis and extremities, primitive brain and face. Actually, the concept of the harmonious development of the type had been refuted many times before. When studying the structure of Archaeopteryx, the link between reptiles and birds, de Beer, 1954, called attention to the fact that this connecting link was already much like the later birds in certain features, such as feathers and wings, while still a reptile in others, its teeth and tail. He designated this type of unequal evolutionary rates as mosaic evolution. Even then this was not a new discovery. The same principle had been discussed in considerable detail by Abel, 1924-21, who, in turn, had learned it from Dallo, 1888, who was profoundly influenced by Lamarck, 1809-58. In fact, the organs that have little importance or are not essential to life are not always at the same stage of perfection or degradation, so that if we follow all the species of a class we shall see that some one organ of any species reaches its highest perfection, while some other organ, which in that same species is quite undeveloped or imperfect, reaches in some other species a high state of perfection. Our reasoning today is very different from that of Lamarck, but his observation of highly unequal rates of evolution of different structures and organ systems was entirely sound. Key character. What is most interesting about the unequal evolution of the type is that one particular feature, a key character, is so often involved in the new departure. In the case of the evolution of birds from reptiles, it was the development of the feather, which almost certainly preceded flight. In the case of the evolution of land-living reptiles from aquatic amphibians, it was internal fertilization. The search for the key character is a major objective in the study of the evolution of higher taxa. In the evolution of man, for instance, a series of key characters were involved in the transition from the arboreal anthropoid stage to that of Homo sapiens. Upright posture, a manipulating hand, tool making, the hunting of big ungulates, and a language-based system of communication 614 are suggested successive key features. The anatomists of the school of idealistic morphology always stress the conservative nature of the type. There is indeed something extraordinarily conservative about the ensemble of features which make up the vertebrate type or the mammalian type or the avian type. It is now evident that much evolution is virtually restricted to the key character and a few other characters correlated with it. A bat, in its entire structure, is still very much of an insectivore except for the flight adaptations, including those involving the sense organs. Even a whale is still very much of a mammal except for its adaptations for life in the seas. In turn, there is hardly any mammalian character that cannot be directly followed back to the reptiles. The unity of the type clearly has a genetic basis with the interaction of genes and regulating genes serving as a conservative, if not almost inert, element. Grades. One of the most characteristic features of macroevolution is the relative rapidity with which shifts into new adaptive zones occur, as that from insectivores to bats or from reptiles to birds. When a phyletic line enters a new adaptive zone, as when birds entered the zone of flight, it undergoes at first a very rapid morphological reorganization until it has reached a new level of adaptation. Once it has achieved this new grade, it can radiate into all sorts of minor niches without any major modifications of its basic structure. For instance, all birds are anatomically remarkably similar to each other, being merely variations on a theme. The importance of the phenomenon of grades has been known for a long time, see Bather, 1927, and was again stressed by Huxley, 1958. 7. The clear recognition that there are highly unequal rates of evolution, as particularly emphasized by Simpson, 1953, alternating with periods of remarkable stability as indicated by the term. Post-synthesis developments. Grade is important both for the theory of classification, see Chapter 5, and for an interpretation of the relations between evolution and ecology. The evolutionary morphology of animals is still in the early stages of its development. Its greatest achievement is, perhaps, that of considerable conceptual clarification. This includes the clear distinction between the functioning of a structure and the biological role of a structure in relation to the organism's environment. The concept of pre-adaptation has been redefined to express the potential of a feature to adopt new functions and new biological roles. Bach, 1959, developed the concept of multiple pathways, and Mayr, 1960, clarified the concept of multiple functions. The major emphasis of the new thinking is on the biological meaning of the structural, physiological, and behavioral features of organisms and on the pathways by which selection forces can gradually modify such features. 1-2 Darwin would have been most gratified over the final conclusion of all these researches. Even the most drastic structural reconstructions proceed gradually, particularly when populations, including founder populations, enter new habitats and carve themselves new niches. In spite of the most determined efforts of botanists, the reconstruction of the phylogeny of plants has lagged behind that of animals, primarily for two reasons. 1. The fossil record of most plant groups is infinitely poorer than that of animals, particularly since remnants of the diagnostically important reproductive system of plants are much scarcer than those of the vegetative system. 2. The differences in the internal anatomy, vascular structures, of the orders of angiosperms are far smaller than the differences in the internal anatomy of the 24 phyla of animals. However, the study of fossil pollen and of various chemical constituents and macromolecules of plants is beginning to open up entirely new dimensions of understanding. Owing to the difficulties encountered by the plant morphologists, it has been possible only within the last decade or two to undertake the kind of causal investigations of plants that have been conducted by the evolutionary animal morphologists. The pioneering work in this new causal morphology is Stebbins, 1974a, study of the evolution of flowering plants. He searches for the adaptive significance of every structure by asking, what kinds of ecological conditions and environmental changes would have been most likely to have given rise to the observed morphological differences. This stress on the adaptive significance of characters is radically different from 616. The approach of the traditional taxonomist, who was only interested in clues to common descent. The same adaptive feature can, of course, be acquired repeatedly in unrelated lines through convergence, a fact which is troublesome for the classifier but a valuable source of information for the student of evolutionary causes. Another landmark study in evolutionary plant morphology is the work of Carlquist on convergent adaptations, such as woodiness, of island plants, 1965, and on ecological strategies of xylem evolution, 1975. An even more recent frontier is the study of the evolution of microorganisms. This is being advanced on two fronts. One is the study of microfossils, initiated by Bargorn, Cloud, and Scove, while the other is the comparative study of macromolecules and metabolic pathways of fungi, protists, and prokaryotes. Unfortunately, lack of space precludes even mentioning the host of exciting problems opened up by these researches. The origin of macroevolutionary diversity. There is one aspect of macroevolution that was neglected to an extraordinary degree in the 100 years after Darwin, the origin of higher taxa, or, to say it in different words, the origin of macroevolutionary diversity. Even during and after the synthesis, this problem was neglected by the paleontologists, who might discuss adaptive radiation but did not at all come to grips with the problem of how the taxa originated that radiated into different niches and adaptive zones. This neglect had a number of reasons, not yet analyzed by anyone, two of which I would like to single out. The first one, of course, was the essentialistic thinking universal among morphologists but most apparent in the schools of idealistic morphology. These anatomists were greatly impressed by the conservative nature of the ensemble of features that make up a morphological type or archetype, whether it is the mammalian, the vertebrate, or the arthropod type. Once such a type had evolved, as Skindi-Wolf, 1969, and other paleontologists were quite right to stias, it was virtually immune to major restructuring. Furthermore, intermediate stages between one type and another, either still living or in the fossil record, were very rare or absent. The gene frequency approach of population genetics was quite unable to supply any solution to this problem of origination. The second reason for the stalemate in the study of the origin, post-synthesis developments of new types was the concentration of paleontologists on straight-line phyletic evolution, that is, on the vertical component of evolution. All the great pre-synthesis leaders of paleontology, Cope, Marsh, Dallow, Abel, Osborn and Matthew, concerned themselves primarily with evolutionary laws, evolutionary trends, and the evolution of adaptation. All this would lead to better adaptation but not to greater diversity. How new diversity originated was either explained in terms of essentialistic saltations or it was not mentioned at all. The latter was true even for Simpson, 1944, 1953, whose evolutionary, that is, vertical, species definition made it difficult for him to analyze the problem of the branching of phyletic lines. Curiously, the answer had been available since the synthesis, Mayr, 1942, 1954, but was ignored by the paleontologists until used by Eldridge and Gould, 1972, in their model of so-called punctuated equilibria. They pointed out that when one looks at the geological record, one finds that most fossils belong to widespread, populous species that show little change in the time dimension until they become extinct. A certain proportion of lineages undergoes a process of vertical phyletic evolution, Gingerich, 1976, in which the species of one time level evolve into descendant subspecies or species at the next time level. Far more frequently the extant species are supplemented by or the extinct species are replaced by new species that suddenly turn up in the fossil record. In the classical literature, this sudden introduction of new species was usually ascribed to instantaneous saltations. Eldridge and Gould, however, accepted Mayr's interpretation that such new species had originated somewhere in an isolate, peripheral or not, and were able to spread far and wide if they were successful. This interpretation of the introduction of new species, as Lyell had called it 150 years earlier, agrees well with the fossil record. Bucott, 1978, Stanley, 1979. That such an origin of new types is not pure speculation is documented by the origin of new minor types in peripheral isolates in the living fauna. In one respect Gould and Eldridge differ fundamentally from Mayr. They maintain that punctuated equilibria are produced by discontinuities of such size that they correspond to Goldschmidt's hopeful monsters. Macroevolution proceeds by the rare success of these hopeful monsters, not by continuous small changes within populations. Gould, 1977, 30. What Goldschmidt had postulated, and this seems to be endorsed by Gould, is the production of new species or higher taxa by a single step through a single 6/7. 618. Individual. Mayr, by contrast, considers evolution in founder populations a populational process, which is gradual evolution on the human time scale. Bach, 1979. It appears to be saltational only when measured on the geological time scale. Undoubtedly regulatory genes are participating in these changes or are largely responsible for them, but this does not require saltations. What is crucial is the fact that prior epistatic and regulatory systems are broken up during a genetic revolution in the founder population, making room for new ones. This greatly facilitates and speeds up the acquisition of new adaptations. These are, of course, not acquired by single steps, and selection for their improvement continues. It may even be accelerated by the establishment of descendant founder populations. It is unknown and presumably variable whether such an evolutionary shift requires a few, scores, hundreds, or thousands of generations, but it is certainly by several orders of magnitude faster than the traditional phyletic evolution described in the paleontological literature as requiring millions of years. Even so, evolution through changes in founder populations is not a process of saltation but one of gradual evolution. The most important departure in the new way of thinking is to treat it as a populational phenomenon. In a few contemporary situations there are fortunate constellations of geography and ecological opportunities that permit us to demonstrate the gradual, step-by-step origin of such macroevolutionary origins. The Hawaiian archipelago, in which the various islands of the chain were colonized from the west, Kauai, to the east, Hawaii, provides a graphic illustration of such almost gradual evolutionary steps. This has been demonstrated by Bach, 1970, for species and genera of honey creepers, Drepanidae, and by Carson and Kane-Shiro, 1976, for Drosophila. The continuing introduction of new species by the process of geographic speciation, Stanley, 1979, is made possible because simultaneously there is a steady loss of species by extinction. Extinction, thus, is the counterpart to speciation, as was realized already by Lyell, and a problem of equal importance, particularly for the ecologist. Extinction. When one observes with what extraordinary faithfulness a mimicking species may copy even rather incidental characteristics of its model, one gains the conviction that nothing is impossible to selection. This, however, is contradicted by the frequency of post-synthesis developments. Extinction in nature. When such highly successful orders and phyla of animals as the trilobites, the ammonites, or the dinosaurs became extinct, why was natural selection unable to reconstruct even a single species in these large taxa in such a way as to permit its survival? As a matter of fact, the ammonites had gone through at least 4 previous periods of mass extinction, during which a single lineage survived in each case and gave rise to a new adaptive radiation. However, at the last of these crashes not a single species had the proper constellation of genes to be able to cope successfully with the environmental challenge it encountered, whatever it was. Extinction, as is becoming clearer all the time, is a highly complex problem. The dinosaurs became extinct only when the last of scores or hundreds of species had become extinct. The question thus is, why did this whole higher taxon become obsolete? A look at the history of the phyla and orders of plants and animals shows that they differ greatly in their proneness for extinction. Indeed, one can establish definite regularities in the pattern of extinction, as shown by Van Vallen, 1973. It is my own conviction that extinction is somehow correlated with the cohesion of the genotype. Surely, the rate of mutation ought to be approximately the same in different species of organisms. However, some of them have a genotype that is so well integrated, and thus has become so inflexible, that it can no longer produce the departures from the traditional norm that might permit a major switch in resource utilization or an answer to the challenge of a competitor or pathogen. These, of course, are only words until we have learned more about the structure of the eukaryote genotype and its regulatory system. The diversity of a fauna or flora depends on the equilibrium between speciation and extinction events. Our vastly increased knowledge of fossil biota has made it possible in recent years to trace species diversity through geological time. The analyses show that there are periods of an exponential increase of diversity, such as in the earliest Cambrian and in the Ordovician, periods of steady state when the diversity remains about the same for millions, if not hundreds of millions, of years, and periods of massive extinction, Sepkoski, 1979. What is perhaps most interesting is the extraordinary stability of certain ecological associations. Instead of a gradual enrichment of such faunas, the species diversity remained the same for entire geological periods, and turnover was largely due to a 1:1 replacement of extinct by newly colonizing species. 619. The Ordovician species explosions may have been due to a replacement of generalists by specialists. More recent changes, particularly in the oceans, may have been due to plate movements, the extent of shallow shelf seas, and climatic events, including ice ages. The pioneering recent researches are clearly only a beginning. There have been a number of periods of mass extinction, as at the end of the Permian and again at the end of the Cretaceous. Indeed, the end of the Paleozoic and of the Mesozoic are defined 620 by these mass extinctions. There have been numerous suggestions concerning an extraterrestrial causation of the extinction, such as the passing of the Earth through a cloud of cosmic dust. Others explained it by drastic changes of climate, in turn caused by plate tectonics. The discovery that at the border between Cretaceous and Tertiary there is a greatly enriched deposit of iridium has induced Alvarez and colleagues, 1980, to hypothesize that the Earth was struck by an asteroid, with the dust cloud blocking out sunlight for several years. As appealing as this theory is on first sight, it raises numerous unanswered questions, such as how does one account for the survival of mammals, birds, angiosperms, non-dinosaurian reptiles, and so forth? Clearly the study of extinction remains a wide-open frontier. The evolution of man. No other thought was as distasteful to the Victorian imagination than that man could have descended from the apes. Even if evolution could be demonstrated for all other organisms, surely man with all of his unique human characteristics must have been specially created. Even A.R. Wallace refused to credit natural selection with the evolution of man, much to Darwin's dismay. Actually, as the anatomists knew very well, man is remarkably similar to the anthropoid apes in his morphology. This is why Linnaeus had unhesitatingly included him among the primates. Within a few years after the publication of The Origin, Haeckel in Germany, 1866, 1868, and T. H. Huxley in England, 1863, published volumes in which man was postulated to have descended from the apes. Even Lyell, 1863, eventually admitted at least the antiquity of man, and Darwin in 1871 published a major work, The Descent of Man, in which the problems of human evolution were discussed in considerable detail. Post-synthesis developments. In the meantime, actually already before the publication of The Origin, the first fossil hominids were found, in particular Neanderthal man, 1856. Haeckel, with his usual romantic imagination, went even so far as to reconstruct the missing link between man and apes, naming him Pithecanthropus.
The search for this missing link was unexpectedly soon crowned with success, when a Dutch army doctor and amateur anthropologist, E. Dubois, found the skull of Pithecanthropus, now included in Homo erectus in Java in 1891. The number of new finds of fossil man has increased steadily since that time, none of them more important than the Tong child, Australopithecus africanus, described by Dart from South Africa in 1924. Numerous subsequent finds of Australopithecines by Broom, the Leakeys, and others have permitted a reconstruction of this remarkable creature. In its pelvis and posterior extremity it hardly differs from modern man, in its dentition and face it is somewhat intermediate between apes and man, and in its brain, about 450 cubic centimeters as compared to 1,500 cubic centimeters in modern man, it is still essentially on the ape level. Additional finds made in Southeast Asia, Ethiopia, Kenya, and Tanzania now permit reconstructing an almost unbroken chain from the oldest Australopithecus, afarensis, through A. africanus, Homo habilis, H. erectus, to Homo sapiens. Chronological as well as morphological considerations suggest that A. africanus was a polytypic species, isolated populations of which gave rise both to the robust Australopithecus robustus, a side line, and to Homo habilis. It is most unlikely that we will ever recover enough fossils to determine where the isolates were located in which these species evolved nor what caused their divergence from A. africanus. Australopithecus robustus, which coexisted with Homo habilis, became extinct more than 1 million years ago. Although Australopithecus can now be traced back to about 4 million years ago, it is still controversial how many million years earlier this hominid line had branched off the line that leads to the African apes, the chimpanzees and gorillas. The ultimate decision depends a good deal on where one places the fossil Ramapithecus and whether one considers it to be ancestral only to the hominids or also to the African apes, or a side branch. It seems increasingly probable that a shift from an ape-like ancestor, Ramapithecus, to the hominid condition occurred very rapidly and perhaps as recently as only 5 to 7 million years ago. Only further fossil discoveries can give us certainty. What is amazing is the extraordinary similarity between man and the great African apes in molecular characteristics and crow. 621. 622. Mosum structure. Here is an evident case of mosaic evolution, where some segments of the genotype, the basic macromolecules, have remained conservative while other segments, those controlling general anatomy and in particular the central nervous system, have evolved at an exceedingly rapid rate. However, the crucial fact that the hominid line branched off from the line leading to the African apes is now no longer in doubt. What is far more important than the uncertainties of chronology is our growing understanding of the steps that led from the anthropoid to the human condition. The assumption of upright posture when our ancestors descended from the trees was apparently the first and perhaps the most decisive step. It freed the anterior extremity for the function of manipulation, which permitted the carrying of objects and far more extensive tool use and eventually tool manufacturing than found in any ape. The hunting of big game and the development of a true language were apparently other major steps in the evolution of man. To characterize man by such criteria as consciousness, or by the possession of mind and of intelligence, is not very helpful, because there is good evidence that man differs from the apes and many other animals, even the dog, in these characteristics only quantitatively. It is language more than anything else that permits the transmission of information from generation to generation and thus the development of non-material culture. Speech, thus, is the most characteristic human feature. It is often said that culture is man's most unique characteristic. Actually, this is very much a matter of definition. If one defines culture as that which is transmitted, by example and learning, from older to younger individuals, then culture is very widespread among animals, Bonner, 1980. Thus, even in the evolution of culture there is not a sharp break between animal and man. Though culture is more important in man, perhaps by several orders of magnitude, the capacity for culture is not unique with him but a product of gradual evolution.
One of the most surprising discoveries of anthropological research has been the rapidity with which Homo evolved. Even allowing for the concomitant increase in body size, the growth of the hominid brain from 450 to 1,600 cubic centimeters was remarkably fast. Perhaps equally remarkable is that once the Homo sapiens stage had been reached, more than 100,000 years ago, no further noticeable increase in brain size occurred. Why primitive man should have been selected for a brain of such perfection that 100,000 years later it permitted the achievements of a Descartes, Darwin, post-synthesis developments, or Kant, or the invention of the computer and the visits to the moon, or the literary accomplishments of a Shakespeare or Goethe, is hard to understand. But then, of course, man will always be a puzzle to man. Eugenics. The recognition that natural selection, and natural selection alone, had raised man from the level of an ape to that of a human being suggested to Galton soon after Darwin's death that one might apply this principle of selection in order to achieve a biological improvement of man. This utopian scheme, to which he gave the name eugenics, found at first many adherents. In fact, a large number of geneticists and other biologists agreed in their writings that it was a noble idea to improve mankind by facilitating the reproduction of the best members of the species and by preventing the reproduction of individuals who had genetic diseases or were otherwise inferior. Actually, two kinds of eugenics must be distinguished. Negative eugenics endeavors to reduce the number of deleterious genes in a population by preventing the reproduction of carriers of dominant genes and by reducing the reproductive rate of heterozygous carriers of recessives, where such heterozygotes can be diagnosed. Positive eugenics strives to enhance the reproductive capacity of superior individuals, Haller, 1963, Osborne, 1968. When one reads the writings of these early believers in eugenics, one is impressed by their idealism and humanity. They saw in eugenics a means to go beyond the improvements made possible by education and a rise in the standard of living. No political bias was at first attached to eugenics, and it was supported by the entire range of opinion from the far left to the far right. But this did not last long. Eugenics soon became a tool of racists and of reactionaries. Instead of being applied strictly to population thinking, it was interpreted typologically. Soon, without the show of any evidence, whole races of mankind were designated as superior or inferior. In the long run it led to the horrors of Hitler's Holocaust. As a consequence it has become almost impossible, since 1933, to discuss eugenics objectively. This does not invalidate the fact, however, that it was through natural selection that man reached humanity, and it is equally true that we know of no method other than selection to improve the human genotype. Nevertheless, to apply artificial selection to man is impossible, at least for the time. 623. Being, for a number of reasons. The first one is that it is quite unknown to what extent non-physical human characteristics have a genetic basis. Second, human society thrives on the diversity of talents and capabilities of its members. Even if we had the ability to manage the selection, we would not have any idea for what particular mixture of talents we should strive. Finally, the concept that people are genetically different, even were it scientifically even better established than it is today, is not acceptable to the majority of Western people. There is a complete ideological clash between 624 the concepts of egalitarianism and eugenics. We must remember that the principles of the United States Constitution are based on the writings of the leaders of the Enlightenment, whose ideals were magnificent but whose knowledge of biology was deficient, to put it mildly. As Bateson said many years ago, not even the patristic writings contain fantasies much further from physiological truth than those which the rationalists of the Encyclopedia adopted as the basis of their social schemes. 1914, 7. At the present time, eugenics is a dead issue and will remain so until populational thinking is more widely adopted and until we know far more about the genetic component in human characteristics. 13. If we would ask what the most characteristic aspect of current evolutionary research is, we would have to use the term interaction. In the reductionist phase the attention was on the action and the fitness of single genes, now more and more attention is paid to the interaction of genes, to regulatory mechanisms, and to the genotype as an active system. Studies of the fitness of the isolated individual are supplemented by studies of kinship selection, inclusive fitness, reciprocal altruism, parent-offspring relations, and so forth. The study of the evolution of plants and animals is enriched by the study of their coevolution, Ehrlich and Raven, 1965. The evolution of herbivores cannot be understood except as a response to the evolution of their food plants. This was long understood, as shown by the frequent references to contributions made by the shift from browsing to grazing in the evolution of horses and other temperate zone mammals during the Tertiary. Most insect evolution from the Cretaceous on is intimately connected with the evolution of the angiosperms. Studies of the evolution of social systems and of ecosystems focus strongly on the effects of interactions. All this is, of course, an obvious consequence of natural selection. Natural selection is exerted by the environment, and the environment of an individual consists not only of inanimate nature but also of other individuals of the same. Post-synthesis developments. Species and of individuals of other species, both plants and animals. In the last analysis, thus, most studies of interactions during evolution are nothing but an expansion in the application of natural selection research. This is splendidly demonstrated in modern textbooks of evolutionary biology, Futuma, 1979, Behavior, Alcock, 1980, and Ecology, Ricklefs, 1978. Unsolved problems in evolutionary biology. The evolutionary biologist is often asked what the unsolved problems of his field are. It turns out that few of them deal with basic principles, since an alternative to Darwinism has become ever more improbable the more we have learned about life. As for problems, one could perhaps mention the question, what proportion of the observed variability of life is the product of selection and what other part is due to stochastic processes? More specific problems are the origin of life, how nucleic acids and polypeptides became associated, the origin of viruses, the details of the conversion of prokaryotes into eukaryotes, the functioning of the eukaryote chromosome, the classification of the various kinds of DNA, structural, regulatory, repetitive, and so on, and their respective roles in evolution and speciation, the relationship and phylogeny of the major types of plants and invertebrates, the respective roles of intra- and interspecific competition in evolution, the evolution of different kinds of behavior and their role as pacemakers in evolution, and the reasons for the extraordinarily high frequency of extinction. Why is natural selection so helpless to prevent it? Any specialist can add to this list. A particularly rich field for investigation is the pluralism, multiple pathways, found in evolution. For almost any challenge posed by the environment, different evolutionary lines have found different answers. What constraints do the different answers, such as the external skeleton of arthropods versus the internal skeleton of vertebrates, impose on the future evolution of these lineages? The whole field of evolutionary constraints is still virtually untouched. The fusion of evolutionary biology with ecology, behavioral biology, and molecular biology has raised an almost endless number of new questions. Yet, to repeat, there is little likelihood that any new discoveries will force a major modification of the basic theoretical framework that was arrived at during the evolutionary synthesis. 625. Evolution in modern thought. The frequency and often violence of controversies in the camp of the evolutionists have confused some non-biologists. As a result, they have become skeptical of the whole concept of evolution, or at least of the Darwinian principle of natural selection. The question is therefore legitimate as to what role evolution and Darwinism play in modern thought. It is perhaps fair to state at the out 626 set that no well-informed biologist doubts evolution any longer. In fact, many biologists consider evolution not a theory but a simple fact documented by the change of gene pools from generation to generation and by the changes in the sequence of fossils in successive accurately dated geological strata. It is probably equally fair to say that the vast majority of well-informed lay people accept evolution as readily as the fact that the Earth circles the Sun and not the reverse. Whatever opposition to evolution survives today is restricted to persons with religious commitments. Certain fundamentalist sects still insist on the unquestioned acceptance of the literal story of Genesis in spite of the falsification of this story by the overwhelming evidence of science. A rational debate between scientists and fundamentalists is impossible because one camp rejects supernatural revelation, the other camp scientific fact. More interesting is the occasional resurgence of anti-selectionism. The most prominent authors of the anti-selectionist literature are usually journalists, jurists, writers, and philosophers, and their arguments are based on such an ignorance of the facts of genetics, systematics, biogeography, ecology, and other branches of biology that a rational debate is impossible. What is disturbing, however, is that a few serious and well-qualified scientists have accepted the arguments of the lay anti-selectionists and have also proclaimed that the formula variation and selection cannot fully explain evolution. Such scientifically qualified anti-selectionists are a very small minority. Their arguments are usually based on a failure to recognize the probabilistic nature of selection, on a failure to realize that the individual as a whole is the target of selection, and on the failure to appreciate the numerous constraints encountered by selection. No special effort is made by evolutionists to refute these authors because the counterarguments have all been stated in the literature many times and in considerable detail. These minor controversies have been unable to delay, much less stop altogether, the impact of evolutionary thinking on all post-synthesis developments. Spheres of human thought. Evolutionary thinking is no longer restricted to biology, and there is no held of human endeavor with a historical component that has not adopted evolutionary thinking and evolutionary methodology. We now use the word evolution very freely, beginning with the evolution of the universe up to the evolution of human society, the evolution of languages, the evolution of art forms, and the evolution of ethical principles. The indiscriminate application of the term evolution, however, has led to some unfortunate formulations, if not absurdities. Non-biologists who favor the evolutionary conceptualization are often unaware of the Darwinian or neo-Darwinian theory and may, for instance, promote orthogenetic schemes, such as the theory that human culture automatically passes through a series of stages from that of the hunter-gatherer to that of the urban megalopolis. Teleological principles have been very popular among those who have used evolutionary language outside of biology, but when these teleological schemes were refuted, it was thought that this refuted the whole concept of evolution. A study of such literature demonstrates rather painfully that no one should make sweeping claims concerning evolution in fields outside the biological world without HRST becoming acquainted with the well-seasoned concepts of organic evolution and, furthermore, without a most rigorous analysis of the concepts he plans to apply. Evolutionary thinking is indispensable in any subject in which a change in the time dimension occurs. However, there are many kinds of evolution, depending on the nature of the causes that are responsible for the change, on the nature of the constraints, and on the nature of the success of the changes. The appropriate analysis of the different kinds of so-called evolution in different areas has not yet been undertaken. Nevertheless, there is no doubt that applying evolutionary principles has greatly enriched many areas of human thought. 627. Variation and its inheritance. IJVEN primitive people are well aware of two aspects of living nature, an immense variability within each species and a tendency for characteristics of parents to be transmitted to their offspring. Philosophers and scientists have attempted explanations for inheritance from the days of the pre-Socratics to the end of the 19th century, but it was only in the year 1900, when Mendel's work was rediscovered, that a maturation of concepts permitted the establishment of genetics as an autonomous science of inheritance. Another 50 years passed by, however, before biologists fully understood what aspect of inheritance is most significant, that is, the existence of a genetic program. It constitutes the most fundamental difference between living organisms and the world of inanimate objects, and there is no biological phenomenon in which the genetic program is not involved. Geneticists, not without justification, have therefore claimed that genetics is the most basic of all biological disciplines. The particular importance of genetics is that it deals with a level in the hierarchy of biological phenomena that bridges the gap between those parts of biology that deal with whole organisms, as do systems and most of evolutionary biology, and those that deal with purely molecular phenomena. It therefore has contributed to the unification of biology by showing that the genetic processes in animals and higher plants are exactly the same. More importantly, genetics help to solve the problems of the mechanisms of evolution and development. A comprehension of the fundamental principles of inheritance is a prerequisite for a full 630. Understanding of virtually all phenomena in all other branches of biology, whether physiological, developmental, or evolutionary biology. Much of the acceleration in the progress of biology in the 20th century is due to a better understanding of the mechanisms of inheritance. Likewise, many of the controversies in biology during the first half of the 20th century were due to the difficulty of integrating the findings and concepts of genetics into the older, previously established branches of biology. At the same time, an important contribution to the maturation of genetics was made by the introduction of concepts from neighboring fields, concepts that had been previously absent from genetics. Such concepts came from systematics, population thinking, information theory, program, and biochemistry. One might even raise the question whether the intensive interaction between genetics and the other branches of biology has not led to the disappearance of genetics as a separate science. Population genetics has become a branch of evolutionary biology, the study of gene action has become part of molecular biology, and the developmental aspects of genetics have become the domain of developmental biology. Some particularly partisan champions of genetics have gone to the other extreme and said that fundamentally all parts of biology are branches of genetics. Considering the fact that the genetic program in some way or another is involved in all biological activities, even where open programs control a certain action, this claim is not altogether as absurd as it may seem. These conflicting points of view serve to emphasize the central and integrating role of genetics in biological thought. The universality of genetic phenomena is, by necessity, the cause of a considerable heterogeneity in the science of genetics. The study of the origin of new genetic programs, mutation, recombination, of their transfer to the next generation, transmission genetics, of the behavior of genetic factors in gene pools, population genetics, and of the translation of genetic programs into phenotypes, physiological or developmental genetics, requires separate disciplines, some dealing with proximate, others with ultimate, causations. The most frequent interactions of any of these disciplines are often not with each other but with branches of biology outside of genetics, such as systematics, embryology, physiology, or biochemistry. My treatment here is focused on transmission genetics and its components, that is, on the units of inheritance, genes, their changes, mutations, their arrangement, in chromosomes, their resortment, recombination, errors of sampling, and their transfer to the next generation. The history of those aspects of genetics that are most important for the causal explanation of evolution, such as population genetics, have already been treated in chapters 11 and 12. Finally, physiological genetics is inseparable from developmental biology and will be treated in a separate volume. Each of these branches of genetics has its own conceptual framework and its own history. Although some historians, such as Barthel Mess, 1952, and Stubb, 1965, unhesitatingly begin their history of genetics with the ideas on inheritance held by the ancients, other historians feel that to trace the origins of genetics to a time before the beginnings of modern science seems, to lose sight of its essence. Dunn, 1965, 14. In this argument I side with Barthel Mess and Stubb. From primitive man on, people had ideas on inheritance, on the causes of resemblances, and on the origins of new kinds of organisms and new characteristics. Most of these ideas were erroneous, but even if one were to assert that not a single one of the concepts and beliefs of Hippocrates or Aristotle had survived to modern times, the historian of ideas nevertheless must study them carefully. Before one can understand the ground on which new ideas grow, one must understand how the old ones were modified or why they were eliminated. Furthermore, ideas on inheritance very often were part of more universal ideologies, like animism, atomism, essentialism, creationism, physiological mechanism, or holism, and certain genetic theories cannot be understood if one is not aware of this philosophical background. Mendelian genetics did not confront a vacuum but rather already available theories of inheritance, such as pangenesis, blending inheritance, or the various theories of multiple determinants. One will never fully appreciate the intellectual force of the Mendelian revolution unless one knows what the existing theories were which it displaced. 631. 14. Early theories and breeding experiments. Every individual in a sexually reproducing species, except identical twins, is unique. This amount of uniqueness is far greater than that found in the world of inanimate objects. Although at the macro level one finds also unique individuals, such as planets or volcanoes, and unique systems, galaxies and weather systems, the most abundant of all individuals, the components of matter, molecules, atoms, elementary particles, are never unique. Most of the laws of the physical sciences are based on this lack of uniqueness, see Chapter 2. A correlate of individuality in organisms is variation. Any living group consisting of unique individuals by necessity displays variation. The origin and nature of variation in living organisms were not understood until the 20th century, and the lack of an established theory of variability was a great impediment for 19th century biology. It was the weakest link in the chain of argument in Darwin's theory of natural selection, a fact of which Darwin himself was keenly aware. Indeed, it worried him all his life. That variation, or parts of it, is somehow connected with inheritance must have been dimly appreciated even by primitive man. That an offspring may resemble its parents or grandparents in certain traits was, of course, ancient knowledge. All animal and plant breeding is based on an awareness that some qualities are inherited. Any endeavor toward improvement of a breed, whether by selection or by crossbreeding, was implicitly based on the postulate of inheritance. Even the role of the sexes in fertilization was well understood in certain cultures. The Assyrians, at least as far back as 2000 BC, fertilized the flowers of female date palm trees with pollen shed by the flowers of male trees. Nevertheless, the nature of inheritance and its mechanism remained rather a mystery. The early observations of the primitive naturalists and agriculturalists, as well as the speculations of physicians and philosophers, raised numerous questions, most of which 633, 634 were debated until the beginning of the 20th century. Perhaps there is no other area of biology in which the refutation of erroneous ideas and dogmas was more important for an advance of understanding than in genetics. Some of the erroneous ideas or dogmas were, 1. That a parental pneuma, rather than a transfer of gross physical substance, is the agent of inheritance. 2. That only one of the parents transmits the genetic elements, opposed by Buffon and Kallreuter. 3. That the contribution made by the father is quantitatively and qualitatively different from that of the mother, from Aristotle to Linnaeus. 4. That the environment and the activities of the body, use and disuse, have a strong determining influence on the genetic material, inheritance of acquired characters. 5. That there are two sharply distinguished kinds of inheritable properties, those that vary discontinuously, by saltation, and those that vary continuously by infinitesimally small gradations. 6. That the characters, properties, themselves are directly inherited, rather than the potential for their formation, in the form of the genetic program. 7. That the genetic contributions of both parents fuse in the offspring. Blending inheritance. This is only a small sample of widely held misconceptions concerning inheritance. Inheritance, being such a conspicuous phenomenon,
became the subject of a diversified folklore science, the remnants of which can be found among laypersons even today. Animal breeders, for instance, insisted that if a female of a pure race had once been inseminated by a male of a different race or by a mongrel, her blood would be permanently impure so that she could no longer be used for breeding purposes. This belief often was also applied to mankind, particularly in the racist literature. It was also widely believed that a single offspring could be fathered by several males so that a child of a female who had received several males in the period during which she had conceived would combine the characteristics of these several fathers. There was also the belief in a great plasticity of the genetic material. For example, it was believed that any accidents of the mother, like being frightened by a snake, might affect the fetus. One of the most characteristic aspects of traditional ideas on early theories and breeding experiments. Inheritance, when seen in retrospect, was the frequent incompatibility of simultaneously accepted views. A belief in an invisible constant essence was combined with a belief in strong environmental influences of all sorts or with a recognition of a differential contribution of the two parents. Strictly quantitative concepts, such as strength of the father's influence, were held alongside purely qualitative ones, the inheritance of individual features, as in Plato's eugenics. The inheritance of somatic damages, mutilations, was almost universally believed in, even though one could readily see that a warrior who had lost an arm did not produce armless children, not to mention the genetic ineffectiveness of thousands of years of circumcision among the Jews. Theories of inheritance among the ancients. Despite thoughtful and critical analysis by a number of Greek philosophers, still no unified theory of either variation or inheritance was developed by the ancients, and the ideas of these philosophers differed widely from one another. However, a principle of inheritance was quite generally accepted, continuing the tradition of the Iliad and other epics, where an inheritance of the heroic qualities of the father by the son was taken for granted. Yet, the Greek philosophers had only the vaguest ideas on how the characteristics of the parents were transmitted to their offspring. Two authors who had the greatest influence in subsequent centuries on the thinking concerning generation and inheritance were Hippocrates and Aristotle. 1 The famous physician Hippocrates, ca. 460 to 377 BC, taught that seed material came from all parts of the body to be carried by the humors to the reproductive organs, De Generatione, sections 1 and 3. Fertilization consists in the mixing of the seed material of father and mother. That all parts of the body participate in the production of seed material is documented by the fact that blue-eyed individuals have blue-eyed children and bald-head men have children that become bald-head. If parts of the body are unhealthy, the corresponding part in the offspring may also be unhealthy. The idea of such a panspermy or pangenesis had apparently been first expressed by Anaxagoras, ca. 500 to 428 BC, and had representatives at least to the end of the 19th century, in 655. 636. Eluding Charles Darwin, see Chapter 16. If one believes in the effect of use and disuse or any other form of an inheritance of acquired characters, as did just about everybody from Hippocrates to the 19th century, one is virtually forced to accept such a theory. Characteristic for the theory of pangenesis is also the alternation between the formation of the body, phenotype, soma, and through it the formation of seed stuff, sperm, genotype, which then directly through growth is converted again into the body of the next generation, a concept essentially maintained until first challenged in the 1870s and 1880s, Galton, Weismann. Aristotle. None of the ancients had a deeper interest in questions of generation than Aristotle, who devoted one of his major works, De Generatione, to this problem. He discussed variation and inheritance also in other writings, as in De Partibus. Aristotle was altogether opposed to the atomistic interpretation of inheritance by Hippocrates and his forerunners. How could it explain the inheritance of characteristics that could not produce seeds, such as dead tissues, like nails or hair, or behavioral characteristics, such as voice or locomotion?
Also, characters may be transmitted by the father at an age when the character is not yet shown, such as baldness or premature graying of the hair. Aristotle likewise rejects the possibility that the sexual product of the male is a tiny preformed animal, as was later believed by some 17th and 18th century authors. Aristotle's theory of inheritance was a rather holistic one. He held, as had some of his forerunners, that the contribution of male and female were somewhat different. The semen of the male contributes the form-giving principle, eidos, while the menstrual blood, catamenia, of the female is the unformed substance that is shaped by the eidos of the semen. He compares the effect of the semen to that of the carpenter's tools on wood. The female always provides the material, the male provides that which fashions the material into shape. This, in our view, is the specific characteristic of each of the sexes, that is what it means to be male or to be female. His statement would suggest a marked difference in the role of semen and catamenia, yet in other places Aristotle postulates a striving, almost a struggle, between male and female seed stuffs. When the male material predominates, a boy will be born. If it is early theories and breeding experiments, only a partial victory, it may be a boy with the characteristics of the mother, or, if the parental strength is inferior to that of the grandparents, it will be a child with characters of the grandparents, and so forth. What is very important in Aristotle's thinking is the role of the eidos of each individual. To be sure, each child has the characteristics of the species to which it belongs, but it also has its own specific individuality. A child of Socrates, says Aristotle, is apt to have the characteristics of Socrates. It has been stated, not without justification, that Aristotle's separation of a form-giving principle, eidos, from the material that is being formed is not too different from the modern concept of the genetic program which controls the shaping of the phenotype, Dalbraic, 1971. This ignores the fact that Aristotle's eidos was a non-material principle. Furthermore, it was rather consistently confused by subsequent authors with Plato's quite different concept of the eidos, with the result that Aristotle's concept was virtually ignored until after 1880. Buffon's concept of a mule interer is superficially similar to Aristotle's eidos, but there seems to be no historical connection. Roger, 1963. Buffon's mold was a strictly material entity. The similarity of Aristotle's ideas to the modern ones was not recognized until 1970. As in other areas of biology, the major contribution made by the Greeks was that they introduced an entirely new attitude toward inheritance. They considered it no longer as something mysterious, given by the gods, but as something to be studied and to be thought about. In other words, they claimed inheritance for science. Indeed, they were the first to pose many of the questions that were the subject of the great genetic controversies of the 19th and early 20th centuries. And one of the schools of philosophy, the Epicureans, introduced a new concept, that of the existence of very small invisible particles, which later became a dominant concept of genetics. For some 2,000 years after the days of Aristotle and the Greek atomists, remarkably little was added to the subject of generation and inheritance that was new. This is equally true for the Alexandrian and the Roman period, and medieval discussion continued largely in terms of such classical models as remained available. Many of the questions that the Greeks had asked but were unable to answer decisively were the major questions occupying the new science of the Renaissance. Some of these questions, not all of them clearly articulated by the Greeks, were 637. 638. 1. What is the nature of fertilization? What is transmitted during copulation that is responsible for conception? 2. Can living beings originate spontaneously, or is a sexual union always necessary for the production of new individuals? 3. What are the respective contributions to the characteristics of a child made by the father and mother? Does the mother make a, we would now say genetic, contribution in addition to serving as the nurse of the developing embryo? 4. Where is the male semen formed, in a special organ, or throughout the body? 5. How is the sex of the offspring determined? 6. To what extent are the heritable characters affected by use or disuse, the environment, or other factors? These and many other questions had to be answered. In fact, they had to be first formulated properly before a science of genetics was possible. New beginnings. When an interest in nature reawakened in the later Middle Ages, it encountered an entirely different spiritual and intellectual climate from that of the Greeks. The will of God and his power of creation were seen in every object and every process. The emphasis was on origins, the generation of new individuals, rather than on the principle of continuity implicit in inheritance. This spirit, particularly well developed in the 16th century, is superbly described by Jacob, 1970, 19-28. Spontaneous generation, the infusing of life into non-living organic matter, was considered as natural as regular reproduction. The production of monsters created hardly more wonder than that of normal beings. The conversion of the seeds or seedlings of one plant into those of another plant, heterogeny, was considered an everyday occurrence. The origin of new beings was always a gene ratio ab initio. Since the emphasis was on the development that follows the original generation, this period of human thought is particularly important for the history of the field that, after about 1828, was designated as embryology. One must remember that from the 15th to the 18th century biology as such did not yet exist. Rather there were two spheres of interest with only tenuous cross-connections, natural, early theories and breeding experiments, history and medicine, including physiology. Generation was primarily studied by professors of anatomy and by medical physiologists who investigated proximate causations and rarely asked questions concerning inheritance. Their interest was in developmental biology. By contrast, the students of natural history had as their major interest the diversity of nature, the result of ultimate causes. Since all members of the species share in the same essence, inheritance was an obvious necessity and was not seen as a scientific problem. When considered at all, it was done within the framework of the species question. Variation, however, was very much in everyone's mind, particularly the naturalists. The herbalists, botanists, hunters, and animal keepers all delighted in aberrant individuals. At first this related only to strikingly different mutations, see below, but eventually, as more and more specimens accumulated in the herbaria and museums, ordinary individual variation also became apparent and was studied. In due time this became an important source of evidence against the validity of essentialism. From the Middle Ages to the 19th century the thinking of Western man was completely dominated by essentialism, see Chapter 2. Since according to this philosophy all members of a species share the same essence, unaffected by external influences or occasional accidents, the study of nature is simply the study of species. So dominant was essentialistic thinking throughout the 16th, 17th, and most of the 18th centuries that no systematic investigation seemed to have been made about the variation of individual characteristics. When naturalists encountered deviations from the typical expression of the species, they might recognize intraspecific varieties, quite typologically conceived, but these merited no special attention. With the emphasis so strongly on the species, it is not surprising that it was the species problem which gave rise to some of the earliest thoughts about inheritance, those of Linnaeus, Kallrötter, Unger, and Mendel. Any study of the mechanisms of inheritance must be based on the crossing of individuals that differ in definite and seemingly constant characteristics. Variation, thus, is the primary problem to be explained by a theory of inheritance. Yet, an essentialist does not know how to handle variation. The conceptual dilemma for him is that essentially all individuals of a species are identical. As a result, different kinds of variation were hopelessly confused with one another to the end of the 19th and even into the 639, 640, 20th century. This confusion was not resolved until population thinking had replaced essentialism in systematics and evolutionary biology. The nature of the difficulties is most easily illuminated by a historical survey. It will show how the heterogeneity of variation was gradually perceived and the differences among the components understood. Linnaeus. As far as the essentialist is concerned, a species, by definition, has no essential variation. All variation is accidental, not affecting the species' essence. For detail see chapter 6. A variant is not a different species, it is a variety. Although variants and varieties had long been known to naturalists and horticulturalists, Linnaeus is generally credited with having formalized the concept of the variety. He had considerable contempt for varieties and made fun of the flower lovers who named them so enthusiastically. On the whole, he considered varieties to be unimportant, reversible modifications caused by climatic or soil conditions. He also knew of monstrosities, which he likewise considered irrelevant. It never occurred to him to ask about the biological importance of much of variation. Varieties are plants changed by some accidental cause. Philosophy Bot, 1751, Para 158. In his Philosophia Botanica, Para 158, Linnaeus characterized the variety as follows: there are as many varieties as there are different plants produced from the seed of the same species. A variety is a plant changed by an accidental cause, climate, soil, temperature, winds, etc. A variety consequently reverts to its original condition when the soil is changed. Here a variety is defined as what we would now call a non-genetic modification of the phenotype. In his discussion of varieties in the animal kingdom, Para 259, Linnaeus indicates that he includes under the term variety not only non-genetic climatic variants but also races of domestic animals and intrapopulation genetic variants. When we carefully go through his writings, we discover that under the name variety Linnaeus includes at least 4 entirely different sets of phenomena. 1. Non-genetic modifications, owing to differences in nutrition, climate, cultivation, or other environmental influences on the phenotype. 2. Races of domestic animals or cultivated plants. 3. Genetic intrapopulation variants. And 4. Geographic races, like the races of man. As time went on and the heterogeneity of the phenomena that had been subsumed under the term variety was discovered, new terms were proposed for different kinds of varieties. Yet the early theories and breeding experiments. Elaborate terminology which resulted from these efforts, see Plate, 1914, 124-143, did not eliminate the problem, because it did not eliminate the underlying conceptual confusion. Most authors failed to distinguish clearly between 1. Genetic and non-genetic variation, 2. Continuous and discontinuous variation, see Chapter 16, and 3. Individual and geographical variation. As a consequence, when different authors talked about varieties, they often had entirely different phenomena in mind. The situation was aggravated by the fact that, beginning with Linnaeus, 2 different traditions developed which divided botanists and zoologists. When zoologists spoke of varieties, they usually meant geographic races. When botanists did so, they usually meant cultivated varieties or intrapopulation variants. And yet this difference in tradition was the first indication of a sorting out of the different kinds of varieties. Mendel's forerunners. It was in the Linnaean era that the first hesitating steps were taken that eventually led to the founding of genetics. Methodologically, there are 2 ways to learn about inheritance. One is the study of pedigrees. It is rather easy to follow conspicuous characteristics in the human species through several generations, and by this method Maupertuis was able in 1745 to record the occurrence of polydactyly, the presence of a 6th finger and toe, now known to be due to a dominant gene, through 4 generations. By a peculiar coincidence, Reaumur, at about the same time, 1751, likewise demonstrated the dominant inheritance of polydactyly in man. Glass, 1959. This was soon followed by similar studies on hemophilia and color blindness. Although these pedigrees were well known to biologists in the 19th century, they were not used as the basis of theories of transmission genetics. The other method of investigating inheritance is by breeding. This method was employed by two schools, the species hybridizers and the animal and plant breeders, schools which had very different interests and objectives. 2. The species hybridizers. Linnaeus is often described as a pedantic schoolmaster interested in nothing but artificial classifying. To be sure, he was quite fanatical in his endeavor to classify anything under the sun that showed variation. On the other hand, he often surprises the reader. 647. ERS of his essays by his highly unorthodox thoughts on all sorts of natural history subjects. As with any author in whose mind a rich fermentation of ideas is going on, he often promoted simultaneously, or at least consecutively, ideas that seemed strangely in conflict with each other. This is well illustrated by Linnaeus's change of mind concerning the nature of species. The constancy of species was the cornerstone of Linnaeus's early work, and his statement, 1735, tot sunt species, is perhaps his best-known dogma, see chapter 6. Yet later in life he played with the idea 642, one can hardly avoid expressing it in these words, that natural species freely hybridize with each other. In one of his theses, Hartmann, 1764, Amon. Academic, 3, 28-62, no less than 100 putative species hybrids are listed, 59 of which are described in detail. In a prize essay, 1760, dealing with the nature of sex in plants, written for the Academy of Sciences at St. Petersburg, Linnaeus described two hybrids claimed to have been produced artificially by hand cross-pollination. One was a hybrid goat's beard, Tragopogon pratensis xt porifolius, the other a hybrid speedwell, Veronica maritima ex verbena officinalis. It is irrelevant whether or not the plants that Linnaeus had produced were really offspring of the mentioned parental species, which is somewhat doubtful. What is important is that Linnaeus asserted here that a new constant species, that is, an entirely new essence, had been produced by the hybridization of two species. This claim was completely in conflict with all of the previous ideas of Linnaeus and other essentialists. The hybrid, unless it had both essences, would have to have an intermediate essence, and if again hybridized with one of the parents or with another species, it would virtually produce a continuity of essences, a conclusion completely contradicted by the well-defined discontinuities among species found in nature. Nevertheless, Linnaeus himself was so convinced of the production of new essences that he gave new species names to both of his hybrids and entered them in his authoritative Species Plantarum, 1753. Linnaeus sent some of the seeds of his hybrid goat's beard to St. Petersburg, where they were raised by the German botanist Kallröder, who himself was occupied with crossing species of plants. The goat's beards raised by Kallröder in 1761, presumably the F2 generation, showed considerable variability, utterly refuting Linnaeus's claim to have produced a constant new species. Early theories and breeding experiments. Kallröder. Joseph Gottlieb Kallröder, 1733-1806, like nearly all other biologists of the 18th century, obtained his education in a faculty of medicine, at the University of Tübingen. He received his degree in 1755 after 7 years of study and went for the next 6 years to St. Petersburg, where he was appointed in the Academy of Sciences as a natural historian. Here he worked on, among other things, fertilization, pollination, of flowering plants and the production of hybrids. Since Kallröder later was often viewed as a forerunner of Mendel, it is important to emphasize that he did not undertake his work on plant breeding with any purely genetic phlogiston. What he was interested in were such problems as the biology of flowers and the nature of species. His first successful cross was that between the two tobacco species Nicotiana rustica and N. paniculata. The hybrids grew extremely well, and the keenest eye can discern no imperfection, from the embryo to the more or less complete formation of its flowers. Indeed, it appeared as if, like Linnaeus, he had succeeded in producing a new species. However, all efforts to pollinate the hybrid flowers with each other were in vain. Not a single seed was produced by the hybrid, while a normal flower would produce 50,000 seeds. This struck Kallrötter as one of the most wonderful of all events that have ever occurred upon the wide field of nature. This finding was a great relief to him, since it restored his faith in an essentialistic species concept. Again and again in the ensuing years Kallrötter crossed species belonging to a large number of different plant genera. Indeed, he undertook more than 500 different hybridizations involving 138 species. The findings were invariably similar. There was a striking reduction in the fertility, if not complete sterility, of the hybrids. In fact, when Kallrötter discovered normal fertility in some of his species crosses, he discarded these, saying they were obviously not good species. He was correct. He left an exact description of all of his crosses, and in retrospect we are able to agree with him. The discarded crosses were indeed crosses among intraspecific variants. When he examined the pollen of the hybrid plants under the microscope, he found that in nearly all instances the individual grains were shrunken, indeed were mere empty husks. No wonder pollination was unsuccessful. He found well-formed pollen grains only in a few cases and was then able to produce some F2 plants. Fertility was greater in back crosses, that is, when he pollinated the hybrid plants with the pollen of either of the two 645. 644. Rental species. Continuing such back crossing for a number of generations, he finally obtained plants that were indistinguishable from the species to which the hybrids had been back crossed. He described this result in a somewhat quaint language as being able to restore the original species. In his other crossing experiments, for instance with various species of carnations, dianthus, there was sometimes a much less drastic reduction of fertility and F2 and F3 generations were much more easily produced, but in principle the results were always the same. Each species was clearly protected to a lesser or greater degree by a sterility barrier. This, of course, had already been shown by Buffon in his studies on the mule and other animal hybrids, but it had not yet been generalized. Another important finding made by Kallrötter concerned the appearance of the first and second generation hybrids, and of back crosses. He found that the F hybrids were all more or less alike and in most of their characters intermediate between the two parental species. As it was often phrased, the characters of the parent species had become blended in the F offspring. F2 hybrids, on the other hand, showed a great deal of variability, and some resembled their grandparents more than their own regeneration parents. These findings were again and again confirmed in the ensuing 100-year period between Kallrötter and Mendel, at least as far as species crosses are concerned. Kallrötter belonged to the school which thought that a scientific explanation in biology had to be physical or chemical in order to be convincing. This is why he explained the difference between the F and F2 generations with the help of a chemical model. Just as an acid and a base form a neutral salt, said Kallrötter, thus in an F hybrid the female seed material unites with the male seed material to form a compound material. In the F2 hybrids they do not combine in equal proportions, and a variety of offspring is produced, some of which resemble more one, some more the other, grandparent. He was unable to explain why this was so, but it is clear that he did not consider the combining of the parental seed material as a process of blending. Indeed, to my knowledge, no experienced plant breeder, except Nageli, has ever asserted blending inheritance as an exclusive mechanism. Kallrötter was aware that the F2 hybrids in some crosses fall into three types, two of them like the two grandparental species and the third like the F hybrid. However, with his focus on the species problem rather than on individual characters, Kallrötter early theories and breeding experiments found only few cases of such clear-cut segregation. His basic objective was to prove that the hybridization of two species does not produce a third species, and with few exceptions this conclusion is as valid today as it was 200 years ago. The only exceptions are allotetraploids discovered 150 years after Kallrötter. Reading Karl Reuter's painstakingly detailed reports on his many crosses fills us with admiration not only for his industry but for the perceptiveness of his inquiry. His demonstration that flowers are sterile if pollen is prevented from reaching the pistil of the female flower proved conclusively that the male seed material was necessary for fertilization. By comparing numerous characteristics of hybrids with those of the two parental species, and by the production of reciprocal hybrids, he was the first to prove the equal contribution made by the two parents as documented by the intermediacy of the hybrids. He thus decisively established the significance of sex as well as of fertilization, 2 points that were still quite controversial in his day. Furthermore, he conclusively refuted preformation, whether of the ovist or spermist variety. To a modern person it is self-evident that both father and mother contribute to the genetic endowment of a child. Curiously, this was not nearly so evident to former generations. The uncertainty goes back to the Greeks, where chauvinistic males ascribed the main character-forming qualities to the father and where, in the writings of Aristotle and others, the father supplied the form and the mother only the substrate to be shaped by the form. In the 17th and 18th centuries the problems became hopelessly entangled with the problem of development. Was there preformation, or even pre-existence, of the germ or epigenesis of an unformed egg? The preformationists by necessity had to choose whether the pre-existing embryo was located in the egg, ovists, or in the sperm, spermists. Almost all the leading biologists of the 17th and 18th centuries, Malpighi, Spallanzani, Haller, Bonnet, were ovists and thus attributed most of the genetic potential to the female. Van Leeuwenhoek and Boerhaave were among the spermists, the former as co-discoverer of the spermatozoon understandably so. How these extraordinarily well-informed and intelligent authors could have such one-sided theories is difficult to explain. All these authors must have been aware of the fact that in the human species every child shows a mixture of the traits of both parents. They knew that the mulattoes, the result of a cross between a white and a black person, were intermediate. They knew that 645, 646 brids between species, like the mule between horse and ass, were intermediate between the two species. All these well-known facts and others clearly refuted not only a naive belief in pre-existence, embodiment, but also any concept of a purely one-sided contribution by either male or female. And yet such observations shook neither the ovists nor the spermists, as if these authors kept these observations in two unconnected compartments of their brain. Some of their contemporaries were more perceptive. Buffon saw clearly that both father and mother made a genetic contribution, but it was P.M. de Maupertuis, more than anyone else, who developed a theory of inheritance that can be considered as foreshadowing later developments. Glass, 1959, Stubb, 1965. Maupertuis espoused a theory of pangenesis, based on the thought of Anaxagoras and Hippocrates, postulating particles, elements, from both father and mother as responsible for the characters of the offspring. Most components of his theory can be found in the later theories of Naughton, Darwin, and Galton. As fundamental as Karl Reuter's findings were for the understanding of sexuality and reproduction in plants, it would be a mistake to consider him a forerunner of Mendel. Karl Reuter always regarded the essence of the species in a monolithic manner. The very fact of the intermediacy of the hybrid which he found in most cases seemed to confirm to him his holistic interpretation. At no time did he partition the phenotype into individual characters and trace the fate of a given character in different combinations through several generations. This is precisely what was necessary to establish laws of genetics, as Mendel and de Vries were the first to recognize. Karl Reuter is to be admired not only for the importance of his findings on flower biology and the nature of hybrids but also because his experimental approach indicated an excellence of planning and execution unknown among his contemporaries. Alas, like many pioneers, he was too far ahead of the interests of his time and directed some of his most elegant experiments on the demonstration of what to us seems obvious, the sexuality of plants. Karl Reuter's results with species hybrids were in conflict with existing dogma to such an extent, and his findings so novel and revolutionary, that they were not accepted by his contemporaries. Learned volumes were published as late as 1812 and 1820 in which the existence of sexuality in plants was denied and the credibility of Karl Reuter's experiments was questioned. In view of this situation, academies in Prussia and Holland offered prizes in the 1820s. Early theories and breeding experiments. And 1830s in order to settle the problem of hybridization in plants and its utilization for the production of useful varieties and species. This stimulated the work of Wiegmann, Gartner, Godrin, Naudin, Wischura, and other hybridizers, which has been well described by Roberts, 1929, Stubb, 1965, 97-110, and Albee, 1966, 37-54, 62-66. All of these investigations were in Karl Reuter's tradition. They dealt with the sexuality in plants and with the nature of species. Only some of the crosses were between Mendelian varieties with if species but, as in the case of Karl Reuter, the results, even when published, were not followed up. All these authors confirmed, again and again, Karl Reuter's results, such as the intermediacy and relative uniformity of the F generation, the increased variability of the F2 generation, with clear indications of reversion to the parental species, the identity of reciprocal crosses, a contribution by both father and mother, usually more or less equal, to the characters of the hybrid and the occasional occurrence of somatic hybrid vigor even in sterile hybrids. Clear-cut Mendelian segregation rarely occurred, even in the F2, which is not surprising, because species differences often, if not usually, are highly polygenic. Furthermore, Karl Reuter's Nicotiana species, as well as many of the species with which the other hybridizers worked, were polyploids, and the number of chromosomes was often larger in one of the parents than in the other, and then the parent with the larger chromosome set predominated in the appearance of the hybrid. Again and again it must be emphasized that these students were not engaged in an investigation of the laws regulating the inheritance of individual characters. They were interested in the essence of the species as a whole, and to some extent they understood this better than those who practiced the beanbag genetics of the early Mendelian period. The great split in evolutionary biology that characterized the period between 1900 and the evolutionary synthesis of the 1930s can, to some extent, be traced back to some of the cross-currents among the plant hybridizers early in the 19th century. Gartner. Carl Friedrich von Gartner, 1772-1850, was by far the most erudite and industrious of the pre-Mendelian species hybridizers. In his main work, 1849, he summarizes the results of nearly 10,000 separate crossing experiments among 700 species yielding 250. 647 different hybrids. Darwin said of this work that it contains more valuable matter than that of all other writers put together, and would do great service if better known. The piling up of the huge amount of information which Gartner had assembled should have resulted in numerous generalizations, if the claims of the inductivists were valid. This, however, did not happen. Neither Darwin, who studied this work so carefully, nor any other contemporary saw any general laws emerge from Gartner's facts. Actually, Gartner asked himself the 648 same kinds of questions that Karl Reuter had asked nearly 100 years earlier and was, on the whole, quite satisfied simply to describe the results of his crosses. Perhaps one can pay Gartner a left-handed compliment by saying that he showed so conclusively what answers could and what others could not be gotten from these questions that he vacated the field for an entirely new approach. We know that Mendel, who owned a copy of Gartner's book, studied it most carefully, and it is more than likely that this work helped him to phrase the new questions, which resulted in his spectacular breakthrough. Among the thousands of crosses which Gartner carried out were a few dealing with intraspecific varieties of peas and maize. In these, as we shall presently see, Gartner was indeed a forerunner of Mendel. Gartner was not the only German plant hybridizer of this period, but the others, such as Wiegmann or Wischura,
likewise worked within the traditional framework and thus failed to add anything of significance to our understanding of inheritance. Naudin. The French hybridizer Charles Naudin, 1815–1899, differed from Gartner in having a very definite theory, but in his basic thinking he was not too far removed from him. He thought that it was an altogether unnatural process to bring the essences of two species together in the production of hybrids. This expressed itself in their sterility and in the reversion of the later generation hybrids to one or the other of the parental species. There was no blending of the parental essences. Furthermore, Naudin treated the species essence as a whole rather than as a mosaic of independent characters, as Mendel would do in his work. Some of Naudin's species were apparently merely Mendelian varieties, for instance those of Datura, and here Naudin apparently obtained clear-cut M-in-Dihon ratios, which, however, were completely consistent with his interpretation of a perfect segregation of the parental essences. Even though the results of some of his early theories and breeding experiments, crosses, such as the uniformity of the first and the variability of the second hybrid generation, were thus quite Mendelian, Naudin was not a forerunner of Mendel either in theory or in methodology, as evidenced by his failure to look for repeatable ratios. For the same is true for his compatriot D. A. Gaudrin, 1807–1880, who is entirely concerned with the same questions, fertility of the hybrids, their return to the parental type, and so forth, as was Kallreuter nearly 100 years earlier. As his other publications show, his major interest was in the nature of the species. The plant breeders. An entirely different tradition developed side by side with the activities of the species hybridizers, that of the practical plant breeders. Their purely utilitarian aim was to improve the productivity of cultivated plants, to increase their resistance to disease and to frost, and to produce new varieties. Although they also made use of species crosses, their major interest was the crossing of varieties, many of them differing, as we would now say, in merely one or a few Mendelian characters. These plant breeders have a far better claim to be considered as direct forerunners of Mendel than the plant hybridizers. The first of them was Thomas Andrew Knight, 1759–1853, who worked particularly with varieties of fruit trees. He is of special interest to us for having recognized the usefulness of the edible pea, Pisum sativum, as genetic material because the numerous varieties of strictly permanent habits of the pea, its annual life, and the distinct character in form, size, and color of many of its varieties, induced me, many years ago, to select it for the purpose of ascertaining, by a long course of experiments, the effects of introducing the pollen of one variety into the prepared blossom of another, 1823. This special suitability of the edible pea was apparently well known among the plant breeders, including Gartner, and was undoubtedly the reason why Mendel eventually devoted most of his efforts to this species. Knight was a careful experimenter who always emasculated the flowers before applying pollen from different plants, and who used unpollinated or openly pollinated flowers as controls. He described both dominance and segregation, in back crosses, but did not count the different kinds of seeds he had obtained and thus did not calculate ratios. Two contemporaries of Knight, Alexander Seton, 1824, and John Goss, 1820, confirmed dominance and segregation and established the true breeding character of what we would now call 649. The recessives. Some of the experiments of these three breeders were contradictory because they did not appreciate that in the F of the pea the appearance of the seed coat, transparent or opaque, is determined by the mother, while the color of the pea itself, the cotyledons, is determined by the genetic constitution of both parents. Gartner at a later date, in crossing experiments with maize, encountered similar difficulties with the seed coat, pericarp, which contributed to his failure to consistently obtain strict Mendelian ratios. The confusion was resolved only many years later. The 650 endosperm is formed through the fusion of two maternal and one pollen nuclei and may, therefore, display paternal characters, a phenomenon,
later investigated by De Vries and Correns, called Xenia by plant geneticists, Dunn, 1966. The crucial difference between the species hybridizers and the numerous plant breeders, C. Roberts, 1929, was that the latter often studied individual characters and followed their fate through a series of generations. A particularly successful application of this new methodology was made by the French agriculturalist Augustin Sageret, 1763–1851. When crossing two varieties of the melon Cucumis mello, he arranged the characters in a set of 5 pairs. Variety 1. Flesh yellow. Seeds yellow. Rind reticulated. Ribs pronounced. Taste sweet. Variety 2. Flesh white. Seeds white. Rind smooth. Ribs barely indicated. Taste sweet/sour. The hybrids he obtained were not intermediate between the two parents. Instead there was a close resemblance in each character either with one or the other parent. He came to the conclusion that the resemblance of a hybrid to his two parents consists, in general, not in an intimate fusion of the various characters that are peculiar to either of them but rather in an equal or unequal distribution of the unchanged characters. I say equal or unequal because this distribution is far from being the same in all the hybrid individuals of the same provenance, and there exists among them a very great diversity. 1826, 302. In the description of his crosses he clearly designates the characters of one or the other parent as dominant. No one before him had used this terminology quite as unequivocally. Sageret not only confirmed the phenomenon of dominance and early theories and breeding experiments, covered the independent segregation of different characters, but he was also fully aware of the importance of recombination. One cannot admire too much the simplicity of means with which nature has provided itself with the ability to vary its productions infinitely and to avoid monotony. Two of these means, uniting and segregating characters, in diverse ways combined, can lead to an infinite number of varieties. Sageret also recognized that ancestral characters occasionally turn up in these crosses, the potential for which existed but the development of which had not before been favored. As we shall see, Darwin later on was greatly interested in such reversions. Sageret unfortunately never followed up his imaginative and innovative researches. The question has often been asked in recent years why these plant breeders had stopped seemingly so near to the achievement of a genetic theory. Numerous answers have been given, most of them clearly inappropriate. An insufficient understanding of cytology is certainly not responsible because Mendel's explanation was not based on cytological theory, nor is it necessary. The failure of these breeders to develop a genetic theory cannot be attributed to faulty technique because several of them were scrupulously careful in preventing unwanted pollinations and in providing control experiments. One has the feeling that they were quite satisfied merely to get clear-cut results. They simply failed to ask questions about underlying mechanisms. If they had asked them, as Mendel later did, they would indeed have had to add to their technique the careful counting of offspring and the calculation of ratios. In other words, ultimately their failure, if this is what we want to call it, consisted in not asking the decisive questions. They failed to do so because they did not think in terms of variable populations. A populational interpretation was a prerequisite for the new approach toward inheritance. And yet by the 1850s a broad basis had been laid, both by the hybridizers and by the plant breeders. They had clearly established most of the facts needed for a genetic theory, such as the equal contribution of both parents, dominance, the relative uniformity of the first filial, F, generation, segregation, the increased variability of F caret, and the usual identity of reciprocal crosses. The stage was set for the appearance, sooner or later, of an exceptional gifted individual, who would ask previously unasked questions and solve them with new methodologies. This individual was Gregor Mendel, see Chapter 16. 651. 652. 15 germ cells, vehicles of heredity. By saying that a child has inherited this or that characteristic from one of his parents, One postulates a process that provides for continuity between one generation and the next. Indeed, continuity is the essence of the entire concept of heredity. The Greeks already vaguely understood that sexual union was the key to the solution of the problem of heredity, but how the genetic material, as it was later called, was transmitted from one generation to the next was entirely a matter of speculation, see chapter 14. Some of the proposed theories were highly improbable because the inheritance of physical and behavioral characteristics was far too precise and detailed to be explained in terms of heat or of pneuma or of other generalized physical forces, as proposed by most early philosophers. The school of Hippocrates seems to have come much closer to the truth when it explained inheritance as due to the transmission of seed stuff. A qualitative theory of inheritance was proposed by Lucretius, according to whom the qualities of hair, voice, face, and other parts of the body are determined by the mixture of atoms contained in the seed inherited from the ancestors. All observations on inheritance suggested that something qualitative corpuscular was transmitted, but, whatever it was far too small to be seen by the naked eye. An entirely new branch of biology, cytology, first had to develop before the challenge of the nature of the genetic material could be met. The development of this new discipline was not possible until the microscope had been invented and applied to the study of cells. One, that eggs are necessary for the development of a new individual had long been evident, and that the male semen is also important was likewise already a widespread belief among the Greeks, and more or less conceded even by most so-called ovists in the 17th and 18th centuries. However, definite proof was not available until the 1760s. The similarity, if not identity, of the hybrids produced in reciprocal crosses, as in the work of Kallrötter, led to the inevitable conclusion that the genetic germ cells, vehicles of heredity, tributions of father and mother, are equivalent. This insight raised new questions. How could eggs and spermatozoa, or pollen grains, be equivalent in spite of their conspicuous differences in size and shape? Where in the body of male and female is the seed stuff produced that acts as the conveyor of the parental characteristics? And how is the seed stuff structured, to be able to transmit the complex characteristics of an individual to his offspring? These questions could not be answered until the cell theory had been established. The discovery that all living organisms, strictly speaking, only the eukaryota, consist of cells and cell products was made possible by one of the greatest technological advances in the history of biology, the invention of the microscope. The earliest simple microscopes were apparently invented around 1590 by some Dutch spectacle makers, but it was not until 1665 that Hooke, in his Micrographia, described and illustrated some pores and box-like structures in a thin slice of a piece of cork. More and better pictures were published by Nehemiah Grew in the years 1672 to 1682 and by Malpighi in 1675 and 1679. What these authors saw were walls, as is evident from the word cell, and nothing was said about the possible biological meaning of their discovery. Soon afterwards, students of animal tissues, particularly of embryos, like Swammerdam, 1737, C.F. Wolf, 1764, Meckel, 1821, Oken, 1805, 1839, and others described globules or bubbles. At this time it is no longer possible to determine which of the observed globules were real cells and which others artifacts. Baker, 1948, Pickstone, 1973. It took a century and a half after Hooke's first description before any real progress was made in the study of cells, a progress made possible by technological advances in the construction of improved microscope lenses. In the meantime, a number of authors, in part, perhaps, stimulated by atomistic speculations in the physical sciences, had begun to ask what were the ultimate components of the human, and animal, body. According to Hippocratic dogma, the body consists of liquids and solids, and Boerhaave and other anatomist physiologists of the 18th century thought that these solids consisted of very small fibers. Haller became a chief proponent of the fiber theory, which was also adopted by Erasmus Darwin. Although the fiber theory was wrong, it had the merit of focusing attention on the problem of the ultimate building materials of the body. Since fibers, globules, or cells were promoted by different 653 authors, and since the findings of botanists and zoologists often seemed to be in conflict, there was an evident need for a unification of this area of biology. Bichat had recognized 21 different categories of animal tissue. Did they have the same building stones, and if so, what were they? The search for some common element seemed particularly important in those days of idealistic morphology. In the 1820s and 30s, microscopes began to be manufactured in England, France, Germany, and Austria, and soon became a 654 regular part of the equipment of the better laboratories. The new instruments incorporated a number of recent improvements and stimulated microscopic research as nothing had done before. Not only did these investigations show how much of the claims of the 18th century had been based on artifacts, but, more importantly, they showed that there was more to cells than a wall. Up to that time, the word cell, as it was used by Haller and Lamarck, was little more than a name. It was largely seen as a structural element with the emphasis on the cell wall, and nothing was said of function. Only gradually did the improved instrumentation permit investigators to pay attention to the cell contents. Then it was found that living cells are not empty but filled with a sticky fluid which was called sarcode by the French zoologist Dujardin, 1835, and protoplasm by Pourcanier, 1839, and von Moll, 1845. Protoplasm was far more than a technical term for the cell contents, excluding the nucleus. By going to the popular literature of the period, one can see that it was widely conceived as the substance of life in a rather vitalistic manner. See Oxford English Dictionary, under protoplasm. It was considered the ultimate building material of everything living, and for nearly 100 years it was interpreted as the real agent of all physiological processes. Later, when biochemistry began to dissect the cell contents, it became apparent that there was no unitary substance deserving the name protoplasm, but it was not until the introduction of the electron microscope, after 1940, that it was realized what a complex aggregation of structures the cell contents are, with functions undreamed of by the early students of protoplasm. The name protoplasm has now virtually disappeared from the biological literature, and the aggregate of cellular structures and cell fluid outside the nucleus is now referred to by Kalliker's term cytoplasm. The importance of the cell wall was more and more de-emphasized. Leydig, 1857, and M.J.S. Schulze, 1861, finally pointing. Germ cells, vehicles of heredity. Out that animal cells had no cell wall, many of them being quite naked, covered only by a membrane. The other conspicuous element of the cell contents is the nucleus. Although nuclei had been observed in plant cells and even in some animal cells at least as far back as the beginning of the 18th century, the British botanist Robert Brown, 1773 to 1858, deserves credit for having been the first, 1833, to consider the nucleus a regular component of the living cell. What its function was remained, however, quite uncertain, and its role in the cell was at first totally misinterpreted. Until the 1870s, cell and protoplasm were considered as almost synonymous and the nucleus as an unimportant cell component that was either present or absent. Indeed, it was believed to be absent from most cells during part of the nuclear cycle. This was an understandable conclusion since the spherical nucleus, surrounded by a membrane, disappears during cell division. The Schwann-Schleiden cell theory. By the end of the 1830s, the uncertainties about the cell crystallized into two major questions: what is the role of the cell in the organism? And, how do new cells originate? These questions received a preliminary answer in the Schwann-Schleiden cell theory. The most influential cytologist of the period was the botanist M. J. Schleiden, 1804 to 1881.
With enormous enthusiasm he not only recruited the zoologist Theodor Schwann, 1810–1882, for cytological research but also developed some of the leading young botanists of the century, like Hofmeister and Nageli. It was he who induced young Carl Zeiss to start his subsequently so important optical firm, and gave him enough orders to ensure success. Zeiss, in due time, more than fully repaid his debt to biology by inventing better optical instruments, particularly microscopes. Schleiden belonged to the generation of young German biologists who reacted violently to nature philosophy and who attempted instead to explain everything in a reductionist physico-chemical way. Buchdahl, 1973. It was unthinkable for him to answer the question, how do new cells originate, by saying from pre-existing cells. This would have been too much like preformation, a theory thoroughly in disrepute at that time. Consequently, Schleiden applied the principle of epigenesis to cell formation and es. 655. 656. Established, in 1838, a theory of free cell formation. He suggested that the first step in cell formation was the formation of a nucleus by crystallization from granular material within the cell contents. 3. This nucleus would grow and eventually form a new cell around itself with the outer nuclear membrane becoming the cell wall. Schleiden gave a detailed account, 1842, 191. New nuclei might form within existing cells, or even crystallize within a formless organic fluid. A major controversy of the ensuing 2 decades was whether or not such free cell formation took place, the eventual answer being negative. Although he was shown to have been wrong, Schleiden decisively advanced cytology by focusing attention on a problem and by proposing a succinct, testable theory. More important, in the long run, was his insistence that the plant consists entirely of cells and that all the highly diverse structural elements of plants are cells, or their products. In a classical publication, Mikroskopische Untersuchungen über die Übereinstimmung in der Struktur und dem Wachstum der Tiere und Pflanzen, 1839, Schwann showed that Schleiden's conclusion also applies to animals. Independently, this was also claimed by Oken in 1839. By examining embryonic animal tissues and by following their subsequent development, he succeeded in demonstrating a cellular origin even for tissues like bone, which when full-grown show no trace of such an origin. The fact that both animals and plants consist of the same fundamental element, cells, was one additional piece of evidence for the unity of life and was celebrated as one of the great biological theories, the cell theory. It helped to give substance to the word biology, coined by Lamarck and Treviranus, until then a largely unfulfilled program. As important as this new insight was, one is somewhat puzzled over the immense excitement caused by the cell theory. No one yet really understood the cell and the functions either of the nucleus or of cytoplasm. At that time, the name cell theory was primarily applied to Schleiden's theory of free cell formation, Virchow, 1858, and perhaps the idea of purely physico-chemical formation of nuclei and cells, by crystallization, had considerable appeal in the prevailing climate of extreme physicalism and reductionism. A very different reason is suggested by the fact that Breuck and others referred to cells as elementary organisms. His thinking evidently was influenced by idealistic morphology. Just as Goethe reduced all parts of the plant to the leaf, so did Breuck. Germ cells, vehicles of heredity, reduce all parts of any organism to the cell. Indeed, Wigand, 1846, called the cell the Eigent like Erbpflanze. Some of these statements, also by other authors saying similar things, have an almost vitalistic flavor. This led to a reaction among the physicalists, as evidenced by Zox's, 1887, declaration that the cell was a phenomenon of only secondary significance, since the formative forces reside throughout the organic substance. Others devalued the cell because for them the protoplasm was the basic substance of life. Clearly the cell did not fit into an explanatory model based on the universality of forces. Claims like those of Sachs were vigorously opposed by E. B. Wilson in the introductory statement of the cell, 1896. Regardless of what it meant to various authors, the cell theory contributed to the firmer establishment of the unity of the living world. Furthermore, it led to the concept of organisms as republics of elementary living units. The characteristics and unity of life cannot be limited to any one particular spot in a highly developed organism, for example, to the brain of man, Virchow, 1971 1858, 40, rather, life is found in an equal manner in each cell. Somehow this was, at that time, considered a strong argument against vitalism. Whether or not Virchow was influenced by somewhat similar ideas of Oken remains to be studied. For Schwann and Schleiden the cell still was primarily a structural element, but already in the 1840s other authors stressed the physiological, particularly developmental, nutritional, role of cells. As the knowledge of cells and their constituents, particularly the nucleus, grew, the meaning of the concept cell theory gradually shifted. Schleiden's theory had the immediate effect of stimulating exceedingly active research on dividing cells of animals and plants. In 1852 R. Remak, 1815–1865, showed that the frog egg is a cell and that new cells in the developing frog embryo are formed by the division of previously existing cells. He emphatically rejected free cell formation. In this he was joined by Rudolf Virchow, 1855, who showed for many normal and pathological animal and human tissues that every cell originated by division from a pre-existing cell. He established as a general principle, that no development of any kind begins de novo, and consequently one must reject the theory of spontaneous generation just as much in the history of the development of individual parts as we do in that of entire organisms. Virchow, 1858, 54. Kolliker, as well as several botanists, arrived at the same con. 657. 658. Illusion at about the same time, even though Schleiden's authority tended to delay its acceptance in botany. In 1868, 370, Darwin was still uncertain whether or not free cell formation occurs. In due time Virchow's famous aphorism Omnis cellula e cellula, 1855, every cell from a pre-existing cell was accepted by everyone, even though the details of the process of division, particularly of the nucleus, were not understood at that time, see below, under mitosis. With this new interpretation of the cell, the stage was set for a renewed consideration of the process of fertilization. If all parts of the body consist of cells, is this also true for the gonads, ovaries and testes? And what about the male and female seed stuff? Does it consist of cells? How different are the sex cells of males and females? Such well-formulated questions were, of course, not asked at the beginning, but they were logical consequences of the cell theory, and it became apparent, in due time, that no viable theory of inheritance could develop until the role of cells in fertilization had been elucidated. It was in these decades that the concept of germ cells emerged. The meaning of sex and fertilization. That there are two different sexes in animals was known from the earliest times, since the analogy with man was inescapable. For sexuality in plants, at least its almost universal occurrence, was a much later discovery. To be sure, sexuality is rather obvious in some dioecious plant species, that is, species in which one individual has only male, and another one only female, flowers, and this knowledge was used by the ancient Assyrians when they fertilized female date palms with pollen shed by the flowers of male trees, see chapter 13. After the Middle Ages, Andrew, 1672, speculated on the role of pollen as the agent of fertilization. However, it was not until Rudolf Jacob Camerarius, 1665–1721, published his De Sexu Plantarum Epistola, 1694, that the sexual nature of plant reproduction was firmly established.
He clearly designated the anthers as the male sex organs, and emphasized that pollen is needed for fertilization, as he had discovered through experimentation. Camerarius was fully aware of the fact that sexual reproduction in plants was the exact equivalent of sexual reproduction in animals. He germ cells, vehicles of heredity. Ask some exceedingly penetrating questions about the exact role played by the pollen grains during fertilization. It would be most desirable, if we could learn from those who have access to microscopes, what is the content of pollen grains, how far they penetrate in the female apparatus, whether they reach the place intact where the seed sperm is received, and what issues from them when they burst. 1694, 30. This challenge was subsequently taken up by Kallrötter and other hybridizers but was not fully met until the work of Amici, Hofmeister, and Pringsheim, from 1830 to 1856, see Hughes, 1959, 59-60, and below. Camerarius also recognized the role of wind in pollination and that seed set might occur under certain conditions even though pollination was prevented. His epistola had a great impact on his contemporaries and was apparently responsible for the increasing number of attempts at experimental plant hybridization in the 18th century, culminating in the work of Linnaeus and Kallrötter, see Chapter 14, and Zirkel, 1935. Still, sexuality in plants continued to be widely denied well into the 19th century. Even Kallrötter and Linnaeus did not sufficiently stress the universality of sexual reproduction in plants and the obligatory need for cross-pollination in the majority of plant species. Nor was it generally realized that plants with flowers, as understood by the layperson, are invariably animal-pollinated. In 1795 Christian Conrad Sprengel, 1750-1816, published a classical treatise on the pollination of flowers by insects which emphasized all these points, but his work was so far outside the standard thinking and interests of the period that it was almost completely ignored. The most remarkable aspect of this volume is that Sprengel carefully described the numerous mutual adaptations of flowers and insects that facilitate cross-fertilization or make self-fertilization impossible. It was the first flower biology, a fact duly appreciated by Darwin. Origin, 98, 1862. An obvious inference from Sprengel's work, although not made until more than a century later, is that individuals of sexually reproducing species are not types or pure lines but members of populations. The nature of fertilization. After the cell theory had been established, it would have seemed obvious that one would have to ask whether this theory could be extended to eggs and spermatozoa. This was done very quickly for the spermatozoa, which von Baer still had considered. 659. To be parasitic worms in the semen. Kolliker showed already in 1841 that they are cells, as can be shown by the study of spermatogenesis. In the case of the egg, things went more slowly. Neither von Baer, who discovered the mammalian egg in 1827, nor Pourquenier, who in 1830 discovered the large nucleus of the ovarian egg, which he called the germinal vesicle, were aware of the cellular nature of these structures. It was Remak who in 1852 showed that the frog egg is a single cell, and Gegenbohr who in 1861 extended this conclusion to the eggs of all vertebrates by demonstrating that 660 the yolk granules were not cells. With modern hindsight one would think that the nature of fertilization in animals would be speedily inferred, once it was realized that the egg is a cell and so is the spermatozoon. Of course, one would say, fertilization is the fusion of these two germ cells, giving rise to a new individual. Actually, it took many decades before this insight was achieved. The same conclusion should have been reached for pollination in plants, on the basis of the observations of Kallrötter, Amici, Mendel, and others. One suggestive observation after another was made between 1824 and 1873, only to be either ignored or to be interpreted in a manner which to us seems clearly contradicted by observation. As late as 1840, so progressive a botanist as Schleiden questioned sexuality in plants. But then, from 1873 to 1884, everything suddenly fell into place. Why had the phenomenon of fertilization caused such difficulties of interpretation for such a long time? There are many reasons, but perhaps the most important one is that this phenomenon belongs both to functional and to evolutionary biology. Embryologists were impressed by the fact that an unfertilized egg may long remain dormant, and does not start to develop until it is fertilized. They assigned therefore to the spermatozoon a purely mechanical role, as is indeed true in the exceptional phenomenon of pseudogamy, corresponding to the dropping of a coin into a jukebox. In contrast, those who were interested in heredity saw in fertilization a process resulting in a mixing of the paternal and maternal hereditary endowment. Not surprisingly, those holding such diverging interpretations of the meaning of fertilization subscribed to entirely different explanatory models. That fertilization has a dual significance, and that the two opposing interpretations were both correct, was not fully realized until the last 2 decades of the 19th century. Since the controversy about fertilization is one of the most germ cells, vehicles of heredity, interesting ones in the history of biology, leading to a direct confrontation of the students of proximate and of ultimate causes, it would seem worthwhile to provide a short survey of the opposing arguments. Much as they differed in detail, theories of fertilization from the Greeks to the early 19th century postulated that the mother supplied a single, more or less uniform, unit of matter, later designated as an ovum, while the male supplied some potency, involving pneuma, heat, or some physical or vital forces that induced the development of the egg. As late as 1764 Wolff still assumed that pollen and animal semen merely served as refined nutrition necessary for the stimulation of growth and development of the embryo. Even von Bayer's 1828 account has a remarkably Aristotelian flavor. In Aristotelian terms, the female contributed the material, the male the efficient, formal, and final causes. This interpretation appeared to be confirmed when it was discovered by Bonnet in 1740 that eggs of plant lice, aphids, can develop even without the presence of males, parthenogenesis. Clearly, the potential of the eggs to develop could be induced by some generative force exercised by the female herself. This was a shocking discovery to Bonnet's contemporaries, but the researches of the 19th century showed that such virgin birth was widespread in the animal kingdom, either as a seasonal phenomenon, as in aphids and rotifers, or as a permanent one. Churchill, 1979. In the 1840s a special kind of parthenogenesis, aeronautica, was discovered in the Hymenoptera, where unfertilized eggs give rise to haploid male offspring. The discoverer of this extraordinary process was Johann Giersen, a contemporary of Mendel and, like him, a Catholic priest of Silesian birth and a beekeeper. He substantiated his hypothesis, 1845, that drones come from unfertilized eggs of the honeybee by ingenious crossing experiments between German and Ligurian bees. A process of uniparental reproduction, apomixis, analogous to parthenogenesis, is even more widespread in the plant kingdom, where it was the source of a great deal of confusion during the early period of genetics. See Mendel's Hieracium crosses, Chapter 16. The special role of parthenogenesis as an evolutionary strategy has been much discussed in recent years. 5. One can observe again and again in the history of biology that problems have their ups and downs, and so it was with fertile. 661. Isation. After the splendid beginnings made by Camerarius, Kallreuter, and Sprengel came a lull in the BRST quarter of the 19th century. When fertilization again began to attract attention in the 1830s and 40s, it was during a period of extreme physicalism. According to von Liebig, all chemical activity depended upon molecular agitation induced by the close contact of two substances and their constituent particles. Coleman, 1965. T.L.W. Bischoff, 1847, articulated this concept more explicitly by applying it to fertilization. The semen acts on contact through a catalytic force, 662, that is, it constitutes a particular form of matter characterized by intrinsic movement which is conveyed to the egg, in which it causes the same or a similar organization of the atoms. There was no thought of a penetration of the spermatozoon into the egg nor of an effect of the gross movements of the spermatozoa. Everything was due to molecular excitation. This interpretation fitted so beautifully into the mechanistic reductionist dogma then prevailing in the schools of Schwann, du Bois-Reymond, and Ludwig that it was almost universally adopted. One of the major proponents of this theory was the great morphologist Wilhelm His, who wanted to reduce all biological phenomena to chemistry, mathematics, and above all mechanics. The fertilized egg contains the excitation for growth. In this excitation is the entire contents of genetic transmission from the paternal as well as from the maternal side. It is not the form which is transmitted, nor a specific form-giving stuff, but merely the excitation to induce the form-giving growth, not the characters themselves but the beginning of a uniform process of development. 1874, 152. It was one of the tragedies of biology and biochemistry that has greatly influenced the thinking of his nephew, F. Mayr. This was in part responsible for the fact that Mayr completely missed the significance of his own discovery of nucleic acid, see chapter 19. As late as 1899 Jacques Loeb could write, "The ions and not the nucleon in the spermatozoon are essential to the process of fertilization." Owing to the powerful influence of the physical interpretation of fertilization, observation after observation was ignored even though they clearly contradicted the reductionist interpretation or at least demonstrated that it provided only a partial solution. Let us review the history of the discoveries which finally provided the key to the riddle of fertilization. Germ cells, vehicles of heredity. The process of fertilization. The first question to be answered was whether it was the seminal fluid as a whole, or the spermatozoa in the fluid, that affected fertilization. As early as the 1780s L. Spallanzani performed experiments which should have given him the right answer, but did not. Male frogs dressed in little panties, permeable for some of the seminal fluid but not for the spermatozoa, were unable to fertilize the eggs of the females with which they were mated. In 1824, two Swiss physiologists, J. L. Prévost and J. B. Dumas, published the results of a series of imaginative and decisive experiments on frogs which demonstrated conclusively that the spermatozoa were the fecundating element and the seminal fluid only the vehicle. The presence of spermatozoa inside of fertilized eggs was shown by M. Berry in 1843 for rabbits and by G. Newport in 1851 for the frog, though neither author observed the actual entry of a spermatozoon into an egg or was able to determine their subsequent fate. Their observations were therefore unable to dislodge the physical theories of fertilization. In 1854 Thuret showed for Fucus, a common kelp, that ciliated spermatozoids surrounded the egg and entered it. Having observed this, he was even able to perform artificial fertilizations. The first conclusive description of the process of fertilization was provided in 1856 by N. Pringsheim for the freshwater alga Oegonium. He actually observed the entry of the male gamete into the female oegonium and drew from this observation the correct conclusions that the first cell, the zygote, of the new organism is formed by the fusion of the male gamete and the female egg cell and that fertilization is achieved by a single spermatozoid. With the sexuality of cryptogams at that time still controversial, this observation likewise was ignored in spite of the decisiveness of Pringsheim's demonstration. Matters were not helped when in the 1850s and 1860s several authors emphasized that the vigor of a plant was enhanced if the germ was the product of fertilization by several pollen grains. It was Mendel, letter of Nageli, July 3, 1870, who set out to refute the opinion of Darwin that a single pollen grain does not suffice for fertilization of the ovule. Darwin's opinion was largely based on a misinterpretation of the work of Naudin, who actually had adopted the one pollen grain hypothesis. Mendel, experimenting with Mirabilis jalapa, obtained 18 well-developed seeds from fertilization with single pollen grains. The majority, 663, of plants raised from these seeds are just as vigorous as those derived from free self-fertilization. This settled the problem unequivocally, alas, owing to Nageli's lack of interest. This correspondence was not published until 1905, Correns, 1905. Other workers at the same period elucidated the sequence of steps during the process of fertilization in plants. In 1823 J.B. Amici saw how an isolated pollen grain put out a pollen tube, and by 1846 he was able to show that an egg cell in the ovule was stimulated, after the arrival of the pollen tube, to develop into an 664 embryo. Neither he nor Hofmeister, who in 1849 confirmed the sequence of events, had any idea just what role the pollen tube played. Botanists had been the pioneers in cell research in the first half of the 19th century. But after about 1850, when adequate methods of tissue fixation became available, animal cytologists took over the leadership. 6. The absence of a cell wall in animal cells made it much easier to concentrate on the nucleus and its changes during cell division, and furthermore, fertilization was not complicated by the phenomena of pollen tube, embryo sac, and so on. After Kolliker and Gegenbohr had proven the cellular nature of both egg and spermatozoon, and with the cell being redefined as a nucleus located in protoplasm, the stage was set for the question, what happens to the male and the female nucleus, and to the male and the female protoplasm, when the spermatozoon enters the egg? For the 25-year period after 1850 the views on fertilization can be considered to reflect two alternate theories, the contact theory and the fusion theory. The physicalists who saw in fertilization a transmission of excitation thought that the mere contact of spermatozoon and egg cell was the essence of fertilization, and if one is only interested in the initiation of the cleavage of the fertilized eggs, that is, in proximate causation, this is a conceivable explanation. Nevertheless, it required considerable credulity and a complete lack of interest in ultimate causation to accept the thesis that a mere exchange of excitations could explain the combination of paternal and maternal characteristics in the newly formed individuals. The opposition to this view was strengthened by the results of the increasingly precise microscopic analysis of the process of fertilization. This eventually led to the abandonment of the contact theory of the physicalists. Germ cells, vehicles of heredity. The role of the nucleus. Even though it was widely appreciated by that time that the spermatozoon consisted largely of nuclear material, the conclusion that the nucleus is really the crucial element in fertilization was not generally accepted. The reason for the hesitation was the common belief that the spermatozoon dissolved once it had entered the egg. To be sure, some authors had seen two nuclei in freshly fertilized eggs, one author even observing that they fused, but they had failed to draw the conclusion that one of these nuclei was nothing but the spermatozoon reconvert into a nucleus. Two technical developments greatly helped in bringing about the final solution. One was the realization that neither the mammalian nor the avian egg were favorable for fertilization studies. Zoologists, as a result, tested the eggs of numerous other kinds of organisms and eventually found that, depending on the particular problem to be solved, whether fertilization, mitosis, or chromosomal continuity, various other species were far more suitable. Even more important was the rapid development of microscopic technique. Microscopes and their lenses were constantly improved, ultimately culminating in the introduction of the oil immersion lens in 1870. Wilhelm Haas invented the microtome, about 1866, and in the ensuing years new types of microtomes allowed the preparation of ever thinner sections. New methods of fixing the various kinds of biological materials were also discovered, and, finally, the invention of aniline dyes made an endless array of new stains available, many of them with a highly specific affinity for certain cell components or molecules. These technical advances increased the amount of visible microscopic detail by at least an order of magnitude. Bütschli, 1873, 1875, and Auerbach, 1874, in nematodes, and Schneider, 1873, in a platyhelminth were perhaps the first persons to observe and understand that the nucleus of the zygote was formed by the fusion of the egg nucleus and a male nucleus derived from a spermatozoon, but their somewhat casual observations were not given due attention. It was Oscar Hertwig who once and for all established the nature of fertilization. Armed with excellent equipment, he studied in the spring of 1875 the process of fertilization in the Mediterranean sea urchin Toxopneustes, equals Paracentrotus, lividus. The eggs in this species are small, with very little. 665. 666. Yolk, and thus transparent even at high magnifications. Both egg and sperm were simple to preserve, fix, and stain. Hertwig clearly demonstrated that the second nucleus observed in the egg right after fertilization was derived from a spermatozoon. He also showed that only a single spermatozoon is involved in fertilization. Finally, he showed that the male and the female nucleus fuse into a single nucleus and give rise, by division, to all the nuclei of the developing embryo. The nucleus of the fertilized egg cell, zygote, never disappears, and there is a complete continuity between it and all the nuclei in the newly developing organism, as had already been shown by Schneider, Beigeli, and others. As Fleming phrased it in a succinct aphorism, omnis nucleus e nucleo. Cytological research reached a level of activity during the 1870s and early 1880s previously unknown in any branch of science. At that time it was not uncommon for the leading cytologists, most of whom worked in German laboratories, to publish up to 7 papers in a year. Hughes, 1959, 61. Hertwig's account, 1876, still contains some errors and was therefore not at once accepted by the other leading students of fertilization. See the specialist literature for the claims of Van Beneden and Strasburger. However, these errors were soon corrected, and Hertwig's valid observations confirmed by the superb investigations of Hermann Fall, 1845–1892. He correctly described the 2 maturation divisions of the egg nucleus, see below, and was able, through enormous perseverance, to observe the actual penetration of a spermatozoon into the egg. He fully confirmed that the male nucleus fuses with the female nucleus and gives rise, as Hertwig had claimed, to the nuclei of all the cells of the new organism. Fall experimentally induced simultaneous fertilization by several spermatozoa and showed that this process always results in aberrant cleavage and non-viable larvae. Fertilization is always effected by a single spermatozoon, Fall, 1879, thus confirming Mendel's observations in plants. Nearly all the students of fertilization, in animals and in plants, henceforth agreed that the fusion of the nuclei was the decisive element. These findings decisively refuted the claims of the physicalists that a transmission of excitation is the essence of fertilization. To be sure, natural and chemically induced parthenogenesis proved that the cleavage process could be induced in eggs without fertilization. But genuine fertilization always consists of the mixing of the substance contained in the nuclei of male and female gametes. The acceptance of this conclusion was only one manifestation of germ cells, vehicles of heredity. The spreading rebellion against the dogmas of physicalism in the second half of the 19th century. The excessive and rather paralyzing preoccupation with forces, movements, and quantities was replaced by a growing recognition of the importance of form and quality. A similar emancipation took place at about the same period in chemistry, Fruton, 1972. Yet, in the 1870s the fascination with forces was still so great that many cytologists devoted far more attention to the locomotory apparatus of the cell, aster, and spindle fibers than to nucleus and chromosomes. Others recognized clearly that a mixing of substances is the true nature of fertilization and that this insight raises an entirely new set of questions, as we will see in the next section. Most of all, it encouraged, indeed it required, a study of the microstructure of cell and nucleus. The material basis of variation. And inheritance. When the importance of variation began to be realized toward the end of the 18th and the beginning of the 19th centuries, questions concerning its causation began to be asked. Variation may affect any aspect of an organism, any of its so-called characters, whether morphological or non-morphological. There had to be some underlying element, some physiological or chemical element that caused this variation. At first, it was not even evident what questions one should ask, and it is only through hindsight that it is possible to phrase them in a precise form. The questions to be answered were, is the totality of characters of a species controlled by a single, uniform, species-specific substance, or is each character determined by a separate particle that can vary independently? Is the genetic material soft, so that it can change gradually during the lifetime of the individual or through generations, or is it hard, that is, completely constant and only changeable through a sudden and radical alteration, a mutation, as it was called subsequently? How are the hereditary particles formed in the body? Do the particles contributed by father and mother during reproduction retain their integrity after fertilization, or do they fuse completely? These were the foremost questions concerning generation and inheritance that were asked in the second half of the 19th century. Some of the most brilliant minds in the whole history of 667, 668 biology puzzled over them and were able to greatly narrow down the number of possible answers. They came up with many ingenious hypotheses, some correct and many of them not, but again and again they found themselves up against seemingly irreconcilable contradictions. How could they have possibly guessed the ultimate answer to their questions, which was found almost a century later by molecular biology? The unprecedented answer was that the genetic material is merely a blueprint, a program of information, not at all forming part of the developing organism, and chemically quite different from it. But it was a long way until this insight was finally achieved. Let us now go back to 1850. Protoplasm had only recently been named and proclaimed to be the fundamental substance of the living organism when it was postulated, Breuck, 1861, that protoplasm could not possibly perform its functions unless it was composed of ultimate units, some sort of structural elements. Indeed, all those who thought more deeply about inheritance realized that the cell as a whole could not serve as the basic element of inheritance. After all, each gamete is only a single cell, and how could such a single unit control, as a unit, the 10,000 or more differences in the characters of an individual? Forerunners of the gene concept. From the 1860s to 1900, the nature of the structural elements in cytoplasm and nucleus was the subject of endless speculation, most of it with little or no experimental or observational basis. This orgy of uninhibited speculation in the period between Spencer, 1864, and Weismann, 1892, was quite in contrast to the attitude of the preceding 30 years, 1835 to 1864, which had been a relatively sober period, evidently in reaction to the preceding excessively speculative period of nature philosophy, from about 1800 to 1835. During the sober period, many authors wrote purely descriptive accounts of the most exciting subjects and resolutely refused to make generalizations, even when they seemed to be staring them in the face. In another sober period, after 1895, Th. Morgan ridiculed Weismann as the philosopher from Freiburg and, with reductionism and positivism on the rampage, nothing but scorn was expressed for speculation. Some of this criticism was deserved, see below. Yet, we are now inclined to think more kindly of the authors of these speculations, for they made one invaluable germ cells, vehicles of heredity. Tribution, even though their answers might have been wrong, they were the people who began to ask the right questions. How can one find answers if one doesn't know what questions to ask? Wrong theories very often bring new life to a stagnant field, and new observations which they engender very often lead almost automatically to their own eventual refutation. Virtually all these authors postulated that the body, including its cells, consisted of minute particles or corpuscles. These corpuscles had to play a dual role, in ontogenetic development and in inheritance. But this was the extent of the agreement. On every other point these authors disagreed with each other. There was vast disagreement as to the nature of these particles, their role in development, and their transmission from generation to generation. Each author would coin a new term for these particles and propose a new theory of development and inheritance. 8. A capacity for self-replication had to be one of the properties of these particles. And this, at once, provided for a drastic difference from inanimate nature, where self-replication does not occur. The growth of a crystal, for instance, proceeds in an entirely different manner from the growth of a cell. Finally, for evolution to occur, these particles had to have the capacity either to change continuously, soft inheritance, or to be nearly constant, hard inheritance. Complete constancy would preclude evolution, so the particles must be able to mutate occasionally, that is, to change from one constant state to another. Thus, a theory of transmission genetics was complete only if it provided simultaneously an explanation for the physical nature of these particles, for their location and arrangement in the cells, for their replication, and for their mutation. In a more or less complete manner, the theories of inheritance proposed in the 90 years between 1860 and 1950 attempted to find solutions to these problems. The first general theory of inheritance and development was the purely deductive one proposed by the philosopher Herbert Spencer, 1820 to 1903. It was strongly influenced by the phenomenon of regeneration, for instance the ability of certain animals to regenerate a lost tail. Spencer, 1864, postulated the existence of physiological units, intermediate in size between cells and simple organic molecules. These units were thought to be self-replicating, species-specific, identical units, within a given individual. Spencer makes seemingly contradictory statements concerning the amount of difference among the units of different individuals of the same. 669. 670. Species. Differences among siblings are attributed to differences in the number of units contained in the respective gametes received from father and mother. The form of an organism is caused by the capacity of these units to place themselves adjacent to each other in a predetermined manner, just as molecules do when forming a crystal. Furthermore, the physiological units have the capacity to respond to the environment and thus bring about an inheritance of acquired characters. The next major theory of inheritance was Charles Darwin's theory of pangenesis, published in 1868 in the Variation of Animals and Plants under Domestication. As De Vries, 1889, correctly pointed out, Darwin's theory actually consists of two components, one being the hypothesis that the hereditary qualities of an organism are represented in the germ cells by a large number of individually different invisibly small particles, the so-called gemmules. These multiply by division and are transmitted from the mother cell to the daughter cells during cell division. The most important part of this hypothesis is that it postulates the existence of an enormous number of different kinds of gemmules, a population of gemmules, so to speak, in contrast to the essentialistically conceived physiological units of Spencer, all of which were identical in a given individual. The second component of Darwin's theory, pangenesis, will be discussed below. In the ensuing 15 years various other authors postulated similar hereditary particles, like the plastidules of Ellsberg, 1874, and Haeckel, 1876, either all identical, like Spencer's, or individually different, like Darwin's, without adding any essentially new ideas. By far the most ambitious and speculative theory of inheritance of that period, however, was proposed by the botanist Nageli, 1884. He asserted, more clearly than most others before him, that the protoplasm of an organism consists of two components, ordinary or nutritive protoplasm and idioplasm, a name for that part of the protoplasm which is responsible for the genetic constitution of the organism. This separation was inferred from the observation that father and mother usually contributed about equally to the genetic constitution of the offspring, even though the egg may have a mass that is more than 1,000 times larger than that of the spermatozoon. Consequently, only a small fraction of the egg, approximately equal to the mass of the spermatozoon, can consist of idioplasm. One would think that this conclusion would have induced Nageli to postulate that the idioplasm Germ cells, vehicles of heredity, is restricted to the nucleus. Curiously, this is not the case, rather, his idioplasm consists of long strands which go from cell to cell, independent of the nucleus. Each strand consists of numerous groups of molecules, micelles, the cross-section through the strand being everywhere identical. Each strand has specific properties, and bundles of such strands control the properties of cells, tissue systems, and organs. Growth consists of the elongation of these strands without any change in their consistency. Nageli explains the activity of the idioplasm as due to differential states of excitation of different groups of molecules within the strands. This is why he called his speculations the mechanical physiological theory of evolution. He concludes several hundred pages of such claims with the modest statement, the idioplasm theory permits the only possible interpretation how inheritance and phylogenetic change can take place naturally, that is mechanically, 1884, 81. Barthelmess, 1952, states that he has presented Nageli's speculations in such detail because they are perhaps the most extreme example of the speculations of the period. Today we are appalled at such a house of cards of fantasies and are amazed at the self-assurance with which the author claims that his is the only possible solution of the great riddle of organic evolution. Nevertheless, precisely because Nageli had speculated about every conceivable aspect of the processes of inheritance and development, he exerted an enormous influence. Indeed, during the next 20 years one does not find a paper in this field that does not quote him extensively, and usually with considerable reverence. After all, the great Nageli was one of the dominant figures of his day. Nevertheless, almost every detail of his theory was radically wrong and almost none of it based on any known fact. One point, which must be kept in mind when evaluating Nageli's theory of inheritance, is that he was mostly interested in species hybrids where Mendelian segregation of characters is rare or absent. This is one reason why he could not understand Mendel's findings in peas, see chapter 16. The one idea of Nageli's that had a truly constructive impact was his insistence on a strict separation of idioplasm from the remaining protoplasm. At about the same time at which Nageli published, 3 other authors independently came to the same conclusion and inferred, additionally, that the genetic material was contained in the nucleus, see below. It is really quite incomprehensible why Nageli failed to recognize the nucleus as the seat of his idioplasm. After all, the role of the nucleus in fertilization was 671. Widely appreciated by 1884, and the relative equality of material and paternal idioplasm, which was the original impetus for his speculations, should have also suggested to Nageli the role of the nucleus. Haeckel, on the basis of far less evidence, had concluded as early as 1866, 287 to 288, that the nucleus has to take care of the inheritance of the heritable characters, while the surrounding cytoplasm is concerned with accommodation or adaptation to the environment. By about 1884 it had become reasonably well established and 672 accepted that fertilization in both animals and plants consists of the fusion of a maternal and paternal germ cell, gamete, that both gametes make an equal contribution to the formation of the new zygote, and that the crucial process is the fusion of the respective nuclei. The attention next shifted to the nuclei. Are they just an amorphous mass of germ substance, as was the unspoken assumption of the epigeneticists, perhaps only the fuse which ignites the developmental process in the egg cell, or is the nucleus, in spite of its minute size, highly structured with its invisible microstructure holding the key to the extraordinarily precise and specific development that follows fertilization? If one envisions the nucleus as nothing but the initiator of cell development and cell division, one will assume that the nucleus is dissolved after it has done its job, to be newly formed before each new cell division or at least before gamete formation. Since nearly all of the cytologists in the second half of the 19th century had been trained as physiologists or embryologists, the emphasis was on developmental problems, and there seemed no need to postulate a continuity of the nucleus. The genetic question of the transmission of the characters of the parental generation to the daughter generation was rarely asked. The last remnants of a belief in free cell formation or in the de novo formation of nuclei were finally eliminated in the years 1875 to 1880, when 5 investigators Balbiani, Van Beneden, Fleming, Schleicher, and Strasburger were able to follow continuously all the events during cell division. They proved 3 important facts: 1. That the division of the nucleus starts before cell division, 2. That there is a regular sequence in the changes of the nuclear material, see below, and 3. That the basic phenomena of nuclear and cell division are the same in the plant and animal kingdoms. It became increasingly evident that the role of the nucleus is not purely physiological, that is, serving as an initiator of cell division. Germ cells, vehicles of heredity. Development in a purely physical sense. Instead, it is a highly structured organ presumably patterned in a highly specific way. The question as to the nature of this pattern has continued to occupy the students of cells from this point on, and the final answers are not yet in. Progress in this research was characterized by ever finer analysis. The steps involved were the shift from the individual as a whole to the cell, from the cell as a whole to the nucleus, and now from the nucleus as a whole to its major structural elements, the chromosomes. Chromosomes and their role. Depending on the interests of the investigator, nuclear division was interpreted in 2 entirely different ways in the 25 years prior to the birth of genetics, 1900. 9. For those primarily interested in development, the big question was, how can the undifferentiated egg cell, by simple division, give rise to the differentiated cells of nerve tissue, glandular tissue, epidermis, and the hundreds of other kinds of tissues recognized by histologists and physiologists? This consideration, for instance, dominated Weissmann's theories. This group of investigators was primarily interested in proximate causes. Those relatively few authors who were interested in transmission genetics were laying the groundwork that eventually led to the question, what are the mechanisms that affect a division of the nuclear material in such a way that exactly equal halves are conveyed to the daughter cells of a dividing cell? The questions the 2 groups of investigators asked were thus quite different. The embryologists asked, how can we interpret cell division as a mechanism that explains the differentiation of the phenotype? The transmission geneticists were, as we would now call it, interested in the accurate perpetuation of the genotype, that is, in the problem of inheritance. The interpretation of the transmission geneticists left the problem of differentiation entirely unsolved, while the answers proposed by the developmental geneticists raised some formidable, and, as later became apparent, insoluble difficulties for the interpretation of genetic transmission. Evidently, not even the first step toward a resolution of the conflict could be made until there was a better understanding of what went on inside the nucleus during cell division, a process. 673. Which I shall not attempt to describe in full detail, even though the mechanics of cell division, mitosis, are among the most marvelous processes known in the living world. Mitosis. A. Tremblay, 1710 to 1784, in the 1740s was the first person to describe cell division of a sort, the fission of a protozoan. Baker, 1952. 10. Cell division was also found, in the second half of the 674 18th century, in diatoms and other algae, and was studied rather intensively by Ehrenberg in the 1830s in various protozoans. From the 1840s on, the process by which a somatic cell divides, named mitosis by Fleming in 1882, was described and illustrated more and more frequently. Wilson, 1896, Hughes, 1959. When a cell divides, its nucleus also divides, and this was eventually recognized as the most important aspect of cell division. At first it was believed that the nucleus was simply filled with granular material which, during cell division, was equally distributed to the 2 daughter nuclei, direct cell division. However, as the quality of the optical equipment and of the microscopic techniques, such as staining, improved, and hence the precision with which every phase of cell, and nuclear division could be studied, the simple picture had to be revised. The nucleus at certain stages of mitosis seemed to be filled with threads, ribbons, or bands which, since they were heavily stained, were said by Fleming, 1879, to consist of chromatin. Since the word chromosome was not proposed until 1888, Wald-Eyre, each author used different terminologies and descriptions. What presumably were chromosomes was seen by Rimac, 1841, Nageli, 1842, Derbs, 1847, Reichert, 1847, Hofmeister, 1848, 1849, and Krohn, 1852, all of whom saw mitotic figures and sometimes provided good illustrations of metaphase plates. One must remember that these papers were published in the period of free cell formation, in which many authors thought that the nucleus dissolves and two new nuclei form anew from the cell sap. The first person who observed the complexity of the reorganization of the nucleus was the French zoologist E. G. Balbiani, 1825–1899. As early as 1861, in beautiful preparations, he pictured in exquisite detail all the stages of mitosis in a protozoan. Unhappily, however, Balbiani completely misidentified what he saw. Not realizing that each protozoan is but a single cell, he identified the nucleus as a testis and the chromosomes as spermatozoa. Germ cells, vehicles of heredity. As a result, this pioneering work was without any subsequent influence. Direct nuclear division was accepted by the majority of authors until the mid-1870s. The technical advances in microscopy permitted the demonstration that the nucleus, and its chromatic contents, do not disappear between cell divisions but are maintained during the resting stage, even though in a different form. Furthermore, it permitted an accurate description of three major, and several minor, stages of mitosis, subsequently called prophase, metaphase, and anaphase, see Fig. 1. The resting nucleus, between cell divisions, does not stain well, but there were indications that much of the nuclear material is organized in one or several thin threads, or a network of threads. As cell division approaches, the membrane around the nucleus disappears, the chromatic threads tend to condense and become more easily stained by the appropriate dyes. Eventually this material contracts into a few heavily staining bands, designated chromosomes. Every species normally has in each cell a constant number of such chromosomes. In man there are 46, and these arrange themselves during nuclear division in an equatorial plate. It is at this stage, metaphase, that each chromosome seems to split into two. At first it was reported that they split transversely, and this error created considerable confusion. Ultimately it was clearly observed, Fleming, 1879, that they split longitudinally. The split evidently occurs before metaphase, that is, when the staining material, chromatin, is still in the uncondensed stage and almost impossible to observe. At the next stage the two halves of the split chromosome separate from each other and move to the opposite poles of the dividing nucleus. Around each bundle of chromosomes, at the two poles, a new nuclear membrane is formed, and the chromosomes revert back to their thread-like and largely invisible resting condition. It took a good many years and the labors of numerous investigators until these various stages of mitosis were recognized and correctly interpreted. The first reasonably accurate descriptions of mitosis were given in 1873 by three investigators, Schneider, Beitschle, and Fall. The importance of this process was recognized at once, and became the subject of furious activity, with the zoologist van Beneden and the botanist Strasburger making particularly important contributions. 8 years later a reviewer listed 194 papers, by 86 authors, on cell division and related topics, published from 1874 through 1878. No one, however, contributed as much to the correct description and interpretation of me. 675. AB. Figure 1. Stages of mitosis,
A. Early prophase, B. Late prophase. Each chromosome splits, apparently in early prophase, into two chromatids, C. Polar view of metaphase, D. Early, E. Late anaphase. J. Telophase. The small circles in A, B, and J represent the nucleoli. 676. Germ cells, vehicles of heredity. Toses as Fleming, who in 1882 provided a superb summary of the state of the held. Observations of mitosis in plants revealed that it proceeds exactly as in animal cells. This was one more piece of evidence for the unity of cellular processes in animals and plants. It was more than half a century later before the pronounced difference between the cell division of eukaryotes and prokaryotes was discovered. Every new observation confirmed the existence of this exceedingly complex process of cell division. Why is such complexity necessary? Why do not cell and nucleus simply divide in half, as Remak had thought? This is the question which W. Roux asked himself in 1883. In an age in which only proximate causes were studied, culminating in Nageli's mechanico-physiological speculations, Roux wanted to know about the ultimate causation. He ventured to ask a why question. Why, he asked, do we have such a complex process if a simple division would do the job? He answers it by saying that a simple direct division of the nucleus would be quite sufficient if the nuclear material was homogeneous. However, if the nuclear material is heterogeneous, if it consists of innumerable particles each of which has a different genetic capacity, then there is only one possible method by which this material can be divided in such a way that each particle is represented in both daughter cells. This method is to arrange all particles serially, like beads on a string, and then to split the string longitudinally, so that each chromatin globule is divided into two halves, so that from each string of globules two adjacently placed strings result. In the preceding years it had been repeatedly suggested, Balbiani, 1881, Strasburger, 1882, that in the resting nucleus all the chromatin is arranged as a single long thread. This is the observation on which Roux's hypothesis rested. The mitotic figures are mechanisms which allow the nucleus to be divided not only quantitatively but also according to the mass and nature of its individual qualities. The essential process in nuclear division is the halving of each of the maternal corpuscles. All other processes serve the object to transfer one of the daughter corpuscles to the center of one of the daughter cells, and the other to the center of the other daughter cell. This process guarantees that both daughter cells are identical, not only quantitatively but also qualitatively. They are identical in every respect. This is Roux's thesis throughout his entire article of 19 pages, but then he gets cold feet. In a single sentence he capitulates to the possibility of unequal division, since the second cleave age division of the frog egg determines the front end and rear end of the embryo, and, since one must assume that the different development of the anterior and posterior part is connected with an inequality of the material, it becomes probable that the nuclear material is divided into qualitative parts during the second division, 1883, 15. This contradicts his principal thesis since there is no difference whatsoever between the mitosis of the first and the second division. A mechanism for equal division, Roux's major thesis, is of 678 course precisely the modern interpretation of mitosis, an interpretation that was curiously ignored by all those, like Weissmann, who in the ensuing years attempted to explain differentiation by an unequal distribution of nuclear material into daughter cells. Yet, as Wilson said, 1896, 306, not a single visible phenomenon of cell division gives even a remote suggestion of qualitative division. All the facts, on the contrary, indicate that the division of the chromatin is carried out with the most exact equality. Roux's theory was frankly a speculation, but it was a speculation quite different from the speculations of Nageli or Jacques Loeb. Roux asked a why question in the tradition of Harvey, whose curiosity over the meaning of valves in the veins was a major contribution to his discovery of the circulation of blood. Indeed, Roux asked implicitly,
What is the selective value of this complicated process? Nageli and Loeb did not ask why questions, rather, they attempted to interpret biological phenomena in a reductionist manner, in terms of physics and chemistry, and that kind of speculation was at that time far more respectable than the teleological or Aristotelian, as it was referred to, approach of Roux. Nevertheless, Roux's hypothesis, like Hertwig's theory of fertilization, was further evidence of the gradual emancipation of biology from purely physicalist interpretations. The story of the nucleus was completed by 1880 because every cytological investigation had confirmed Fleming's aphorism. The center of attention, from this point on, shifted to the chromosomes. What do the chromosomes do during cell division? From the nucleus to the chromosomes. In 1883 the Belgian cytologist van Beneden published a brilliant analysis of fertilization in the horse threadworm Ascaris bivalens, an unusually suitable organism because it has only 4 chromosomes. He was able to show that the gametes have only germ cells, vehicles of heredity, 2 chromosomes, and that the fertilizing male nucleus did not fuse with the female nucleus in such a way as to produce a blending of their nuclear substance, but that the 2 chromosomes of the male nucleus merely join the 2 chromosomes of the egg nucleus, forming the new nucleus of the zygote with 4 chromosomes, which he calls chromatic globules. At the first cleavage division of the fertilized egg, zygote, each of the 4 chromosomes divides longitudinally as in every other mitotic division, and each daughter cell receives the same 2 paternal and 2 maternal chromosomes as had participated in fertilization, see chapter 17. Although van Beneden observed that exactly 1/2 of the nuclear material of the new individual is derived from the father, the other half from the mother, he did not establish any connection between his observation and inheritance. Not being a theorist, he did not draw the obvious conclusions from his brilliant cytological demonstration. This was done almost simultaneously and independently of each other by 4 German biologists, although Gabon, 1876, had preceded all of them. 1 Weissmann, 1883, in a penetrating analysis of the problem of inheritance, concluded that the nuclear material was the hereditary substance, which he designated by the name germ plasm. 1 year earlier than Nageli's idioplasm, heredity is brought about by the transference from one generation to another, of a substance germ plasm with a definite chemical, and above all, molecular constitution. 1-2 In 1884 the leading animal cytologist, Oskar Hertwig, and the leading plant cytologist, E. Strasburger, reviewing the extensive literature of the past 10 years, were able to demonstrate conclusively that no other interpretation was possible but that the nucleus is the carrier of inheritance. All of them gave Haeckel credit for having been the first to have postulated this role of the nucleus. Hertwig and Kolliker, 1885, went one step further by asserting that the truly effective material in the nucleus was nothing but the peculiar chemical isolated by Mayr from cell nuclei, and named by him nuclein. This, Kolliker declared emphatically, must be the material basis of inheritance. Eventually it was even possible to demonstrate experimentally that the nucleus is the seat of the genetic material. Bovary, 1889, in a series of ingenious investigations, fractured eggs of a sea urchin by vigorous shaking, and found that large non-nucleated egg fragments could be fertilized with sperm of a different, morphologically quite distinct species, and genus, of sea urchin. Even 679. 680. Though this haploid hybrid egg fragment had only the paternal chromosome set in the maternal cytoplasm, it developed normally, but the resulting larva had chiefly paternal characteristics. Control larvae produced through simultaneous fertilization by the spermatozoa of 2 different species had intermediate morphological characters. Here was clear-cut experimental proof that the nucleus determines the characteristics of an organism. 1-3 The study of the behavior of chromosomes during fertilization clarified the problem of the fusion of the gametes. Yes, there is a fusion of the gametes, indeed even a fusion of the nuclei of the gametes, but there is no fusion of the paternal and maternal chromosomes. This new insight opened up an entirely new field of research, the question of the joint or independent action of the paternal and maternal genetic material and the question of the feasibility of blending inheritance, see Chapter 17. It is necessary to look back to Schleiden's theory, 1838, that each nucleus originates de novo in each new cell by a process of crystallization in order to appreciate the enormous advance made in these 45 years. Not only was the continuity of the nuclei now firmly established, but also established was the fact that the crucial aspect of the production of a new individual is the combining of the genetic elements in the nuclei of the male and female gametes. From 1884 on, the thesis that the nuclei play the predominant role in inheritance was no longer challenged, even though some scientists postulated for another 50 years or so that important components of the genetic material might also reside in the cytoplasm. What remained unclear was the connection between nucleus and cytoplasm. Was the nucleus the dominant element and the cytoplasm a two-way street enabling the cytoplasm to return material to the nucleus and thereby affect its heritable qualities? The next 15 years were years of speculation by Nageli, De Vries, Weissmann, and others. The cytological understanding was consolidated but no major new insights were added. Indeed, the knowledge of chromosomes and cell nucleus had reached a remarkable degree of maturity by the 1890s. Wilson's Magistral book, The Cell in Development and Inheritance, 1896, 1900, is convincing evidence for this. The time had come when the venerable problem of the inheritance of acquired characters had to be reviewed in the light of the new cytological knowledge. 16. The nature of inheritance. Intuitively all students of nature felt the existence of some conflict or contradiction between the facts of inheritance, she is exactly like her mother, and those of variation. Inheritance implies continuity and constancy, variation implies change and divergence. When a breeder crossed animals or plants, he often encountered unexpected variance among the offspring. Even when one compared siblings with each other, one often found amazing variation. Eventually it became an important question, where does the new variation come from? But it was not until Darwin had established his theory of natural selection that the source of variation became a key problem in biology. Natural selection can be effective only if there is an abundant supply of variation, a supply that must be forever renewable. How can this be reconciled with a belief in the constancy of inheritance? The answer traditionally had been that inheritance is not necessarily constant, that not all of it is hard. To be sure, in some characteristics an individual might closely resemble his father or mother or even a grandparent or earlier ancestor. All animal breeding is based on the fact that such hard inheritance exists. But, if inheritance were completely hard, there could be no variation. Hence, it was reasoned that there may be two, not mutually exclusive, sources of variation. Either some inheritance is soft, that is, susceptible to various influences, or else the genetic material is hard but has the capacity to generate new variation occasionally. Throughout the 19th and first third of the 20th century, the question of soft inheritance and of the source of genetic variation remained controversial. Darwin and variation. One of the two cornerstones of Darwin's theory of natural selection was the postulate of the availability of an unlimited supply of 681. Variation. Each individual is unique and different from every other one. These individual differences are highly important for us, as they afford materials for natural selection to accumulate. Origin, 45. But where does this variation come from? What is its source? This question puzzled Darwin all his life. What a large role variation played in Darwin's thinking is documented by the fact that he devoted a 900-page work to the variation of animals and plants under domestication, 1868. He had planned to write a corresponding work on variation in nature but never did so, being 682 overwhelmed by the abundance of material. His enormous information on variation was condensed into the first two chapters, 59 pages, of the Origin. Recent writers on Darwin, such as Gazellin, 1969,
Vortimer, 1970, authors of several journal articles, have fully appreciated the importance of variation. Inheritance, as such, and its laws were of much less immediate interest to Darwin than variation and its causation. Even at the present time, variation and its causation are not fully understood. In the middle of the 19th century, the subject was enveloped in great confusion. How difficult this subject is becomes apparent when one realizes how bewildered even Darwin was, who had been preoccupied with variation all his life and who had thought deeply about it. In retrospect, it is obvious that much of it could not be clarified until after the rise of genetics, for example, the distinction between genotype and phenotype. However, some of the confusion was also due to the failure to apply population thinking consistently. The most fascinating aspect of Darwin's confusions and misconceptions concerning variation is that they did not prevent him from promoting a perfectly valid, indeed a brilliant, theory of evolution. Only two aspects of variation were important to Darwin: 1, that it was at all times abundantly available, and 2, that it was reasonably hard. Instead of wasting his time and energy on problems that were insoluble at his time, Darwin treated variation in much of his work as a black box. It was forever present and could be used in the theory of natural selection. But the investigation of the contents of the box, that is, the causes of the variation, occupied Darwin only occasionally and with little success, as in his pangenesis theory, see below. Fortunately for the solution of the major problems with which Darwin was concerned, for example, the success of individuals in the struggle for existence, a study of the contents of the box was unnecessary. It could be postponed until more auspicious times. One of the secrets of success. The nature of inheritance in science is to select soluble problems, Mayr, 1967. There were two aspects of variation that caused Darwin particular difficulties. 1. The distinction between intrapopulational and interpopulational variation. Darwin, unfortunately, never made a clear distinction between individual and geographical varieties, and this, particularly after the 1840s, bedeviled his discussions of speciation. Mayr, 1959a, Kotler, 1978, Soloway, 1979, see also Part 2. It also affected his discussion of variability under domestication, individuals, of our older cultivated plants and animals, generally differ much more from each other than do the individuals of any one species or variety in a state of nature, I Origin, 7. Actually, individual, that is, intrapopulational, variation in strains, breeds, and races of domestic animals and plants is often extraordinarily low, and to have uniform breeds is one of the ideals of the breeder. What Darwin had primarily in mind was the range of variation within domesticated species as a whole, that is, interpopulational variation. However, where stabilizing selection is not exercised by the breeder, individual variation may increase. 2. The belief that there are two entirely different kinds of intrapopulational variation. 1. Breeders and naturalists, in fact, anybody having to do with variation, believed until well into the first quarter of the 20th century that there are two kinds of variation, discontinuous and continuous, also called individual variation. Discontinuous variation is represented by all striking deviations from the type, that is, by any variant not connected with the normal type by a graded series of intermediates. Albinos would be one example of discontinuous variation. For an essentialist, anything new can originate only by a drastic deviation from the type. A mutation or saltation and discontinuous variation therefore played an important role in the evolutionary theories of essentialists, see Part 2. Even though Darwin acknowledged the existence of discontinuous variation as a separate category, he considered it evolutionarily unimportant. In contrast to all earlier writers, he emphasized the universal prevalence and biological significance of individual or continuous variation. From where did Darwin derive this crucially important insight? He owed it primarily to the study of the works of the animal breeders who, from Bakewell and Sprite on,
had stressed the uniqueness of individuals, a fact which made selection and an improvement of breeds possible. This lesson was reinforced by Darwin's taxonomic studies, where he 683. 684. Found, like other taxonomists before him, that no two individuals were entirely identical when examined carefully. It is this individual variation, as Darwin never failed to emphasize, which provides the raw material for selection and thus for evolutionary change. The nature of this continuous variation, about which Darwin himself was very uncertain, remained controversial until the genetic researches of Nilsson L. East, Bauer, Castle, Fisher, and other geneticists settled the issue after 1910, see Chapter 17. Those who disagreed with Darwin raised two objections in particular. First, they claimed, up to Johansen and later, that such continuous variation merely reflects the plasticity of the phenotype but is not heritable. Their second claim, going back to Lyell and earlier, was that such variation is severely limited, never being able to transgress the limits of the type. Both of these claims were subsequently refuted, and the paramount importance of individual variation is today unchallenged. Furthermore, as we shall presently see, genetics eventually showed that there is no real difference between the genetic basis of continuous and discontinuous variation. Merely to assert that there is abundant variation was not sufficient for Darwin. For him, a true child of his times, variability had to be ascribed to an identifiable cause. He did not believe in spontaneous variation. I do not believe that variability is an inherent and necessary contingency, under all circumstances, with all organic beings, as some authors have thought. Origin, 43. The most important causes of variation for Darwin were various influences on the reproductive system of the parents, particularly those caused by shocks or severe changes of the environment. These influences, he believed, do not produce specific variants or directional variations, rather, they simply increase the variability of the offspring, providing increased scope for the exercise of natural selection. Occasionally, Darwin admits he had somewhat carelessly spoken of variation as having been due to chance. This, of course, is a wholly incorrect expression, but it serves to acknowledge plainly our ignorance of the cause of each particular variation. Origin, 131. Darwin's friend Hooker saw much more clearly that there was no need for a causal connection between special conditions and a particular type of variation occurring under these conditions. I incline to attribute the smallest individual variation to the inherent tendency to vary, a principle wholly independent of the nature of inheritance. Physical Conditions, Hooker to Darwin, March 17, 1862, 1918, I. 37. For Darwin, an inherent tendency to vary probably smacked of the same spirit as Lamarck's inherent tendency toward perfection. To accept genetic variability simply as another manifestation of the imperfection of the organic world was not sufficiently causal for Darwin. Both Darwin and Hooker were rather vague on the actual subject of their disagreement. Were they referring to variation as a process or to variation as the product of this process? Also, what was meant by chance? In an age when only those processes were scientifically respectable that obeyed a law, it was not admissible to acknowledge stochastic perturbations. In spite of all his disclaimers, Darwin's opponents pounced upon his statements that variation was due to chance. In various forms, are mutations random? This argument has continued virtually into our day. What the opponents of Darwinism failed to grasp is that Darwin and his followers never questioned the strict physico-chemical causation of all variations, they simply denied that it had a teleological component. Genetic variation is not a specific response to an adaptive need. To sort out the gradual change in Darwin's thinking about the causes of variation is particularly difficult because it is correlated with a simultaneous change in his thinking about the causation of adaptation, natural selection, and about the nature of inheritance, whether soft or hard. Anyone who does not believe in natural selection is forced to rely on soft inheritance and, furthermore, is forced to postulate the existence of adaptive responses to environmental needs. Once Darwin had adopted natural selection as the mechanism of evolutionary change, all he needed was a process, or processes, that generates variability. However, if inheritance is normally hard, and, as we shall see, Darwin had reached this conclusion, that is, if the characters of the parent are normally transmitted unchanged to the offspring, then it will require some special stimulus to make them vary. And since the offspring is a product of the reproductive system, that stimulus somehow must affect the reproductive system. This chain of arguments was completely logical. And it seemed to Darwin that he had the evidence to support his argument. Seeing that there are in nature both highly variable as well as very uniform species, he concluded that there must be factors that could affect the variability of species. At this point he remembered domesticated species, like the races of dogs or the 685, 686 varieties of cabbage, each presumed to be derived from a single ancestral species. And he observed that the most favorable conditions for variation seem to be when organic beings are bred for many generations under domestication, 1844, 91. And what particular aspect of domestication is it that is responsible for this increase in variability? What is it that causes the normally so stable genetic constitution to vary? It is simply due to our domestic productions having been raised under conditions of life not so uniform as, and somewhat different from those of the parent species. Origin, 7. Darwin does not postulate, as might be read into the statement, a direct induction of new characters as a result of life in a different environment, but merely that some factor, perhaps an excess of food, increases genetic variability as such. And Darwin believes, furthermore, that this increased variability is due to the fact that male and female reproductive systems appear to be far more susceptible than any other part of the organization to the action of any change in the conditions of life. Origin, 8. See also similar statements elsewhere in Darwin's writings. The crucial difference between this interpretation and that of the adherents of soft inheritance is that Darwin's variation was not given any special direction by the environment or by any needs of the organism. Whatever directional trend is observed in evolution has a different cause, it is the steady accumulation through natural selection that gives rise to all the more important modifications of structure. Origin, 170. Implicit in many statements scattered through Darwin's writings is the conviction that the genetic material is usually not affected by the environment. In this belief Darwin was virtually alone prior to the 1870s. As is evident from his notebooks, Darwin had struggled with the problem of inheritance from the time he first started thinking about evolution, but he said relatively little about this subject in the Origin. What he did believe was that most individual variation is heritable. Perhaps the correct way of viewing the whole subject would be to look at the inheritance of every character whatever as the rule, and non-inheritance as the anomaly. Origin, 13. Obviously, natural selection cannot favor any non-heritable character, hence any variation which is not inherited is unimportant for us. Origin, 12. It was not until the variation of animals and plants under domestication, 1868, that Darwin published his ideas on inheritance, in the form of his hypothesis of pangenesis. This I will take up presently, but in order to facilitate the analysis the nature of inheritance. Want to mention that there are two components of Darwin's theory of inheritance on which the historians of science have not yet come to a complete agreement. The first is whether Darwin believed in blending or in particulate inheritance. Since the nature of this argument cannot be fully illuminated, except in terms of Mendelian inheritance, we will postpone its discussion until after the treatment of the rediscovery of Mendel, see chapter 17. The second disagreement concerns the question to what extent Darwin believed in any form of soft inheritance and, in particular, in an inheritance of acquired characters. Soft or hard inheritance. The belief that either the environment or use versus disuse, or both, would affect the heritable qualities of characters was universally held almost to the end of the 19th century. Zirkel, 1946, and by numerous biologists well into the 20th century, Mayr and Provini, 1980. This belief is usually referred to by the words inheritance of acquired characters, but this terminology is imprecise because the belief usually also included the postulate of a modifiability of the genetic material by general climatic and other environmental conditions, geophroism, or by nutrition directly, without peripheral, phenotypic, characters necessarily serving as intermediaries. A belief in an effect on the offspring of various experiences or encounters of the pregnant mother is recorded in the Bible, Moses 1:30, and was accepted in the teratological literature as a major cause of the birth of monsters. In these cases, a non-genetic modification of the phenotype is often the correct explanation. The basic concept underlying this belief is that the genetic material itself is pliable, or soft. For this theory, it does not matter whether the genetic material changes slowly or fast, nor whether it changes directly or via acquired characters. What matters is that the genetic material is believed not to be constant, not unchangeable, not hard. Curiously, soft inheritance was so universally accepted, it was considered so axiomatic, that it was not until after 1850 that even the first attempts were made to justify it and to work out its mechanisms. Darwin, Spencer, and Haeckel were among the first who tried to do so, Churchill, 1976. Except for a few ignored pioneers, the first suggestions of the 687, 688 possibility of exclusively hard inheritance were made even later, see below. Among the Neo-Lamarckians at the end of the 19th century, it was assumed that Lamarck was the father of the concept of inheritance of acquired characters. Actually, it was the standard concept in the 18th century, held by all outstanding biologists of the period, including Buffon and Linnaeus. Blumenbach, for instance, believed that the dark-skinned human races were derived from the light-skinned races by the action of the strong sunlight of the tropics on the liver. This resulted in a blackening of the bile, which in turn caused a pigment deposit in the skin. Those with more experience with human races than Blumenbach had little trouble in refuting him by pointing out, as did Herder, that white people living in the tropics as well as their children did not become black-skinned, while the descendants of the African slaves remained dark-skinned after many generations of life in the temperate zone. Whenever a noticeable change of skin color was observed, it was due to the interbreeding of races. No one, however, demolished the claim of an influence of climate on the racial characteristics of man more thoroughly than Pritchard, 1813. He concluded that the color acquired by the parent on exposure to heat, is not imparted to his offspring, and has consequently no share in producing natural varieties. The same impotence of the climate could be demonstrated for animals. Species which were bred in menageries or zoological parks for many generations did not change their appearance in the slightest. In spite of such early indications of the invalidity of this concept, soft inheritance was tenaciously held onto by most authors. The only concession its adherents made to the opposing evidence was to assume that there is both hard and soft inheritance. The acceptance of an unchanging essence, the basic credo of the essentialists, would seem to necessitate a belief in hard inheritance. It puzzles me therefore how universally the essentialists at that period were able to reconcile soft inheritance with the concept of an unchanging essence. They escaped the dilemma by defining all characters subject to soft inheritance as accidental, their variation not affecting the essence. Louis Agassiz compromised by claiming that it was part of the intrinsic potential of the essence to be able to change, to respond to the environment, and even to be prophetic. More consistent essentialists looked for instances, like migrating human races, where a change of climate was without permanent effect. C. F. Wolf, for instance, noticed with Sat. The nature of inheritance. Is faction that even though certain plants had changed dramatically when transplanted from Western Russia, St. Petersburg, to Siberia, their descendants nevertheless returned to their original form when taken back to St. Petersburg. This proved to him that the influence of the external factors was unable to penetrate to the essential organization of the organism. Rakow, 1947, 1952. Here was a possible basis for a theory of hard inheritance, but it was not followed up. The question of the existence of soft inheritance became of crucial importance as soon as the evolutionary theory was proclaimed. Was evolution due to an inheritance of acquired characters, as believed by Lamarck? The transplantation of plants into other environments, particularly from the lowlands to the mountains and back, became a favorite method after 1859 to test the influence of the environment, by such experimenters as Mayr and Kerner. Yet, the method was not very satisfactory, because individuals of most lowland species were unable to tolerate the alpine climate, and when species were employed that had alpine ecotypes, it required extreme precautions to prevent a mixing up of the transplants and the local ecotypes. Hence, Kerner's conclusion, in no instance was any permanent or hereditary modification in form or color observed, had little influence. The matter was finally settled by the work of Clausen, Hayesi, and Keck from the 1930s on, but by that time a refutation of an inheritance of acquired characters was no longer necessary. Darwin and soft inheritance. Throughout his life Darwin believed in both soft and hard inheritance, changing his opinion only on the relative importance of the two. In his early notebooks soft inheritance clearly dominated. He even recorded the possibility, though he was not fully convinced, of a paternal influence on later pregnancies in interracial crosses, b. 32, 181, c. 152, as well as the possibility that wishing of the parents might affect the offspring, b. 219. Most of his statements are sufficiently vague so that they can be equally interpreted as accounts of non-genetic changes or as effects on later generations, b. 3, 4, c. 68, 69, 70, 195, 220. Darwin, even at that time, definitely denied that drastic bodily changes such as mutilations could have genetic consequences, c. 65 to 66, 83, d. 18, 112. In The Origin, more than 20 years later, Darwin no longer 689 mentions any dubious folklore of the breeders and, having adopted natural selection as the causative agent in evolutionary change, relies in the main on hard inheritance. A careful reading of the work reveals, however, that Darwin still cites occasionally evidence seemingly in favor of soft inheritance. He accepted three potential sources of such variation. The first one, an effect of changes in the environment that induce increased variability by way of the reproductive system, can be reconciled with hard inheritance. The other two demand a belief in soft inheritance, the direct effect of 690 the environment, and the effect of use and disuse. Direct effect of the environment. The environment was one of the factors considered by Darwin as a possible cause of variation. Repeatedly in The Origin he states that climate, food, etc. probably produce some slight and direct effect, p. 85, similar statements are made on pages 15, 29, 43, and 132. Darwin frequently commented on the great number as well as great variability of races of domestic animals and cultivated plants. He ascribed this increased variability to changed and particularly favorable conditions of life. Actually, in cultivated plants hybridization is the main source of increased variability, as Darwin was aware, to some extent, while in some breeds of domestic animals, on the contrary, it was the destruction of well-balanced epistatic systems by intensive inbreeding that was responsible. Lerner, 1954. Equally often, Darwin stresses that such direct effects are of quite subordinate importance to the effects of natural selection, p. 209. This unimportance of the conditions of life in producing new variation is also recorded on pages 10 and 134. Darwin actually expressed himself much more clearly in a letter to Hooker, LLD, 274. My conclusion is that external conditions do extremely little, except in causing mere variability. This mere variability, causing the child not closely to resemble its parents, I look at as very different from the formation of a marked variety or new species. The formation of a strong variety or species I look at as almost wholly due to the selection of what may be incorrectly called chance variations or variability. As Darwin made no clear distinction between genotype and phenotype, it is impossible, in virtually all the cases listed by him, to say whether he considered the variation induced by the environment to have been genetic or not. There was perhaps no other period during which Darwin rated the direct influence of the environment as low as that. The nature of inheritance. In the writing of The Origin. But 1862, after having completed the first volume of Variation, he wrote to Hooker, "My present work is leading me to believe rather more in the direct action of physical condition," and by 1878 he admitted, "I probably underrated the power of external conditions in the earlier editions of The Origin," in Vortimer, 1970, 264. To Gabon he wrote in 1875, "Every year I come to attribute more and more to such agency modification by use and disuse during the life of the individual. The effect of use and disuse. Among all the phenomena that Darwin considered as evidence in favor of soft inheritance, none was as important to him as the effect of use and disuse. It was the study of domestic animals which led him to adopt this belief. There can be little doubt that use in our domestic animals strengthens and enlarges certain parts and disuse diminishes them, and that such modifications are inherited. Origin, 134. Darwin was so strongly convinced of the importance of this factor that he devoted to its discussion a whole section, pages 134 to 139, of Chapter V of The Origin. As examples he discusses the reduction of wings in flightless birds, the loss of anterior tarsi in dung beetles, winglessness in beetles of Madeira, in part, the reduction of eyes in moles and other burrowing mammals, and the loss of eyes and pigment in cave animals. Regarding rudimentary organs in general, Darwin states, "I believe that disuse has been the main agency, p. 454, in their production." The importance he attributes to this factor is indicated by the frequency with which he invokes it in The Origin as an agent of evolution, for instance on pages 11, 43, 134, 135, 136, 137, 168, 447, 454, 472, 473, 479, and 480. Use and disuse, of course, is of importance only if one believes in an inheritance of acquired characters. This Darwin affirms repeatedly. He describes how the constant milking of cows leads to an inherited increase in the size of the udder. Darwin is quite positive, modifications caused by use and disuse are inherited, p. 134. The modern evolutionist has no difficulty in explaining all alleged effects of disuse as due to a relaxation of stabilizing selection, often reinforced by counter-selection forces. Although Darwin realized that selection made a contribution to the production of rudimentary organs, p. 143, he was not prepared to go to the extreme of relying entirely on selection to explain rudimentation. His thinking was still so much conditioned by pre-Darwinian concepts that he sometimes interpreted observations in terms of use and disuse, which to us seem obviously due to natural selection. By careful measurements, Darwin found, for instance, in the domestic duck that the bones of the wing weigh less and the bones of the leg more, in proportion to the whole skeleton, than do the same bones in the wild duck, p. 11. Darwin, curiously, does not ascribe this to selection during domestication but assumes the modification to be, in part, non-genetic, corresponding to differences in plants growing in different soils, and in part due 692 to the domestic duck flying much less, and walking more than its wild parent, p. 11. His experience with plants and plant breeders had persuaded Darwin to accept a far greater phenotypic plasticity in animals than is actually found. There is one other line of evidence revealing Darwin's belief in soft inheritance. He thought that the genetic basis of a character would be strengthened if the organism was exposed to the same circumstances for a long time or if the structure were as used steadily,
variety when long in blood gets stronger and stronger, c. 136. When considering whether some actions become hereditary and instinctive and not others, he concludes, therefore it can only be those actions which many successive generations are impelled to do in the same way, c. 171, and, the longer a thing is in the blood the more persistent any amount of change and shorter time less so, d. 17, also d. 13. It took another 100 years before it was recognized that this is the result of stabilizing selection. The conclusion he drew from this was that the older a domestic breed or a geographical variety, the stronger was its influence in crosses. He refers to this as Yarrell's law, after William Yarrell, one of his animal breeder friends, from whom Darwin apparently had this generalization, c. 121, d. 7-8, 91. He admits however that this law does not always work, e. 35. On the other hand, a character would be weakened if exposed to adverse conditions. He believed that if we were to cultivate, during many generations, the several races of the cabbage in very poor soil, that they would to a large extent or even wholly, revert to the wild aboriginal stock. Origin, 15. Ideas like this were widely held at that period among animal and plant breeders. Several recent historians have accepted Darlington's claim, 1959, that Darwin had recognized nothing but hard inheritance in the first edition, 1859, of the Origin but fell back on the nature of inheritance. Assumption that acquired characters were inherited after reading in 1867 Jenkins' Critical Review. This claim is erroneous in every detail, as was shown by Vortimer, 1963, 1970, and others, and by the preceding analysis of Darwin's views on soft inheritance. Admittedly, Darwin in his later years conceded a little more influence to soft inheritance than he had in 1859, but it never became a major component of his interpretation. Whenever he compared the contribution to evolutionary change made by the inheritance of acquired characters to that made by natural selection, he always made it quite clear that he continued to consider selection as the decisively important factor. Darwin's Theory of Pangenesis. Chapter XXVII of Darwin's Variation of Animals and Plants under Domestication, 1868, is devoted to his provisional hypothesis of pangenesis, as it is called in the chapter heading. 3. Darwin justifies his hypothesis because it may be serviceable by bringing together a multitude of facts which are at present left disconnected by any efficient cause, 1868, 357. And in a chapter subheading Darwin lists the facts to be connected under a single point of view, namely, the various kinds of reproduction, the direct action of the male element on the female development, the functional independence of the elements or units of the body, variability, inheritance, reversion. No simple theory could provide all the answers to this ambitious program, and Darwin's theory of inheritance, to which he himself somewhat misleadingly affixed the term the hypothesis of pangenesis, is indeed a whole package of theories. The first of these is that the transmission of heritable qualities, as well as the guidance of development, is caused by individually different, very small, and hence invisible, particles, the so-called gemmules, see above. Each kind of cell in the body is represented by its own kind of gemmule. The mosaic of characteristics in hybrids is due to the mixing of parental gemmules, and the facts of reversion to ancestral characteristics, a phenomenon which greatly fascinated Darwin, is due to the activation of previously dormant gemmules. As de Vries, 1889, was the first to point out succinctly, this genetic theory of Darwin's, proposing that the various characters of an organism have separate, independent corpuscular bases, was the first well-rounded and internally consistent theory of inheritance. It permitted the explanation of a large number of 693 variations, and it is a historical fact that all subsequent theories of inheritance, particularly those of Galton, 1876, Weismann, 1883-1892, and de Vries, 1889, were greatly influenced by Darwin's theory. It permitted an explanation, not very different from the subsequent Mendelian one, of prepotency, dominance, and reversion, recessiveness, regeneration, and other genetic and developmental phenomena. As stated so far, this theory was unable to account for an inheritance of acquired characters. How could the effect of U694 and disuse on peripheral organs, hands, skin, eyes, brain, be communicated to the reproductive organs? To account for this, Darwin proposed a transportation hypothesis, as De Vries later called it. In any stage of the life cycle, cells may throw off gemmules, which circulate freely throughout the system, and when supplied with proper nutriment multiply by self-division, subsequently becoming developed into cells like those from which they were derived. Darwin, 1868, 374. This circulation of the gemmules is the second part of Darwin's theory. It permits the gemmules to accumulate in the sexual organs or, in the case of plants, in buds. Finally, in variations caused by the direct action of changed conditions. The tissues of the body, according to the doctrine of pangenesis, are directly affected by the new conditions, and consequently throw off modified gemmules, which are transmitted with their newly acquired peculiarities to the offspring, pages 394-395. This is the pangenesis theory in the more restricted sense, and it is the theory Darwin's critics usually had in mind when referring to Darwin's pangenesis theory. The idea of a transport of germinal material from the body to the reproductive organs was by no means original with Darwin, and Zirkel, 1946, was able to list 94 runners, from Hippocrates on, see also Olsky, 1950, 1294-1343. Darwin himself, 1868, 375, refers to the somewhat similar theories of Buffon, Bonnet, Owen, and Spencer, while pointing out where his theory differs from theirs. Darwin was quite reticent about his transportation theory, referring to it as a mad dream and stillborn, yet thought that it contains a great truth. It was, of course, soon refuted, see below. The ironical part is that the theory became quite unnecessary when 15 years later Weismann rejected soft inheritance, basing his rejection on quite a formidable array of facts and theory. If there is no inheritance of acquired characters, then there is no need to postulate a migration of genetic material from the soma to the germ cells. The nature of inheritance. The decline of soft inheritance. Darwin was one of the first authors to stress the prevalence of hard inheritance, but even he, as we saw, was unable to abandon soft inheritance altogether. Who then was the first author to do so unequivocally? Every preformationist ought to reject soft inheritance implicitly, but I am not aware that any author ever articulated this principle. It is sometimes said that Pritchard in the first edition, 1813, of his researches in the physical history of man was the first to reject soft inheritance. Pritchard, indeed, denied that climate is responsible for racial differences in man, but he still allowed for soft inheritance with respect to culture and other factors, and he accepted soft inheritance to a greater extent in later editions of his work. Lawrence, 1819, even though he said, the offspring inherit only the parents' connate peculiarities and not any of the acquired qualities, nevertheless allowed for the origin of birth defects owing to influences on the mother, and gives other indications of an occasional belief in soft inheritance. Wells, 1971. So did every other author up to the 1870s. Perhaps the first person to deny the occurrence of soft inheritance categorically was his. Until it has been refuted, I stand by the statement that characters cannot be inherited that were acquired during the lifetime of an individual. 1874, 158. Weismann, 1883, Kolliker, 1885, Ziegler, 1886, and others followed him in due time. Churchill, 1976.
The controversies between the pioneers of hard inheritance and their opponents, for example, Virchow, show how axiomatic the belief in an inheritance of acquired characters still was in the 1880s and to what extent it was supported by contemporary ideas on the nature of life. Darwin's cousin Francis Galton, 1822–1911, rejected soft inheritance largely but perhaps not altogether. In the 1870s he developed some extraordinarily prophetic ideas on inheritance, which were apparently completely ignored by the contemporary biologists, in part because Galton published in non-biological journals and in part because some of his most original thoughts were not published at all. This is, for instance, true for an explanation of the characters of hybrids, which Galton communicated to Darwin by letter on December 19, 1875. Here he proposes a typical Mendelian theory of particulate inheritance with the hereditary units not fusing but able to segregate, Albee, 1966, 72. Yet, he was not particularly interested in conspicuous, discontinuous characters, like red versus white in flowers. He was far more concerned with 695. 696. Generalized characters, such as size or, in man, intelligence. In 1876 Galton published a detailed, well-rounded theory of inheritance in which he anticipated many of the ideas, including the reduction division, subsequently developed by Weismann and others. Galton accepted Darwin's theory of a multitude of organic units, each of which possesses its own proper attributes. Since he rejected Darwin's thesis of pangenesis, or at least the part called by de Vries the transportation theory, he concentrated on the fact that the entire potential of an organism is encased in the fertilized ovum. For this sum total of the genetic particles, he coins the term stirp, apparently the same as Weismann's germplasm, 1883, and Nageli's idioplasm, 1884. Like Darwin, Galton was much impressed by reversions to ancestral conditions and by the sudden appearance in individuals of characters not observed in the parents. He therefore concluded, as had Naudin, 1865, before him, that comparatively few of the host germs in the stirp achieve development, the others remaining dormant, sometimes for generations, 1876. He discussed the meaning of sex, and concluded that it functions to maintain genetic variability, that is, to prevent the loss of genes, as we would say it now. He stated that such a loss is very unlikely to occur when the fertilized egg is composed of the contribution of two parents. He appreciated the necessity of a reduction division of the nucleus. He developed, long before Weismann, a theory of germinal selection, 1876, 334, 338. Like all his contemporaries except Mendel, he believed that each genetic determinant is represented in the stirp by numerous identical replicas. He discussed random fixation, and had many other interesting ideas. Unfortunately, in the Spencerian tradition, he thought of inheritance very much in terms of movements and forces, and consequently his explanation of ontogeny as a result of inheritance is very unsatisfactory. After 1885 Galton developed an entirely different theory of inheritance, see chapter 18. The part of the stirp that is not used up during individual development is transmitted from generation to generation. Just how evolutionary change occurs is not made clear, and even though throughout the years Galton rejected soft inheritance, it is implied in the cryptic statement, it may well happen that some species of germs may have failed in achieving development during very many generations, by the end of which time they may have become considerably modified, 1876, 338. He adopted this. The nature of inheritance. Explanation because he accepted the evidence that structural changes might react on the sexual elements, p. 348, but he rejected Darwin's transportation hypothesis. To disprove it experimentally, Galton made blood transfusions among rabbits with different coat colors. He then inbred the transfused rabbits, but among their offspring there was never any deviation from the parental color, as there should have been if alien gemmules had been circulating in the blood, as Darwin had hypothesized. These experiments did not induce Darwin to give up his pangenesis hypothesis. He said rather angrily that the experiments merely show that the gemmules are transported by other means than by blood circulation. This possibility was decisively refuted by Castle and Phillips, 1909, who transplanted the ovaries of an immature black guinea pig to an albino female whose own ovaries had been completely removed. She was then mated to an albino male and in 3 successive litters bore only black offspring. Galton, a dilettante and maverick, pioneered in many areas. He was a strong proponent of population thinking, appreciating the uniqueness of the individual more clearly than any of his contemporaries. This led him to his discovery of the uniqueness, and hence absolute diagnostic value, of fingerprints and to his development of populational statistics, Hiltz, 1973. 2 of the major concepts of statistics were created by Galton, regression and correlation. He is perhaps most widely known as the founder of eugenics. The 1870s were a period of transition. The attacks on soft inheritance were disorganized, relating only to certain aspects of that doctrine. In Darwin's theory of pangenesis, the cell was still accepted as the unit of structure in the organism. Even Galton, who had the most progressive theory of inheritance, failed to connect it with the new findings of cytology. As a consequence, he was unable to lay a theoretical foundation for his speculations. He, like Darwin, failed to understand that entirely new problems arose as soon as it was recognized that the nucleus rather than the cell as a whole is the carrier of the genetic material. One now had to ask, what is the relation between the nucleus and the cytoplasm of the cell? Is there any input from the cytoplasm into the nucleus, and particularly into the nucleus of the germ cell? It must be remembered that ideas about inheritance and its physical basis had been exceedingly vague until the 1870s. This all changed when the nucleus was recognized as the vehicle of inheritance and when the complex structure of the chromatin in 697 side the nucleus was discovered. The elaborate architecture of the germ plasm did not look like a structure that would respond appropriately to general environmental influences like climate and nutrition. A finely organized chromatin structure seemed more compatible with hard than with soft inheritance. How reliable was the evidence that had so far been accepted as proving soft inheritance? Did the new evidence help to refute it? Unfortunately, both Galton and Darwin were unaware of the spectacular advances in cytology made at this period in Germany. 698. August Weismann. The first person who not only asked these questions quite unequivocally but also gave decisive answers to them was August Weismann, 1834–1914, one of the great biologists of all time. 5. He was unique among all those who worked on cytology, development, and inheritance in the last century by being an uncompromising selectionist. His theory of evolution, which excluded all remnants of a belief in an inheritance of acquired characters or other kinds of soft inheritance, was designated as Neo-Darwinism, Romanes, 1896. From the point of view of scientific methodology, again, he was notable for his period in his careful, rational analysis of every problem he encountered. When he wanted to interpret a given phenomenon or process, he attempted to reason out all the possible alternate solutions. Almost invariably this included the solution that is now considered to be the right one. Owing to the insufficient and sometimes even faulty information available at his time, Weismann himself sometimes chose an alternative that is now rejected. This does not in the slightest diminish the magnitude of his intellectual achievement. He never made a hasty decision but always first surveyed the entire field of possible solutions. His was the first truly comprehensive theory of genetics, and his theorizing prepared the way for the research of the entire next generation. As Correns said, the rediscovery of the Mendelian rules in 1900 was no great intellectual achievement after Weismann had paved the way. As a youth, Weismann, born January 17, 1834, in Frankfurt, had been an enthusiastic collector of butterflies, beetles, and plants. He first studied medicine and even practiced it some years, but then shifted to zoology, histology. Almost at once he was hit by the nature of inheritance. Serious eye disease that made microscopic work impossible and forced him into partial retirement, which turned out to be a blessing. He switched from empirical to theoretical studies and devoted his time to thinking deeply about biological problems and their solution. Evolution through natural selection, the material basis of inheritance, and the mechanisms of development were the three interrelated areas of his concern. He saw more clearly than any of his contemporaries that the great controversy about the validity of Darwinism could never be settled without a comprehensive theory of inheritance. His first major paper on inheritance was published in 1876, a whole series of important essays appeared in the 1880s, and finally, in 1892 he published his monumental Chiemplasma, 628 pages. Like all imaginative pioneers, Weismann was quite open-minded and never hesitated to revise his theories when he thought this was required by new evidence. Unfortunately, his revisions, particularly those published after 1890, were not always improvements, when seen in the light of modern knowledge. In A Theory of Heredity, proposed in 1876, Weismann explained inheritance as due to molecular movements, citing with approval von Helmholtz's statement, 1871, 208, that all laws must be reduced in the last analysis to laws of motion. When he rejected Darwin's pangenesis theory, it was because it was based on stuff rather than on motion, and not because it sponsored soft inheritance. Weismann at that time still believed in the influence of external conditions on the inheritable evolutionary material, 1868, 12. Yet, his trust in soft inheritance was apparently weakening, for he tested it by numerous experiments in the years 1875–1880. The genetic theory which Weismann proposed in 1883 and 1885 was not only vastly different from his first attempts but also truly comprehensive. It was dominated by two new insights. The first was that all the genetic material is contained in the nucleus. As stated quite explicitly by Weismann, his theory was founded upon the idea that heredity is brought about by the transmission from one generation to another of a substance with a definite chemical and, above all, molecular constitution, 1889, ENG trans, 167. The second insight was a rejection of an inheritance of acquired characters in any form. There are three ways to refute an inheritance of acquired characters. The first is to show that the mechanisms by which it is supposed to operate are impossible. This was primarily Weiss. 699. 700. Mann's approach. There is nothing in the structure and division of cells that would make an inheritance of acquired characters possible. In fact, in certain organisms, Weismann specifically cites hydroids, the future germ cells are segregated at very early larval stages after only a few cell divisions and are put on ice, so to speak, until the reproductive process is initiated. There is no possible way by which the influences on the remainder of the organisms could be transmitted to the nuclei of the segregated germ cells. This observation led Weismann in 1885 to his theory of the continuity of the germ plasm, 6, which states that the germ track is separate from the body, soma, track from the very beginning, and thus nothing that happens to the soma can be communicated to the germ cells and their nuclei. We now know that Weismann's basic idea, a complete separation of the germ plasm from its expression in the phenotype of the body, was absolutely correct. His intuition to postulate such a separation was faultless. However, among two possible ways for effecting this, he selected the separation of the germ cells from the body cells, while we now know that the crucial separation is that between the DNA program of the nucleus and the proteins in the cytoplasm of each cell. A second way to refute an inheritance of acquired characters is by experiment. If there is an inheritance of acquired characters, then something must be conveyed from the affected part of the body to the germ cells. The old theory of use and disuse, in which even Darwin believed mildly, could be tested by a total disuse of a structure, Payne's experiments, Alternatively, if any body part sends gemmules to the germ cells, then amputation of this body part through many successive generations would result in a gradual size reduction of this organ. Finally, if changes of the phenotype in plants due to cultural conditions were heritable, selective breeding from the largest and smallest individuals of pure lines should produce progressive results. Johansen, 1903. Beginning with Hoffmann and Weismann, such experiments were conducted up to the 1930s and 40s and the results were uniformly negative. See also Galton, Romanes, and Castle and Phillips. In other words, the theory failed every test of its validity. The third way of refuting the theory of the inheritance of acquired characters is to show that the phenomena that are claimed to require the postulate of an inheritance of acquired characters can be explained equally well or better on the basis of the Darwin. The nature of inheritance. Ian theory. Much of the evolutionary literature of the 1920s, 30s, and 40s was devoted to this third approach. See Part 2. Weismann believed in an inheritance of acquired characters throughout the 1870s. Exactly what brought about his eventual conversion is not clear. Nor is it clear whether Weismann had first become convinced of the invalidity of the theory of an inheritance of acquired characters and then adopted the germ tract theory or vice versa. The fact is that he already cites in his 1883 paper so many lines of argument against soft inheritance that one can well imagine that this general conviction preceded the proposal of a specific mechanism. This interpretation is strengthened by the fact that Weismann was a strict selectionist already in the 1870s and presumably had simply no need for an additional mechanism. Weismann's revolutionary rejection of soft inheritance encountered great hostility. It was attacked not only by the neo-Lamarckians, who reached the height of their influence in the 1880s and 1890s, but even by orthodox Darwinians, who continued to accept Darwin's occasional reliance on the effects of use and disuse, for example, Romanes, 1896, Plate, 1903. However, it was adopted by Lancaster, Poulton, and this Elton Dyer in England and had probably, up to the 1930s, more adherents in England than in Weismann's home country. Near universal acceptance did not occur until the 1930s and 40s, as a result of the evolutionary synthesis, Mayr and Provini, 1980. Weismann's theory of inheritance. Having eliminated the complicating factor of soft inheritance, Weismann was ready to propose his own theory. When evaluating it, one must remember that like all the other German students of cytology and generation, Weismann was far more concerned with explaining the genetic control of development than the mechanism of transmission from generation to generation. He concluded that the orderly changes during embryogenesis must be the result of corresponding systematic changes in the idioplasm, 1892, 61. Some years later, 1899, 21, he recalled that at the time he proposed his theory, there were two alternatives to explain ontogenetic differentiation: 1, the hypothesis of a systematic and progressive dissection of the totality of the genetic potential contained in the germ plasm into ever smaller groups to be segregated into different cells, or 2, the hypothesis that the determinants of all characters remain together in all the cells of the developing organisms, but that each of them is tuned to respond to a specific stimulus which only activates the straight, a pure dissection and a pure activation theory. I decided in favor of the former, because on the basis of the facts available at that time it seemed to be the more probable one. As we all now know, it was the wrong choice. Before presenting in detail Weismann's theory of inheritance, I call attention once more to the clarity with which he realized the difference between genotype and phenotype. Indeed, in some of 702 his statements he comes very close to proposing that development is controlled by a genetic program. He rejects the idea postulated in Bonnet's evolution theory that the genetic determinants are the preformed rudiments of the to-be-developed parts themselves, and instead considers them active living units which intervene in grief and in the process of development in a specific manner, that is, in such a way that the character is produced which they have to determine. 1899, 23. Since Weissman approaches the problem of inheritance from the point of view of the developmental physiologist, he attempts to explain the nature of the genetic material on the basis of its effect on ontogeny. The chromatin is able to give a specific character to the cell in whose nucleus it resides. Considering that the thousands of cells of which an organism is composed possess very different characters, it is evident that the chromatin which controls them cannot be the same in every cell but must differ according to the nature of the cell. 1892, 43. Weissman postulates an elaborate hierarchy of hereditary units that control ontogeny. The smallest is the biophore, each consisting of an aggregate of diverse molecules having the capacity for growth and replication. Each biophore controls a specific feature, property, of a cell. All living substance is composed of biophores. 1892, 56-57. The number of possible kinds of biophores is unlimited, that is, it is as great as the number of possible combinations of molecules. Nucleus as well as cytoplasm are composed of biophores, even though the properties of the cytoplasm of a cell are determined by the nucleus. Muscle cells, blood cells, and other components of the body are controlled by specific compounds of biophores which Weissman calls determinants and which represent the next higher rank of units in the hierarchy of particles. The determinants are genotypic units while the biophores carry out the physiological implementation. A single cell may contain numerous replicas of the same. The nature of inheritance. Determinant, 1892, 81. This is particularly true for the nucleus of the gamete. The crucial difference between Weissman's theory and the Mendelian theory of inheritance is that Weissman postulates that a single cell, including the gametes, may contain numerous replicas of the same determinant, 1892, 81, while in the Mendelian theory there are only two, one from each parent. This single difference in the two postulates requires two entirely different theories of inheritance. The determinants, in turn, are joined together in a phylogenetically acquired architecture into still higher units, the ids which, Weissman sometimes implies, are the same as the chromosomes. The germplasm consists of several if not many ids, which, like the biophores, can grow and replicate. The rate of replication of each kind of unit is independent of that of the others. The crucial components of Weissman's theory seem to be these: 1. There is a special particle, biophore, for each trait. 2. These particles can grow and multiply independent of cell division. 3. Both nucleus and cytoplasm consist of these biophores. 4. A given biophore may be represented by many replicas in a single nucleus, including that of the germ cell. 5. During cell division the daughter cells may receive different kinds and numbers of biophores, unequal cell division. As we now know, postulates 2, 5 are wrong and are responsible for the fact that Weissman was not able to arrive at a correct theory of inheritance. By adopting an entirely different strategy, Morgan and his school were able to succeed where Weissman had failed. Instead of trying to explain the gene ontogenetically, they concentrated on the gene from a phylogenetic point of view, that is, instead of studying the unit of developmental genetics, they studied the unit of transmission genetics. Weissman's ingenious theory was at once vigorously attacked, particularly by botanists who favored the activation theory of ontogeny, see above. The fact that in many kinds of plants a bud may be produced almost anywhere which can develop into flowers, as well as the fact that one can often reconstitute a new plant, with flower-producing germ cells, from a single leaf or other vegetative structure, completely refutes a strict separation of germ tract and soma tract. These and other experiments likewise prove that unequal nuclear division, that is, an unequal partitioning of 703. 704. The genetic particles of the mother cell in the two daughter cells, cannot take place. Furthermore, as Roux, 1883, had demonstrated so convincingly, the entire elaborate process of mitosis makes no sense unless one postulates an equal division of the germ plasm during cell division. Kolliker,
1885, Oscar Hertwig, 1894, and Driesch, 1894, summarized particularly effectively the evidence against Weismann's dissection theory. An alternate theory of inheritance. The various criticisms led to a different interpretation of the genetic processes during ontogeny, which incorporated two major new concepts relating to the connection between nucleus and cytoplasm and to the problem of differentiation. Strasburger, 1884, aware of the chemical difference of nucleus, nucleon, and cytoplasm, proposed that the nucleus remains at all times intact but produces molecular excitations which are conveyed to the surrounding cytoplasm and there determine the metabolic processes of the cell and give it a species-specific character. Wilhelm Haas and others adopted similar physical interpretations. Haberlandt, 1887, suggested instead that the nucleus sends not vibrations but specific molecules to the cytoplasm and thus regulates its activities. De Vries, 1910, 203, identified Haberlandt's molecules with enzymes. Unfortunately, Haberlandt never followed up this remarkable theory, which so nearly anticipates messenger RNA. De Vries himself instead suggested that the genetic units, the pangens, migrate from the nucleus to the cytoplasm and thus determine the character of the respective cells. This suggestion was adopted by Weismann, Churchill, 1967. He was fully aware that not all genetic units can be functional at all times and in all cells. Nevertheless, he rejected an activation theory of the gene for two reasons. First, he thought that the activity of a cell was controlled by a determinant, aggregate of biophores, and he was unable to visualize what would happen to a cell if the determinant controlling it was inactivated. Furthermore, he simply could not think of a mechanism that would control the activation or deactivation of the hundreds of thousands of different determinants of an organism. If one would assume that all determinants of the germplasm are transmitted during ontogeny to all cells, then one would have to explain the entire differentiation of the body by an orderly inactivation of all determinants of a cell with the exception. The nature of inheritance. Of the single one which is specific for this particular kind of cell, 1892, 86. It did not occur to him that each biophore, we would now say gene, could be activated and deactivated independently or that the activity of the cell was due to an interaction between the diffuse cell products in the cytoplasm and the products of the activity of the nucleus. Weismann did not deny activation and inactivation but restricted it to the determinants rather than to the biophores, 1892, 100 to 101. His opponents accused him of believing in extreme preformationism. There is much justification in this accusation. Complex characters are caused by pre-packaged assemblages of biophores, determinants. The eyes on the feathers of a peacock could not possibly be produced by large numbers of independent genes. They require a carefully packaged set of determinants, said Weismann. His emphasis was entirely on structural elements. No allowance was made for rates of growth, developmental fields, temporary periods of activity or inactivity of biophores, and so forth. This atomistic interpretation of the determination of traits in the activation theory contributed to its rejection. The controversies stimulated by Weismann's elaborate theories came to deal more and more with problems of development and, in a way, moved more and more away from a genuine theory of inheritance. This is quite evident, for instance, in the work of Oscar Hertwig, 1898. Hugo de Vries was about the only author who continued to focus on transmission genetics, see below. The meaning of sex. The distribution of genetic factors during cell division was not the only aspect of inheritance on which Weismann theorized. Having thought deeply about these matters, he contributed several major new theories, one of which had to do with the controversial role of sexual reproduction. Why should a mother waste half of her reproductive capacity by producing male offspring, when females in parthenogenetic species can reproduce without fertilization and thus double their reproductive potential?
Weissman pointed out that there is no sound evidence in favor of any of the previously proposed physiological theories of sexuality, for instance, that sexual reproduction is a rejuvenation process. Rather, said Weissman, sexual reproduction is the only way by which the unlimited individual variation can be produced that is so characteristic of biological populations. During fertilization, two groups 705, 706 of hereditary tendencies are, as it were, combined. I regard this combination as the cause of hereditary individual characters, and I believe that the reproduction of such characters is the true significance of sexual reproduction. The object of this process is to create those individual differences which form the material out of which natural selection produces new species. 1886, 279. This was by no means a novel idea, because as far back as the 1780s Herder, 1784 to 1791, 138, had stated most perceptibly that the most successful method by which nature combines in her species both diversity and constancy of form, is the creation and conjugation of two sexes. How wonderfully combined are the traits of both parents in the face and body build of the children, as if their souls had been poured into them in different proportions and as if the thousand-fold forces of their organization had been distributed among them, and how often do we find the traits of former generations in the children. But, of course, there is no biological significance to such variation unless one adopts also natural selection. In Darwin's thinking, curiously, sexual reproduction as a source of individual variation played only a very minor role. There is no doubt that Weissman was the major champion of the importance of sex as source of variation, see Chapter 11, even though Galton, 1876, 333, had also recognized it. 7. When we look at the total work of Weissman, we are awed by the diversity of the problems he analyzed and by the sound intuition with which, again and again, he suggested the correct interpretation. His only major mistake was to reject the activation theory, which forced him to adopt unequal cell division, which he called the dissection theory, and a hierarchy of particles. In numerous essays, Weissman raised a great diversity of biological problems, some of which, like what is the biological meaning of death, had hardly ever been raised before. Inheritance and evolution were his main interests. E. B. Wilson, long ago, stated that the modern theory of genetics rests on the Weissmanian foundation. In an age in which soft inheritance was at the height of its popularity, he was the champion of exclusively hard inheritance. In an age relying on physical forces, it was he who stressed particles and what might be called neopreformationism. His theory of inheritance was based on the assumption of particulate inheritance. Indeed, the theory of blending inheritance was specifically refuted by him, 1892, 388, 544. It was he who emphasized that the units of inheritance are carried by the chromosomes and who predicted the occurrence of a reduction division, see Galton, 1876. The nature of inheritance. 334, and Chapter 17. Weissman played an equally important role as an evolutionist by his uncompromising emphasis on natural selection, neo-Darwinism. Although the early Mendelians, including T.H. Morgan prior to 1910, rejected Weissman, his ideas ultimately prevailed, particularly where the application of genetics to evolution was concerned. Hugo de Vries. The Dutch plant physiologist Hugo de Vries, 1848 to 1935, differed quite fundamentally from Weissman and the German cytologists in two ways. He had been educated in organic and physical chemistry, which permitted him to see the functional problems of inheritance in a different and much more meaningful light than contemporary zoologists and botanists. Furthermore, his main genetic interests were transmission genetics and the origin of organic diversity. When studying de Vries's influence on our understanding of variation and inheritance, one must distinguish the impact of three publications: his Intracellulare Pangenesis, 1889, quotations are from English translation of 1910, the report of his rediscovery of Mendel's rules, 1900, and his mutation theory, 1901 to 1903. The theory of intracellular pangenesis, which was published prior to 1892 and influenced Weismann's theory of inheritance, incorporated the same advances in the understanding of cells as Weismann's work had, yet differed by placing a primary emphasis on questions of transmission genetics. This brilliant and persuasive work, curiously, did not have the influence it deserved. Only after Weismann's theory had been refuted was it remembered how much closer de Vries had been to the later findings. Also, the mental preparation which intracellular pangenesis had given de Vries predestined him to become one of the rediscoverers of Mendel. De Vries's primary interest in heredity was evolutionary and started, as with Unger and Mendel, see below, with the species problem. De Vries rejected the concept of the species as a unit and the totality of its specific attributes as an indivisible concept, 1889, 11. But if the species characters are regarded in the light of the theory of descent, it soon becomes evident that they are composed of single factors more or less independent of each other. A study of organism leads inevitably to the conviction of the composite nature of specific characters. There were two important influences on de Vries's thinking: the year he had spent in the reductionist mechanistic laboratory of Julius Sachs in Würzburg, and his close relations with the physical chemist Jacobus Hendrikus van 't Hoff in Holland. It is not surprising therefore that he wanted to carry the analysis down to the basic units of the living world. The character of each individual species is composed of numerous hereditary qualities based on factors that are the units which the science of heredity has to investigate. Just as physics and chemistry go back to molecules 708 and atoms, the biological sciences had to penetrate to these units in order to explain, by means of their combinations, the phenomena of the living world, 1889, 13. Genetic units. The various authors from Spencer to Weismann postulated three theories about the nature of genetic units. In a rather simplified manner, these theories may be stated as follows: 1. Each unit has all species characters, it is, so to speak, an entire species homunculus, Spencer, Weismann's ids, Nageli's idioplasm. 2. Each unit has the features of a single cell, Darwin's gemule, Weismann's determinant. 3. Each unit represents a single species character or trait, de Vries's pangen, Weismann's biophore. De Vries's 1889 theory differed from that of Weismann, 1892, by giving each pangen independent existence and the capacity to be activated and to vary independently of the others. Weismann's biophores were tied together into determinants. De Vries, 1889, 67-68, refutes with well-reasoned arguments Weismann's objections against the recognition of individual units for each hereditary trait. One can summarize de Vries's genetic theory in these statements: 1. Inheritance is due to material bearers of hereditary qualities, to be called pangens. 2. Every hereditary character has its special kind of pangen. 3. The more highly differentiated an organism is, the more kinds of pangens it has. 4. Each pangen can vary independently of any others. 5. All nuclei contain the same pangens but only a very limb. The nature of inheritance. Ith number of pangens are released into the cytoplasm of a given cell, all others remaining inactive in the nucleus of that cell. 6. A given nucleus may contain many identical replicas of a given pangen. 7. In order to become active, a pangen must move from the nucleus to the cytoplasm. 8. There is no movement of pangens from the cytoplasm to the nucleus. 9. There is no movement of pangens from one cell to another. 10. Pangens always divide during cell division but may also divide between cell divisions so that a given pangen may be represented in the cytoplasm, as well as in the nucleus, by many identical replicas. 11. The entire protoplasm of an organism consists of pangens. 12. Occasionally a pangen changes, and this forms a starting point for the origin of varieties and species. 1889, 71. This is the source of his later mutation theory, see chapter 12. De Vries had every justification to claim that his theory was an excellent foundation for an experimental analysis of inheritance, and soon after the publication of his brilliant book, 1889, he himself initiated such an experimental program. It was based on the thesis of the independent variation of each genetic unit. Consequently, each one can of itself become the object of experimental treatment in our culture experiments. 1889, 69. There is little doubt that de Vries's genetic theory is closer to current concepts than any other that preceded it. However, two of his major assumptions were drastically wrong: that the pangens themselves move from the nucleus to the cytoplasm, and that a given pangen could exist in the nucleus in multiple replicas. He thought that this explained dominance and quantitative characters. If certain pangens are fewer in number than others, then the character represented by them is only slightly developed. If there are very few, the character becomes latent. 1889, 72. De Vries shared this erroneous postulate with Weismann and all other authors in the 1880s and 90s who theorized about heredity. It is very obvious that it would be meaningless to calculate Mendelian ratios if one makes such an assumption. The crucial next step in the history of genetics was the overthrow of the multiple replica. 709. Theory of genetic factors. The total refutation of blending was another one. The period from the 1860s to the 1890s was a period of quite uninhibited speculation. We must conclude this whether we look at the writings of Spencer, Haeckel, and Darwin, or those of Galton, Nageli, de Vries, and Weismann. This period also continued to be handicapped by erroneous concepts and the failure of an adequate discrimination between components in complex problems. This includes the failure to cleanly separate character transmission between generations from gene physiology, differentiation. It includes the failure to distinguish, except for de Vries, unit characters from the species essence, and the failure to discriminate between genotype and phenotype. And yet this period was an indispensable stage in the development of genetics. It was in this period that the right questions were first asked, that an interest in the corpuscular and chemical nature of the transmitted genetic material developed, and that the cytological foundation was laid without which no causal theory of inheritance could have been elaborated. At the end of the period, almost all conceivable alternatives had been proposed, and the stage was set for the new insight or discovery that would permit unequivocal choices between competing theories. This decisive event was the rediscovery in 1900 of the work of Mendel. It gave rise with one stroke to an entirely new branch of biological science. Gregor Mendel. It is one of the great ironies in the history of science that the answer to the problem of heredity had already been found while so many distinguished investigators searched for it so assiduously during the 1870s, 80s, and 90s. It had been published in the Proceedings of the Natural History Society of Brno, Brno. 9. Father Gregor Mendel had given 2 lectures to that society on February 8 and March 8, 1865, in which he described the results of plant breeding experiments he had conducted since 1856. The report, published in 1866, is one of the great classics of the scientific literature, a model scientific report, clearly setting out the objectives, concisely presenting the relevant data, and cautiously formulating truly novel conclusions. Who was this hidden genius, and why was his work neglected until 1900, when it was suddenly rediscovered? Johann Mendel, 1822–1884, the name Gregor was given to. The nature of inheritance. Him when he became a priest, was born in Austrian Silesia, the son of poor peasants. He was not at all the obscure monk he is sometimes described, even though he carried out his genetic experiments in Brno in virtual intellectual isolation. Mendel had received an excellent education in the high schools of Troppau and Olmütz and, ultimately, for 2 years, 1851–1853, at the University of Vienna, in order to be qualified to teach physics and other sciences at the high school level. He was, thus, actually a well-trained young scientist who had been educated in Vienna under some of the outstanding physicists and biologists of his time. Of special importance is the fact that Franz Unger, his professor of botany, had adopted a theory of evolution in 1852 which included the opinion that variants arise in natural populations which in turn give rise to varieties and subspecies until finally the most distinct of them reach species level, see Chapter 8. He thus implied that the study of varieties was the key to the solution of the problem of the origin of species. This idea apparently greatly stimulated his student Mendel. It is highly significant that, as in the case of Darwin, it was the species question which inspired Mendel in his work on inheritance, quite in contrast to the German embryologists and cytologists whose basic interest was the physiology of development. In his famous 1866 paper, Mendel states that his time-consuming experiments were necessary in order to reach the solution of a question, the importance of which cannot be overestimated in connection with the history of the evolution of organic form. Evidently he wanted to test Unger's theory, and this meant a study of varieties. As a consequence of his evolutionary approach, Mendel adopted, as Thode, 1966, has correctly pointed out, the method of population analysis rather than the study of the single individual that is traditional in functional analysis. He analyzed large populations of offspring and was fully aware that it was necessary to observe without exception all members of the series of offspring in each generation, 1866, 4. He literally analyzed tens of thousands if not hundreds of thousands of seeds and plants, his experiments requiring the work of 8 planting seasons. Everything we know about Mendel indicates that he was an extremely meticulous person. He kept careful records of weather, sunspots, and other variable phenomena, and was fascinated with numerical relationships. This ideally predestined him for a populational approach to inheritance. Of decisive importance for Mendel's success was the fact that 712. He had been trained in physics as thoroughly as in biology, or more so. His favorite high school teacher had been a physicist, and physics seems to have been the major subject in his own teaching. In Vienna he took courses with the famous Doppler and with other physicists, and he even served for a time as a demonstrator at the Physics Institute of the University of Vienna. It is this experience which must have taught him to keep careful records of his experiments, to arrive at numerical generalizations, and to attempt a rudimentary statistical analysis. This approach, of course, was particularly suitable, indeed necessary, for a population analysis. Thus, although his concepts, population, evolution, came from biology, most of his methodology came from physics. Owing to his excellent grasp of the botanical literature, and particularly his thorough reading of Gärtner, see above, Mendel was keenly aware of the extreme importance of selecting the right kind of plant for his experiments. Selection of the plant group for experiments of this kind must be made with the greatest possible care if one does not want to jeopardize all possibility of success from the very outset. The experimental plants must necessarily, 1. Possess constant differing traits. 2. Their hybrids must be protected from the influence of all foreign pollen during the flowering period or easily lend themselves to such protection. 3. There should be no marked reduction in the fertility of the hybrids and their offspring in successive generations. Mendel, 1866. The latter point was of crucial importance, considering one great weakness in Mendel's conceptual framework: he had little idea what a species was. He designated the forms which he crossed sometimes as species or as subspecies or as varieties, because in any event, the rank assigned to them in a classification system is completely immaterial to the experiments in question, just as it is impossible to draw a sharp line between species and varieties. It has been equally impossible so far to establish a fundamental difference between the hybrids of species and those of varieties, p. 5. Actually, there is indeed a drastic difference, as Karl Reuter had intuitively appreciated better than Mendel. Differences among intrapopulation variants are usually single gene differences and dis. The nature of inheritance. Play uncomplicated Mendelian segregation, while the differences between species are often highly polygenic and fail to segregate cleanly. As long as Mendel faithfully adhered to the third of his stated principles, he was safe. When at a later period he turned to other material, because devastations by the pea weevil, Bruchus pisci, made further work on peas impossible, Mendel ran into disturbing complications which seemed to undermine the generality of his previous findings. However, in 1856 he had fortunately decided to select the P. pisum sativum and related forms as his experimental material owing to a large number of advantages of this species which had been appreciated by plant hybridizers from Andrew Knight on. Owing to his uncertainty as to what a species is, Mendel used the term hybrid indiscriminately, both for actual species hybrids and for heterozygotes of a single gene. This has confused certain historians. Even though Mendel occasionally calls himself a hybridizer and in his paper often refers to Kallrötter, Gartner, and other plant hybridizers, he himself does not at all belong to that tradition. As a student of Unger and of the problem of evolution, Mendel was concerned with single character differences and not, like the hybridizers, with the species essence. To understand this fully is very important for the interpretation of Mendel's work. It is totally misleading to say that Mendel's conceptual framework was that of the hybridizers. It is precisely the breaking away from the tradition of the hybridizers that characterizes Mendel's thinking and constitutes one of his greatest contributions. Another remarkable aspect of Mendel's work was that it quite evidently employed the hypothetico-deductive method. The entire planning of his experiments, the explanation of his method, as well as the choice of his material permit no other interpretation than that already early in his work Mendel had a well-formed theory in his mind and that his experiments actually consisted in the testing of his theory. His approach thus differed widely from that of both the earlier hybridizers like Gartner, who through an inductive approach piled up mountains of results without getting to any conclusion whatsoever, and workers like Nageli, who speculated wildly without ever attempting to test the validity of their speculations. The hypothetico-deductive approach, of course, was not new with Mendel. It had been adopted by perceptive investigators from the 18th century on, among both physicists and biologists, Darwin and Schleiden being typical examples. Stripped to its essentials, Mendel's theory was that for each 713, 714 heritable trait, a plant is able to produce two kinds of egg cell and two kinds of pollen grain, each representing either the paternal or the maternal character, if they are different. Or, to express the same hypothesis in different words, each character was represented in the fertilized egg by two hereditary elements, and no more than two, one derived from the mother, from the female gamete, and one derived from the father, from the male gamete. It is admittedly controversial to which extent Mendel and the early Mendelians thought in such terms. Exactly when this theory was formed in Mendel's mind we shall never know, because his voluminous notes and manuscripts were all burned either late in Mendel's life or after his death. All we can do is to conjecture. Most likely this theory came to Mendel about 1859 after some preliminary breeding, but was firmly in his mind during the later years of intensive breeding work. Mendel's findings. Mendel procured 34 more or less distinct varieties of peas from several seed dealers and subjected them to 2 years of testing. Of these varieties, 22 remained constant when self-fertilized, and these he planted annually throughout the entire experimental period. In these 22 varieties, 7 pairs of contrasting traits were chosen for experimental testing. 2 plants differing in a given pair of traits were hybridized, and the behavior of the trait was followed in the ensuing generations. The 22 varieties differed from each other by far more than the 7 selected traits, but Mendel found the other traits unsuitable because either they produced continuous or quantitative variation not suitable for the study of the clear-cut segregation that he was interested in, or else they did not segregate independently. The traits chosen were the following: 1. Whether the ripe seeds were smoothly round or angular and deeply wrinkled. 2. Whether the ripe seed,
cotyledon, is yellow or green, 3. Whether the seed coat is white or gray, 4. Whether the ripe pod is smooth and nowhere constricted or deeply constricted between the seeds and more or less wrinkled. The nature of inheritance. 5. Whether the unripe pod is green or vivid yellow, 6. Whether the flowers are proficient along the main stem or are terminal, 7. Whether the stem is long, 6 to 7 feet, or short, %h/2 feet. What Mendel found is now familiar to every beginning biology student. He had chosen 7 character pairs, one of which was always clearly dominant. In all of his experiments, therefore, the first hybrid population, Fx, was uniform and agreed with the character of one of the parents. Dominant were, for instance, round seeds, yellow seed coloration, gray coloration of the seed coat, green coloration of the unripe pod, long stems, and so on. Mendel introduced, probably independently of others such as Martini and Sageret who had used a similar terminology, the term dominant, dominierend, for this predomination of one character in the first hybrid generation, and recessive, smiley face, recessive, for the alternate characters. When the F hybrids were self-fertilized, producing an F2 generation, the recessive character reappeared. In the case of seed shape, among 7,324 seeds collected from 253 self-fertilized hybrid plants, 5,474 were round and 1,850 wrinkled, giving a ratio of 2.96:1. In the case of seed color, 8,023 seeds collected from 258 hybrid plants gave 6,022 yellow and 2,001 green seeds, representing a ratio of 3.01:1. Mendel summarizes the results of the crossing of first-generation hybrids as follows: in this generation along with the dominant traits the recessive ones reappear in their full expression, and they do so in the decisively evident average proportion of 3:1, so that among each 4 plants of this generation 3 show the dominant and 1 the recessive character, 1866, 10. Mendel did not stop at this point, but produced an F3 generation by self-fertilizing a large number of plants of the F2 generation. In his experiment with round versus wrinkled seeds, which had given him 75% round and 25% wrinkled in the F2 generation, he found that all the plants raised from wrinkled seeds bred true for this character. Plants raised from round seeds showed segregation in the F3. Among 565 plants raised from round seed, 193 yielded only round seeds, thus being constant for this trait. However, 373 plants produced both round and angular seeds in the proportion of 3:1. In other words, among the round seeds 1/3 bred true for this character, and 2/3 gave round and wrinkled seeds. Mendel carried most of his experiments. 715. 716. Through 4 to 6 generations, and the results were always the same. He had clearly discovered a law-like regularity. What interpretation did Mendel give to his findings? The distinction between genotype and phenotype was not made until nearly 50 years later, and the concepts of pangens and genes, and of chromosomes and other cell and nuclear elements, had not yet been developed. It would have been miraculous in the absence of such factual and conceptual assistance if Mendel in 1865 had created all of Mendelian genetics out of nothing. And he did not. Nevertheless, it was so natural to interpret his presentation in Darwinian and Weismannian terms that De Vries, Correns, and Bateson did just that automatically when they read Mendel's paper. None of them even attempted to question Mendel's priority. This honor was reserved for historians. Albee, 1979, has recently suggested that Mendel was no Mendelian. The validity of this claim depends entirely on one's definition of Mendelian. If one needs to have adopted all the genetic findings made from 1900 to 1915, then, indeed, Mendel was no Mendelian. He did not name genes and assign them to definite loci.
Throughout most of his paper he referred to the inherited characters in a language remarkably similar to that by which Bateson referred to unit characters, as would anybody who does not make the genotype-phenotype distinction. Considering that Mendel did not know any of the findings of cytology, most of which were made in the 1870s and 80s, how did he visualize the transport of the characters in the chiomund pollenzellen, female and male gametes? He postulated that the characters are represented by Gleichartige identical oder differierend differing element. He does not specify what these element are who could have done so in 1865, but considers this concept sufficiently important that he refers to these element no less than 10 times on pages 41 and 42 of the Werkbuch HC. Evidently they correspond reasonably well to what we would now call genes. Where Mendel differed from the later genetic interpretation is that he ascribed a different fate to the Gleichartigen and differierenden elements. He thought that if they were identical, the homologous elements of male and female gamete would fuse completely after fertilization. This is why in the F2 he wrote A and A, instead of A and A. If the elements were different, he assumed that the association in the hybrid plant would be only temporary, to be dissolved again during the formation of the gametes of the hybrid plant, 1866, 42. The nature of inheritance. Mendel summarizes his hypothesis, his word, of the behavior and the attributes of the elements by saying, the distinguishing traits of two plants can, after all, be caused only by differences in the composition and grouping of the elements existing in dynamic interaction in their primordial cells, p. 42, trans. Stern and Sherwood, 1966. Where Albee and colleagues are correct is in refuting the assumption, universally made among geneticists arid previously by Mayr, that Mendel had a clear picture of pairs of alleles which neatly separated during gamete formation. His description of the Vereinigung Gleichartiger element, union of identical elements, through fusion falsifies this claim. The absence of a concept of gene loci with sets of alleles is confirmed by Mendel's description of polygenic color inheritance in a phaseolus cross where the same recessive Merkmale is postulated for the two simultaneously present Merkmale D and A2. In modern terminology, the recessives at these two independent loci would have to be designated differently, as AX and A2. Then why did Correns, de Vries, and Bateson assign to Mendel the priority of having discovered Mendelism? The main reason, as Correns pointed out quite succinctly, is that after the cytological researches of the 3 preceding decades and after the genetic theorizing of de Vries, 1889, and Weissmann, 1892, the 3:1 ratios could be explained in no other way than by assuming that during gamete formation there is a 1:1 segregation of the unlogen for equivalent characters. Indeed, this was what Mendel had already almost, but not quite, postulated. He did postulate it for the differierend Merkmale, 1866, 42, while for the Gleichartigen Merkmale he merely postulated that each must be represented in the gametes. Mendel himself never says explicitly that they must be represented in the gamete by only a single element, but 3:1 ratios would not occur with such law-like universality if this were not the case. With the vastly expanded knowledge of cytology and inheritance available in 1900, Mendel's rediscoverers immediately took this for granted. The 3:1 ratios left them no other alternative. Albee and the others who have recently questioned the nature of Mendel's contribution are thus right in insisting that Mendel did not, by a single stroke, create the whole modern theory of genetics. He did not have a theory of the gene, but neither did his rediscoverers, as Albee points out quite correctly, 1979, 58. However, Mendel's various discoveries, segregation, constant Ra. 717. 718. Teos, independent assortment of characters, combined with the new insights acquired between 1865 and 1900, led, one is tempted to say automatically, to the theory quite legitimately called Mendelian. Among Mendel's more important conclusions concerning a single set of characters are these: 1. dominant and recessive genes do not affect each other while associated in the heterozygote. Even if one were to cross round-seeded peas with wrinkled peas for 100 generations, the round peas would remain as round as they were at the beginning, and the same would be true for the wrinkled ones. 2. Gametes always contain only the onloga of one of the two alternate characters. This is as true for the gametes produced by heterozygotes as for those produced by homozygotes. Evidently, the determinants of the parental traits are separated prior to gamete formation. This explains the phenomena of segregation and of recombination, so well known to breeders. 3. A plant produces thousands of egg cells and millions of pollen grains, or spermatozoa, in the case of animals, and the meeting of gametes with different genes is a matter of chance. When small samples are used, one has to expect deviations from the 3:1 ratios, but the range of these deviations is statistically predictable. Important for the planning of his crosses was Mendel's conviction, experimentally tested by him, that propagation in phanerogams is initiated by the union of one germinal and one pollen cell into a single cell, 1866, 41. The insight that only a single pollen grain is involved in fertilization was based on the work of Amici and other botanists, which Mendel had evidently learned from Unger, whose excellent textbook of the anatomy and physiology of plants he owned and who had written elsewhere about this subject. It was a great handicap for Darwin to have accepted from the breeders the belief that egg cells are simultaneously fertilized by several male gametes. Mendel now applied his new insight to crosses involving two pairs of characters. He found, for instance, that when a plant with round yellow seeds is crossed with a plant with wrinkled green seeds, one can obtain 4 different combinations in the F2. For instance, in a given cross he obtained 350 round yellow, 108 round green, 101 wrinkled yellow, and 32 wrinkled green seeds, coming rather close to the expected 9:3:3:1 ratio. The conclusion was evident: each character is inherited independently of the other, and the nature of inheritance. The dominant to recessive ratio is unaffected by the other character, 1866, 42. Finally, Mendel made a cross involving 3 sets of characters, showing that all 3 were inherited independently. By clearly focusing on individual characters and their behavior in subsequent generations, Mendel was able to arrive at certain generalizations. He formulated the law of combination of different characters, now referred to as the independent assortment of characters. Correns, 1998, phrased it as follows: in the gametes of an individual hybrid, the onlogen for each individual parental character are found in all possible combinations, but never in a single gamete the onlogen for a pair of characters. Each combination occurs with approximately the same frequency. It is self-evident, but needs special emphasis, that the laws of inheritance can be worked out only if the two parents differ from each other in their genetic constitution. This permits the demonstration of 2 important factors of inheritance. First, the equal contribution of both parents, and second, the maintenance of the integrity of differing elements, their non-blending in subsequent generations. Mendel stressed this in his correspondence with Nageli. I am inclined to regard the separation of parental traits in the progeny of hybrids in Pisum as complete, and thus permanent. I have never observed gradual transitions between the parental traits or a progressive approach toward one of them. Correns, 1905. In his smaller samples, Mendel had some rather pronounced deviations from the expected 3:1 or 2:1 ratios. 10 He was fully aware of the statistical nature of such sampling errors, and to compensate for them, in an age long before the existence of statistical tests of significance, he simply grew large populations of his crosses. Fischer, 1936, raised the question of whether Mendel's results were not too good, since the deviations from expectancy, as calculated by chi-square tests, are smaller than expected, he said. However, the internal evidence as well as everything we know about Mendel's painstaking and conscientious procedure make it quite evident that no deliberate falsification is involved. It is possible that Mendel threw away a few particularly deviant crosses, thinking that they had been falsified by foreign pollen. It is also possible that he continued repeating a certain cross until the numbers approached the expected ratio, not realizing that this introduced bias into his method, but it is most likely that the bias is introduced by the fact that pollen, during maturation, is produced in 719. The form of tetrads, and that this, particularly in cases of self-fertilization and limited amounts of pollen, may lead to results that are too good. Thode, 1966. Furthermore, if germination in Mendel's plants was only 8 or 9 out of 10, as is usual in such experiments, it invalidates Fisher's chi-square calculations and brings Mendel's results right in line with those of other p hybridizers. Weiling, 1966, Orell, 1971. Thus there was really nothing drastically wrong with Mendel's figures. Indeed, Mendel was an almost pedantically precise recorder of data, as also shown by 720 his work in meteorology. Mendel's most significant contribution. The almost explosive development of genetics after the rediscovery of Mendel's work suggests that there is something crucial in Mendel's findings that permitted the field to make a new start after more than 30 years of floundering with erroneous or at least premature speculations. What was this crucial component? Dominance, reversion, the identity of reciprocal crosses, the uniformity of the first hybrid generation, and the variability of the second generation had been described by numerous authors before. Zirkel, 1951. Nor was his postulate new. In 1900, that there are certain elements, particles, that control characters. This was essentially Darwin's theory of gemmules, and more particularly de Vries's theory of pangens. Nor was the refutation of blending inheritance Mendel's decisive contribution. First of all, he himself believed in a fusion of the Gleichartigen element, but, more importantly, de Vries and Weismann believed, at least in part, in particulate inheritance. Yet, Mendel greatly contributed toward the eventual eradication of the last remnants of a belief in blending. He emphasized that, if the factors derived from father and mother differed, they would never fuse but would invariably again separate during the formation of the germ cell. It was only a small step from this to the postulate that the Gleichartigen element would likewise remain discrete after fertilization. This independence, and separate existence, so to speak, of the genetic factors in the germ plasm simultaneously gave a great boost to a belief in hard inheritance. 11. I stressed above that although Mendel's method had been strongly influenced by physics, his conceptual framework was supplied by biology. Unlike the physicalists, his, Loeb, Bateson, Johansen, inheritance for Mendel was not due to forces or excitations but due to concrete materials supplied by maternal. The nature of inheritance. Egg cells and paternal pollen cells. The basis of inheritance was Th equality of the transmitted parental matter. From Haeckel, 1866, and Darwin, 1868, on this was the standard assumption of all those who approached the problem of inheritance as naturalists or whole organisms biologists. What, then, was the outstanding contribution made by Mendel? When we carefully compare his theory of inheritance with those of Darwin, Galton, Weismann, and de Vries, 1889, we discover two crucial differences. First, all these earlier authors postulated the existence of numerous identical determinants for a given unit character in each cell, each nucleus, and speculated, likewise, that many replicas of a single determinant might be transmitted simultaneously to the germ cells. If this were the case, no consistent ratios would be found in crosses. This assumption made the development of a clear-cut genetic theory almost impossible. The universality of the 3:1 ratio refuted the multiple particle postulate. It is consistent only with a single particle postulate. This was Mendel's greatest contribution. Mendel's other significant contribution was the discovery that these particles exist in sets genes and their alleles, we would now say. Through this assumption it was possible to explain segregation and recombination. his inference that each character is represented in a fertilized egg cell by two, but only two, factors, one derived from the father and the other from the mother, and that these could be different, was the new idea which revolutionized genetics. What Mendel provided was an exceedingly simple theory which any amateur could easily test on a given set of alternate characters. Indeed, this is so simple that experiments of this sort are now done by teenagers in the science classes of some high schools. At the same time, Mendel's simple generalizations laid the foundation for the development of genetics after 1900. The rediscoverers of Mendel rather concealed the true nature of Mendel's discovery by speaking of Mendel's three laws: 1. The law of segregation, 2. The law of dominance, and 3. The law of free assortment. Phenotypic segregation in the F2, of course, had been found by many pre-Mendelians from Kallrötter, Knight, and Sageret on. However, it was never as central in anybody else's work as in Mendel's, nor previously applied to the genetic material itself, die element. Emphasis on segregation was an effective way to counteract any leanings toward a belief in blending inheritance, but segregation alone is not the essence of Mendelism. If one has 722 multiple determinants for a simple character, as was believed by everybody but Mendel before 1900, one can have segregation without 3:1 ratios. What was crucial in Mendel's theory was his insistence that when the parents differ in a character, the elements or anlagen for these characters remain discrete in the hybrids and separate again in the formation of the germ cells of these hybrids. This clearly is one of Mendel's decisive contributions, the other one being the inference, made necessary by the 3:1 ratios, that each character is represented in the germ cells by one, and only one, element. Dominance, as we shall presently see, is not a law. That there was dominance in all 7 of Mendel's character pairs was evidently due to his deliberate choice of such characters. Finally, free assortment is also not a valid law, because it was discovered soon after 1900 that characters could be linked, by having their determinants on the same chromosome, see chapter 17. Mendel's laws may have been a helpful didactic device in the early days of Mendelism, but by now they have rather lost their usefulness and have been replaced by others. Why Mendel's work was ignored. The clarity of Mendel's writings, the simplicity of his theory, and the desperate need for such a theory at the time when it was published, 1866, make it a disturbing puzzle why his work was so utterly ignored. The glib answer that the world was not yet ready for it is no answer. If Mendel was ready for it, why not some others? The question is sufficiently important for some of the basic tenets in the history of ideas to be studied more carefully. What then are the possible causes? The first, of course, is that Mendel published very little. Of the immense amount of data which he must have accumulated between 1856 when he started his work and 1871 when he discontinued his crosses, he published only his lecture to the Bryan Natural History Society and one other short paper, on hawkweed crosses, 1870. To put it mildly, Mendel was not a prolific author. From his correspondence with Nageli, Stern and Sherwood, 1966, we know that he found the Pisum results completely confirmed in crossing experiments with Mathyla annua, M. glabra, Zea, and mirabilis, work done in 1869. Alas, this was long before the days of the admonition, publish or perish, and Mendel never in The Nature of Inheritance formed the world of this confirmation of his earlier discovery that had been announced in a single publication. The Verhandlungen of the Bryan Society were sent to the libraries of 115 or more institutions, including the Royal Society and the Linnean Society in Great Britain. Mendel had 40 reprints made of his paper, and we know that he sent them, presumably among others, to 2 famous botanists, A. Kerner von Marilaun at Innsbruck, well known for his transplant experiments, and Nageli, one of the leading botanists of his time and known to Mendel as a student of hybrids. This resulted in an active correspondence with Nageli of which, unfortunately, only Mendel's letters have survived. It is quite evident that Nageli either did not understand Mendel's thesis or, more likely, opposed it. Instead of encouraging Mendel, he apparently did just the opposite, nor did he invite Mendel to publish his results in one of the prestigious botanical journals where they would have come to the attention of others. Instead, he encouraged Mendel to test his theory of inheritance in the hawkweeds. Hieracium, a genus in which, as we now know, parthenogenesis, apomixis, is common, leading to results that are incompatible with Mendel's theory. In short, as one historian has put it, Mendel's connection with Nageli was totally disastrous. When Nageli in 1884 published his great book on evolution and inheritance, he entirely failed to mention Mendel even a single time in a long chapter dealing with hybridization experiments. This is almost unbelievable since everything else in this chapter is of far less significance than Mendel's work. Was Nageli contemptuous of the Catholic priest in far-away Moravia? Or was it simply scientific intolerance? Presumably it was the latter. It is rarely pointed out that Nageli was one of the few biologists who subscribed to a theory of pure blending inheritance. Mayr, 1973, 140. During fertilization the maternal and the paternal idioplasms blend, according to him, owing to the fusing of the homologous strings of micelles into a single strand. To accept Mendel's theory would have meant, for Nageli, a complete refutation of his own. Without studying Mendel's work as carefully as he should have done, Nageli simply concluded that Mendel must be wrong. Weinstein, 1962. Mendel's modesty did not help his case. After having been snubbed by Nageli, he apparently made no effort to contact other botanists or hybridizers or to lecture at national or international meetings. He referred to his 7 years of work involving more than 30,000 plants as one isolated experiment. 725. 124. Mendel was fully aware of the fact that the situation in the pea is an unusually simple one. This no doubt is the reason why he chose this species as his principal material. Almost all the complications of chromosomal inheritance which have since been discovered were already present in one or the other of the species of experimental plants with which Mendel had worked. With the means available to him, he would surely have been stumped by the complications introduced by linkage, crossing over, and polyploidy. Indeed, the apomixis of Hieracium later thwarted him completely. Mendel therefore was under the impression that his findings were perhaps not true for all species of plants, and said himself, a final decision can be reached only when the results of detailed experiments from the most diverse plant families are available. 1866, 2. Perhaps Mendel's attitude, in this instance, was adversely affected by his training in physics. The physicists, at least in Mendel's times, always searched for general laws. Hence, the laws which Mendel had found for peas would be valid only if they also applied to Hieracium and to all other plants. Did Mendel think his Pisum laws were not valid, because he found some other kinds of plant to which these laws did not seem to apply? As I pointed out above, there was another weakness in Mendel's approach. When he decided that the validity of the laws proposed for Pisum needs confirmation, 1866, 43, he turned to the hybridizing of species. Even though Mendel realized that this was not quite the same as hybridizing varieties, p. 39, nevertheless the work on species hybrids made him unsure and unwilling to promote his Pisum results as vigorously as they deserved. He was particularly puzzled by alleged constant species hybrids. In this Mendel was not alone. The nature of species was what hybridizers were most interested in and, prior to 1900, Mendel's crosses of species of beans, Phaseolus, and hawkweeds, Hieracium, were mentioned by the hybridizers, from Nageli to Hoffmann and Fock, rather than his Mendelian ratios of varieties of peas. For a long time after 1900 it was widely believed that continuous variation obeyed entirely different laws of inheritance than those of Mendel, and this might add another reason for the neglect of Mendel's work. After all, gradual continuous variation was widely considered after 1859 as the only variation of interest to the evolutionist.
Historians have determined that Mendel's work had been cited about a dozen times prior to 1900. The most important of these is Fock's great review book Die Pflanzenmischlinge, 1881. Any. The nature of inheritance. One subsequently working on hybridization consulted Fock, and nearly all those who referred to Mendel after this date stated that they had discovered the reference in Fock. Yet, Fock himself never realized the importance of Mendel's work and referred to Mendel's work in a way that would not encourage anyone to consult the original paper. In 1864 Mendel was forced to discontinue his Pisum work owing to the heavy infestation of pea weevils and to exciting results in other plant genera. He abandoned all of his crossing work in 1871 after he had been elected abbot of his monastery and had become too preoccupied with administrative burdens. After Mendel had died of nephritis in 1884 at the relatively young age of 62, it took another 16 years before the world appreciated the greatness of his discovery. Finally, it should be mentioned that the rediscoverers of Mendel, particularly Correns, with their advanced understanding of cytology, read more into Mendel's account than is actually there. Hymans and Albee deserve credit for having pointed out deficiencies in Mendel's interpretation. This by no means diminishes Mendel's greatness. But by showing that his theory was not as complete and therefore not as fully explanatory as had been claimed by geneticists for 3/4 of a century, Hymans and Albee make it easier to understand why the work was ignored for 34 years. For reasons that are not at all clear, Mendel's age was not particularly interested in pure transmission genetics. Inheritance was generally considered only in connection with other biological phenomena, such as the species problem, and that of species hybrids, environmental induction, and the inheritance of acquired characters, differentiation during development, the consolidation of species characters in isolation and their breakdown, blending, following the removal of the isolating barrier, and so forth. There has been much speculation as to what effect Mendel's paper would have had on Darwin had he read it. I agree with those who think it would have had little influence if any. It took many years, after 1900, before the true Darwinians, as they like to call themselves, understood that gradual evolution and continuous variation could be explained in Mendelian terms. Darwin, presumably, would have had the same difficulty. He knew Sageret's work, but apparently it did not help him to understand variation. And when it comes to the problems in which Darwin, as an evolutionist, was most interested, such as the mysterious 725, 726 laws of correlation, the acquisition of reproductive isolation, and the establishment of the cohesion of the genotype, even we are still very much in the dark, 80 years after the rediscovery of Mendel. Without any knowledge of chromosomal cytology, without the theoretical analysis by Weismann, and without the benefit of the many other seminal discoveries made between 1865 and 1900, Mendel had discovered a new way of looking at the phenomena of inheritance. He emphasized the behavior of unit characters and used this insight to arrive at far-reaching generalizations. His achievement was one of the most brilliant in the history of science. Mendel was a dedicated scientist, reflected in the enthusiasm with which he reports his findings to Nageli, April 18, 1867. Every day from spring to fall, one's interest is refreshed daily, and the care which must be given to one's wards is thus amply repaid. In addition, if I should, by my experiments, succeed in hastening the solution of these problems, I should be doubly happy. Stern and Sherwood, 1966. His short treatise, Experiments on Plant Hybrids, as Kurt Stern has characterized it so well, is one of the triumphs of the human mind. It does not simply announce the discovery of important facts by new methods of observation and experiment. Rather, in an act of highest creativity, it presents these facts in a conceptual scheme which gives them general meaning. Mendel's classic remains alive as a supreme example of scientific experimentation and profound penetration of data. Stern and Sherwood, 1966, v. 1-1. The Flowering of Mendelian Genetics. Darwin's Variation, 1868,
De Vries's Intracellular Pangenesis, 1889, and Weissmann's Germplasm, 1892, created an accelerating interest in the problem of inheritance. One Hugo de Vries and Karl Correns began in 1892 with systematic crossing experiments, and both published in 1899 important results of their experiments on xenia, endosperm formation by the pollen nucleus, see Dunn, 1966. Then, in the spring of 1900, one of the most extraordinary events in the history of biology took place with seemingly explosive suddenness, though it was actually only the climax of a long development. Three botanists, de Vries, Correns, and Tschermak, within a period of a few months published statements that they had independently discovered certain laws of inheritance, only to find, when checking the literature, that Mendel had anticipated them by 35 years. Ever since that memorable spring, suspicions have been expressed as to whether the statements made by the three rediscoverers were to be taken as literally true. The problem seems to be important enough to be looked into a little more closely. 2. The rediscoverers of Mendel. De Vries in his 1889 Intracellular Pangenesis had clearly formulated the view that inheritance was to be dissected into unit characters, each inherited independently. 3. He had also outlined a program of experimentation. Being preoccupied at that time with physiological experiments, he did not seriously begin crossing experiments until 1892, at first concentrating on Silene, Papaver, and Oenothera. In 1894, among 536 F2 plants of Silene, he found 392 hairy and 144 smooth ones, 2.72:1. In an F2 cross of poppies in 1895 he got 158 black to 43 white petal spots, 3.67:1, and found in 1896 that the white-spotted ones bred true. Other experiments in these years reinforced these findings. By the autumn of 1899, 727, he had obtained clear segregation in over 30 different species and varieties. He was finally convinced that the segregation of alternate characters obeyed a general law and that he was justified in publishing his results. In March 1900, he submitted 3 papers within a few weeks of each other, describing his findings, 2 to the Académie des Sciences in Paris, to be presented at the session of March 26, 1900, and 1 to the German Botanical Society, received March 14, see Kraseniecki, 1965. The Paris papers were actually published a few days earlier, prior to April 21, than the 728 German paper, April 25. In a footnote to the German paper, de Vries wrote, "I first learned of its Mendel's paper existence after I had completed the majority of my experiments and had deduced from them the statements communicated in the text." Albee, 1966, 129, on the basis of a good deal of indirect evidence, concluded that de Vries might have read Mendel's paper as early as 1896 or 1897, Zirkel, 1968, thought it was not until 1899 and Kotler, 1979, found further evidence for the later date. In his notes for lectures in these years de Vries still used his own terminology active, A, latent, L, instead of Mendel's dominant and recessive, and in a demonstration plate for students he used variable percentages for segregation, 77.5%, 22.5%, 75.5%, 24.5%, as if he were not yet aware of the true causation of segregation. It is also worth mentioning that of his very numerous Oenothera crosses, he referred in his 1900 paper only to the Lamarckiana X brevistylis cross, the latter being the only genuine gene mutation he had found in his Oenothera material. For as he clearly stated in his correspondence with Bateson, de Vries made a distinction between progressive and derivative characters, only the latter obeying the Mendelian rules. De Vries says that he had found the reference to Mendel in the bibliography of an article published in 1892 which he apparently consulted a few years later and which induced him to read Mendel's original publication. There is no doubt that at that time he had already found segregation ratios which we would now interpret as 3:1 ratios, as well as the true breeding of the recessives, but this does not necessarily mean that these findings had induced him to abandon his earlier erroneous notions. Like all other investigators of the 1880s, de Vries had originally believed that characters might be controlled by multiple particles, see chapter 15. Ratios like 394 to 144, or 158 to 43, or 77.5% 22.5% do not mean anything if one believes in replicate factor determination. When using ratios, de Vries referred to 2:1 or 4:1 ratios, Kotler. The Flowering of Mendelian Genetics. 1979. Did the reading of Mendel's paper cause him to abandon his original theory and adopt Mendel's theory of a single element from each parent determining an individual character? We shall never know. As it is, we must accept de Vries's statement that he had deduced from his own experiments the law of segregation, just like Mendel had derived this law from similar results. By concentrating on the experimental analysis of unit characters, de Vries had certainly come very close to the solution. It was only a small step to abandon the last erroneous component, frequent pangene replication, of his earlier theory. Yet, Bateson failed to find the Mendelian explanation, in spite of good Mendelian ratios, prior to reading the de Vries paper. Clearly de Vries was deeply disappointed at having been anticipated by Mendel, and this may be one reason why he did not pursue the more strictly genetic consequences of his findings but shifted instead to the evolutionary interpretation of progressive mutations. Speciation is where his major interest seems to have been all along. Evidently, de Vries thought that Mendelian inheritance was only one of several genetic mechanisms. How else can we explain his statement to Bateson, October 30, 1901, "It becomes more and more clear to me that Mendelism is an exception to the general rule of crossing." Hence, he more or less abandoned Mendelism to study other forms of inheritance which he considered to be of more importance for evolution. For three reasons, de Vries will always be remembered as a great figure in the history of genetics. 1. Because independently of Mendel he promoted the idea of dissecting differences among individuals into unit characters. 2. Because he was the first to demonstrate the operation of Mendelian segregation in a wide variety of plant species, and 3. Because he developed the concept of the mutability of genetic units. Thus, he was far more than a rediscoverer of Mendel. De Vries had, of course, a great advantage over Mendel. He was able to make use of the results of then recent cytological research when developing his theory. While Mendel wisely refrained from speculating on the nature of the element, the physical basis of his characters, de Vries related them to redefined Darwinian Pang-NS. With respect to inheritance, he synthesized Darwin and Mendel. The case of Carl Correns, 1864–1933, the second rediscoverer of Mendelian inheritance, is more clear-cut. He states that the interpretation of Mendelian segregation came to him like a flash as he lay awake in bed toward morning, in October 1899. 729. He was busy with other researches, however, and did not read Mendel's memoir until a few weeks later, but referred to it in December 1899 in his Xenia paper. Only when, on April 21, 1900, he received a reprint of de Vries's French Academy paper did he write up, in a single day, his results, which were reported in the April 27 session of the German Botanical Society and published about May 25. Correns, from the beginning, did not consider his part in the rediscovery very important, and includes a reference to Mendel's rule, in the title of his first communication. 730 He realized that the intellectual labor of finding out the laws anew for oneself was so lightened through the research of the past 30 years, particularly the work of Weismann, that it stands far behind the work of Mendel. The only thing that might be suspect about Correns' independent rediscovery of Mendel is the fact that he was a student of Nageli, whose niece he married, and might have known of Mendel's work all along. This possibility, however, is made implausible by the fact that it would have been most peculiar if Correns had not followed up this clue much sooner, if it had been available to him for 20 years. The third person who is always listed as another independent rediscoverer of Mendel's rules is the Austrian plant breeder Erich Tschirmach. As Stern, 1966, 11, has shown, there is little justification in including Tschirmach among the rediscoverers. He had indeed found Mendel's paper but had failed in his 1900 papers to understand the basic principles of Mendelian inheritance. Nevertheless, Tschirmach had an important share in directing the attention of the plant breeders to the importance of Mendelian genetics. Just why so many of the early Mendelians, Mendel, de Vries, Correns, Tschirmach, Johansen, were botanists has never been fully explained. Presumably there was a richer tradition of breeding varieties among horticultural and other cultivated plants, because plants are so much easier to cultivate and breed than animals. Perhaps there are also more discontinuous characters in leaves and flowers than one finds in domestic animals such as sheep, cattle, and pigs. Most characters studied by animal breeders were highly polygenic and not at all suitable for an elementary Mendelian analysis. Still, soon after 1900 Bateson started to work on the domestic fowl, Quinot in France and, in 1902, Cassel in the United States began to work on rodents, and in 1905 Cassel introduced Drosophila as an experimental animal. Soon the work in animal genetics caught up with plant genetics and surpassed it. The flowering of Mendelian genetics. When the schools of Morgan and Chetverikov got going. Already in 1914 A. Lang required 890 pages to report merely on the results of mammalian genetics obtained since 1900. Plants, even higher plants, have a much richer diversity of genetic systems than animals. This can be very misleading for one who wants to establish universal laws. Examples are the apamic systems of Hieracium which frustrated Mendel, the balanced heterozygous chromosome rings of Oenothera which led de Vries into an erroneous speciation theory, and the self-fertilizing near homozygous beans, Phaseolus, which led Johansen to belittle natural selection. 6 cytoplasmic effects are apparently much more common in plants than in animals and have monopolized the attention of many plant geneticists, especially in Germany, without yielding, in the premolecular period, particularly interesting results. On the other hand, the plant kingdom has supplied not only the pea but also cereal species, particularly wheat, barley, maize, cotton, gossypium, tobacco, and many other genetically highly informative species. No one has yet undertaken a comparative analysis of the positive, and negative, contributions made by the various species of animals and plants used in genetic research. Much work, it must be admitted, merely produced a confirmation of something already established by work on Drosophila or maize. Prior to the molecular period most genetic work was done either in botany or in zoology departments, and the interactions among plant and animal geneticists were not always as active as might have been desirable. After the 1930s lower plants, algae, fungi, yeasts, and prokaryotes, bacteria, viruses, became increasingly the favorite material of the geneticists. Realization of the pronounced differences in the genetic systems of eukaryotes and prokaryotes has revived an interest in the genetics of eukaryotes since the 1960s. The classical period of Mendelian genetics. The early history of genetics falls into 2 periods, the first from 1900 to about 1909, the second beginning with 1910. The earlier period, often designated as Mendelism, was preoccupied with evolutionary controversies and with doubts as to the universal validity of Mendelian inheritance. This period was dominated by de Vries, Bateson, and Johansen, who have often been designated as the early Mendelians. The term Mendelism conveys different meanings to different people, depending on what aspect of Mendelism one wants to emphasize. To the members of the genetics establishment it refers to the period in which particulate inheritance was nailed down and the hardness of inheritance was emphasized. To the evolutionists it means a period in which utterly erroneous ideas about evolution and speciation were promulgated by leading geneticists and during which mutation pressure was considered far more important than selection, ideas which 752 resulted in the alienation of the naturalists. The same term Mendelism was thus used sometimes with an approving and sometimes with an unfavorable connotation. The second period, beginning in 1910 and dominated by the Morgan School, was occupied much more intensively with purely genetic problems such as the nature of the gene and the arrangement of the genes on the chromosome. The term genetics, proposed by Bateson in 1906, was in due time accepted for this broadened concept of the science dealing with inheritance. It took 34 years for Mendel's publication to be rediscovered, but the subsequent dissemination of Mendel's findings occurred at an unprecedented rate. Both Correns and Tchermak learned of de Vries' paper at the end of April 1900 and published their own findings in May and June. In Great Britain, William Bateson reported on Mendel's experiments at the May 8 meeting of the Royal Horticultural Society, and in France Quinot also soon referred to Mendel's work. As is true for most major scientific movements, subsequent progress occurred at very different rates in different countries. Great Britain, without any question, assumed leadership in Mendelian genetics, soon to be followed and eventually to be overtaken by the United States, Castle, 7 East, Morgan, and others. German genetics, continuing the tradition of the 1880s, concentrated on developmental genetics and on unorthodox phenomena, actual or seeming cytoplasmic inheritance, protozoan genetics, and so forth. In France, after the promising beginnings made by Quinot, not much happened until the 1930s. In Russia, as Gasinovich, 1971-98, has remarked, genetics began to develop as a branch of science only in the Soviet period. In the non-Western world no science of genetics ever originated. Where genetics flourished and in what direction it developed depended entirely on the leading personalities in the field. Curiously, however, neither Correns nor de Vries played a major role in the subsequent. The flowering of Mendelian genetics. Advances of Mendelian genetics. The major credit for this, at least in the early years, must be given to William Bateson, 1861-1926, who appreciated the importance of Mendel better than the so-called rediscoverers, Darden, 1977. Bateson had been interested in discontinuous variation, see Part 2, since his stay in Professor W. K. Brooks's laboratory at Johns Hopkins University, 1883-1884, and had conducted breeding experiments since the 1880s, but intensively only since about 1897. On July 11, 1899, he presented a paper to the Royal Horticultural Society entitled Hybridization and Crossbreeding as a Method of Scientific Investigation. It is evident from this lecture that at that time he had still not yet developed a theory of inheritance, in spite of many results now easily interpreted in Mendelian terms. The illumination did not occur to him until he read Mendel's original paper on May 8, 1900, on the train from Cambridge to London. At once he became an enthusiastic Mendelian, had Mendel's paper translated, and published it with footnotes in the Journal of the Royal Horticultural Society, 1900. Part of Bateson's enthusiasm was due to the fact that he saw in segregation a confirmation of his, erroneous, thesis, 1894, that speciation is the result of discontinuous variation. De Vries had the same evolutionary theory, and he also saw the discontinuity of Mendelian factors as important evidence for his saltational theory of speciation. Thus, paradoxically, much of the publicity and attention which Mendel got was for peripheral, if not the wrong, reasons. The opposition which the Bateson-de Vries thesis aroused is treated in Chapter 12, and I shall deal here only with Bateson's contributions to transmission genetics. It is Bateson to whom we owe some of the most important technical terms in this field. He coined the term genetics for the new science, 1906, and also, 1901, the terms allele, originally allelomorph, heterozygote, and homozygote. Availability of these semantically unambiguous terms greatly facilitated communication during this period. But Bateson and his collaborators were also responsible for important factual contributions to our understanding of inheritance. They were the first to discover certain deviations from the simple Mendelian situation, for example, polygeny and incomplete linkage. Through him, genetics gained an impetus in Britain that was entirely lacking in any other European country. Bateson was a complex personality, pugnacious to the point of rudeness in his controversies, but at the same time completely 733. 734. Dedicated to research. He was a peculiar mixture of a revolutionary and a conservative who found it very difficult to accept new ideas. In the first 10 years after 1900 he was the major spark plug of genetics. Indeed, there is much justification in Cassell's statement, 1951, that Bateson was the real founder of the science of genetics. After 1910, however, his opposition to the chromosome theory, see below, and his continuing advocacy of instantaneous speciation seemed no longer constructive. In his role as a revolutionary he made the immortal remark, 1908, 22 treasure your exceptions, when there are none, the work gets so dull that no one cares to carry it further. Keep them always uncovered and in sight. Exceptions are like the rough rock work of a growing building which tells that there is more to come and shows where the next construction is to be. In his own research he concentrated very much on actual or seeming exceptions, and some of his important discoveries were the result of his following this motto. Advances in Mendelian genetics. The rate at which the new finds of genetics occurred after 1900 is almost without parallel in the history of science. Whether we look at Locke's textbook of genetics, 1906, particularly 163-275, or Bateson's textbook, 1909, we are surprised at the maturity which the understanding of Mendelian inheritance had reached so soon after 1900. What were the reasons for this rapid progress? One of them, of course, was that the beauty and simplicity of the new theory invited anyone to undertake genetic experiments to test its universality. Since the field was brand new, almost anybody had a chance to make new discoveries. The Mendelian laws permitted predictions about modes of inheritance and an immediate testing of these predictions. A second reason is more doubtful: the magnificent achievements which cytological research had made in the 35 years prior to 1900 had laid such a sound foundation that it should have been possible to explain almost any purely genetic discovery in cytological, and more specifically in chromosomal, terms. Chromosomal cytology formed a bridge to other areas of biology, and it was a bridge which had been built before it could be used. But, curiously, even after it could be used, it was almost completely ignored by the geneticists, such as Bateson, Cassell, and East, prior to Morgan. The knowledge of the mechanism of inheritance was used to shed new light on phenomena in various areas of biology, such as the flowering of Mendelian genetics, evolutionary biology, see chapters 12 and 13, or developmental physiology, a subject I will cover in a subsequent volume. In the following discussion the emphasis will be on aspects of transmission genetics. Semidominance. Among the 7 pairs of characters which Mendel had analyzed, he recognized only 2 variants of each pair, those that are dominant and those that are recessive. But this does not hold for all character pairs, as Mendel himself discovered. He remarked that flowering time is almost exactly intermediate between that of the parent plants. Correns, 1900, found, likewise, that certain factors are not fully dominant but only semi-dominant, thus producing an F phenotype somewhat intermediate between that of the 2 parents. 2 years later, Bateson found such semi-dominance when crossing white with black fowl. The F was the blue Andalusian fowl. This not only confirmed semi-dominance but also established the fact that Mendel's laws are as true for animals as they are for plants. At about the same time Knott demonstrated this on the basis of work on the coat color genes of the house mouse. Considering the fact that cells and nuclei of plants and animals show completely equivalent phenomena, this finding was perhaps not altogether unexpected. Nevertheless, the discovery that the Mendelian laws of heredity are valid in both kingdoms further contributed toward breaking down the ancient barrier between zoology and botany. The gene, the unit of inheritance. Prior to 1909, no generally accepted term was available for the genetic factor underlying a given visible character. Spencer, Haeckel, Darwin, De Vries, Weismann, and others who speculated about inheritance had postulated the existence of certain corpuscles with various qualities, but the names they had used were not widely adopted, see Chapter 16. Mendel kept his speculation about the nature of the genetic material to a minimum, a wise decision on his part, considering the rudimentary understanding of nucleus and chromosomes in 1865. He referred in his experiments to traits, Merck-Male, and characters, Charakter, essentially restricting himself to the phenotypic level, even though the symbols A used by him are generally considered to refer to the constitution of the genome.